Any quick questions in the beginning before we start? Okay, so again, it's a revision session, so I'll be quickly going over all the major concepts and the common types of questions that you get on these topics. All right, we're starting with binomial first of all, so let's begin with this. All right, so what's binomial expansion? First of all, binomial expansion is when you have two terms being added like this and you have a power on top of that. If you have a plus b whole raised to power 1, for instance, that's fairly straightforward. That's a plus b. But you've learned to know in O-levels or IGCSE, for instance, what a plus b whole squared expands to. It's a squared plus 2ab plus b squared. But if you have to expand higher powers like a plus b whole raised to power 3, 4, 5, it becomes very tedious to do it manually like this. We need some general formula to be able to do that, right? And in binomial expansion formula, what we can do is, using this binomial expansion formula, we can expand any integer power for an expression like this. So if we have two terms adding in a bracket like this, and we have a power on top of that like this, we can use this formula to expand that expression to whatever is the number of terms that it has. Now, there's a condition for using this formula, and that condition is that the power has to be a positive integer. Now, in paper 1, you will always get questions in which power is a positive integer. If it's not a positive integer, you will not get that in paper 1. You have another binomial formula that's given in the formula sheet. Since you get the same formula sheet in the exam, just be careful that the other formula that looks something like this, that's not what you end up using here, because that's not relevant for this. 1 plus nx something. This is the formula that we'll be using, a raised to power n plus nc1 into a raised to power n minus 1b, and so on. All you have to do is just input values in the formula. Whatever is the first term, that's going to be a. Whatever is the second term, that's going to be b. For instance, if you want to expand a plus b whole raised to power 4, what you do is, you basically figure out what is in place of a in the formula. You've got a here. What's in place of b? In place of b, you've got b. In this case, there's nothing different inside the bracket, but the power is 4. All you have to do is, in the formula, replace n with 4, right? That's all that you're doing, just replacing n with 4. And now, how exactly do you evaluate this? This is straightforward, a raised to power 4 minus 1 into b, a raised to power 4 minus 2b squared, and so on. But what about 4c1, 4c2, 4c3? It's a function that you have in your calculator. If you look at the division button on your calculator, on top of this division button, you have this button in yellow. You can use that to evaluate these numbers, 4c2. So what you do is, for example, if you have to evaluate 4c1, on your calculator, you go like this, you press 4. You press the NCR button, and then you press 1, and that gives you the result. That's 4c1. 4c1 is 4. Similarly, if you want to evaluate 6c2, you press 6 here, then you have 2. 6c2, that gives you 15. So evaluating this is going to be fairly straightforward after that. Once you've input values in the formula, you just evaluate this on your calculator, 4c1, 4c2, and so on, and then you just multiply those numbers like this. Now, that's a fairly straightforward case. What if you have something else like this? For example, if you have x minus 2y whole raised to power 8, x minus 2y whole raised to power 8. If you have an expression like this, what about this now? In place of a, we've got x. In place of b, we've got minus 2y, and the power is 8. Okay. Now, all you have to do is, in the formula, wherever you've got a, you replace that with x. In the formula, wherever you've got b, you replace that with minus 2y, right? And wherever in the formula you've got 8, you replace that. Wherever in the formula you've got n, you replace that with 8. And that's it. Then you just simplify this and you get the result. In this case, you have x raised to power 8 plus this, plus this. Just be careful with the negative signs here, because when there is a negative here, that is going to be part of the value for b, because the formula has a plus b whole raised to power n. If the second term, for instance, is negative, that means the value for b is negative. That's minus 2y. Okay. So when you input the value here, make sure that you put that inside brackets like this. A lot of careless errors happen in this step. Just make sure you write values inside brackets so that you do not make those sign errors. And then you can just evaluate this and see what the result turns out to be. If it was something more complicated, sometimes you can have fractions like this as well. X squared plus 1 over 2x. Now, in place of a, you've got x squared. In place of b, you have 1 over 2x. And in place of n, you have 7. All you have to do is, in your calculator, in the formula, you replace a with x squared, b with 1 over 2x, and n with 7, and just simplify everything. Now, how are you going to evaluate this on your calculator? Don't try to do it manually, even if your mental math is good. Yes, you can think about the result on in your head as well. However, the actual calculation you should be doing on your calculator. For instance, if you have to evaluate this, what you would do would be on your calculator, you input it like this. You'll say it's 7c1. Now, this thing should be put inside brackets. Otherwise, you can end up getting errors sometimes. So you have to be careful about that. You input this inside brackets, 7c1. 7c1. And now you've got x squared. Now you can't put x in your calculator like that. It will not give you any result for that. You ignore x, think of x as 1, and just input all the numbers instead. What are the numbers? We've got this number left, 1 and 2 in the denominator. So now you put 1 over 2 in the denominator like this. And that will give you the result 7 over 2. Now that was fairly straightforward. But the next one is going to be much more useful now if you use the calculator directly. We could skip this particular step that we're doing, and we could directly write value from the calculator. For instance, you can say this is 7c2, and then inside the bracket, what do you have there? 1, that's one number. 2, that's another number. In your calculator, ignore x, input this number, 1 over 2 whole squared. Let's input that. 1 over 2 whole squared. You'll get that number directly, the coefficient of that term, that's 21 over 4. So this coefficient and this coefficient, you can get that directly from the calculator. And now, just do this manually, the powers of x. Power of x here, x raised to power 2 into 6, that's 12. In the denominator, you've got x. You subtract 1 from that, and you get x power 11 from that. So you just have to calculate the powers of x yourself. Everything else you just put on your calculator. Okay, don't do it manually. That will make you do careless errors. Just put the numbers in your calculator like that. Okay, now in the formula sheet that you get in the exam, the formula is going to be written in a slightly different form. So you have to be familiar with that. Yes, you should remember this formula anyway, but in case you forget some particular term in the formula, in the formula sheet, you've got the formula written in this form. Okay, now it's not the form that we normally use because the calculator has the NCR button, this button. So normally we use NCR in the formula that we write. In the formula sheet, when it says N1 like this, that basically is equivalent to NC1. In the formula sheet, when it says N2, that's equivalent to NC2. And the rest of the formula is as it is. So in case you forget the formula, look at the formula sheet, just replace this expression with NCR, and you would get that formula. For example, this is NC1, this is NC2, this is NC3, right? Okay, so it's in the formula sheet, it's written like this. You should be familiar with that. Okay, now that's the basic idea of this, how to use the binomial expansion formula to expand something. Now let's look at some different types of questions that you will see on this. Now, one thing is that you expand an expression using the formula. Sometimes what they do is they give you the final result that you would get from that expansion, and they want you to find some missing values in that expansion, some missing letters, some missing variables from that expansion. So in this case, for instance, we've got this constant a that we do not know what it is. We have this power n. Again, we do not know what that power n is. How do you find the values of a and n? They have given us that the expansion of this is 32 minus 40 plus bx squared. right? They've given the expansion to us. Now, how will you find the values of a and n from this? We will do the expansion ourselves. We've got 2 plus ax whole raised to power n. We apply the binomial expansion formula on this and see what we get from that. 2 raised to power n plus nc1 into this plus nc2 into this. And now we simplify that and we end up getting an expression that looks something like this. 30 minus 40x plus, we get this expansion from this. And they gave us in the question that the expansion is 32 minus 40x plus bx squared, right? In the question, they said that this is the expansion. All you have to do now is compare these terms. The first term that you're getting here, the constant term, you are getting 2 raised to power n. They said in the question that this term is 32. So these should be equal to each other. 2 raised to power n should be equal to 32. The second term that they gave us was minus 40x. What we're getting is nc1 into 2 raised to power n minus 1 into ax, right? So these should be equal. And similarly, the third term, the x squared term, they should be equal. We make 3 equations from this, and we solve those 3 equations simultaneously to find the values of those unknowns. For example, in this case, when we solve the first equation, we get n equal to 5 from that. When we solve the second equation, we get this expression. We put the value of n in that we have found there. The value of n is 5. And then to simplify that, that gives us the value for a. And similarly, from the last one, then we can find the value of b as well. Now, sometimes in questions like these, you can end up getting an expression like this. NC0 or NCN or sometimes NC1. And if you do not know the value for n in this, you should be able to figure out what they evaluate to without even knowing the value for n. For example, if you have NC0, you need to remember what that evaluates to. For example, if you try on your calculator 6C0, what's that? That is 1. If you try 8C0, what's that? That's 1. Any number C0 that always is equal to 1. So in case you get something like this, NC0, you should know that you can write that as 1 directly. NC0 is always equal to 1. Similarly, when the number on top of this function and the number at the bottom of this function, when they're both the same, in that case as well, it always evaluates to 1. So in case you end up getting NCN somewhere, you should know, if you do not know the value for n, that means you cannot input that in your calculator. You should know that NCN should always evaluate to 1 because 6C6 is 1, 7C7 is 1, 10C10 is 1. So we can say in general, NCN is always equal to 1. And if you have NC1, that always evaluates to n. Okay, so sometimes this number on top might be unknown. You should be able to simplify that like this. NC1 simplifies to just n. Okay, because 9C1 is 9, 15C1 is 15, 4C1 is 4. So whatever is the number on top, if you have 1 at the bottom, it always evaluates to the number on top. Okay, this is going to be helpful in some problems. There are very few of them in past papers, maybe just a couple, but you should know how to simplify this. Okay. Now, there's another complication that comes sometimes that instead of 2 terms, you have 3 terms inside the bracket. Okay, so for example, you have something like this: 2x minus x squared, and then whole raised to power 5. Now, binomial expansion only works for 2 terms at a time. In this case, you can use a substitution sometimes. Now, in most questions, they will ask you to expand something in the first part, and then you have to use that to do this expansion of 3 terms. Now, for instance, in this case, they asked us to expand 2 minus y whole raised to power 5, and that expanded to this thing. And we got 32 minus 80y plus 80y squared at the end from that. Now, using that, what if we had to expand this? 2 minus this whole thing. Now you compare these two, and you see, in place of y, you are getting 2x minus x squared here, right? So in that expression, inside the bracket, what has changed is that in place of y, now you have 2x minus x squared. So all you have to do is, in the expansion that you've done in the first part, you just replace y with 2x minus x squared, simplify that, and you get a result from that. In this case, they were asking for the coefficient of x squared. So we simplify that, and we see what's the term in x squared that we're getting, and we write down the coefficient. That's 400 in this case. All right. So you should know how to expand 3 terms inside the bracket like this. it'll be done using a substitution. They might, in more difficult questions, in recent papers, they have started increasing the difficulty level sometimes as well. They might just skip the first part and they might directly ask you to expand this. 2 minus 2x minus x squared whole raised to power 5. Now, how would you do that? You would use a substitution yourself. You would say, let's substitute this thing with something else. So you'll say, let u or any other letter that equals 2x minus x squared. And then you will write that expansion like this, 2 minus u whole raised to power 5. You will do this expansion. And then once you've done that expansion, in that expansion, you'll replace u with 2x minus x squared and then simplify that so that you get that expansion, right? So 3 terms as well. Sometimes they can give you something like this to expand that. All right, let's move on. Now, in questions, you will see sometimes they use this terminology that there's no term in a particular power. For example, no term in x squared, no term in x cubed, no term in x raised to power 5. What does that mean? If there's no term in x cubed, you could have something like this. For example, 5x raised to power 4 minus 2x squared plus 7x minus 3. So this is an expression that does not have any term in x cubed. Now, when they say there's no term in x cubed, what that actually means is the coefficient of x cubed is supposed to be 0. Because when the coefficient of x cubed is 0, then 0 times x cubed, it's going to get eliminated. And we would get an expression like this that does not have any x cubed term in it. So whenever in a question they use this terminology, there's no term in a particular power of x. What that means is the coefficient of that particular power of x, that's going to be 0. So you'll find that term, put the coefficient of that equal to 0. Then there's another terminology that you'll see being used in questions like these, and that's that find the term independent of x, term independent of x. What does that mean? In this expression that I wrote above, this term is independent of x. That means it does not have any x in it. It does not depend on x, right? It's not, x is not multiplying with this. Now, what exact term is that? That's the constant term. Or you can think of it as the x power 0 term. So when they ask you for the term that's independent of x, that means it's a constant and the power of x in that case is equal to 0. Okay. All right. Now let's have a look at a couple of questions on this. So in this question, they asked you to expand this in ascending powers of x first of all. So let's say you've done that. Now they're saying find the value for k for which this expression has no term in x squared. Now, what does that mean? If there's no term in x squared, the coefficient of x squared that you get at the end, that should be 0. Okay, so what we do is, in the first part, we've done this expansion, 2 minus x whole raised to power 6. In the second part, they ask us to expand this, 1 plus kx into 2 minus x whole raised to power 6. What we'll do is, we will put that expansion in the second part, 64 minus 192x plus 240x squared. Simplify this. Find the coefficient of x squared. Now, in this case, it's not necessary to do this whole multiplication, as we will see in a few minutes. You could just, do these 2 multiplications as well. But once you've found the coefficient of x squared, what you do at that point is, you put that coefficient equal to 0. So what's the coefficient that we're getting? We're getting 2 x squared terms. One is 240x squared, and the other is minus 192kx squared. We write both of them down, take x squared common. That gives us that the coefficient of x squared is therefore 240 minus 192k. Now, since we want no term in x squared, that coefficient should be put equal to 0, and we find the value of k from that. Okay, so whenever they say there's no term in a particular power of x, you put that coefficient equal to 0. Now, the next major thing that you need to know is sometimes they ask you to find a specific term in an expansion, right? So simple expansions are fairly straightforward. You just apply the formula and you get the result. Now, sometimes they don't ask you for a complete expansion. They will ask you to find the coefficient of a particular power. So in this case, they ask you for the coefficient of x squared, for instance. How do you find a particular power or a particular term in an expansion? Now, whenever you have binomial expansion, let me show you these examples above. The powers of x that you get at the end. For example, this was one expansion that we did. This one, x squared plus 1 over 2x whole raised to power 7. You see what the powers of x turned out to be? It was 14, 11, 8. Do you see any pattern in these powers? all of them have a constant difference. It started from 14, then the next was 11, the next was 8. So it's a linear sequence. It's an arithmetic sequence. The next power necessarily is going to be x power 5. The next after that is going to be x power 2. And the next after that is going to be x power minus 1, and so on. It's always in an arithmetic sequence. Okay. Now, that is something that can help us find a specific term in an expansion. So in this case, for instance, we want to find the coefficient of x squared in this expansion. Yes, there's a general term formula that exists, but this is much easier, much quicker, and less prone to errors. What you do is you just do the expansion the normal way. Okay, so x plus 2 over x whole raised to power 6, you just expand it like you normally would. The first term turns out to be x power 6. The second term turns out to be this thing. We just note the coefficient, the power of x that we would get from that. The first term is x power 6. The power from the second term is going to be x power 4. How? Because we've got x power 5 in the numerator. We've got x power 1 in the denominator. That simplifies to x power 4, right? Now, these two terms are going to give us a pattern. The first power is 6. The second power is 4. What's the next one going to be? X squared. And the next one, x power 0. And the next one, x power minus 2. Which specific power do we need? We needed x squared. So we know that the next term after this, after x raised to power 4, is going to be x squared. And that's it. We don't have to expand any further. We just simplify this particular term, and that will give us the result that we want. Okay, so we just simplify that and we get that result. Now, this was relatively simpler because we got that coefficient, we got that specific power of x in the very beginning, just in the third term. Sometimes what can happen is it might be further along the way on the right side after maybe 7, 8 terms. What do you do in those cases? Let's look at this example. So we want to find the term independent of x in this expansion. Okay, independent of x means that's the term that has x raised to power 0. That's the term that we are looking for in this expansion, x power 0 term. Now we do it the regular way. We say, let's use the expansion formula on this expression and see what we get. Now we expand the first term, and that turns out to be 4x cubed whole raised to power 8. Okay, what's the power of x that we're getting? 3 times 8, that's 24. Okay, what about the next one now? When we expand this, we get x power 21, and then there's an x in the denominator as well. So 21 minus 1, that's x power 20. And that gives us the pattern. The first term is 24. The next power is 20. Now we know the next is going to be 16, and then 12, and then 8, and then 4, and then 0. And this is the term that we are looking for. Okay, that's the term that we're looking for. Now, how do we know what that term is? Do we write all of these values? This one, this one, this one, this one, and this one, and then we reach that final term? Now, for this, you can remember this general term formula. Now, where does this general term formula come from? Where is the formula? Let me just go back to that quickly. Should have copied that beforehand. Okay, that was the formula that we had, right? In the NCR form. Now, look at the pattern that you see in this. So that's a way to remember the generator term formula. That's why I'm just going through that quickly. This is the binomial expansion formula, right? Look at the terms. Look at this term. What's that? NC1 into a raised to power 1, a raised to power n minus 1 times b, and so on. You see, in every term, the only thing that's changing is this number. This is 1 in this term. This is 2. This is 3. That's the only thing that's changing, right? So from this, you get a general term formula. This is the only number that's changing, right? So you can write this expression like this. You can say this is NC something, and then A raised to power N minus something, and then B raised to power something. That's that same number. We call this number R. That's NCR into A raised to power N minus R into B raised to power R. That's the general term formula that we have. Okay, so if you forget that, you can make it yourself from the expansion formula. Just replace these numbers with R and you get that formula. So every term is going to be of this format. Okay, every single term in this expansion is of this format. And it starts from R equal to 0. The first term is when R is equal to 0. The second term is when R is equal to 1. In this case, R is equal to 3, right? This is 3. Sorry, 2. Then the next one is when r is equal to 3, and so on. So we have a general term formula that looks like this: NCR into a raised to power n minus r into b raised to power r. So from this pattern, what we can do is we can figure out what the value of r is going to be, and that's it. So let me explain what that would be. So we started from this: x power 24, r is equal to 0 here. X power 20, r will be equal to 1 in the next case. And then we are looking for this particular term. What's the value of r going to be there? That's all that we need to figure out. 2, 3, 4, 5, 6. This is what we get. R is equal to 6 there. Now you would remember this general term formula: NCR into a raised to power n minus r into b raised to power r. Just input that value of r here and simplify that, you'll get that result. So in this case, a is equal to 4x cubed, b is equal to 1 over 2x, n is equal to 8. Just input those values, and the value for r is equal to 3. Input those values, simplify that, and you would get that term that you're looking for. Okay, so this pattern is very helpful. You can find any specific term that you want from this expansion like this, right? Just find the value for r and input that value of r in this general term formula then. Now, sometimes when they ask you for specific terms, they have products like this. Okay. Now, in the first part of this question, 1 plus 2x whole raised to power 6, they want us to find the coefficient of x cubed in this expansion. And that's straightforward. We know that the first term is x power 0, then the next is x power 1, and then the next is x power 2. This is the term that we're looking for. We simplify that, and that turns out to be 160. Now, in the second part, they say, find the coefficient of x cubed in this expansion. Now, we've got two things multiplying, and we want to find the coefficient of x cubed from that product. How do you find the coefficient of x cubed from this product? The first thing that you should always do in questions like these is think about what terms you would end up needing from this expansion, right? Because in the first part, they just made you find the coefficient of x cubed, and that was this. Now, that's not the only term that you would need for the second part. You might need something else as well. So before you do anything, think about what terms you are going to need from that expansion. How do you figure that out? X cubed is what you want. You've got 1 here. What do you multiply 1 by to get x cubed? You multiply 1 by x cubed term to get x cubed, right? X power 0 will have to be multiplied by x cubed. So that's one term that you need from that expansion. You need x cubed from that. 3x, what do you multiply 3x by to get x cubed? That's x power 1. You have to multiply this by x squared to get x cubed. So this will have to be multiplied by x squared. So from this expansion, we need two terms. We don't just need x cubed, we also need x squared. Now, this is where expanding it like this without the general term formula becomes so much more helpful, because we've got both of those terms there already. We don't have to do any additional working, just simplify this term as well, and that gives you 60x squared. Now, these are the two terms that you need for the next part. You say 60x squared plus 160x cubed. These are the two terms that you need from this expansion. You just write those two terms, ignore everything else. You could write that, but it's not required. It's much more efficient to just use those specific terms from this. Now, since you're looking for x cubed, you just do the multiplications that in this case. X cubed would be when we multiply 1 by 160x cubed, and that gives us this number. And the other x cubed would come when we multiply minus 3x by 60x squared, and that gives us this other number. We could just ignore everything else, just do these two multiplications, and that would give us the result. Simplify that, and you get the coefficient of x cubed from that. So when you have a product like this, and they want you to find a specific term, you first should think about what terms you would need from that expansion, so that you use those terms in the expansion that you've already done in the previous part. Or if you've not done that, you expand that expression up to that many terms at least. Let's take one more example of this. Okay, it's taking time. I'm a bit too slow today. Okay, find the coefficient of x squared in this expansion. Again, what do we do for this? We use that pattern. expand a few terms, and you get the coefficient of x squared. The first term is x power 6, this is x power 4, and the next one has to be x squared. That's what we need. Okay. All right. Now, what about this? The second part. You want the coefficient of x squared in this expansion. Again, the first thing you have to do is you have to think about what terms you are going to need from that expansion. You want x squared at the end. 1 plus x squared. Think about what terms you need from that expansion. What do you multiply 1 by to get x squared? You multiply 1 by x squared to get x squared. What do you multiply x squared by to get x squared? You multiply that by a constant or x power 0 term. That means from that expansion, you will need these two terms, x squared and x raised to power 0. Okay. So you just, simplify those two terms from that expansion. The x power 2 term, and then you have to expand one more term, that's x power 0. You bring those two terms down here, 60x squared from here, and then minus 20 from here, and then just do the multiplication that you need to do. Multiply 1 by 60x squared, multiply x squared by minus 20, and then simplify that, you get that coefficient. Okay, so you see, in the second part now, you just write down one more term and you get that next term as well. If you were to use that general term formula, you'll have to use that all over again, and that will be like double working. So if you were to use general term formula, yes, you'll have to find this coefficient separately first. And then for the next part, since you need x power 0 as well, you apply that again on this to get minus 20. If you just do the expansion like this normally and look at the pattern, you get both of those terms from this expansion directly. Okay. All right, let's move on. Now, this is something that you will see in some recent papers as well. They ask you for coefficient of 1 over x, 1 over x squared, 1 over x cubed, something like this. Now, don't get confused by that. 1 over x, what's that? 1 over x is actually the same thing as x power minus 1, right? 1 over x squared is just x raised to power minus 2. 1 over x cubed is just x power minus 3. Okay, so what they're asking you for is the coefficient of these powers, x power -2, -3. So when you have x in the power, you just bring that to the numerator, make the power negative, and you find that particular coefficient from that. In this case, now it's a relatively more complicated example that you will see in past papers. They're saying the coefficient of x in this expansion is p. The coefficient of 1 over x, that means x power -1 in the second expansion, that is q. And then they're saying p is equal to 6 times q. Find the possible values of k. Now, how do you think about this? First of all, you find the value of p and the value for q. How do you do that? They've told you how to find that coefficient of x. That's going to be the value for p. You find the coefficient of x, you say that is equal to p. Then you're given that p is equal to 6 times q. You find the value of q from that. And the coefficient from here, the coefficient of x power -1, that is going to be equal to q. So you find that coefficient, put that equal to q, and you get the result. Okay, you can have a look at this working in your own time. But this is one relatively more complicated example that you'll see in recent papers. It's nothing very complicated as far as the method is concerned, but they've just asked about a specific term in a slightly different way than the other questions that you will see in past papers. This is very important now. Look at this question. It says it's given that in the expansion of this, the coefficient of x squared is k. It's also given that there's only one value of a which leads to this value of k. So sometimes now in recent papers, you'll see that they've started combining combining quadratics with a number of topics. You'll see questions where they require you to use quadratics as in b square minus 4ac in equations of circle. In this case, you have to use it along with binomial expansion, and there are other topics as well in which you have to use that b square minus 4ac thing. So think about this. They're saying that in the expansion of this, the coefficient of x squared is equal to k. Okay, so first of all, what we do is we find the coefficient of x squared in this expansion. How do we do that? First of all, we have to think about which specific terms we need from this expansion. How do you figure that out? What do you multiply 4 by? What do you multiply 4 by to get x squared? You multiply, you multiply this by x squared to get x squared. What do you multiply 2x by to get x squared? You multiply 2x by x to get x squared. So these are the two terms that you need from that expansion, x and x squared. You do that expansion, you find those two terms, do the multiplication, and you end up getting the coefficient of x squared that looks like this. Now they said that the coefficient of x squared is supposed to be equal to k. So we put that equal to k like this. And that gives us an equation like this. It's a quadratic equation. And then they're saying there's only one value of A. Look at the question. They said there is only one value of A which leads to this value of K. What does that mean? This equation has only one solution. It has only one solution. It's a quadratic equation. When does a quadratic equation have only one solution? When b squared minus 4ac is equal to 0. So you convert it to the standard form, ax squared plus bx plus c. You say that a is equal to 320, b is minus 160, c is minus k. Put b squared minus 4ac equal to 0. That gives you the value for k. Once you have the value for k, you can solve that equation then to find the corresponding value for a as well. So when they say there's only one solution and you have a quadratic equation, that should remind you about the discriminant that b squared minus 4ac should be equal to 0 there. Okay, it's a binomial question. Sometimes you don't even think of quadratics in questions like these, but that's what it is about the recent papers. They combine a lot of things in a single question. Okay, so you have to have your concepts really strong. Okay, so that's it with binomial. If you guys have any quick questions on this, let me know. Otherwise, we're going to move on to coordinate geometry next after this. Which paper was the previous question from? I'm not sure. You'll have to search for that. You can take a picture. You'll have these notes available as well. You can maybe search for that. So the way to search for a particular question on Google is that you find some unique words in that and put them on Google in inverted commas along with 9709 math, and generally it pops up as the first two, three inside the first two, three results. In this case, though, there does not seem to be any unique words as such. Maybe you can try this equation, p equals 6q, input this in inverted commas and possible values of k in inverted commas, and then put 9709, and you'll hopefully find that question. Okay. Abdulhadi, that's okay. That's perfectly okay. So whatever method you generally learn first, you tend to find that easier. So it's okay. Whatever method you prefer, that's perfectly okay. Yeah, you can Google scan now as well. I have not used that, but yeah, that's a good idea. That's not something that is always going to be true. So the question is, so let me know if I understand your question correctly. You're saying a plus b whole raised to power n. If you have an expression like this, you are saying if a was a fraction, then in the formula a raised to power n plus nc1 into a raised to power n minus 1 into b plus nc2 into a raised to power n minus 2b squared, and so on. You are saying we apply the power r and not n minus r. So you're saying you switch this, you have this power 1 and this power n minus 1, and this power 2 and this power n minus 2. Is that what you're saying? That would not make sense. There's no reason to do that. If you want to do that, you would actually have to switch these terms. You would have to write b first and a second, right? And then you can treat the first term as b and this term as a. Otherwise, you would not do that. That does not make sense otherwise. So whatever is the first term, you take that as A. Whatever is the second term, you take that as B. Okay, so I think I understand where you're coming from. So sometimes, in fact, in questions, sometimes they say expand something in ascending powers of x, and sometimes they say expand something in descending powers of x. Now, in all the past paper questions that you will find, whatever order they ask for, it automatically comes from the expansion, from the expression that they've given. For example, if you have 1 over, or maybe 5x raised to 5x squared plus 1 over x, and you want to expand this, if you expand this, it will automatically turn out to be in descending powers. It will automatically turn out to be in descending powers. The first power would be 5x squared power, let's put 7 here, this power 7. The next one would be NC, or 7C1 into 5x squared whole raised to power 6 into 1 over x power 1. It's going to be in descending powers. They will say in the question, expand this in descending powers. It will automatically come in that order. If it happens, it hasn't happened until now, but there's always a first time for everything. And the recent papers, Cambridge has proved that there's always a first time for, doing giving you something totally new that you haven't seen in the other past papers. You might get this expression, and they might ask you to expand this in ascending powers of x. So if they ask you to expand this in ascending powers of x, for instance, now, if you do the expansion the normal way, you're getting it in descending powers. How do you convert this to ascending powers? In that case, you would switch these two. If you had to find this in ascending powers, you would switch these terms. You would say, let's write this as 1 over x plus 5x squared whole raised to power 7. And then you treat this as A and this as B, and now it will come in ascending powers. Okay, so if you want to switch descending to ascending, you just, switch these two terms. That is one case in which you might have to do it, but I haven't seen any question like this in past papers in which the order that they ask for, it doesn't come automatically. If it does, then you just switch those terms. You consider the second term as A and the first term as B. That's what you can do. We normally do ascending, no, whatever they say. So sometimes they say descending in question, sometimes they say ascending in question. You generally don't worry about that because the expansion that you do, it automatically comes in that order. So if they say ascending, just expand normally, it turns out to be ascending. If they say descending, just expand normally and it turns out to be descending. Okay. If it doesn't happen to be that way, again, it hasn't happened until now in past papers, but if it happens, I told you what to do. In that case, switch A and B, right? The second term first term second, and the order will switch. Okay. You get the grade for all the components combined. That's always an overall grade. Weightage of this topic, it's normally 4 to 6 marks. If they combine some other topic, for example, in this case, they combine quadratics with this, in that case, the number of marks slightly increases. But generally, it's 4 to 5 marks, sometimes 6. It depends on the question. All right, so I think we can move on. There's going to be Maghrib time soon as well. Okay, so I think we might actually need to extend our classes a bit. I hope you don't have any problems with that. If anyone has any clashes, because in case we end up having to extend our class time a bit, you will have the recording available, of course. I'll try to be quick now, but in case you have to attend another class or you have something more important to do, which I don't know why you would have that, but if you do, then you can watch the recording later on as well. Okay, just one last thing. In some recent questions, you will see that do the complete expansions. For example, they might ask you to do something like this. 2x plus 1 over x squared whole raised to power 4. And generally in the earlier past papers, they always say expand the first 3 terms, first 4 terms maximum. Sometimes they say in the recent past papers, find the complete expansion. Find the complete expansion of this thing. Now, what does complete expansion mean? You expand all the terms of the sequence of this expansion, all terms. Now, all terms, what does that mean? Just input values in the formula. It will be 2x whole raised to power 4 plus 4c1 into 2x whole raised to power 3 into 1 over x squared whole raised to power 1 plus 4c2 into 2x whole raised to power 2 into 1 over x squared whole raised to power 2, and so on. The next term is going to be 4c3 into 2x whole raised to power 3, so power 1 into 1 over x squared whole raised to power 3. You keep going on like this, but how do we know when to stop? When exactly do we stop? We stop when the numbers on top of C and at the bottom of C, they become equal to each other. When these two numbers are the same, we stop at that point because we can't go any further than this. The next term on this pattern would be 4C5. That's not something that's valid. It gives you an error. You can try that on your calculator as well. So if you've done S1, it's saying that select 5 objects out of 4. Doesn't make sense. If you put that on your calculator, 4C5, that gives you an error, right? So you stop when the number at the bottom becomes bigger than the number on top. You can't go any further than this. When in fact you stop when they become equal, right? But you can't go beyond that. And that's your complete expansion. You will simplify this and you'll get the result. Okay. So that's binomial expansion. I hope that was helpful. Let's move on to the next one now. Yes, the fifth term would be when n is equal to 4. Okay, now the next thing is arithmetic and geometric progressions. Okay, let's start with this now. Arithmetic and geometric progressions. Now, what are arithmetic and geometric progressions? This is just another name for sequence. Progression, sequence, series, right? These are all the same thing. For our purposes, series does have some detail that you will study in university later on. But for our purposes, we treat all of these 3 different letters, 3 different words the same way, right? They all mean the same thing. Now, there are 2 sequences in your syllabus. In O levels, you used to have a number of different sequences. In A levels, you can only have 2 types of sequences. It's either going to be an arithmetic progression or it's going to be a geometric progression. There can't be anything else apart from these 2. Okay. What are arithmetic progressions? This is just another name for linear sequence. If you have a sequence like this in which the difference between consecutive terms is constant, we call this an arithmetic sequence. An arithmetic sequence is described by 2 things: the first term and the common difference. To be able to write down the nth term of an arithmetic sequence, we need these 2 things: the first term and the common difference. Now, the first term is obvious. Whatever is the term that's coming in the first place, that's the first term. What about the difference? Difference is calculated like this: next term minus the previous term. Next term minus the previous term. Now, you have to be a bit careful when the values are decreasing. For example, if you have 5, 2, minus 1, minus 4, minus 7, if you have a sequence that looks like this, in this case, don't just say 5 minus 2, the difference is 3. No, you have to subtract the first term from the second term. So 2 minus 5, that will be the difference. Minus 1 minus 2, that will be the difference, right? So next term minus the previous term, that's the difference. So when the terms are decreasing, the difference is going to be negative. Now, we need to know the nth term formula for an arithmetic progression and the sum formula. This is what the nth term formula for an AP for an arithmetic progression looks like. A plus n minus 1 times d. So if you have a sequence that looks like this, 5, 2, minus 1, minus 4, minus 7, and so on, and you have to find a particular term of the sequence, for example, the 50th term, what would we do in that case? We will say the value for A is 5, we input that here. The value of n is 50 in this case, we input that here. The value of d is minus 3, we input that here. And that gives us that specific term, and we get that result. If you have to write down the nth term formula for this sequence, how would you do that? Sometimes they ask you to write down the nth term formula as well. What's the nth term formula of this sequence? You would write that in terms of n, right? So you don't put any value of n there. What's the value of A? A is equal to 5 here. And then n minus 1 times difference, which is minus 3. You simplify that and you get that nth term. you can see what that turns out to be. 5 minus 3n plus 5 minus 3n plus 3, and that gives you 8 minus 3n. That's the nth term formula of the sequence, 8 minus 3n. You put n equals 1 into this, you get the first term. You put n equal to 5, you get the fifth term, and so on. Now, in the formula sheet, you have this formula given, but it's written as un. We normally use tn. That's, I think, what most of you would have used. In the formula sheet, it says un. So just understand that's the same thing as the nth term, right? Tn or un, they mean the same thing. Now, let's have a look at this example. So you could have something as simple as this. They are saying that there's a sequence that starts from 5, and the 30th term is 55. What does that mean? The value of the 30th term, T30, that is equal to 55. And what we have to do is we have to find the common difference. Now, how can we do that? We can just input values in this. T30, what would that be? Using the nth term formula, the nth term formula looks like this: a plus n minus 1 into d. You input the value for a in this, input the value of n, that is 30. In this case, d is missing. And then you just replace T30 with 155, you find the value of D from that. So you might have a specific term given, and the first term or the difference, one of those two things might be missing. You can find that like this. Now, another thing that you need to know about this is how to find sum of a specific number of terms. Now, for this, we have a sum formula. We call that Sn. That gives us sum of the first n terms of a sequence. For an arithmetic sequence, the sum formula looks like this: half n into 2a plus n minus 1 times d. That's the more common formula that we use. There's another as well. We'll talk about that. What does it stand for? Sn, it's the sum of the first n terms, starting from the first term. So for example, if we have S10, that means sum of the terms from 1, 2, 3, 4, all the way up to 10. Okay. So for instance, in this case, S3 would be these three terms added. But if you had to find, for example, S10, you can use the formula, just input values n, a, and d in this, you would get the result for for the sum of those number of terms. That's one formula. There's another one that's written like this in the formula sheet: half n into a plus l. Half n into a plus l. Now in this formula, a is the first term, L is the last term. Now there's a specific meaning that we have for this letter L here, the last term. Let's suppose we have a sequence that looks like this: 4, 10, 16, 22, and so on. It goes on like this. And we want to find the sum of the first 10 terms of the sequence. Now, if we want to use this formula, the value for n would be 10, the value for a would be 4, that's the first term. But what about L? There's no end to the sequence. It just continues like this. What's the last term going to be? The last term here basically means out of the terms that you want the sum for, what's the last term? So how many terms do you want the sum for? You want the sum for the first 10 terms. These are the first 10 terms. What's the last term in these 10 terms? That's 58. So the 10th term in this case, when you're finding sum of the first 10 terms, that's considered the last term. So we often write this formula in a slightly different way. In the formula sheet, it's written like this. In order to save yourself from confusion, you should write it like this: half n into a plus tn. So this L basically stands for the nth term, right? So if it's S10, then this is T10, the nth term. Okay, and that's how you can use this formula. Mostly, you would be using the first formula. That's what works in most cases, this formula. Sometimes the second formula is going to be more efficient when you have the last term given or when you have to find the last term. In those cases, this other formula is going to be more efficient, but otherwise, the first formula works every time as well. You can use that as well. Okay. Now, I will let you think about this example. There's one going on here. We'll have one more break and then we'll resume. Okay, let's just we'll have a break from Maghrib in about 15-20 minutes, inshallah. Just after APGP, we'll have a break. We'll have a longer break, about 25-30 minutes. 25 minutes, not 30. But you'll have to wait for that a bit, okay? All right, let's move on now. Let's see this example. It says, find the sum of all the terms between the 15th term and the 25th terms, both inclusive. So sometimes you have to find the sum of some terms in the middle of the sequence. Now, the formula that we've got is for the first n terms. Sn is for the first n terms. How do you find the sum of these terms that are in the middle somewhere? So what exactly are we looking for? We've got the sequence. We know the first term of the sequence. We know the difference of the sequence. We can find that. We want the sum of 15th to 25th term, right? 15th term all the way up to 25th term. Now, how can we use the sum formula to find this specific sum? You can think of it like this. You can say, let's find the sum of all of these 25 terms. So I've written down the terms here like this: T1, T2, T3, T4, and so on, all the way up to T25. What you can do is, one idea is you find the sum of these 25 terms. Using the formula, you can do that, right? You can find the sum of the first 25 terms using this formula. And then, since you only want the sum of 15th to 25th term, okay, you only want sum of the 15th to 25th term. You do not want the first 14 terms, right? You want the 15th term, that has to be included in the sum. But what you don't want is the first 14 terms. So what you do is you subtract from S25 S14. So S25 gave you the sum of all the terms from 1 to 25. If you subtract the sum of 1 to 14, what are you left with? You're left with 15 to 25, and that's what you want. So if you want the sum of all the terms from 15 to 25, you can use the sum formula like this. You can say find S25, subtract from that S14, not 15, S14, and that will give you the result. After that, it's fairly straightforward. You just input values in this and you get the result from that. Okay. All right, let's move on. Now, this is relatively straightforward. If you have three consecutive terms that are given for an arithmetic progression, what does that mean? How do you find the value for x here? One possibility is that you say, find the difference from these two terms and find the difference from these two terms. Since the difference has to remain constant, x minus 30 should be the same as 72 minus x here. X minus 30 should be the same as 72 minus x. So you make an equation like this, find the value of x from that. In arithmetic progression, there's another way as well, and that is the middle term is always going to be the average of the terms on the sides. So if you have one term here, 30, another term on the side, that's 72, the middle term is always going to be average of those two terms, right? So you can say x is equal to 72 plus 30 divided by 2, okay? Or you can say that the difference remains constant. Now, let's move on. Let's move on to geometric sequence. Now, this is a geometric sequence. Geometric progression or geometric sequence. Now, what about a geometric sequence? A geometric sequence is in which the ratio between consecutive terms remains constant, right? So you multiply by the same number to get the next number. In APG, in arithmetic progression, we used to either add or subtract the same number to get the next number, right? In this case, we multiply or divide by the same number to get the next number. For example, 3 times 4 is 12, 12 times 4 is 48, and so on. So the ratio in this case is 4, right? In the next case, 10 over 2 is 5, 5 over 2 is 2.5, 2.5 divided by 2 is 1.25, or in other words, we can say 10 times 0.5 is 5, 5 times 0.5 is 2.5, and so on like this, okay? Now, we write this in product form generally because the ratio is considered to be this number that you have to multiply by to get the next number. A geometric progression is described by two things, the first term and the ratio. For an AP, it was first term and difference. In this case, it's the first term and the ratio. How do you find ratio in this case? Ratio is next term divided by the previous term. So for any two consecutive terms, if you divide the next term by the previous term, you get the ratio from that. For example, in this sequence, you could do 20 divided by 80, and that will give you the ratio. That's 1/4. You could do 5/20, or you could do 1.25/5. Any of them is going to give you the ratio of the sequence. Now, this is the nth term formula for a GP. AR raised to power n minus 1. That means the first term, for example, is going to be, the first term is just A, but then the second term is going to be AR squared, AR cubed, and so on, right? And then we have the sum formula. It looks like this: A into 1 minus R raised to power n divided by 1 minus R. These are both given in the formula sheet. Just need to be able to use them. Again, this formula is for sum of the first n terms, okay? For the first n terms. Okay. Now, let's consider an example. Let's say we've got a sequence like this. The first term of the sequence is 2. How do you find the ratio? Take any two terms, divide the next term by the previous term. So minus 6 divided by 2, what's that? That's minus 3. That's the ratio of the sequence. Okay. Now, if you want to find the 15th term, for instance, just use the formula. What's the formula? The nth term formula is AR raised to power n minus 1. We just input values in that. T15, we say A is 2, R is minus 3, n is 15, and that simplifies to this number. The sum formula is like this: A into 1 minus R raised to power n divided by 1 minus R. Just input values in that, and that gives you the result. In your calculator, when you input this, be careful about negative numbers. When the ratio is negative, make sure to always put that inside brackets. So this number, for example, in the power, this is R raised to power n, right? So ratio is -3. -3, that whole thing is going to have this power 10, okay? So you have to write the negative inside the bracket like this. And now you can just put this whole thing on your calculator directly. So when you put this on your calculator, be careful, put it exactly like this. Use the fraction button. 2 multiplied by 1 minus, and then inside bracket -3 raised to power 10, and then close that bracket outside. And then in the denominator, you have 1 minus -3, that becomes 1 plus 3, and that gives you the result. Okay, so put it exactly like this in your calculator, making sure you put the negative values inside the brackets. Okay, all right. And now you can write the nth term formula as well. If you have a sequence like this, -100, -50, and so on, what's the nth term formula for this going to be? What's the first term here? The first term is -100. What about R? Ratio is not negative here. The ratio is going to be positive. When you calculate it, -50 over -100, that's 0.5. You have the value for A, you've got the value for R. If you wanted to find the nth term formula, in this formula, just input the value of A and the value for R, you will get that nth term formula. Okay. All right, let's move on. Now, you will get questions in which they'll have some scenario given, and a lot of those questions, they will have something increasing by a certain percentage, something decreasing by a certain percentage. Whenever there is a percentage increase, there's a percentage decrease, remember that's always going to be a geometric progression. This is always going to be a GP. Okay, you'll be multiplying by some number to get the next number. Now, how exactly do you get that ratio? Let's suppose they say there's a 5% increase, 5% increase. Now you know percentage change. For every next number, you're increasing the number by 5%. That has to be a geometric progression. Now, how do you find the ratio of this geometric progression? What's the way to do that? If it's a 5% increase, you say the original value would be 100%. When you add 5% to that, what do you get from that? 105%. Write 105% in decimals. That will be your ratio. Okay, 100% plus 5%, that gives you 105%. Write that in decimals. That's 1.05. That's your ratio. Let's have a look at some more examples of this. If you are increasing something by 15%, what does that mean? 100% plus 15%, that's 115%. What's the decimal for that? 115 over 100. Ratio is 1.15. If something is decreasing by 8%, that means it's 100% minus 8%, that gives you 92%. What's 92% in decimal? 0.92. If something is increasing by 140%, what does that mean? 100% plus 140%, that becomes 240%. The ratio becomes 2.4. Okay, so you can find the ratio like this. If you have the percentage increase or percentage decrease given, you see how much change is going to be from 100%, and then you find the ratio according to that. Now, this is something that you'll see a lot in the recent papers. You'll have 3 consecutive terms given for a GP, and you'll have to find something that's unknown. Now, this is a simplified version of that. If you have one number that's 15, another number that's x, another number that's 135, these are 3 consecutive terms of a geometric progression. Okay, if you had to find the value for x in this, that's the term in the middle. How do you do that? Now, one possible way of doing that would be using the nth term formula, but that becomes very complicated in some cases. I would not recommend that you do that. So that would be like this, that you say T2 is equal to, so first of all, you find the ratio. You find the ratio like this. You say ratio is x over 15, and then you say that the second term is going to be a, which is 15, into r, which is x over 15 in this case. Now that equals the second term. In this case, that does not give us anything anyway. You can find the ratio from the other one, 135 over x. So basically, the idea is that you, in this example, probably that will not work very well, that explanation. But when you have 3 consecutive terms like this, a lot of people, what they try to do is they find the second term using a times r. They try to find the third term using ar squared. Equate AR with X. Yeah, so that's what they would try to do. AR equal to X. And then they would say AR squared, that is equal to 135. And then use that to find the missing value. Now, in the more difficult questions, it will become very, very complicated. And it's very unlikely that you would end up getting the correct answer at the end, because they end up being too many variables. And you almost certainly end up doing some careless errors there. The more efficient way of doing problems like these is when you have 3 consecutive terms given in a geometric progression. You say the ratio can be calculated as this, x over 15. That's one way to calculate the ratio. The ratio can also be calculated as 135 over x. That's another way to calculate the ratio. These two are supposed to be equal to each other. So we make an equation like this. We say it's x over 15 equals 135 over x. We solve this equation, find the value of x from that. So in this case, we get 2 possible values of x, which are plus minus 45. Both of these are geometric progressions. We could have the middle term 45, it could be minus 45. If it is 45, the ratio would be 3, right? You're multiplying by 3. If it is minus 45, that means the ratio is minus 3. This is another important point. Whenever the ratio is negative in a geometric sequence, you will find that the terms alternate. One term will be positive, the next will be negative, then positive, then negative. They will always be alternating like this whenever the ratio is negative. Because when you multiply by a negative number, the sign changes, right? So it changes in every single term. So you'll have plus, minus, and so on like this. So that's how you find the missing term in problems like these. Okay, so that's the general rule that we have. If you have 3 consecutive terms, for a GP, you say B over A, that equals C over B. Okay, now that was about geometric progressions. I've already done that. That ended up being copied twice. Okay, now what about sum to infinity? That's the last major concept that we have in APGP, finding the sum to infinity of a geometric progression. Now, what is sum to infinity? It's basically sum of all the terms of a never-ending sequence. So if you have a geometric progression that looks like this, 2, 3, 4.5, 7.5, and so on, and it never ends. It continues like this. There's no end to it. Infinity means a very large number. So sum to infinity means sum of all of these terms, some of these infinite terms. Now, that looks like it doesn't make any sense, because if you were to add an infinite number of terms, the result should turn out to be infinite. That is true in some cases, because in this case, for instance, if the GP is 2, then if the first term is 2 and the ratio is 1.5, what happens is the numbers keep increasing. 2, 3, 4.5, 7.5, and it continues like this. If you were to add all of these terms, you will see that the sum turns out to be infinity, and it'll turn out to be infinity. Because the numbers keep getting bigger, these numbers are going towards infinity. So if you add all of them up, the sum is also going to be infinity. However, if you have a GP that looks like this, in which the first term, whatever it is, the next term is smaller than that in numerical terms. The next term is smaller. Then what happens is these values keep getting smaller and smaller, and eventually these values converge to zero, right? They approach zero. They become almost equal to zero. So when you have a GP that looks like this, in which the next terms are becoming smaller and smaller until you get zero at the end, in that case, the sum of all of these terms is actually a finite number. That's not infinite. Now, there's a whole background to this, how this formula comes. But now this is given in the formula sheet. A over 1 minus R. This is the sum to infinity formula. When does this sum to infinity formula work? Only when the GP is like this, that the terms are becoming smaller. The terms are becoming smaller. When does that happen? When do terms become smaller? When the ratio is between -1 and 1. The ratio is between -1 and 1. Because when you have a number that's less than 1 in numerical terms, when you multiply by that, the value becomes smaller, right? So if you have a GP that looks like this, in which the ratio is between -1 and 1, the sum to infinity is given by A over 1 minus R. If R is greater than 1, the sum formula is R before 1. You could do that. There's no as in it's not required that you write it that way. There's only one formula. You could write it two ways. This formula can be written in two ways. You can write it in this way, or you could also write it in this way: a into r raised to power n minus 1 over r minus 1. Both of these formulas are correct for any r. Okay, they're both correct for any value for it. Doesn't make any difference. No, it doesn't make any difference. They're both correct. They're both equivalent. They work for any r, negative, positive. It doesn't matter. So sometimes some teachers, what they do is they ask you to use this when the ratio is less than 1, and they ask you to use this when the ratio is greater than 1, because they don't trust that you will be dealing fine with the negative numbers. Because when you have r less than 1 here, you would end up getting, on the first formula, when r is greater than 1, you would end up getting a negative number inside. And that may make some people do careless errors, but it's not necessary. Both of these are correct. You can write this formula like this or this. They're both the same. There's no difference between these formulas. They work for r, for any value for r, apart from 1, of course. In that case, you get 0 in the denominator. That doesn't work. But otherwise, they work for any value of r. Okay? All right. Now, this is the sum to infinity formula, a over 1 minus r. This is the sum to infinity formula. Sum to infinity only exists when r is between -1 and 1. Okay? Now, this is another thing that you will find very few questions for, but it's important. You will find it more in the recent papers. Convergence of a GP. When does a sequence converge? Converge means that it approaches one fixed value, and it doesn't change after that. If you have a GP like this, in which it's becoming smaller and smaller, that means the ratio is between -1 and 1. What happens is the values keep getting smaller and smaller, and eventually they approach 0 every time. We call this in mathematical terms that the sequence converges to 0. Okay, the sequence is basically converging, it's approaching, it's becoming stable at, it's becoming almost stable at 0, right? It'll approach 0. Okay, that's what it means. It converges to that value. When does a geometric progression converge? The condition for that is the same as the condition for the sum to infinity, that the ratio is between -1 and 1. So whenever they say in the question, given that a sequence converges and then they want you to find something from that, you find the ratio, you put that ratio between -1 and +1, and you solve that inequality. Okay, and see you see whatever you get from that. So whenever a geometric progression converges, ratio is between -1 and 1. That's the condition that we've got for that. This is how the formulas are written in the formula sheet. You should be familiar with them. You should, of course, when you're done enough practice, you will start remembering the formulas anyway. But the formulas are written in the formula sheet in this format. Okay, the nth term is a plus n minus 1 times d for arithmetic progression, and these are the sum formulas. And in place of tn, they write un here. Just understand that. Okay, just give me a minute. I'll be back. Okay, so this is how the formulas are given in the formula sheet. Just be familiar with that. That in place of tn, they write un. Everything else is the same. And also for the sum to infinity, they write it in this form: modulus of r is less than 1. That's basically just the same thing as r being between -1 and +1. Okay, so that condition is the same as this. This I would recommend that you remember, because I think many of you are not familiar with this function, the modulus function. So just remember it like this, that r is between -1 and +1. Okay, all right. Let's move on. Now, let's have a look at some questions quickly. We're getting late for as well. Yeah, okay. In an AP, the sum Sn of the first n terms is given by this. Now we have the sum of the first n terms formula. So sometimes what they do is they give you the formula themselves in the question, and they ask you to find, for example, in this case, the first term and the common difference. Now, in this case, one quick way of doing this would be that this is the sum formula, 2n squared plus 8n, right? What you do is you say, you are looking for the value for A and the value for D, right? These are two values that we want to find out. Using the sum formula, we can say, let's find the sum of the first one term, first two terms, first three terms, and use that to find the values of A and D. For example, in this case, if I input n equal to 1, that should give me the sum of the first one term. That's basically just the first term. So if I input n equal to 1, I get 10 from that. So that means that the value for A is equal to 10. If I input n equal to 2 in this, what does that give me? That gives me 24. That's the sum of the first two terms, right? S2. Now, if I know the first term is 10, and the sum of the first two terms is 24, that means the first term, which is 10, plus the second term, that should equal 24. And we can find the second term from that as well. And then once we have the first term, we have the second term, we can find the difference. That turns out to be 4. This is one way to do problems like these. So when you have a formula given, you input some values of n from that, n in that, and use those values that you get to figure out whatever they've asked for. Now, in more complicated examples like this, you'll have to use another method as well. For example, in this case, they gave us that 2n squared plus 8n. That's the sum formula. They might have some constant there sometimes. They might give you something like this, 2n squared plus 8k times n. And then you have to find the value of k there as well, somehow. In those problems, you should do it another way. And that's like this. In the question, they gave us that for this arithmetic progression, it's an arithmetic progression, right? It's an AP. For this AP, the sum formula is 2n squared plus 8n, right? What's the general sum formula for an AP that looks like this? Half n into 2a plus n minus 1 into d. This is the formula that we know, this is the formula that they gave us for that particular sequence. They're both supposed to be the same, right? Because they're both sum of the first n terms of the AP formula. What we can do is we can compare both of them. How do you compare them? For comparison, we need both of them to be in the same format, right? Both of them have to be in the same format. Now, how are they going to be in the same format? We would have to simplify this. So we simplify this. At the end, we get a form that looks like this. And then we say, let's look at the coefficient of n squared that we have here. That's half d. That's the coefficient of n squared. And look at the coefficient of n that we have here. That's a minus half d. And do comparison. They gave us that it's 2n squared plus 8n. We are getting this. That means the coefficient of n squared that we have and what they have, they should be the same. And the coefficient of n that we have and what they have, they should also be the same. So we compare them, and that gives us the values of a and d like this. Okay. Now, in this case, it was much quicker and much easier to use this method, but in some problems, when it's not possible to find S1, S2 like this, because it ends up being in terms of some other constant. They might have an extra constant here in this formula. In that case, you can use the comparison method as well. You use the standard formula that's given in the formula sheet, compare that with the formula that they gave us there. Okay, so you'll often see examples, see questions in which you have something increasing or decreasing by a percentage, but you'll have scenarios for that. You'll have to interpret them. In this case, for instance, there's a prize money that's increasing by $1,000 each day. What does that mean? It's increasing by the same distance, same value. So if it was 1,000 initially, then it becomes 2,000, 3,000. That's an AP with a difference of 1,000. If the prize money is increasing by 10% each day, what does that mean? 100%, it's a GP, right? First of all, it's an increase or decrease by a percentage. What's the ratio going to be? We say 100% plus 10%, that gives us 110%. In decimals, the ratio will be 1.1. So you should be able to interpret from a scenario like this, whether it's an AP or it's a GP. If it's a percentage increase or a decrease, remember, it's always going to be a geometric progression. Now, this is a very common type of question that you will see in past papers. And that is when they give you two sequences and they say some specific terms from one sequence are equal to some other specific terms from the other sequence. And then they want you to find something that's missing. Now, in this case, they tell us that for an arithmetic progression, the first term is 8. And the first term of the AP and the first term of a GP, they are both the same. So what are they saying? The first term of the AP and the first term of the GP, they're both the same. And then they're saying fifth term of the AP and the second term of the GP, they're both the same. And then the eighth term of the AP and the third term of the GP, they're also both the same, right? We need to write down two equations to find the values of R and D somehow. Now, how you would approach these questions would be, you will write down both the sequences in two rows like this. You write down the AP and you say, okay, the first term is 8. Fifth term, we'll figure that out. And then you have the eighth term. These are the three terms that they're talking about. In the next row, you write down the three terms of the GP that you need, first, second, and third. Now, in this case, you knew that the first term is 8 for the AP. Since the GP is the same, that means that is also going to be 8, right? How do you write down the next terms now? You have the nth term formulas for AP and GP. So we have to compare the fifth term of the AP and the second term of the GP. What we can do is we can use the nth term formula of the AP and GP to write down those terms. For example, the fifth term here, what would that be? A, which is 8, plus n minus 1, that means 4, times the difference, which is unknown. So that's 8 plus 4d. Similarly, this turns out to be 8 plus 7d. And then you write the nth terms of the second and third terms of the GP as well. The formula is a raised to power n minus 1. If you know the nth, if you know the first term is 8. This would be 8 times r. This would be 8r squared. And now just compare them. make equations, you say that these two should be equal to each other and these two should be equal to each other. You get two equations, solve them simultaneously, and you get the result from that. This is something that happens a lot in recent papers. Yeah, I'm sorry, we're getting late. Just one last question. So you just compare them and you get the result. Okay. Just one last question, then we end. Okay, so you just compare them and you make equations and solve them simultaneously, you get the result. So you'll see these questions like these in recent papers a lot. Now, one last thing, and that is sometimes you will see questions involving circles and they have angles there. Remember, whenever they have a circle and they're talking something about angles, you'll always have one equation that basically says that the sum of all angles is equal to 360 degrees, or if it's in radians, 2 pi radians. It sometimes is something that you don't think of in the exam because of the stress, but the given information in the question that will tell you that will give you some information to make one equation. But then, since in this case they're talking about angles, remember, whenever they talk about angles in a circle, you can make an equation like this, that sum of all the angles, that should be 360. So in this case, for instance, we had 6 angles. So we can say S6, that should be equal to 360. I just wanted to point this out separately because you see a number of questions like this in recent papers when they have circles like this, okay? Sum of all angles should be equal to 360. And then finally, we talked about this already. They have these 3 consecutive terms of a GP. If you wanted to find the value for k in this, the most efficient way of doing this would be, you say the second term divided by the first term, the third term divided by the second term, they should be equal. So we get k plus 6 over 2k plus 3 and k over k plus 6, they should be equal to each other. And then you solve that to find the result. Okay. So this is very important. In this case, if you use the nth term formulas, that makes it much more complicated. When you have 3 consecutive terms of a GP given, you make equations like these. You say second over first should equal third over second. All right. I hope that was helpful. I'll take your questions after the break now on APGP. We will stop here for namaz and just for a general break as well. We'll come back in about 25 minutes, inshallah, at 7:40. Okay, 7:40. You can let me know if you have any questions at that point as well on APGP. We're going to be doing coordinate geometry next, and that including equation of circle. That's going to be an important part, and then hopefully we can do quadratics as well. Let's see. Okay. Okay, so let's quickly have a look at this. It says a circle is divided into 6 sectors in such a way that the angles of the sectors are in arithmetic progression. Okay. So angles are in arithmetic progression. What that means is we can say if the first angle is A, then the other 5 angles, they are going to be in an arithmetic progression. They have also given that the angle of the largest sector is 4 times the angle of the smallest sector. So if the first angle is A, then the last is supposed to be 4 times A, right? If we have written them in increasing order, if it's an arithmetic sequence and we're saying the smallest angle is the first one, and it's increasing like this, and the last one will be 4 times A. Now they're saying, given that the radius of the circle is 5 centimeters, find the perimeter of the smallest sector. Okay, we'll talk about that later. First of all, can we find the value of A from this? We've got this AP. That's what we know. We know that the sum of all of these 6 terms, what is that supposed to be? Since it's a circle, it's part of a circle, right? A circle is divided into 6 sectors. Sum of all angles in a sector in a circle is always 360 degrees, or you can say 2 pi radians. That means the sum should be 360. And now, since in this question, we know the last term, that is 4a, and we know the first term, this is that type of question in which using that second formula for sum of an AP is going to be more efficient, where we say half n into a plus l. So in place of l, I said we will be writing tn. So using that formula becomes much more efficient here. We input values in this. We put S6 equal to 360. On the right side, we put the value for n, that is 6. the value of the first term and the last term. That gives us the value for A. Once we've got the value for A, we know the angle for the first sector, and that's the sector for which we want to find the perimeter for, right? We've got the radius of the sector, we found the angle, we can find the perimeter using S equals R theta. So this is actually from a time when we had not done circular measure yet. So that's why I'm using the O-level formulas here, but you can use S equals R theta as well, or use these formulas. Both of them are fine. That will give it the result. Okay. All right, let's move on now. Okay, so next we've got coordinate geometry. Coordinate geometry, this is now a relatively straightforward one. So I'll try to be quick. So what do you need to know about coordinate geometry? Most of the stuff is O-level stuff. There's nothing that's very new. So you need to be able to find distance between 2 points. You need to remember this formula. It's not given in the formula sheet. x2 minus x1 whole squared plus y2 minus y1 whole squared, square root of that. There's a plus in the middle. Do not forget that. And these are minus signs. Okay, some people end up mixing these up. Just make sure that you get these signs right. x2 minus x1 whole squared plus y2 minus y1 whole squared and square root of that. That gives us distance between 2 points. Midpoint formula, x1 plus x2 over 2 plus y1 plus y2 over 2. That's what you need to remember. Gradient of a line y2 minus y1 over x2 minus x1, really straightforward. That's basically change in y over change in x. Now, how do you interpret the gradient? What does this gradient mean? If a line has gradient 1.25, how do you interpret that? That basically means if on the x-axis something increases by 1 unit, how much does y change? That's what the gradient represents. So if it's 1.25, what that means is if the x coordinate increases by 1 unit, the y coordinate increases by 1.25 units. That's the interpretation of this gradient. Okay. If the gradient is negative, for instance, -3, what does that mean? If x increases by 1 unit, that means y would decrease by 3 units. So it's going to be a line like this, that as you go 1 unit to the right, you go 3 units down, right? That's what a gradient of -3 means. So gradient tells you for 1 unit increase in x, how much does y change, right? That's the interpretation, that's the understanding of gradient. Okay, now lines like this have positive gradient, right? Upward sloping, these are called upward sloping line. As you go from left to right, if the line is going in the upward direction, that's positive gradient. As you go from left to right, if you're going downwards, that's negative gradient. If it's a horizontal line, the gradient of this line is 0 because there's no change in y in this case. So the numerator is going to be 0. The gradient turns out to be 0 in this case. For vertical lines, gradient is undefined, right? Because if you find the gradient of any vertical line, what happens is the change in x, there's no change in x. In the denominator, you end up getting 0. And anything over 0 is what? That's undefined. So for vertical lines, we say that the gradient is undefined. Now, some people say it's infinity. At this level, you can say that, although this is more mathematically correct, but you can also think of it for now. Don't quote me when you go to university that I taught you wrong, that it's not infinity, but for now, you can say that this is infinity, okay? That's okay. For this level, that's okay. All right, now, parallel lines have equal gradient. Parallel lines have equal gradient. So if one line has gradient m1 and the other line has gradient m2, then we say they're both going to be equal if they're parallel. Perpendicular lines, the product of gradients of perpendicular lines, that's always equal to -1. So if we have one gradient, the other is going to be negative reciprocal of that. Okay, so for instance, if you know that the gradient of one line is 4, then the other is going to be -1/4. So what you do is you change the sign and you take reciprocal. If gradient of one line is -7, for the other it's going to be +1/7, and so on. If for one line it is 5/6, for the other it's going to be -6/5. You change the sign and take reciprocal. That's what gives you the gradient of the other line if the lines are perpendicular. Okay, so gradients of perpendicular lines, they are negative reciprocals of each other. Now you need to be able to find equations of straight lines. So let's say you have this straight line that you see on the right side. We want to find the equation of this line. Equation means a line that represents every single point, an equation that represents every single point on the line. So for instance, if we say that this is the equation of the line, what that means is every single point on this line, it satisfies the equation of this line. So If you have this point 0, 3, if you input that point here, it will satisfy the equation. Every other point, you take any other point on the line, it will always satisfy this equation. And in other words, you can also say, you can find every single point on the line using this equation. How? If you input x equals 0, you get 1 point. If you input x equals 1, you get another value for y. If you input x equals to 10, you get another value of y. If you input x equals minus 51, you get another value for y. So you put different values of x, you get different values of y. All of those points are going to lie on that line. Okay, so that's the connection between that line and this equation. How do you find this equation? This is the standard form for a straight line equation, y equals mx plus c. M represents the gradient here, c represents the y-intercept. If you want to find equation of any straight line, all you have to do is you need the gradient of that line and the y-intercept. If you want to use this form, this is one possible form of straight lines. Let's take an example. If you want to find the gradient of a line that passes through 0, -3, now that's the y-intercept, right? Because the x-coordinate is 0, and x-coordinate is 0, that's the y-intercept, right? Gradient is 5. What's the equation of this line going to be? Y equals 5x minus 3, because the gradient is 5. We put 5 in place of m, and in place of c, we put -3. That's the equation of this line. Now, you won't always have the y-intercept given already. They could say something like this. You have a point, and it has a point on the line, and the gradient of the line is 1/2. Now, this point is not the y-intercept. So what do you do in this case? You say y is equal to mx plus c, and then gradient is 1/2. You input that point in this, find the value of c from that, and that gives you the equation. It turns out to be this. Okay. Then you could also have the gradient not given as well. For example, they could give you 2 points. What do you do in this case? How do you find equation? You find the gradient of the line first. Then you put that gradient in the line in the equation y equals mx plus c. Find the value of c by inputting any one of these 2 points in that equation. Once you have the value for c, just put that in y equals mx plus c form, and you get that equation. Now, this is one way to find equations of straight lines, y equals mx plus c. A lot of times in A levels, the more efficient method is going to be the other one, this other form that's called the gradient point form. It looks like this: y minus y1 equals m into x minus x1. If somebody is interested in where this comes from, so you can just have a look at this later on. This is where that form comes from, but that's the other form that you got. Y minus y1 equals m into x minus x1. You have this other form that is more efficient whenever the y-intercept is not given. How do you use this? You remember this. First of all, y minus y1 equals m into x minus x1. M in this case as well is the gradient, and x1, y1, these are basically the coordinates of any specific point, any given point on the line. So if you want to find equation of a line that passes through this point and has gradient this, we did this using the other method earlier, but now if you use this equation, y minus this form, y minus y1 equals m into x minus x1, you can write down the equation directly. You'll say y minus -5, and this is y1, this is x1, and this is m. Just input their values in this form, and you get the equation. It turns out to be y minus -5 equals half into x minus 2. Now, in a lot of questions, this is going to be acceptable as the final answer, right? They won't require you to convert it necessarily to another form. So if the person is silent about it, they don't say anything about this final form that they want, you can actually leave your answer in this form, and that will be acceptable. So that saves your time as well. If you want to convert it to the other form, you can do that. If you had 2 points, again, you find the gradient. First of all, gradient is required in this form as well. So you have to find that gradient. But once you have the gradient, what you can do is you can input that in this form along with any one of these 2 points. You can call any of them x1, y1. You can call this x1, y1. You can call this x1, y1. Just input them in this form, and you get the equation of the line. Okay, that's fairly basic stuff. So how do you decide which form to use? This is what I would recommend. If you have the y-intercept given, it's better to use y equals mx plus c. If you don't have the y-intercept given, it's more efficient to use y minus y1 equals m into x minus x1. Both of them work in every case. It's just that in some cases one is more efficient, in other cases the other is more efficient. Now, then the next thing that you need to know about in this topic is solving simultaneous equations. Now, there are multiple ways that you have for solving simultaneous equations. You have elimination, you've got substitution, and you've got two different ways of doing substitution. You can solve these equations using any method that you prefer. You can use elimination if you want. You've done that in O levels. A lot of times we just don't do it because for some reason students find it difficult. But if you want to do it, the idea is that you make one of x or y terms the same in both equations, right? So for instance, in this case, the first equation has x plus 6y, the second has minus 4x plus 3y. If we make, for instance, the y terms the same in them, how do we do that? We can multiply the second equation by 2. When we do that, that becomes minus 8x plus 6x plus 6y equals 66. Then we can just subtract these two, and that will give us an equation in terms of x. Find that value of x from that, put that in the other equation, and get that result. You could do that with y, you could do that with x as well. You could say, let's multiply x with minus 4. In fact, this first equation by minus 4 or plus 4, doesn't matter. You can multiply it by plus 4, and that gives you 4x plus 24y equals 44, and then you just add those two equations to eliminate x. That's one possible method, but mostly we will be using substitution. How does substitution work? If you have two equations like these, one equation is this, and another equation is this. Substitution is that you make one variable the subject in one equation, put that in the other equation. Generally, it's easier to make that variable the subject that does not have any coefficient with it. So for example, if you have these two equations, in the second equation, you see, with x, I don't have any coefficient. So it's going to be more efficient and easier if you make x the subject from the second equation, put that in the first equation. Why? Because that will avoid fractions. When you don't have any coefficient with a variable, when you make that the subject, you would not have any fractions. That will make it simpler for you to solve that equation, right? So that's one way to do substitution. You make x the subject here, put that in the other equation, get the value of y from that, put that in the other equation back, and get the corresponding value of x. And another way of doing substitution is that we do a lot of times as well, that we make the same variable the subject in both equations, right? That's also possible. For example, one way to solve these simultaneous equations could be that we make y the subject in both equations. So we make y the subject in the first equation, we make y the subject in the second equation, and then we just equate both of them, right? This is also substitution, but it's a slightly different way of doing substitution, because we make the same variable the subject in both equations first of all, and now we are basically saying, let's input this y value in place of this y here. So it turns out that we are just equating the two equations essentially. This is also substitution, but a slightly different way of doing this. You find the value of x from this, and then you find the corresponding value of y from that. That's how you solve simultaneous equations. Now, whenever you have two functions, whenever you have any two functions, any two graphs, and you have to find out their points of intersection, any two random graphs, how do you find points of intersection? You always find points of intersection of any two graphs by solving those functions simultaneously, right? So if you have any two graphs and you want to find the points of intersection, what you do is you solve their equations simultaneously, and that gives you the result. Okay, now sometimes what you have to do is that you're given the equation of a straight line, and you have to find the gradient of the line using that. Okay, so you're given the equation and you have to find the gradient. How do you do that? If it's an equation in this form, y equals minus 5x plus 3, then the standard form is y equals mx plus c. You compare with that and you say, in place of m, you've got minus 5, so that's the gradient. But if it is not in that form, for example, if it's minus 2y equals 7x minus 4, in this case, if you want to compare it with y equals mx plus c, then you first have to make y the subject. So you make y the subject, and that gives you minus 7 over 2x plus 2. Now, after you make y the subject, now you can compare with the standard form. In place of m, you've got minus 7 over 2. So that's the gradient of this line. Similarly, here you have minus 5x plus 2y. If you want to find the gradient of this line, what you do is you make y the subject, compare with y equals mx plus c. So the gradient turns out to be 5 over 2. You can also compare with the other form. If you have an equation like this, for instance, 5 plus 3 into minus 2 into x minus 5. If we have this equation, now converting it to y equals mx plus c might take a couple of steps. You could just directly compare it with y minus y1 equals m into x minus x1 as well, and that gives the gradient as well. Although this works every time y equals mx plus c, so if you understand this, that's going to be sufficient as well. Okay, then you have to find equations of perpendicular bisectors. Now, what is a perpendicular bisector of any 2 points. Perpendicular bisector is that it's a line that passes through the midpoint of those 2 points. So if I have 2 points like this, there is one point A here, there's another point B. Perpendicular bisector would be a line that passes through the midpoint of A and B and is perpendicular to that. So perpendicular means the angle is 90 and bisector means that it cuts in half. Okay, so you want to find the equation of a line that cuts AB in half and makes a 90 degrees with that. How do you do that? For any equation, for any straight line equation, you need two things. One, gradient, and the other a point. Okay, I think I'm getting tired now. So am I speaking too fast, by the way, or is it okay? Anyone having a problem understanding me? It's okay. All right. All right. Find the perpendicular bisector of the line joining A and B such that the coordinates are 1, 2, and -5, 7. Now, perpendicular bisector is when you have a line that makes the 90 degrees with that original line and it cuts that in half. So my chain of thought broke there. Yeah. So you want the equation of the perpendicular bisector. What you do is you want the midpoint of that line. So you use the midpoint formula to find that. And you want the gradient of that line. Now, since these lines are perpendicular, their gradients are supposed to be negative reciprocals of each other. So what we can do is we can find the gradient of AB. Gradient of AB turns out to be -5/6. So the perpendicular bisector, that gradient is going to be negative reciprocal of this. So that's 6/5. Once you have these two things, the midpoint, that's a point on that perpendicular bisector, and you've got the gradient of the perpendicular bisector. What you can do now is you can just use the form y minus y1 equals m into x minus x1, and that will give you that equation that you're looking for. Now, a lot of times people end up using point A or point B in the equation of the perpendicular bisector. You cannot do that. Perpendicular bisector is not passing through B or A, it's passing through their midpoint. So you have to use the midpoint of those 2 points for this equation. Okay, now this is important. Using vector method to find any missing point. So sometimes what happens is you are given a line, and on this line, let's say you've got 2 points. One is A here and another is B. The point B is known, but the point A is not known. You have to find that point. But what you also know is the midpoint. You know the midpoint of this line. The midpoint is 2 and 4. Now, one possible way of finding the coordinates of A is that you use the midpoint formula. That works, you can do that. But that is slightly longer. So you would say that, okay, if the coordinates of A are x and y, then x plus 5/2, that's the x coordinate of the midpoint. Y minus 3/2, that's the y coordinate of the midpoint. You equate that with 2 and 4. You get two equations from that, and you solve those two equations to find the values of x and y. That's one possibility. You can do that, and that'll work. But a more efficient way of doing this is you have this point B, and you've got the midpoint, and you have to find the point A. Now, how can you do that? You think of this in terms of vectors. You say, okay, this is the x coordinate of this point, that's 5. The midpoint has an x coordinate of 2. How many units do you have to go in order to go from 5 to 2? You have to go 3 units to the left. 3 units to the left. Now, this point is the midpoint. How far would you go further to the left to get to the point A? You'll go 3 units more. So in order to go from B to M, you have to go 3 units. So how do you go from M to A then? You go 3 units further. So 2 minus 3, that gives you -1. Similarly, for the y coordinate, you can think of it like this. You can say the y coordinate of this point is -3. Y coordinate of the midpoint is 4. How many units do you have to go in order to go from -3 to 4? 7 units. You go 7 units more to get to the y coordinate of the point A. What would that be? 4 plus 7, that turns out to be 11. Now, how will you show this working? In the exam, you'll do something like this. You'll write down one coordinate, B, the one that you know, that's 5 minus 3. Okay. And then you write down the midpoint. You write down the midpoint. Midpoint is 2 and 4. And what you're looking for is the point on the other side. How do you find that point? You see, okay, from 5 to 2, you have to go -3. In order to go from -3 to 4, you have to go +7. You go -3 more, 2 minus 3, that gives you 1. You go +7 more for y, 4 plus 7, that gives you 11. So this is often used when you have the midpoint given and the point on one side given, and you have to find the point on the other side. It's called the vector method. You can do it like this. Another case where you will have to use this method, apart from the midpoint, is when you have figures like this: a triangle, a rhombus, a parallelogram, something like this, in which the opposite sides are parallel to each other. Now, in this case, if you have one point missing, one vertex missing, and you have the other vertices given, for example, you have A given, you have B given, and you have C given, but D is unknown. How do you find the coordinates to point D? You could say, whatever is the number of units you have to go from in order to go from B to C, that's the same number of units, right, left, and up, down, that you will have to go in order to go from A to D. So from B to C, how do you go from B to C? The x coordinate of B is 12. The x coordinate of C is 14. So from 12 to 14, we have to go +2 units. So in order to go from A to D as well, we say the x coordinate of A is 5. We do +2 with that, and that gives us 7. That should be the x coordinate of the point 7. All right. Similarly, in order to go from B to C, how many units do you have to go on the y-axis? 1 to 6, that is 5 units. You go the same number of units on the y-axis in order to go from A to D as well. So you go 3 plus 5, and that gives you the y coordinate of the point D. And you can find it like this without any working, and that makes it much more efficient. Okay, so that's called the vector method. You can use it like this. Then there are some properties of diagonals of some quadrilaterals that you need to remember. These are very important. You need to memorize these because they are tested in the questions that you get. There are 3 things that you need to know about all of these quadrilaterals. Number 1, are the diagonals equal to each other? Do they meet at midpoints? As in this point where they intersect, is that the midpoint of the diagonals? And the third thing, are they perpendicular to each other or not? Now, for a square, all of these properties are true. For a square, the diagonals are equal. The diagonals meet at midpoint. That means this point M, that's the midpoint of both the diagonals. And also, they meet at right angles. This is very important. Diagonals of a square, they make right angles with each other. Okay, so the point of intersection is the midpoint. The angle between the diagonals is 90 degrees, and the diagonals are also equal. For a square, all 3 of these things are true. Now, we need to know about these for all of these quadrilaterals. After a square, we've got rhombus. For a rhombus, the diagonals are not equal. They're not equal. However, they meet at midpoints and they're perpendicular. Okay, they're not equal, but they meet at midpoints and they're perpendicular. Now, for both square and rhombus, for both a square and a rhombus, the diagonals meet at midpoints and they are perpendicular. Does that remind you of something? Diagonals are perpendicular and they meet at midpoints. That's the definition of a perpendicular bisector. So for a square and a rhombus, remember this: diagonals are perpendicular bisectors of each other. So if you know one, you can find the other. Just find the perpendicular bisector, you'll get the other diagonal from that. So diagonals of a square and the diagonals of a rhombus, they are perpendicular bisectors, right? One diagonal is perpendicular bisector of the other diagonal. That's true for both a square and a rhombus. Okay, but rhombus does not have equal diagonals. That's important. For a rectangle, the diagonals are equal. They meet at midpoints, but they are not perpendicular. They're not perpendicular. These are used in coordinate geometry questions that come with circles as well. In circles, you get kite, for instance. You sometimes get square, you get rhombus. They are used there, these properties. Okay. So diagonals are equal for a rectangle. Diagonals meet at midpoints for a rectangle, but they're not perpendicular. For a parallelogram, they're not equal. They meet at midpoints. In the previous example that we saw here, it was a parallelogram. Since they meet at midpoints, if you knew the diagonals and you were given the midpoint, for instance, you see some such questions in past papers. If you have the midpoint and you have this point B, you should know that this point of intersection of the diagonals, that's the midpoint of the diagonals. Okay, that's an important property to remember. So for a parallelogram, the diagonals meet at midpoints. However, they're not perpendicular and they are not equal as well. Now, this is very important. The kite in circle questions, you often have this kite when you have a tangent and you join that point with the radius. When you have two tangents coming from a point outside the circle, you always get this kite shape. For a kite, the diagonals are always perpendicular to each other. Diagonals are perpendicular to each other. They're not equal. They're not equal. What about meeting at midpoints? The point of intersection, this point of intersection is the midpoint of one diagonal, but it's not the midpoint of the other diagonal. So the point X here, the point of intersection of these two diagonals, it's the midpoint of AC, but it's not the midpoint of BD. So the point of intersection in case of a rhombus, in case of a kite, is midpoint of one diagonal, but not the midpoint of the other diagonal. Okay. But they are perpendicular. This property is very important that they are perpendicular to each other. For a trapezium, none of these properties is true. That the diagonals are not equal, they don't meet at midpoints, and they are not perpendicular. Now, these properties are used a lot for a parallelogram, that the diagonals are equal, for a kite that they are perpendicular and they meet at midpoints. So all the tick marks that you see here, all of them are used in past papers. You need to remember these properties. Okay. All right. So there's a line going on here. We'll have a 1 minute break and then we'll resume. Okay, let's resume. So you do get questions like on this in recent past papers, since the focus is more on circle equations. You don't get a direct question on this in recent past papers, but when you have in circles, when you have tangents and they're joined with the radius, you sometimes do get figures like rhombus, kite. You will see that in the recent past papers, but in the earlier past papers, you will see a lot of questions like these, where you have these shapes, trapezium, parallelogram, we have some point given and another point is missing. So you get a number of questions like this in past papers where you have to use those properties. Okay. What I can do is I can share this. So you'll find this in any topical worksheet. If you are interested, I can post in the WhatsApp group and I'll share this worksheet. One of my students can probably share this with you, and you can have a look at those questions. Okay. All right, let's move on. Now, this is another thing that you won't find a lot in past papers, but there is going to be some questions on this in the past papers that you will see. but since it's not very frequent, you might have missed it as well. So let's understand this as well. Sometimes what happens is they give you coordinates of a figure and they want you to find the area of that figure using those coordinates. For example, if you have a triangle that looks like this, it has these 3 points, 2, 5, 2 minus 3, and minus 4, 2. These are the vertices of this triangle. And we have to find the area of this triangle ABC. We have to find the area of this triangle ABC. Now, how do you find that? Using coordinates. Now, in 99% of the questions that you will see on this, especially when you have a triangle, you will have one side of the triangle that is either horizontal or vertical. Either horizontal or vertical. What you do is, whatever side is horizontal or vertical, you take that as the base. For example, in this triangle, we have one side that's vertical. This side, AB, this is vertical. You take that side as the base. Okay. When you take that side as the base, height is always perpendicular to the base. So height is going to be perpendicular to that like this. This is going to be height. And then you can use the area formula that gives you the result. That gives you the area of that triangle. So whichever side is horizontal or vertical, you take that side as the base. Okay. Whichever side is horizontal or vertical, you take that as the base. And then the height is going to be perpendicular to that. And then what you can do is you can find the base and the height using coordinates. How do you do that? You've got the coordinates of A, they're 2 and 5. This is 2 and minus 3. So what's the vertical distance from minus 3 to 5? That's 8 units, right? So this distance is 8. Similarly, since we know that this x coordinate is 2 at this point, and this x coordinate is minus 4, what's the height? Minus 4 to 2, that's 6 units. So it can be done in one single line. You say half into base and height. Base is 8 in this case, height is 6, and you get the area using the half into base into height formula. All right. Mostly in 99% of questions that you get like this, you can find it directly like this. So if you have this shape, for instance, you have a base that is horizontal. You have one side that is horizontal, you take that as the base. If that's the base, height is going to be perpendicular to that. In this case, the height is going to be outside the triangle, right? This is perpendicular. So you say the height, that's from 5 to 11, that's 6 units, because this y coordinate was 5, this is 11, so the height becomes 6. And the base from this point to this point, that's from minus 3 to 2, that's 5 units. So base is 5 units, height is 6, just use the formula half into base into height, and that will work. So whenever you have a triangle in which one side is either horizontal or vertical, you take that side as the base, and then the height would be perpendicular to that. Sometimes, very rarely, you could get a question in which none of the sides is either horizontal or vertical. Either horizontal or vertical. In that case, you use this method that we call the shoelace formula. I would not recommend using it in simple cases like this. That's just so much extra work. If you just use some brain, you can just find the base and the height directly, and then just use the formula. Shoelace formula ends up making you do a lot of careless errors sometimes. But this is a method that you can use when none of the sides is perpendicular. None of the sides is horizontal or vertical. Okay, none of the sides is horizontal or vertical. In that case, if you have 3 points A, B, and C, then what you do is you have this formula that we call the shoelace formula. This is the actual formula that you see here. But to remember this, we use this form. And the idea is, we say these 3 points, they have coordinates x1, y1, x2, y2, x3, y3. We write down those coordinates like this: x1, y1, x2, y2, x3, y3. And then at the end, the first point is repeated. At the end, the first point is repeated. Outside, you've got 1/2 multiplied. Okay. And then what you do is you multiply these coordinates like this. and add them up together. X1, Y2, X2, Y3, X3, Y1. This is what you get. And then you multiply the other diagonals, these, and you subtract them in the formula. So that gives you a formula that looks something like this. Then you just input those values. You have those coordinates, just input those values here in this formula, X1, Y1, X2, Y2, X3, Y3. And then just simplify this and you get the result. You have these vertical lines on the side. This is basically the modulus function. What it does is, whatever is the number inside, if the number inside turns out to be negative, you will just make that positive, right? That's all that this notation means, these vertical lines, that if the number inside is negative, you'll make that positive because area cannot be negative. Then you can use this like this. Do we multiply by 1/2? Even if it's not a triangle. So this method is actually a general method that works for any figure, for a quadrilateral, for pentagon, and so on. This works for any figure. So for a quadrilateral, for instance, you could extend like this: X1, Y1, X2, Y2, X3, Y3, X4, Y4, and then at the end, this first point is repeated. The number outside, that remains the same. That remains 1/2. Yes, that does not change. Okay. All right. So if you want to understand this in detail, can someone please share the shoelace formula video somewhere, maybe in the group or in the chat? Share the link for that, because I think some people do not know about that. So you can go through that. Okay, could we draw perpendicular bisect from P to height? Okay, let me actually come back to the question later on. Then you have area of a rhombus and a kite. Area of a rhombus or a kite. Area of a rhombus or a kite, that's given by this: half into D1 into D2. That's the formula that we've got for area of a rhombus or area of a kite, where D1 and D2 are the diagonals of that shape. For both rhombus and kite, this formula works. One way to do this would be, of course, that you break the triangle into two parts. You break the kite or rhombus into two parts. Make two triangles. For example, if you break it like this, you make two triangles, and then you can find the area of one triangle, multiply that by 2, and you get the area of the complete figure. Okay, that's one possibility. But from that, we actually get this direct formula as well that you can use if you want: half into D1 into D2. So if you know the diagonals, the area of a kite or a rhombus is given by this: half into D1 into D2. All right. Now, this is another important thing that a lot of people forget, because again, it's tested in just a few questions in the past papers, maybe 5, 6. Area between a line and x-axis, or area between two lines. Area between any line and x-axis, it is given by this formula: tan theta equals the gradient. Tan theta equals gradient. If you want to find angle between a line and the x-axis, how do you find that? You would need the gradient of that line. For example, if you have a line that has gradient 2, you can say tan theta equals 2. That gives you theta equal to 63.4. That's the angle between that line and the x-axis. Sometimes they say find the obtuse angle. Then you would just use the formula, find the angle that you get. If it turns out to be acute, you do 180 minus that, and you get the corresponding obtuse angle from that as well. All right. So that's the formula that we can use to find gradient, but as the angle between a line and x-axis. Tan theta is gradient. Okay. Now, from that method, we actually can derive another method that's called, that's basically angle between any two lines. We can generalize that. And the formula that we have is tan theta equals m1 minus m2 divided by 1 plus m2. If you want to find angle between any two lines, and you have their gradients, m1 and m2, then you can use this formula to find the angle between those two lines. Just input one gradient in place of m1, the other gradient in place of m2, and that will give you the angle that you're looking for. You need to remember these formulas. For angle between line and x-axis, tan theta equals gradient. For angle between any two lines, this is the general method that works for any two lines, where one line does not necessarily need to be the x-axis. It could be any two lines. You say tan theta is equal to m1 minus m2 divided by 1 plus m1 m2. All right. In case if you forget this formula, in the formula sheet, you have an identity written that looks something like this. Tan of a minus b. Now, if you have not done paper 3, you might not be familiar with this, but at least you can read that you have this identity given in the formula sheet. Tan a minus tan b divided by 1 plus tan a tan b. Just replace tan with m1, m2. So tan a, put m1 in place of that, tan b, put m2 in place of that, and you get that formula. Okay, so in case you forget, in the formula sheet, you will find this identity given. It actually comes from this identity. So if you forget the formula, a lot of times people end up mixing up the signs. They forget that this is minus and this is plus. How do you remember this? In case you forget, how do you remind yourself about it? Look at this identity in the formula sheet. It's written in the trigonometry page. Just replace tan a with m1 and replace this with m2. And you get that formula, tan theta equals that. Okay. All right. Then you can use this to find angle between any two lines. For example, if you have gradient of one line, that's 2/3. Gradient of another line, that's -1. Then tan theta equals m1 minus m2 divided by 1 plus m1 m2. And that will give you the result. Okay. So these are the two formulas. Tan theta equals gradient. Tan theta equals gradient. It's used for angle between any two lines. Okay, I'm sorry. Angle between a line and x-axis. Tan theta equals gradient. The first formula, and the second formula, tan theta for any two lines. Okay. Where does this come from? It comes from trigonometry. Again, that's out of the scope of this revision video. You can find the detailed video where I've explained that, but just remember these formulas. Tan theta equals gradient of line. When you have to find the angle between a line and x-axis, and for angle between any two lines, you use this other formula. Okay, that's coordinate geometry. All right, that's what you need to know about this. Apart from equation of circle, we move on to equation of circle in a while. Any quick questions before we move on to the next one? Any quick questions? I think everyone is getting tired. It's okay. It's just a month. We'll be free, inshallah. Okay. All right, good. There was a question there in the middle that I'll just quickly respond to. Perpendicular bisector from P to find height in previous question. Okay. Okay. So one of you suggesting that we find in this triangle, for instance, we find the perpendicular bisector of QR, and that will give us this height. Number one, that will become quite long. That's one problem with this, and the other problem is that it's not correct. It's wrong, right? That's actually the more major problem. Why are you assuming that this is the midpoint? You can't assume that where you make a 90 degrees here, that's going to be the midpoint. You can't make assumptions, right? So no, that would not work. But that's going to take too long anyway. Even if it was the midpoint, that will require you to find that midpoint first of all. In fact, no, that's not going to take that long. You just find the midpoint, and then you find the distance between these two lines, and then you also find the distance QR using the distance formula. Still much longer than this, and also incorrect. Again, that's the major problem. Okay, all right. So we're just saying, any side that is either horizontal or vertical in the triangle, you take that as the base. Whatever side is either horizontal or vertical, you take that side as the base of the triangle. Then height is always perpendicular to that. Height is always perpendicular to the base. So in this case, base is this yellow line. What would the height be? The perpendicular coming from the third point of the triangle to that base. So that's, in this case, it's going to be outside the triangle. So that's this length here. That will be the height. And you can find this height now. How do you do that? You know that the y coordinate at this point is 5. The y coordinate at this point is 11. What's the difference between them? That's 6. The x coordinate at this point is -3. The x coordinate at this point is -2. What's the difference between them? 5. So that's the base. Base is 5. Height is 6. And then you just input those values in the formula. If you have any side in the triangle that is vertical, you take that as the base, and the height would be perpendicular to that, like that. Is that okay? We can take any side as the base. Logically, we can take any side as the base. The formula would work. But if you take any other side as the base, finding the height would be very difficult, right? Because if you take this side as the base, finding this height is very difficult. How do you find this height? That's the problem. So we take the horizontal side as the base, because then if we know the coordinates, you just have to do plus minus to find the lengths for base and height. So that makes it much more quicker and much more easier. Make sense? Okay, all right, let's move on. Let's move on to the next part of coordinate geometry, and that's equation of circles. Please don't pray for anything like this, cancellation of exams, delay of exams. You will be regretting this later. Every year, this has been happening for the last 4 years, and your grades get affected by that, because the expected grades that you get on those missed papers, they're not very good generally. Yes. Okay, let's move on to the next one. Equation of circle. Okay, so this is also part of coordinate geometry, but this is relatively more difficult. And the concepts are not that difficult, but the questions that you get in this, they are sometimes quite tricky. All right, so what do we need to know about this? First of all, remember what the equation of a line represents. If you have an equation of a line like this, y equals 2x plus 5, what does that equation represent? This equation represents every single point on this line. Now we want something similar for a circle as well. So let's say we have a circle that looks like this. We want to find equation of the circle such that that equation represents every single point on the circumference of the circle. Okay, so the equation that we're going to find, it should represent every single point on the circumference of the circle. It would not represent points inside the circle or outside the circle. Only points on the circumference of the circle. Now, what's that equation? It looks like this: x minus a whole squared plus y minus b whole squared equals r squared. That's the standard form for the equation of a circle. You need to remember this. Coordinates of the center are a and b, and r is the radius of the circle. Just like for straight line, we have y equals mx plus c, we have y minus y1 equals m into x minus x1. For a circle, we've got the standard form: x minus a whole squared plus y minus b whole squared equals r squared. In order to write down the equation of a circle, you need two things: center and radius. For straight line, you need it gradient and a point. For circle, you need center and the radius. All right. And this equation represents every point on the circumference of the circle. Let's take an example. Let's say we want to find the equation of a circle that has radius 7 and its center is at 4 and -5. Now 4 and -5, these are going to be values of a and b. A is equal to 4 and b is equal to -5. And radius is 7, so r is equal to 7, right? All you have to do is just input values in this form. Input 4 in place of a, input 5 in place of b, and input 7 in place of r. You get that equation. This is the equation of the circle. Now, this is one form for the equation of a circle. This is the completed square form. You can also write the equation in the expanded form. So if you expand this whole thing, you get this form, this equation. This is another way to write down the equation of the circle. They can sometimes specify that they want the equation in this form. In that case, you would write the equation first in the standard form, then simplify that to get this final form. Okay, so you should be familiar with both of these forms. So that's one thing, that given the center and the radius, you should be able to write down the equation of the circle. This is not a formula. This is the standard form that you need to know about, just like y equals mx plus c, or y minus y1 equals m into x minus x1. This is not given in the formula sheet. You need to memorize this. Find the radius. So sometimes you have to do it the other way around. That you're given the equation and you have to find the radius of the circle and the coordinates of the center of the circle. How do you find that? Let's say we've got this equation. We want to find the equation of the. We want to find the radius of the circle and the coordinates of the center. We compare this with the standard form: x minus a whole squared plus y minus b whole squared, that equals r squared. Compare with that. Minus a equals 5. That means a is equal to minus 5. Minus b equals minus 6. That means b is equal to 6. And r squared equals 121. So r equals 11. What happens is you'll always just flip the sign. So this is plus 5. You flip this to get minus 5. That's the x coordinate of the center. This is minus 6. You flip the sign. That becomes plus 6. That's the y coordinate of the center. So the coordinates of the center, therefore, are minus 5 and plus 6. All right. And then the radius, what's that? Radius is going to be equal to 11. That's the square root of this number. Okay. Now, what if you have this expanded form? So sometimes they can do something like this as well, that they give you this expanded form, and then they ask you to find the radius of the circle and the center of the circle. How do you do that now? You remember the standard form. The standard form looks like this: x minus a whole squared plus y minus b whole squared equals r squared. That's the standard form. So what you do is you complete the square for this equation. So you complete the square for the x term separately. So x squared minus 18x, then you do plus 9 squared minus 9 squared, complete the square for this. Similarly, you complete the square for the y term separately, and then you convert them to the standard form. And then you can compare to find the coordinates of the center and the radius. And that's one possible way of doing this. Another possible way of finding the radius and the center of this equation is that you do the other way around. You've got this equation in expanded form. So what you do is you have the equation in this form. That's what you remember. Instead of completing the square for this, for the equation that they gave, what you do is you simplify the standard form. You expand that, and you get something like this from that: x squared plus y squared minus 2ax minus 2by plus a squared plus b squared minus r squared equal to 0. Look at the coefficients. Coefficient of x squared, that's just 1, so that does not give us anything interesting. But coefficient of x, for instance, you have minus 2a here in the equation that they gave. That was minus 18. You compare them, you get a equals to 9 from this. Compare the coefficients of y, that gives you b equals minus 6. Compare the constant, and that gives you the radius as well. Now, some people memorize this as well. If you think your memory is really good, you can do that if you want. That makes things quicker. But yeah, so this is what we can do. Dina, let me answer that at the end. Okay. So it basically comes from here. Basically, r is equal to r is equal to or a square plus b square minus r square. That equals this constant term that you've got here. Okay, you can do something like this. Then if you rearrange this, you will get that formula that you're talking about. It will always work if you use it correctly. That will always work. But I don't recommend memorizing a lot of stuff because that ends up, you end up getting something wrong in the exam. You end up forgetting some plus minus. If you're very sure about your memory that you will not forget that, then you can try to memorize those complicated formulas. But otherwise, I think this is not that complicated. You can just, either complete the square for that or expand the standard form and then do comparison. What you can remember is, apart from the radius, you can write down the coordinates of the center relatively easily. And that would be like this. If you have this expanded form, if you divide the coefficient of x by minus 2, that gives you the x coordinate of the center. If you divide the coefficient of y by minus 2, that gives you the y coordinate of the center. So Finding the coordinates of the center is pretty straightforward. You can do that directly without completing the square. You just divide these numbers, the coefficients of x and y, by -2, and you'll get the coordinates of the center directly. For radius, it's relatively more complicated. You'll have to do something like this. So in this equation, for instance, you would, first of all, divide this number by 2, square that. That's 9 squared, plus this number. So essentially the coordinates of the center, you have r squared equal to a squared plus b squared minus this constant, right? Whatever you want to call that. You can call that k or something. So minus that constant, and then you take square root of that to get the radius. If you want to remember this, you can do that. Otherwise, just do it using the base that we've just discussed. Is that okay? All right, can I move on? Okay. Then, so these are the core concepts, that the key concepts that we have in equation of circle. Okay, but along with this, you will need to know some other things as well. For example, you will need to be able to use the angle properties of circle that you've done in O levels. All of these properties, if you remember, the circle theorems, angles in the same segment are equal to each other. Angle made by diameter is 90. If a line coming from the center, it cuts a chord at midpoint, the angle made is 90 there. This property where you have two tangents coming from outside a circle, how the two tangents are equal, and some other properties that you have along with that. Angle at center is twice the angle at circumference. Cyclic quadrilateral, and tangent is perpendicular to the radius. All of these properties, you need to be able to use them. Now, I'll specifically spend some time on the properties that are used more often. This is the one of the more commonly used properties. Angle made by diameter is equal to 90. Angle made by diameter on the circumference of the circle, that's always 90. So every angle, so if this yellow line is the diameter, every angle that it makes at the circumference is 90. Not just this, the only chord that can make a 90 degrees angle on the circumference is diameter. So if you know there's any chord in a circle, any random chord, so let's say I've got this chord, and I don't know if it's the diameter or not. If I know that it makes 90 degrees at the circumference, then we know for sure that this line has to be the diameter. This is used a lot in circle equation questions. If you know that the angle at the circumference is 90, then this line definitely has to be diameter, because no other chord apart from the diameter can make 90. Okay, that's one thing. Then, so angle made by diameter on the circumference is 90. Angle made by the diameter inside the circle. So if you have a point inside the circle, let's call this alpha. This angle is always going to be greater than 90. Angle made by diameter inside the circle, that's greater than 90. Angle made by diameter outside the circle, that is less than 90. So if this is beta, this angle is less than 90. On the circumference, the diameter makes 90. Inside the circle, it makes greater than 90. Outside the circle, less than 90. Okay. All right. So that's one property that's used a lot. This one, chord coming from the center of the circle. Line coming from the center of the circle to the midpoint of a chord, it always makes a 90 degrees. And it's also true the other way around. If the angle that a chord is making at if a line coming from the center of the circle to the midpoint of a chord, okay, let me repeat. So it can be understood two ways. One, if you have a line coming from the center of the circle to the midpoint of a chord, the angle that it makes is 90. That's one thing. And the other thing is, if you know that there's a line coming from the center of the circle and the angle that it's making is 90, then that means that this point is the midpoint. So it works both ways. If you know that point is the midpoint, the angle is 90. And if the angle is 90, that point is the midpoint, right? So one basically requires the other to be true as well. Okay, the angle is 90, point is midpoint. If the point is midpoint, then the angle is 90. Now, this is again used a lot. From this property, we actually get something very useful in circle equations, and that is for every chord, for any chord that you have in a circle, for example, this chord, if you were to draw perpendicular bisector of this chord, these perpendicular bisectors will always pass through the center of the circle. Perpendicular bisector of every single chord in a circle always passes through the center. Okay, it always passes through the center. That's a property that you need to remember as well. Perpendicular bisector of every chord in a circle passes through the center of the circle. So sometimes when you have to find the center of the circle to find the equation of a circle, for that you often have to do this, that you use perpendicular bisector of a chord, right? And you say that it has to pass through the center, so you use that to find the center somehow. This is the next property that's used a lot in equation of circle problems. If you have a tangent coming from a point outside the circle, two tangents coming from a point outside the circle. So let's say you've got these two tangents coming. I'll just get rid of that so that it makes it easier to understand. We have two tangents coming. So we have a point P outside, and from that point P, we have two tangents coming that are touching the circle at 2 points. Let's say that they are Q and R. Okay. Now, these two tangents are always going to be equal to each other. PQ is going to be equal to PR. These tangents are going to be equal to each other. PQ is going to be equal to PR. But not just that, a lot of other things follow from this property as well. What are those things? Whenever you have two tangents like this, you will always make a kite figure like this. So you will join the radii here as well. So you'll join that point with the center, you'll join this point with the center. And you get a figure like this. Since tangent and radius, they're perpendicular to each other, you've got a 90 degrees angle here, you've got a 90 degrees angle here. And that means this figure that you get, OQPR, this is a kite, because these are two radius. These radii are equal to each other. The tangents are equal. And that's the definition of a kite. The adjacent sides are equal. It's a quadrilateral having equal adjacent sides. So that's a kite. Now, all the properties of kite apply here as well. What are those properties? If I were to divide this into two parts like this, these two triangles are congruent. And the angles that we get here, if this angle is X, then this angle is also X. If this angle is Y, then this angle is also Y. These angles are going to be equal to each other. These are going to be congruent triangles. And if I make the other diagonal of this kite like this, then it's a kite. Diagonals of a kite meet at 90 degrees. This angle here is also going to be 90 degrees. Okay, this angle here is also going to be 90 degrees. So all of these things follow from this one property. All right. This is something that you have to use sometimes as well. And then finally, this is another commonly used one. Radius perpendicular to tangent. That's fairly straightforward. Radius and tangent, they are perpendicular to each other. Okay. Now, if you have 3 points given on the circumference of a circle. So let's say we have the circle and we know 3 points on the circumference of the circle. What are those 3 points? Points A, B, and C. A, B, and C. And we want to figure out the equation of the circle. Now, how do you find the equation of the circle? Equation of a circle needs two things: center and radius, right? These are the two things that we need to be able to write down the equation of a circle: center and the radius. Now, how do you find the center? If you can find the center, you can find the radius easily after that. For finding the center, we use that property. We say, let's make any two chords. Let's make chord AB. Center should lie on the perpendicular bisector of this. So center should lie on the perpendicular bisector of this chord. Make another chord. You can make AC or BC. Let's make BC. The perpendicular bisector of BC is also going to pass through the center of the circle. And now what you can do is, once you find these two perpendicular bisectors, you can solve them simultaneously, and that is going to give you the coordinates of the center. Okay. Once you have the center, then you can find the distance of the center from either A or B or C, and that will give you the radius. And you can write down the equation of the circle. So if you have points given on the circumference and you want to find out the equation of the circle, what you do is you make any two chords, find their perpendicular bisectors equations, solve them simultaneously, and that will give you the coordinates of the center. All right. So this is the summary of that. You can have a look at that, take a picture of this. We'll have this in the notes as well. If you want to find the center, find perpendicular bisector of AB, perpendicular bisector of BC. Since we know that perpendicular bisector of every chord passes through the center, then that is going to be the point of intersection of these two perpendicular bisectors. We solve these two equations simultaneously, and that gives us the center. Once we have the center, we can find the radius by finding distance of O from any of those points. Okay. Cannot assume that midpoint of any of these chords is the center. These are not diameters. Okay. All right. Let's take some examples of this now. Now these are difficult questions. Some of these, not all. The point A has coordinates 1, 5, and the line L has a gradient -2/3, and it passes through the point A. There's a circle that has center at 511, and its radius is under root of 52. So we have a point A with these coordinates. We have a point. We have the line L that is gradient this, and it passes through A. And we're given some information about the center and the radius. We need to show that line L is a tangent to the circle. How do we show that line L? How do we show that line L is a tangent to the circle? In order to prove that a line is a tangent to a circle, we need to prove two things. One, that line is perpendicular to the radius at that point, and it touches the circle at some point. Okay. Now, let me repeat. The question says, show that L is the tangent to the circle at the point A. The point A is 1, 5. Now, how do we prove that? We have to prove two things here. Number one, the point A lies on the circle, first of all. We don't know that. It's not given that point A lies on the circle. So if line L is a tangent at the point A, we will need to prove that A lies on the circumference. How can we do that? We can input that in the equation of the circle. If the equation of the circle is satisfied, that means the point A lies on the circumference. That's one condition for it being a tangent. The second thing is that the line OA, this radius is perpendicular to the tangent, right? Radius is perpendicular to the tangent. How do you do that? You find the gradient of OA, you find the gradient of this line L. If they are negative reciprocal of each other, that necessarily means that they are perpendicular to each other. When both of these conditions are met, since tangent is perpendicular to radius, we can say line L is a tangent to the circle. So in order to prove that line is a tangent to a circle, we have to show two things. One, the point lies on the midpoint, and the point lies on the circumference. And number two, that it makes a 90 degrees angle there. Yes, so that's another idea. Another idea could be that you find the equation of the line. Find the equation of the line. We have a point, we have the gradient, we can write down the equation of the circle as well. If the line is a tangent to the circle, you can find the discriminant. You'll have to write down the equations of both of them first, then start solving them simultaneously, like put the y value from the line in this equation. So for example, in this case, the equation of the line is going to be y minus 5 equals -2/3 into x minus 1. You make y the subject from this. Y equals -2/3x plus 2/3 plus 5. That will, I think, be 17/3. You put this value in this equation of circle, and then you say, let's find b square minus 4ac. If b square minus 4ac turns out to be equal to 0, then that means that the line is a tangent to the circle. That could also be used here, although that will be slightly longer, but you can do that as well. Okay, so that's one thing. How do you prove that a line is a tangent in the circle, these are the two conditions that have to be met. The point has to lie on the circumference and it should be perpendicular. Both of them have to be shown in order to in order for this to be a complete proof. Then it says find the equation of the other circle that has radius under root 52, for which line L is also a tangent at that same point. So we have another line L. So we have the same line L, and now they're saying this line L is also a tangent to another circle. Where would that other circle be? That other circle is going to be on the other side of the line like this. Then this would be a tangent. How do you find the equation of the circle now? The question said it's the same radius. Okay, same radius. So it's the same size circle. We know the radius. How do you find the center now? You can use the vector method. You can say, we know the coordinates of the center of the first circle. We know this point A. The point A will be the midpoint of these two circles. We can use the vector method to find the center of the other circle and then use the standard form for the equation of a circle to write down our final equation. Okay? This is the same method that we use when sometimes they say, find the equation of another circle that is a reflection of this first circle in the line L. So if you had to find the equation of a circle that's a reflection of that first circle in the line L, we do exactly the same thing for that. If L is the line of reflection, we say the radius is going to be the same. The radius is going to be the same. And then since A is going to be the midpoint of the centers, we can use the vector method or the midpoint formula to find the center of the other circle, right? And then you can write down the equation. All right. Now, sometimes you have to prove that there's a point that is outside the circle. How do you do that? So there's this point. We have to prove that this point lies outside the circle. This is the equation of the circle. How can we do that? We know that the radius of the circle is 10, square root of 100. Find the distance from the center to this point. From the center of the circle to the points. What's the center of the circle? Center of the circle is 8 and 4. If the distance from the center of the circle is more than the radius, then that necessarily means that point is outside the circle, right? Because if you have a circle, then if the radius is 10, if some point is more than 10 units away from the radius, from the center, then it has to be outside the circle, right? So that's a common question that you see in past papers as well. To prove that a point lies outside the circle or inside the circle, that's what you do. You find the radius and find the distance of that point from the center and compare them. If the distance is less than the radius, it lies inside. If the distance is more than the radius, the point lies outside. If the distance is equal to the radius, then that point lies on the circumference. All right. This is a good question. You can look at the working for the rest of the question here. But let's move on to this now. So we are given 3 points that lie on the circumference of a circle, right? We have 3 points, 7, 1, 7, 9, and 1, 9. And we want to find the equation of the circle. 3 points on the circumference. How do you find the equation of that? Using that method that we learned, we could do that we find the perpendicular bisectors of any 2 chords. We can make chords ourselves, right? Even if they're not given there, we can make chords ourselves, right? So if we have a point A and we have a point B, we can make a chord. We can just join those points to make a chord. Make 2 chords, find perpendicular bisectors of each of them, solve them simultaneously, you'll get the center. However, in a lot of questions, it's often going to be much easier than that. How? This is where you'll understand why it is important to draw good diagrams in the circle equation questions. Always draw diagrams whenever you have a circle equation question. In this case, if you were to draw a circle and mark these 3 points, how will these 3 points look like? One point is 7, 1, another point is 7, 9, another point is 1, 9. 7 and 7. These 2 points have the same x coordinate. That means they're going to be on the same vertical line here, right? Because the x coordinates are the same. So if the x coordinate is 7 here, if point A is here, point B is going to be here on the same vertical line. Similarly, the point C and point B, they have the same y coordinates. This is 9 and this is also 9. That means if there's some point at which the y coordinate is 9, then B and C are on the same horizontal line. What does that tell us? That tells us that in this case, the angle that we're getting at the point B, what's that angle? That angle is 90 degrees. So this angle here is 90 degrees. Why? Because one line is horizontal and the other is vertical. Between horizontal and vertical, we've got a right angle. Now, if that's a right angle, does that remind you of something? 90 degrees on the circumference. What does that mean? That necessarily means that this line here, the line AC, that is going to be the diameter. That has to be the diameter. Okay. Now, if that's the diameter, finding the center becomes so much easier. Just find the midpoint of A and C, and that will give you the diameter. That will give you the center's coordinates. Now, that only works in this case because we have figured out that AC is the diameter. If it was not the diameter, then we could not do that, right? Because center is not the midpoint of every chord. It's only the midpoint of diameter. So since in this case, we know that this is going to be diameter because that angle is 90 and only diameter can make 90 degrees on the circumference. That means that the line AC is the diameter, and the midpoint of that is going to give us the coordinates of the center. And then once we have the center, we can find the radius and write down the equation of the circle from that. Okay, all right. Now, which part do I want to cover for this? The last part. Yeah, in this case. So we have this situation. So I'm not going to go through the whole question. You can have a look at this working later on in your own time. This last part, it says point R lies on the positive y-axis. The point R, there's some point R. So, okay, so let me give you some context. So we have an equation of a circle that's given. So that circle looks like this. We have found the center's coordinates and the radius coordinates, all right? And then in the second part, we have showed that PQ is the diameter of C. So we have shown that PQ, P and Q, this is point P here, and this is point Q. If you join P and Q, that's the diameter of the circle. Okay. Now they're saying the point R lies on the positive y-axis. The point R lies on the positive y-axis, and the angle PRQ is equal to 90 degrees. The angle PRQ is equal to 90 degrees. Okay. Find the coordinates of that point R. How can we do that? How can we find the coordinates of the point R? This is the only information that we're given. The point R lies on the positive y-axis, and the angle PRQ is equal to 90 degrees. Okay. Now, it lies on the y-axis, so it has to be on this y-axis. But it lies on the positive y-axis. That means it has to be on the positive side. That means only in this part. It has to be somewhere here. Now, where exactly is it going to be? How do you find that point R? We are given that angle PRQ is 90 degrees. Now, the line PQ, we know that that is the diameter of the circle. This line is the diameter of the circle. We have proved that in the previous part. Now, if the angle at R that this line is making is equal to 90 degrees, and this line is diameter, then that necessarily means that the point R has to be on the circumference. Earlier we said it could be anywhere on this y-axis. But then since the angle is 90 and PQ is diameter, that point R necessarily has to be this point here, because only then the angle can be equal to 90 degrees using that property that only diameter can make a 90 degrees on the circumference. So that this point has to lie on the circumference. So this is that point R. Now we can find this point R because now we know that it lies on the y-axis. That means its x coordinate is 0, and it also lies on the circumference of the circle. So all we have to do is in the equation of the circle, put x equal to 0, and that gives us two y values. We consider the one that's positive because it's above the x-axis, and that's the point that we were looking for y equals to. So if we know that a diameter is making 90 degrees with some point, that point necessarily has to be on the circumference. It can't be outside or inside. All right. So using that, we've spotted that point R, and then we found its coordinates. Now this is something that has happened the first time in a very recent paper. I think this is March 2025. We were doing it the other day. So you have to, we normally study this in complex numbers in paper 3, but it turns out that you need to know this here as well now. If you have a circle, and it has some center, and there's a point outside the circle, let's say there's a point here. Let's call that point X. If we want to find out what's the smallest distance or the greatest distance from the point X to any point on the circumference, how do you find that? So the point X, its shortest distance to any point on the circle. Is this the shortest distance? It's not. Where is the shortest distance going to be? Somewhere around here, right? Somewhere around here. But what exact point is this? This point is, if you were to extend this line up to the center, then the point where this line cuts the circle, this is the shortest distance between this point and the circumference. Okay. And if they ask you for the longest distance, for the maximum possible distance, what happens in that case? The maximum possible distance from that point to any point on the circumference, that is going to be when you go on the other side of the circle. Now, where exactly? That would be when you pass through the center of the circle and reach the other side of the circle. That will give you the greatest possible distance. Let me show that to you here. The greatest possible distance would be if you were to pass through the center of the circle and reach a point on the other side of the circle. This distance is going to be the greatest distance between the point and the circumference of the circle. Okay. So from point to a circle, the shortest distance and the longest distance, they always come when you join that point with the center. Where it cuts the circle first, that's the shortest distance. When it cuts the circle on the other side, that's the greatest distance. Okay, this is the concept that's used in a recent paper. The most recent paper, March 2025. You can have a look at this working of the working of this question. It uses that concept. Okay, so that's something that you need to know. And then finally, the concept of discriminant. The concept of discriminant. The concept of discriminant is also used in circle equations sometimes. How exactly? You have a circle and you have a line, and they say the line is a tangent to the circle at the point P. Okay? Line is a tangent to the circle. If you were to solve these equations simultaneously, you would get a quadratic equation from that. Since you can get a quadratic equation from that, and you are given that the line is a tangent to the circle, that means b square minus 4ac, that is going to be equal to 0. So what you do here is you equate these two equations, or start solving them simultaneously. This is the equation of the circle, this is the equation of the line. We put y equals half x plus 6 in the equation of the circle. Simplify this, you get a quadratic equation from that. And then, since we have a tangent, that means they are only going to have one point of intersection, one point where they meet each other. When we convert it to a standard form, ax squared plus bx plus c equal to 0, then we put b square minus 4ac equal to 0. So discriminant can be used with circles sometimes as well. Just be wary of that, be aware of that. And then you can find the values of a from that. All right, so that's how you would deal with circle equation problems. Its questions are difficult, require a lot of practice. Make sure that you do that practice, because in terms of concepts, the standard concepts, there isn't much, but in questions, they make you think a lot. Now, what's the logic of this? The logic of the shortest distance? Remember, shortest distance between a point and a line, what's that? That's always the perpendicular distance, right? So here as well, we basically are looking for the perpendicular distance from this point to the circle. Now, where will the perpendicular be made? This is the radius. If you draw a tangent here, that would look like this. That means this line and this line, they're perpendicular to each other. So the direction of the circle and the direction of this line, they are perpendicular to each other. So we're kind of thinking of the perpendicular distance, right? So that's where it comes from. Okay, so that's about equation of circle. If you have any questions now, I will answer the questions quickly, and then we have a short break. I'm sorry for making this too long for you. I'm very aware that your generation unfortunately has very short attention spans, and I've made you sit here for like so long. It's the same with us as well, by the way, by now. But yeah, I'm sorry about that. We don't have a choice, unfortunately. We'll have to extend it. So you have the recording available as well. If you are not able to focus, then you can keep attending and try to understand as much as you're able to. But then you can go through the recording as well. Okay, all right. It's the normal to the center. Normal to the center. Yeah, you can normal to the circle. Yes, you can say that normal to the circle at that point. Abdul Hadi, no irrelevant talk, please. We're already late. We don't want to indulge in that. Okay, let's move on. Discriminant. Okay, we already answered that. Midpoint formula, yes. Walaikum assalam. So I answered that as well. I think that if it does not have a chord, we can make a chord ourselves, right? Abdul Hadi, did you understand that when I explained that? I think that was right here. Quadratics. We'll just do quadratics, and that's it for today. Then the rest tomorrow, where I will again make you sit for long hours. Okay, good. All right. So let's have recording for today's session. It will not be posted right now. After tomorrow's class, by tomorrow night, inshallah. By tomorrow night. Tonight is going to be difficult. I will try if I can do that. Okay. What I'll do is I will make the recording available. You need to have your email addresses. Notes I'll share right away. You need to have your email addresses working. The ones that you have in the registration form, they need to be working, and you will get access to that. In fact, for now, I will just give you access, and then the email will have to be working after tomorrow at least. I might not restrict that for now for you. All right, so I think we're done with the questions then. Okay, at this point, so we basically had to find the center of the circle. We learned above that center of a circle, it lies on perpendicular bisector of every chord. So any chord that you have in a circle, for example, you have chord AB, this chord AB. If you draw perpendicular bisector of that, it has to pass through the center. You have another chord BC. If you draw perpendicular bisector of that, that also has to pass through the center. Now, both of these lines are passing through the center. So that means their point of intersection is going to be the center. So you just solve them simultaneously, and you get the coordinates of the center from that. Does that make sense? All right. So I need some break now. Maybe around 13 minutes. Let's resume around 9:30, inshallah. Okay, everyone. So let's begin with this. Quadratics. This is the next one that we're doing now. Let's begin with this. So first of all, there are some concepts that you already should know from O-levels, some very basic stuff like solving quadratic equations. So you can solve quadratic equations using factorization, using, that's the middle term breaking thing, right? Or the quadratic formula. Solving equations using completing square, that's not necessary for you to know. But quadratic formula and factorization, you should know both of these methods. So I think you already know how factorization works. I'm not going to spend time on that. For instance, in this case, 2 into -4, that gives you -8. So you think about the factors of 8 that, when subtracted, give you 7 somehow. So in this case, that's 8 and -1, and that gives you 7. You break the middle term like this. This middle term basically gets split into two parts. So we break the middle term, and then we factorize whatever we can from the first two terms and from the second two terms, and we get the result from that. Now, at this point, this is something that you must understand. You have two things multiplying. When you have two things multiplying and the result is equal to 0, that means necessarily either the first thing is equal to 0 or the second thing is equal to 0. When you have a product, the result can only be 0 when at least one of those expressions is equal to 0. Right? So either the first is 0 or the second is 0. Compare that with an equation like this: 2x minus 1 into x plus 4 equals 2. Now, this is not true. This is not correct. If you do it like this, that you say either 2x minus 1 is equal to 2 or x plus 4 is equal to 2, that would be incorrect. That would not make sense. It only makes sense when you have 0 on the right side, because 2 could come from any other combination as well. It's not necessary that if the product is equal to 2, then 2x minus 1 is equal to 2 or x plus 4 is equal to 2. Not necessarily, because we could have 2 when we multiply, for instance, 0.5 and 4. That also gives us 2. It's not necessary that any of them has to be equal to 2. When it's 0 on the other side, then it's necessary. You can't get a product of 0 when at least one of those numbers is equal to 0. Right? So that's why we put each expression equal to 0 in those questions separately like this. How do you solve an equation like this? You would have to simplify this, take 2 to the other side, solve it as a normal quadratic, and that would work. All right. Now, when you are factorizing, be careful. Sometimes what happens is when you take wrong factors inside the bracket, you end up getting different signs. Don't forcefully make them the same. Okay, let's just make the second one x plus 2 as well. Don't do that. That basically is a sign that you're doing something wrong. If the expressions inside bracket, they turn out to be different. Okay, so how do you solve this equation then if factorization does not work? You have another method, that's quadratic formula. You take everything to one side, and then if something cannot be factorized, in this case, for instance, you cannot factorize this, you use the quadratic formula. This is what the quadratic formula looks like. It's given in the formula sheet as well: minus b plus minus square root of b square minus 4ac divided by 2a. You know how this works. The first term is a, this is b, this is c. Just input values and you get the result. Now, when you're solving equations when you're solving any quadratic equations, it's necessary to show the working for that. You cannot write down answers directly. You will not get marks for that. You will not even get marks for the answer, even if that's right, if you're not showing the method. Okay, so showing the method is important. If you're using the quadratic formula, at least show this particular step where you input the values in the quadratic formula. Then you can write down the answer after that. But if you write down the answer without showing this step, you get 0 marks for that part. Okay, you don't get any marks for that. So make sure that you show at least this step when you are solving using quadratic formula, and at least the factorization part, at least this step when you are solving something using factorization. Okay, this is important. Okay, so that's how we solve quadratic equations. Now, what exactly do these solutions represent? So we solve this equation: 2x squared plus 7x minus 6 equal to 0. We got two values of x equals 0.712, x equals this. What do these values represent? These values represent the x-intercept. These values represent x-intercept of x-intercepts of this function, right? The values where the graph of this function, the function on the left side that cuts the x-axis. Why is that? Because this graph that I have, this graph is y equals this, right? Y equals this. When we input y equal to 0, we get this on the right side. Now, when is y 0? When y is 0, we have the x-axis. Right? That's the equation for the x-axis, y equals 0. So when we have an equation like this, when we solve this, the solutions of that equation that represent the x-intercepts of this function that is there on the left side. Okay. Now, you need to know how to sketch graphs of quadratic functions. There are two shapes that you can have. You can either have a U shape or an N shape. The first shape or the second shape, smiley face and sad face, however you want to remember that. How do you get each of these shapes? If the coefficient of x squared is positive, if it's positive, you get the first shape. If the coefficient of x squared is negative, you get this second shape, the n shape. Okay. Now there are some properties of this graph that you need to know about. It's called parabola. You should know that name. It's symmetric about the center of the curve. So if you draw a line here like this, it's the line of reflection of this curve. So the graph is symmetric about this vertical line. And this point here, this is the turning point of this line. We can call this the minimum point in the first case, and this is the maximum point in the second case. There are multiple names that you have for this point that, again, you should be familiar with. You can call this point turning point, you can call this vertex, and in differentiation later on, you will also be calling the same point stationary point, right? So these are different names of the same point that you should know about. Now, on one side of this quadratic function, on one side of this quadratic function, the function is going to be decreasing, and on the other side, the function is going to be increasing. For example, in the first case, if it's a U-shaped graph, on the left side, you see, the graph is going in the downward direction. As you go from left to right, the graph is going downwards. So if you think about the gradient of this graph is negative. If the gradient is negative, we call this a decreasing function. And if the gradient is positive, we call this an increasing function, right? Again, we'll do this in differentiation later on as well. Sometimes you get this in quadratics too. On the right side, this is an increasing function. Okay. For the other curve, on the left side, the graph is going upwards, so gradient is positive. On this side, the curve is increasing. On the right side, when it's going down, the curve is decreasing because the gradient is negative on that side. So you need to know about these properties of these graphs. Also, this constant that you have here, the c, that is the y-intercept of this graph. That's true for all polynomials, for cubic as well. Whatever is the constant value, that's the y-intercept of the graph. How do you find turning point of a quadratic function? If you just need to find the turning point and there's nothing else that you need, you don't need a specific form as such. In that case, what you do is you say, let's use the formula x equals minus b over 2a. This is the formula that you have to find the x coordinate of the turning point of a quadratic function. X equals minus b over 2a. If you say this is a and this is b, you can use this formula minus b over 2a, and that gives you the x coordinate of the turning point of this function. Okay, how do you find the corresponding y coordinate? You put this value of x, for example, in this case, we got this, put this value of back in the function, value of x back in the function, and that gives the corresponding y coordinate, and that's the turning point of this function. Okay, it comes from the quadratic formula. If you forget this, just think of the quadratic formula. In the quadratic formula, just get rid of this part, and that's minus b over 2a. That's actually where this comes from. That's the x coordinate of the turning point of a quadratic function, right? That's the quickest way of finding this, apart from differentiation. That also works the same way, similar way, as in the same number of steps. That's how you can do that. Now, there's another method that you need to know. That's completing the square. Sometimes they will specifically ask you to complete the square for a function. Now, how will that work? Now, this is the standard method that most of you would probably be familiar with for completing the square. Let me go through this first. So one possibility is, if you have a function that looks like this and you want to complete the square for this, complete the square means you want something that looks like this: a into x minus h whole square plus k. Now, the signs could be different here. It could be plus here, it could be minus here, it could be plus here, it could be minus here. They could use different letters here. They could use, b and c here in place of h and k, but that's roughly what the form is going to look like. That's in fact the standard form for the completed square form. Now, how do you convert this function to this form? That's the question, right? Now, this is one way to do it. Whatever is the coefficient of x squared, you take that common outside. You have to make that coefficient 1 first of all. You take that common outside. So you take 2 common. And then what you do is the coefficient of x, after you've taken 2 common outside, you divide this number by 2. 7 over 2 divided by 2, what does that give you? That gives you 7 over 4. Now you will square that number. You'll square that number, and both add that inside the bracket and also subtract that inside the bracket. Okay, so this is a fraction that makes it a bit more complicated. If it was, for instance, inside, if it was 8x, what you would do would be, you would say, let's add 4 squared and also subtract 4 squared inside bracket, and that will give you the perfect square. But a lot of times you get fractions like this as well. You should know how to do that. So yeah, if you have 7/2, you divide that by 2, square that, and you add that number here and also subtract that number inside the bracket. And now these first three terms, they give you a perfect square. From the first term, you take just x. From the second term, you take the sign. And from the third term, you take this number that is inside. And that gives you this perfect square, x plus 7/4 whole squared. And then outside, you've got this left. You simplify this. And then at the end, what you do is you multiply this number 2 inside the bracket. And that gives you the final result in that completed square form. This actually comes from these identities. Where are they? Do they have them here anywhere? No. So this process basically comes from those identities that you have: a squared plus 2ab plus b squared. That is a plus b whole squared, and a squared minus 2ab plus b squared. That's a minus b whole squared. Right? That's where it comes from. That's the logic behind it. But that's what you need to remember now. If you want to use this method, that's what you do. You take the coefficient of x per common outside, and then you divide the coefficient of x by 2, square that, both add and subtract that inside the bracket, and then you get a perfect square from these first three terms, and then you simplify everything, and you get that result. Now, this is the standard form that we've got, a into x minus h whole square plus k, right? Now, in this form, h and k are the coordinates of the turning point of the function. So in this case, for instance, if you've got this completed square form, this form here, then what's the turning point from this form? You would compare with the standard form. In the standard form, you've got minus h. You'll need to remember this. You should remember this form. X minus h whole square plus k. Compare these numbers, this number and this number. Minus h equals 7/4. That gives you h equals minus 7/4. Compare the numbers outside. That's minus 81/8 and plus k. The value of k turns out to be minus 81/8. If it's the standard form like this, all you have to do is change the sign of this number. That becomes minus 7/4. Keep this sign the same. That's minus 81/8. And that gives you that turning point. So using this completed square form, what you can do is you can find the turning points as well. However, if you just want to find the turning point and they've not asked you for a specific form, in that case, minus b/2 is much quicker. But if you have already converted something to this form, then you can write down the turning point directly from this form, flip the sign, and this remains the same. These are going to be the coordinates of the turning point if it is the standard form. If it is the standard form, this is one way of completing the square. Another way of completing the square is using this method, which I think is much easier, much quicker when you have more complicated expression like this. For example, when you have fractions, in these cases, this other method is much quicker. But since a lot of students have learned that first method at O-levels, they don't trust me on this for some reason, and they still stick to that. So a lot of people, they find learning new things difficult. But think about this. If you had that same expression, 2x squared plus 7x minus 4, you want to convert this to the standard form, a into x minus h, the completed square form, right? What you can do is you can mix up those two methods that we have learned. Remember what the standard form is. The standard form of a complete square function, it's a into x minus h whole square plus k. A standard completed square form. Now in this form, you know that h and k are the turning points, the coordinates of the turning point. If you remember this form, what you can do is you can find the turning point using minus b/2a. So what I've done is I've used the formula minus b/2a to find the turning point. It turns out that the x coordinate of the coordinate of the turning point, that is minus 7/4, and the y coordinate is minus 81/8. So now we've got the turning point. Once we have the turning point, we know this is the value for h, this is the value for k. Just input those values here. A is going to be the same as this. So a was 2 here. That remains the same. A is 2. And then you just input the values of h and k there, and you get that completed square form, and that's it. All right, that's another alternative that you have for this form, for converting something to that form that you can also use. Now you can use whatever you prefer. This is another possibility, however. All right. Okay. Now, if you have the completed square form, from that, how do you write down the coordinates of the turning point? We discussed that. You flip the sign in the middle. For the x coordinate, you flip the sign, it becomes -3. For the y coordinate, you just keep the sign, that's -8. Okay. And you can look at it for the rest of these expressions. If you have x plus 11 here, and this is 4, what does this become? -11 and 4. Whether it's a maximum or a minimum is decided by the number outside. If this is negative, then that's a maximum because we know that's going to be an N-shaped curve. If there's a positive number outside, then that means it's going to be a minimum because that shape is going to be a U-shaped curve like this. Now, sometimes you'll end up getting something like this. 2 into x minus 4 whole squared. What about this? What's the turning point of this? There's no number outside. Since there's no number outside, we assume that that's 0. So the x coordinate is 4 and the y coordinate is 0. If you have this, 5 into x squared minus 3, what about this? What's the turning point of this function? You can think of it as like this. You can say this is 5 into x minus 0 whole squared minus 3. The number inside is 0. So the x coordinate of the turning point, that's going to be 0. And the y coordinate is the number outside, that's -3. That's the turning point. Okay. And sometimes you get a slightly different completed square form. That's not the standard form. For example, you'll get something like this. 4x minus 8 whole squared plus 7. Now, what's the turning point of this function? For this function, we are not just going to say that the turning point is 8 and 7. That's not correct because this is not standard completed square form. We've got this 4 inside as well. In the standard form, we can't have any coefficient of x here. So in this case, the x coordinate is not going to be 7. The x coordinate is going to be found by equating this thing to 0. 4x minus 8 equal to 0. And that gives us x equals 8 over 4, which is 2. The x coordinate is going to be 2 here. And the y coordinate is going to be 7. So the turning point is actually going to be 2 and 7. That's going to be the turning point, 2 and 7. Okay. So the general rule is whatever is inside, you put that equal to 0. That gives you the x coordinate of the turning point. And the number outside, that's going to be the y coordinate. That works in this case as well. For example, for x plus 11, if you put that equal to 0, you get x equals -11. So that's the x coordinate, right? If you have 4x minus 8, you put this equal to 0, you get x equals 2. That's the x coordinate, the coordinate of the turning point. For the y coordinate, it remains the same as the number outside. That remains 7. Okay, so that's how you complete the square. Now you've got the concept of discriminant. So for any quadratic function, we have something that we call discriminant, b square minus 4ac. B square minus 4ac. You're saying something? Okay. We'll discuss that. That's coming. Okay. X square minus 7x plus 12. Let's say we got a function like this. If we solve this equation, how many roots do you get from this? You get 2 different roots. If you solve now this equation, you solve 2 equal roots. If you solve another equation, you get no real roots. What's the difference between all of these 3 equations? I got 3 equations here. These are the 3 functions that they are: the blue one, the green one, and the orange one. I solved all of them, and it turned out that one of them gave me 2 different solutions. One of them gave me 2 equal solutions, and the other one, the last one, gave no real solutions. What's different in all of them? Look at this working. In one of them, inside the square root, I'm getting a positive number. In the second, I'm getting 0. When I have a positive number, I get one value with plus that and another value with minus that. So I get 2 different roots in this case. When I have 0 inside the square root, I get 6 plus 0 and 6 minus 0. That does not change anything. Both these points turn out to be the same. When I have negative inside, that does not give us anything because square root of a negative number, that is not real. So we don't get any solution from that. So this number that's inside the square root, that's very important. What's that number? That's basically this discriminant b square minus 4ac. Inside the square root, you've got this thing called b square minus 4ac. We call this discriminant. That is basically what decides how many roots you're going to get for a particular quadratic equation. Now there are 3 different cases, in fact 4 different cases, 3 base cases, and then one is derived from them. One possibility is, in the first case, for instance, when the number inside is positive, you get 2 different solutions. So when b square minus 4ac is greater than 0, you get two real and distinct or different roots or solutions. When b square minus 4ac is equal to 0, you get two real and equal solutions. Or you can also say that's just one real root because it's the same thing coming twice. And the last case is that you have no real roots. When does that happen? When b square minus 4ac, the part inside the square root that's less than 0. In that case, you get no real roots. Now, graphically, what does that mean? Graphically, what that means is the function that we have and the line that we have on the other side. In this case, the line was the x-axis. Sometimes it could be some other line as well. Graphically, that means that the curve and the line, in the first case, they're meeting at two different points. In the second case, they're only touching at one point. The line is a tangent to the curve. And in the third case, they're not meeting at all. So you should know, you should understand both the graphical interpretations and the interpretation using the roots. When b square minus 4ac is greater than 0, graphically, the line and the curve, they intersect at two different points. When b square minus 4ac is equal to 0, they often say it like this: the line is a tangent to the curve, or we can say the line only touches the curve or only meets the curve at one point. And then finally, in the last case, b square minus 4 is less than 0, the line and the curve, they do not meet each other, right? So whenever you have any of these statements written in the questions, understand what that's referring to. At 2 points means this is greater than 0. It's tangent to the curve. It's equal to 0. They don't meet. B square minus 4ac is less than 0. Now, this is only for quadratic equations, right? When you get a quadratic equation after equating the functions, it's only for that case. If you're not getting a quadratic equation, then b square minus 4ac is not relevant. Then you use differentiation. That's not what we're discussing right now. But then we have another case. Sometimes what they say is two functions, they have real roots. Or they might say the line and the curve, they meet each other without specifying at how many points. So if they have real roots, they could have, two different roots. They could have two equal roots, one root, two roots. We're not sure about that. If they say the line and the curve, they meet each other. Now, at how many points do they meet? Do they meet once? Do they meet twice? We're not sure about that. When they say any of these statements, when it's not clear whether it's at 2 points or 1 point, you basically combine the first two cases. You say, in this case, b square minus 4ac is greater than or equal to 0. That's the combination of the first two cases because it could be any of those two, right? If the line and the curve they meet, that means they could meet at 1 point or 2 points. So we combine these. B square minus 4ac is greater than or equal to 0 in that case. So these are three base cases that you need to know about. And then one case that's derived from the first two cases. Okay. Now, let's have a look at this example. So we did completing square above. Sometimes they ask you to convert something to a form that is not the standard completed square form. For example, they might ask you to convert this expression to this form, 2x plus a whole squared plus b. Now, this is not standard form. In this case, you've got 2x inside. In the standard form, you cannot have any number inside the bracket. Multiplying with x. In this case, they have that. Now, how do we deal with problems like these? One way to do this is that you complete the square the normal way, whichever way you prefer. You can do it that way, right? I've done this using minus b over 2a method here. You can do it using the other method. Eventually, what happens is you get this standard form, right? This is something that everyone can do, I think. You get to this form. But now they don't want in the form that they've given, they don't want any number outside the bracket. They have a number inside the bracket. Now, what do we do for that? The number that's outside 4, we take that inside, but we can't take that inside as it is because this bracket has power 2 and this 4 only has power 1. They have different powers. In order to multiply 4 inside, we need to make the power the same for the number outside as well. How would that work? We write 4 as 2 squared. And now, since the powers are the same, that means you can multiply the bases. So it becomes 2x minus 3 whole squared minus 9. And that is the form that they wanted there. This is one way to do this, that you do it using the standard way. And then the number that's outside, you write that in square form and then multiply the base inside. And that gives you the result. Another possibility is using comparison method. This is also something that can be used for normal completing square as well. It'll work there as well. So what they did was they gave us this expression and they wanted us to convert it to this form. We can compare them. We can say, okay, this is the original form, 4x squared minus 12x. And this is the form that they want us to convert it to. We can say, let's simplify this thing. 2x plus a whole square plus b. What does that give us? That gives us 4x squared plus 4ax plus a squared plus b. And now we could compare the two. We can say the coefficient of x squared is 4 here. This is also 4. That does not give us anything interesting. The coefficient of x here is minus 12. This is 4a. You compare them, the value of a turns out to be minus 3. And the constants, there's no constant here. This is a squared plus b. We compare them, and that gives us a squared plus b equal to 0. So we get two equations. 4a equals minus 12. That gives us the value for a. A squared plus b equals 0. And from that, we can find the value for b. And then once we have those values, the value for a and value of b, all we have to do is input those values in that form that they gave, and that gives us the final form. All right, so that's what we can do as well. Okay, let's move on now. I think around 15-20 more minutes, probably. Let's see, because there is still some stuff to go, because we have some difficult questions coming up that might take a bit of time. Okay, now let's look at another example. Let's say we've got a curve that looks like this. Y equals x squared minus 3x plus 4. We need to show that the whole of the curve lies above the x-axis. How do we do problems like these? The whole of this function lies above the x-axis. Now, what's the shape of this graph? It's a U-shaped graph. The coefficient of x squared is positive. Since it's a U-shaped graph, what I'll do is I'll just get rid of that part. Yeah, okay. If it's a U-shaped graph, that means it looks like this, right? Now, if the whole of this curve has to lie above the x-axis, then that means the turning point here, its y coordinate should be positive. So how do we prove this? We find the turning point of this function. What's the turning point of the function going to be? This is the function y equals x squared minus 3x plus 4. Find the turning point, minus b over 2a. You get the x coordinate 1.5, the y coordinate is 1.75. And the y coordinate turns out to be 1.75. Since that's positive, that means it's above the x-axis. It's a minimum point. The minimum point is above the x-axis. If the minimum point is above the x-axis, that means the whole curve, therefore, is going to be above the x-axis, right? That's one way to prove this. Another way to prove this could be, if the whole curve lies above the x-axis, then you could also say that the discriminant is going to be less than 0, right? So you find b squared minus 4ac for this. That turns out to be negative, but that's not enough proof. That's not sufficient proof. If you just say b squared minus 4ac is less than 0, it could be two possibilities. It could either be this form, or it could be this, that the whole curve lies above the x-axis if it's a U-shaped curve, or it lies below the x-axis if it's an N-shaped curve. B squared minus 4ac less than 0 could mean either of these. So if you use b squared minus 4ac method, in that case, you would say b squared minus 4ac is less than 0, but at the same time, it is a U-shaped curve. So it's this case, not this case. And these things, both of these things together, they mean that the whole curve lies above the x-axis. That's another method that you can use for this as well. All right. So either show that the minimum point lies above the x-axis, or find the discriminant that's negative, and also say that it's a U-shaped curve. That is why the whole curve lies above the x-axis. That's what you have to prove there. Second part, that's also another important one. Find the set of values of x for which this is a decreasing function of x. Now, we talked about increasing and decreasing function before. It's a U-shaped curve. If it's a U-shaped curve, we know this part here is decreasing. The part that has a negative gradient, that part is decreasing. Now, what's that part? What are the values of x in this part? We found the turning point. If you did it using the turning point method in the first part, you can just use that. If not, you would have to find the turning point in this part now. The turning point was 1.5 and 1.75. They wanted us to find the set of values of x for which this is a decreasing function. So decreasing function is on the left side of the turning point. What are the corresponding values of x that we get from this? To the left of 1.5, that's x less than 1.5. That's the solution that you have there. Okay. All right. If you have to find point of intersection between a line and a curve, you just solve them simultaneously, right? Just like we do in coordinate geometry. This is a line, this is a curve. If you want to find the point of intersection of them, we solve them simultaneously. We can make y the subject in both of them and then equate them, or make y the subject in the linear equation, put that in the other equation, and then you can solve it simultaneously like this. Okay. All right. Now, let's look at this. We have a line that has this equation mx minus 2m. Okay, so I'm going to skip the first part. That's pretty straightforward. Let's say we have a line mx minus 2m. And they're saying, find the two values of m for which the line is a tangent to the curve this. The line is a tangent of the curve. Does that remind you of something we just discussed? If a line is a tangent of the curve, that means b square minus 4ac is supposed to be equal to 0, right? If line is a tangent of the curve, b square minus 4ac is supposed to be equal to 0. So now we have a straight line, which is mx minus 2m. We have a curve, and this line is a tangent to this curve. So that means they are only going to have one point where they meet each other. So b square minus 4ac should be equal to 0. Now, how do we use b square minus 4ac? The first thing we have to do for using b square minus 4ac is we first of all equate these two functions. We start the process of solving them simultaneously. Either do substitution or make the same variable the subject and equate both of them. Once you equate them, you get one single equation like this, right? Using those two equations, when you start solving them simultaneously, you get one equation from that. You convert this equation to the standard form ax squared plus bx plus c equal to 0. You bring all terms to one side and leave only 0 on the other side. Okay, once you've done that, the coefficient of x squared, that is going to be 1. That's going to be the value for a. The coefficient of x, that's going to be the value for b. So if you have multiple x terms or multiple x square terms, you take x square common to, in this case, you take x common and you see what the coefficient of x turns out to be. In this case, that's minus into 4 plus m. That whole thing is the coefficient of x. So that's the value for b. And then similarly, the constant is everything that does not have any x in it. So that's the constant. All right. Now, this is the constant, 5 plus 2m. Since the line was a tangent of the curve, we put b square minus 4ac equal to 0, solve that, and find the values of m that we get from that. Now, sometimes what they ask you for is to find those points at which the line is a tangent to the curve. Once you have found the values of m, now you know what that equation is. You know the equation of the line now, but it will be two possible cases, right? One possible case when the value for m is 2. In that case, you have y equals 2x minus 4. The other possible case is when m is equal to minus 2. In that case, you get this equation. And now what you do is you solve these two equations simultaneously to get those points at which the line meets the curve. Okay? All right, let's move on. Hidden disguised quadratic equations. Sometimes you have equations that are in this form, such that they're not quadratic. However, you can convert them to a quadratic form. For example, you could have something like this: x raised to the power 4 minus 7x squared plus 12 equal to 0. This is not a quadratic equation. This is a power 4 equation. Now, we don't have a general method that we have in our syllabus to solve quartic equations, power 4 equations. So how do we solve this equation then? We can think of it as a quadratic equation. It's a hidden quadratic. How do we do that? And how do you figure out if it can be converted to this form? The power should be in the ratio 2:1. The power should be in the ratio 2:1. One power should be twice the other power. So in this case, one power is 4, the other power is 2. One is twice the other. What we do is we use a substitution. We replace the smaller power with another letter. So in this case, we say that u equals x squared. And then u squared will become x raised to the power 4. Solve this equation, put that substitution back at the end. In place of u, you put x squared back again, and you get the solutions from that. Compare that with this equation. In this case, substitution does not work because the powers that you've got, there are three different powers, right? You've got x power 4, x power 2, x power 1. So substitution does not work here. That would not work. It's not a hidden quadratic equation. If you had something like this, 6x into 7x raised to power 1 over 2 plus 2, again, in this case, that works because you've got one power and the other power is twice that. So it does satisfy that condition. We replace the smaller power with another letter and then solve it as a quadratic. And then at the end, we put that substitution back. This is another example. You have these two equations, and we have to find the points of intersection of these two curves. This is one curve, this is another curve. How do you find points of intersection? If you were to equate them, you would get an equation like this: x raised to power 2 over 3 minus 1, that equals x raised to power 1 over 3 plus 1. And that gives you x raised to power 2 over 3 minus x raised to power 1 over 3 minus 2 equal to 0. Now, one power is twice the other. You can see that this is 1 over 3, this is 2 over 3. So what you do is you replace the smaller power with another letter. You say u is equal to x power 1 over 3, and then u square would be x raised to power 2 over 3. And this can be written as a quadratic equation: u square minus u minus 2 equal to 0. You solve this quadratic equation, at the end put that substitution back, and you get the result. Next thing you have to know about is solving quadratic inequalities. How do you solve quadratic inequalities? When you solve equations, what do you get from that? For example, if you solve this quadratic equation, x square minus 7x plus 12 equal to 0. When you solve this equation, you get two answers from this: x equals 3 and x equals 4. They represent the x-intercepts of this function, right? Why? Because we've got this function y, and we're saying that is equal to 0. When is y equal to 0? Y is equal to 0 on the x-axis, right? So these solutions represent the x-intercepts of this function. But what if instead of an equation, we have an inequality? For example, if you have something like this less than 0. Now, you cannot do it like this, that you say, let's just factorize this and then say either x minus 3 is less than 0 or x minus 4 is less than 0. That's not how it works, because if both numbers are negative, their product is actually going to be positive, right? So it's not going to be negative, it's going to be positive. So this logic does not work when you have an inequality. So how do you solve inequalities then? Whatever inequality it is that you have to solve, what you do is, first of all, you treat this as an equation. Treat this as an equation and find its x-intercepts. So remove the inequality sign, treat this as an equation. You know how to solve the equation. You can solve it like this. Find the values of x that you get from that. Now it's a U-shaped curve. Draw that U-shaped curve and think about it. If it's a less than sign, that means y is supposed to be less than 0. You're supposed to be below the x-axis. Which part of this graph is below the x-axis? That's this yellow part. What are the corresponding values of x for this part? 3 to 4, right? It's between 3 and 4. This part of the graph is below the x-axis when x is from 3 to 4. So that's what your answer is going to be. You say x is between 3 and 4 like this. When you write this form, when you have middle region, you always write it like this: smaller number on the left side, bigger number on the right side, and you have less than signs, these signs in the middle. Okay, whenever you have two-way inequality, inequality bounded on both sides, you always write it like this: smaller on the left, bigger on the right, and the less than signs in the middle, right? That's the convention that we have for writing down this inequality. Now, if instead of less than sign, you had a greater than sign there, what would you do in this case? When is y greater than 0? That's this part or this part, right? This is where the y value is greater than 0. So what are the corresponding values of x that we get from this? Either to the left of 3 or to the right of 4, right? These are the corresponding values of x that we have. So that means x is either less than 3 or it's greater than 4. Since in this question statement, you had an equal to sign as well, we put equal to signs with the solution as well. All right. Okay. So these are the inequalities that we get. This is the solution to this equation. Now, if this inequality was like this, if the coefficient of x square was negative, then you would say it's an n-shaped curve, right? So you would draw an n-shaped curve. So if it's a less than sign, what does that mean? Where is the graph below the x-axis? It's to the left of -1 over 2 and to the right of 4. So you solve it as an equation. First of all, once you've solved the equation, you find the values of x from that. And then using the graph, you can write down the final inequalities. Another possible way of doing this could be that if you're not comfortable with a negative sign here, you can just multiply the whole inequality by minus first of all. That will change the inequality sign as well. That will make it positive, because whenever we multiply or divide by a negative number, the inequality sign also changes. So now we've got this inequality. Treat this as an equation, solve this equation, you get two x-intercepts again, but now in this case, since we have a greater than sign, that means we're looking for the for the part of the graph that is above the x-axis. The corresponding values of x that we get from that is to the right of 4 or to the left of -1 over 2, right? These are the corresponding values of x that we get from this. So that's the solution. Now, just an exam trick that I'm sure you would like. If you have this inequality, and you don't like graphs and you often get this wrong, you can just use your calculator. How do you do that? You show this process. You show this process. This is necessary to show, okay? You have to show this process where you solve it as an equation, right? Treat the inequality as an equation. Find the two x-intercepts. Once you find the two x-intercepts, this is what most people get wrong. The final solution after that, just put this on your calculator. So you should have a good calculator. That really helps with the exam. So on this version, I have this inequality solving function. I can just go there. The degree of this polynomial is 2. Let's put that there. Which option do we select here? It's a less than sign, right? Less than 0. That's number 2 in this. Input those coefficients, -2, 7, and 4. And you get that answer. So after you're done with this part, you found these x-intercepts. If you're not sure about the inequality signs, you get them from the calculator. X is less than -1/2, and x is greater than 4, and that's your final answer. All right. So that's it. That gives you the result. So you don't have to show this graph. There are no marks for showing this graph. You just write down the answer directly. Okay. All right. Okay, let's move on. Now that's pretty much all in terms of concept. Now let's have a look at some tricky questions, and then we end. The equation x squared plus px plus q. Equation x squared plus px plus q equals 0, where p and q are constants. It has roots 3 and -3 and 5. We need to find the values of p and q. How do you find values of p and q in this case? This is the equation. We have to find the values of p and q. We are given two solutions of this equation. One solution is -3 and one solution is -3 and the other solution is 5. One idea could be that we say, since these are solutions to this equation, we can input those solutions in this equation and the equation should satisfy. And you get two simultaneous equations from that. You solve those two simultaneous equations and that gives you the result. That's one possibility. That's one idea. That will work, but it takes quite long. Okay. But a quicker way of doing this could be, it's only 2 marks, right? You're given the solutions -3 and 5. Think about what happens when you solve a quadratic equation. If you have this, x squared minus 7x plus 12 equal to 0, when you solve it, you get a form like this first, factorized form, and then you say either x minus 4 is equal to 0 or x minus 3 is equal to 0, and then you get the solution x equals 4 and x equals 3. If you had the solutions given and you wanted to go back to the original equation, how would you do that? You can just go backwards in this direction. You can say, okay, we've got x equals 4, we've got x equals 3. Let's go one step back. Bring 4 to the left side, bring 3 to the left side, and that gives you this x minus 4 equals 0, x minus 3 equals 0. Go one step further back, combine these factors, multiply them, and then you can simplify everything to get back to that original equation. So that's another idea that we could use here that will be much more efficient in problems like these. So you are given that the solutions are -3 and 5. Okay. Now, if those are the solutions, we can say, okay, x equals -3 and x equals 5. That gives us x plus 3 equal to 0, x minus 5 equal to 0. And now we can multiply these two factors, x plus 3 into x minus 5, that equals 0. Simplify this and you get the equation x squared minus 2x minus 15. They told us that the equation is x squared plus px plus q equal to 0. Compare the two, you get the value of p, that's -2, and you've got the value of q, that is -15. That's another way to do this. That's much simpler. Now, there's a complication here that you could have. For example, in this case, if they had said that the original function is of this form, it's not x squared plus px plus q, it's actually -3x squared plus px plus q equal to 0. And the solutions are the same. What happens in that case? How do you find the values of p and q in that case? Now, when you get to this point, you are getting x squared minus 2x minus 15. This is what you're getting. Now, you cannot compare these two equations because the coefficients of x squared, they are different from each other. You cannot do comparison in this case. That would not work. In the previous case, they were both the same, so we could compare them. Now we can't. So how do we compare them? We can only do this if we first, from this form, get to this form. How do we do that? We just multiply the whole equation by -3. Multiply the whole equation by -3 so that the coefficient of x squared also becomes -3. When that becomes -3, these coefficients become the same, and now we can compare p and q. We can say the value of p turns out to be 6, and the value of q turns out to be 45 here. So whatever you know in those equations, those numbers should be equal. So in this case, we knew the coefficients of x squared, so they had to be equal before we could compare these two equations, right? So that's a more complicated example that you would see. All right. Now, sometimes what they do is they don't tell you that the line and the curve they meet at multiple points. They won't tell you that the line is a tangent to the curve, or they don't meet each other. But they would ask you to show something. So, for example, in this case, look at this question. It's a very common one in recent papers now, and it's a bit complicated sometimes. You've got the equation of a curve that looks like this, and you've got the equation of a line that's this. They want us to show that for all values of m, that means no matter what the value of m is, the line intersects the curve at two distinct points. Now, how do we show that? The line intersects the curve at two distinct points. What does that mean? B square minus 4ac is greater than 0. But is that given to us? That's not given. They're not telling us that the line intersects the curve at two distinct points. They want us to show that. So we are not going to start with this assumption that b square minus 4ac is greater than 0. We have to show this. So how will this work? We've got the equation of the curve. We've got the equation of the line. First of all, we equate both of them. Simplify everything. Convert it to the standard form, ax squared plus bx plus c equal to 0. Now, from that form, we find b square minus 4ac. Now, we are not going to say that b square minus 4ac is greater than 0. We are not going to say that. We're just going to simplify b square minus 4ac. So we input the values of b, a, and c, simplify b square minus 4ac, and that gives us this eventually. 4m squared minus 32m plus 68. Okay? This is what we get. Now, once we've got this form, b square minus 4 is equal to 0, we have to prove that this is greater than 0. This is always greater than 0. No matter what value of m you put there, this is always greater than 0. How do you do that? This is an expression. This is a quadratic expression. It's a quadratic expression. Can you find the minimum point of this expression? Not the minimum point of the original function. Minimum point of this discriminant. Discriminant is a quadratic function here. How do you find minimum point of any quadratic expression? You can do that using minus b over 2a, right? So what's the x coordinate of this turning point going to be? Minus b over 2a. We use that. We get h equal to 4 from that. The x coordinate of the turning point, that is going to be 4. Put that back in this function, and that gives the corresponding y coordinate. What that means is this curve, it's not the original curve, it's the discriminant. This is b square minus 4ac. We are graphing the discriminant. That looks like this. The minimum value of the discriminant, what's that? The value of the discriminant is 4. That necessarily means it's always greater than 0. If it's always greater than 0, that means that the line and the curve, they meet, they intersect at two distinct points, no matter what the value of m is going to be. Does that make sense? This is one idea. The other idea here after this point could be that you complete the square. Complete the square. When you complete the square for this, you would get a form like this: 4 into m plus 4 whole squared. 4 into m minus 4 whole squared plus 4. When you complete the square for this, you get something like this. And then from this also you can say, and this part is always positive, or you can say this is always greater than or equal to 0, right? Because we have 4, that's positive. This is a square. Square can never be negative. And this is plus 4. So that means the overall thing is always going to be greater than 0. Since it's always greater than 0, that means the line and the curve, they intersect at two different points. Okay. That's another idea. You complete the square and argue based on that. What you need to remember is don't put greater than 0 in the beginning. Start with just b square minus 4ac. Simplify that. And then the expression that you get to somehow prove that that is always positive in this case. All right. Another similar question like that, you can do that yourself. You've got this curve, you've got this line. Again, they're saying show that for all values of k, the curve and the line meet. What does that mean? Curve and the line meet. At how many points? We're not sure. They've not given us how many points they meet at. It could be 1 point, it could be 2 points, but they meet. Now that means b square minus 4ac is greater than or equal to 0. Greater than or equal to 0. It could be both possibilities. But is that given to us? No, it's not given to us. We have to show this. How do we show that? We equate both of them, find b square minus 4ac, simplify that, and at the end, the result that we get, we find the minimum value of that. If it's 0 or above, that means b square minus 4ac is greater than or equal to 0. Okay? And then finally, we have this function f of x that's defined for all real values of x. F of x is equal to x squared minus 6x plus c, where c is a constant. It's given that f of x is greater than 2 for all values of x. What does that mean? F of x is greater than 2. It's greater than 2 for all values of x. Okay? Find the set of possible values of c. Now, how do we understand that? So we've got this quadratic curve. It's a U-shaped curve. It looks like this. It's a U-shaped curve, right? It'll have some minimum point. Can we find that minimum point somehow? X squared minus 6x plus c minus b over 2, that gives us x equal to 3. That's the x coordinate of the minimum point. Then we find the corresponding y coordinate. That turns out to be c minus 9. So we've got the turning point's coordinates. The x coordinate is 3. The y coordinate is 7. Is c minus 9. Now, what's the range of this function? The minimum point is c minus 9. So the range of the function is going to be greater than c minus 9. Y is supposed to be greater than c minus 9. That's the range of this function, right? They have given us that y is greater than 2. We are getting y greater than c minus 9. Compare the two. What do you get from that? If y is greater than 2, then from here, we get c minus 9. That should be greater than 2. So think of it like this, in fact. If they're saying f of x is greater than 2, then the y coordinate here should be 2, because that's what the y value is greater than. It's always greater than 2, right? So we say c minus 9, that should be greater than 2, and c is greater than 11 from that. Does that make sense? This is one idea. This is one way to do this. This is going to make it much more complicated. Let's just stick to this. So y greater than 2, that was what was given to us in the question. That for all values of x, y is greater than 2. This function is greater than 2. We are getting that the turning point of this function, its y coordinate is c minus 9. So c minus 9, therefore, has to be always greater than 2. So we say c minus 9 is greater than 2. That gives us c greater than 11. All right. So that's another type of question that you will see in recent papers sometimes. That's it. I hope that was helpful. If you have any questions, you can let me know now. And you can finally go and sleep if you want. Although, even though you're saying you're tired and all, you are all going to be watching reels now, watching YouTube shorts. It's only while studying maths that you get tired. Ask her. Sorry, that was not a valid question. Yes, let me know if there are any questions. Can we have two curves instead of a curve and a line? It's possible. You could have a curve like this, y equals 2x squared plus 7x minus 3. Another curve might be y equals, I don't know, 4x squared minus 3. The idea remains the same. You just equate both of them. If after equating them, you get a quadratic equation, then yes, that's possible, right? Because after equating them, b squared minus 4ac only works when after you equate both the functions, When after you equate both the functions, you get a quadratic equation. So you could have any two functions. If after equating them, you get a quadratic equation, then yes, that is possible. You can get that. This last question, it's the same idea that we did before. You will equate both of them. 2x squared minus 3x plus 1 equal to kx plus k squared. Take all terms to one side, convert it to ax squared plus bx plus c form. Once you have done that, find the value of b squared minus 4ac. Simplify that. The result that you get, you have to show that that's greater than or equal to 0. Complete the square for that, and that will help you understand that. The one above. Okay, what about this? Do you have a specific question on this? So let me repeat what I've done. So we had to show that b square minus 4ac is greater than 0. We had to show that, right? So what we did was we equated both the functions first of all and found b square minus 4ac. I think you understand until this point at least, right? We found the value of b square minus 4ac and we got this form. And now we need to show that this b square minus 4ac is always greater than 0. No matter what the value of m is, it's always greater than 0. Now, one idea that I explained was that we say it's a quadratic expression, 4m squared minus 332m plus 68. That's a quadratic expression, m squared. You find the minimum value of this using minus b over 2a. Minus b over 2a, that gives you h equal to 4. That means the x coordinate, that turns out to be 4. The corresponding y coordinate that you get when you input x equals 4, here you get the corresponding y coordinate. So this value is the minimum value of this expression, 4, right? So b square minus 4ac, its minimum value is 4. If its minimum value is 4, that means b square minus 4ac is always greater than 0. And that's what you had to prove, that b square minus 4ac is greater than 0. Okay. Yeah, so whatever value of m you have there, since you have proved that the minimum value is 4, it's always going to be greater than that. If the minimum is 4, it can't go below 4. So that's greater than 0. Okay, if you find this confusing, just complete the square. Complete the square and you'll get something like this. 4 into m minus 4 whole squared plus 4. That is what you would get from this. Now, rather than thinking of the minimum point of that curve, because some people may find it confusing that why are we drawing the discriminant there, just think of this expression. This is 4. 4 is a positive number. This is m minus 4 whole square. That's a square. A square can never be negative. It has to be greater than or equal to 0. It cannot be negative. And then you have a plus 4 here. That's also a positive number. So overall, the whole expression is going to be greater than 0, right? Because we have plus 4. Even if this becomes 0, 0 plus 4, that becomes greater than 0. So all you have to write down is, you say b square minus 4ac is, after this, after converting it to completed square form, you can just write b square minus 4ac is greater than 0. And that shows that the line in the curve then meet for all values of x. Is that all right? Abdul Hadi, we have not drawn this curve. That's not the graph that we have drawn there. This graph is for the discriminant. This expression is discriminant. The original curve and the line, they meet at 2 points. That will be like this. The curve is like this, and the equation of line is like this. They are meeting at 2 points. This is not the graph of the curve. This is the graph of discriminant. The discriminant is always greater than 0. If the discriminant is always greater than 0, that means that this curve and the line, they always meet each other. Okay. Okay, so let's start with the next topic. This is functions. First of all, you need to understand what functions are about, what function notation is. So if you have any function that, any equation that's of this type, for example, y equals minus 2x plus 5, there's another way to write this, and that is you say this is f of x equals minus 2x plus 5, right? That's just another way to write down this equation that was in terms of y earlier. You can write that in terms of f of x like this as well. So what does f of x mean? F of x means this thing is a function of x. It's defined in terms of x. You need to understand how to deal with this notation as well. For example, in this notation, when you say input x equals 0, you get y equal to 5 like this. In function notation, the corresponding notation would be that in place of x inside the bracket, you replace 0. That means you're inputting x equal to 0 inside this. And then the result that you get from that, this is the value for y. 5 is the value for y. Similarly, if you want to input x equals minus 3 in this, you have minus 3 in place of the, inside the bracket here. And the result that you get from that, that's the value for y. That's 11. All right. Now, it could be something other than numbers like this as well. So for example, if you have a function that looks like this, f of x equals 2x squared plus 4x minus 3, and you want to evaluate f of x cubed. What does that mean? Wherever you've got x in this function, what you do is you replace that with x cubed. So let's try doing that. When we replace x with x cubed, this is what we get. Then we simplify that, and the result is going to be the expression for f of x cubed. Okay. Similarly, if you wanted to evaluate f of x minus 1 in this case, all you have to do is just replace x in this function with x minus 1, and then you simplify that, you get the expression for f of x minus 1. Okay, so that's how function notation works. Now, how exactly does a function work? If you have a function that looks like this, f of x equals minus 2x plus 5, what that means is when you input x in this, x is the input that goes into the function, and the function gives you an output. The output that you get, that's what we call f of x, or it can also be represented by y. So how does a function work? You give this function an input. That's normally the value for x. The function applies some operations on that. For example, in this case, the operation the function is applying is that it's multiplying this value by minus 2, and it's adding 5 to that. It's adding 5 to that. These are two operations that the function is applying, and it gives you an output from that. For example, if you input minus 4 in this, minus 2 into minus 4, that will become 8 plus 5, and you would get 13 as the result. Now, the first major thing that we need to know about functions is the concept of domain and range of functions. Okay, I'm sorry. Just give me a second. I forgot to send the link to somebody who just joined. Just give me a second. Just got reminded of that. Okay, so the first major thing that you need to know about functions is domain and range of functions. Okay, now what's the domain of a function? Domain is the set of values of x that a function can take as an input. And what about the range of the function? Range is the set of values of y that you can get as an output from the function. So values of x, they're known as the domain. Values of y, we call them the range. Now about domain, there are only a few things that you need to know about. And that is, for instance, if you have a function that looks like this, f of x equals minus 4x plus 6. Now, does this function have any restriction as far as the as far as the values of x that you can input in this is concerned? Is there any restriction? It's a straight line function. You can input any value for x in this, and that will work. For example, you can put a negative value in this, you can put a positive value in this, you can put 0 in this. There's no value for x at which this function is not defined. For a function like this, we often say the domain of the function is all real values. Now, you should be familiar with this notation. If it says something like this, x belongs to R, what that means is x can be any real number, right? So in the straight line, there's no restriction. The value for x can be anything. You can input any value of x in this. There's no restriction. It could be all real values. Compare that with this function. F of x equals 2 into square root of x minus 3. Now you have a square root function here. In a square root function, inside the square root, you cannot have anything negative, right? So whatever is inside the square root, you want that thing to be positive. So, or it could be 0 as well, but it can't be negative. So x minus 3, that should be greater than or equal to 0. That means that the value for x should be greater than or equal to 3. So the domain of this function will have to be x greater than or equal to 3. Any value that's less than 3 will not work in this function. The function will break because you will end up getting a negative number inside the square root. So that's one thing that you need to know about square root functions, that inside the square root, you can never have something negative. Similarly here, in this function, the part that is inside the square root, that has to be greater than or equal to 0. So what's the corresponding domain that you get from that? X greater than or equal to 7. And the second thing that you need to know about domain is if you have x in the denominator. So if you have minus 3 over 2x minus 8, is this function defined for all possible values of x? Well, pretty much all values, but there's one exception, and that is that the denominator cannot be equal to 0, because division by 0 is not possible. If you end up getting 0 in the denominator of a fraction, that fraction becomes undefined. So how do you get 0 in the denominator here? For 2x minus 8 equal to 0, what's the value of x that you get from that? You get x equals 4. That means that's the value at which this function becomes undefined. So what would you say about the domain of this function? You would say it's all real values. However, there's one exception, that x cannot be equal to 4. So for reciprocal functions in which you have x in the denominator, the denominator's value, that cannot be equal to 0. So whatever is the corresponding value of x that you get from that, that value is not supposed to be equal to 0. Now, these are just two restrictions that you need to know for the domain, that inside the square root, you want something greater than equal to 0. And in the denominator, you want something that is not equal to 0. Apart from this, they will always tell you what the domain of a function is. So these are two things that you may have to figure out yourself, but generally they will tell you the domain of the function themselves if there is some practical consideration. So these are inherent limitations of these functions, that square root cannot take negative value. You cannot have something, you cannot have 0 in the denominator, but there's some functions that may not have any inherent limitation in them, in terms of their in terms of their mathematical evaluation. For example, if it's a linear function, there's no problem inputting. You can input any value for x in this. You can put a negative value, you can put a positive value. It can take any value of x and it would still be defined. However, there might be some practical considerations because of which there might be some restriction on x. For example, if x represents price, in that case, price generally cannot be negative. So you would say that the value for x would have to be greater than 0. If there's any consideration like this, they will always tell you the domain of the function in the question themselves. So that's why mostly when you see a question on functions, they will tell you the domain, and what you would have to do generally would be to find the range of that function. Now, that's the major part of this topic, finding the range of different functions. For domain, we only have those two cases, but for the range of functions, we have a number of cases for which we need to, for a number of different types of functions for which we need to be able to find the range of the function. Let's start with those different types of functions. First of all, we've got linear functions, straight line functions. Let's suppose we've got a function that looks like this, f of x equals 2x plus 5. And the domain of this function is x greater than or equal to 3. Now, if this is the domain of the function, what's the range of this function? Remember, domain is the values of x, range is the values for y. If it's x greater than or equal to 3, what you can think about is, you can think about the graph of this function. Now, whenever you're thinking about range of functions, for some specific kinds of functions for which you know how the graph should look like, you should always sketch the graph. Linear function and quadratic functions in particular, you should always first sketch the graph, and from the graph, try to think about what the range is going to look like. For example, in this case, 2x plus 5, that's a straight line. It's going to look like this. It's going to be upward sloping line like this from left to right. And now you consider the domain. It's x greater than or equal to 3. Now, what you do is you find the y value at this point. When x is equal to 3, what's the corresponding value for y that you get? You're getting 11 from this. So this is the point that lies on the line. 3, 11, this is the point that lies on this line. And now you think about which part of this graph satisfies this condition. What's the condition? That x is supposed to be greater than or equal to 3. Now, if you have 3 here, If you have 3 here, which side of this function is going to be valid? The right side. So look at the graph. This is the part of the function that is valid, the yellow part. So what's the range going to be? Range is the values of y that on the vertical axis, how much you can go up and how much you can go down. On the right side here, in the upwards direction, you can say the values of y are always greater than or equal to 11. So that's the range of this function. Now, you might think that it was not really necessary to draw the graph here because we got the value for y, that was 11, and the range turned out to be y greater than or equal to 11. Because this was a greater than sign and this was a greater than sign. So we could just put that greater than sign without drawing the graph. But that's not going to work every single time. Why is that? Because think about this example. F of x equals minus 3x plus 8. Let's say we've got a function that looks like this. In this function, let's say the domain is given to be x greater than or equal to 4. How do you think about the range of this graph now? You input that value of x in this. The value of x is 4. The corresponding value of y that you get is minus 4. Now, what's the range going to be? You might think this is greater than or equal to 4, so the range should be y greater than or equal to minus 4, but that's not correct. And that's something that you understand when you think of the graph of this function. It's a downward sloping line. It's minus 3x plus 8. What does the graph of this function look like? It's going to be going in the downward direction. From left to right, the graph goes in this direction, like this. So what you do is you think about this point. The value for x at this point is 4. What's the corresponding value for y? The corresponding value for y is minus 4. So this is the point that we're talking about. Which part of this function is valid? When x is greater than or equal to 4, which side of the graph? That's the right side of the graph. So from that point, consider the right side of the graph. Look at the yellow part. What's the range of the function? It's going to be below minus 4, less than minus 4. Remember, range tells you about the values of y. Values of y means vertically how far can you go in the upwards direction and how far you can go in the downward direction. So in this case, what's the maximum value of the graph? What's the highest value of the graph? That's negative 4. Lowest value, it can go up to negative infinity. So the range of the graph is going to be y less than or equal to minus 4. That's the range of the graph. You cannot figure that out if you do not think about the graph of this function. So thinking about graphs is really important in problems like these. Take another example. Let's say we've got a function like this. F of x equals minus 5x plus 4. What's the domain of this function? Domain of the function is from minus 2 to 3. Again, you can think of the graph. It's a downward sloping line because the gradient is negative. So it's going to look like this. That's the shape of the graph. It's a downward sloping line like this. From minus 2 to 3, this part of the function is valid. From minus 2 to plus 3. So we have a point on the graph at minus 2, the value for y turns out to be 14. At x equals 3, the value for y turns out to be minus 11. So what part of this function is valid? The part between these 2 points. So on the x-axis now, you are saying any value between minus 2 and 3, that is valid. On the y-axis, any value between minus 11 and 14, that is going to be valid. So what's the range of the graph? The range of the graph is from minus 11 to 14. But now again, you've got to think about the inequality signs as well. Minus 2 has an equal to sign with this. What's the corresponding value for minus 2? That's 14. The corresponding y value for minus 2, that's 14. So on the vertical axis, on the y-axis, the range is also going to have an equal to sign with 14. The domain does not have an equal to sign with 3 there. So the corresponding value for 3, that's minus 11. Minus 11 is not going to have the equal to sign here as well. Okay, so inequality signs, you have to think about them, whether you're going to have an equal to sign or not. You think about the original x value. If that's included, the corresponding y value will also be included. If the original x value is not included, then the corresponding y value would also not be included. Okay. In a linear function, if the domain is all real values, what about the range? The range is also all real values, because horizontally, if the function can go as far as possible on the right side and as far as possible on the left side, Vertically as well, there's no restriction. The graph can go up to positive infinity, and in the downward direction, it can go up to negative infinity, right? So there's no restriction. There's no restriction in the vertical direction as well. You would say the range of this function is all real values. Now that's about linear functions. In linear functions, all we have to think about is the endpoints of the domain. Think about what happens at 3, think about what happens at 4, find the corresponding y value, and look at the graph and see what the range is going to look like based on that. Similarly here, the domain was from -2 to 3. We just looked at the endpoints and we found the corresponding y values, looked at the graph to figure out the range of the corresponding function. Now, the next type of function is when you have reciprocal functions. They're a bit confusing sometimes. These are functions when x is in the denominator. So there's any x in the denominator. This type of function is called a reciprocal function. For example, you could have something like this: 4 over x minus 2 minus 8 over x squared plus 1. We call these reciprocal functions because we've got x in the denominator in these functions. How do you find range of functions like this? Again, you think of those endpoints. However, the graphs of reciprocal functions are a bit confusing. If you know them, you can draw them. However, we can do this without the graph as well. This is one function for which we will not be drawing any graphs ourselves. Sometimes they give the graph in the question themselves. We'll have a look at an example like that. But mostly they will not give you any graph for this. And for this, since the graph is going to be slightly tricky, we would not look at graph. We will do it without that. Now, how exactly is this going to work? Let's say we've got a function like this. For reciprocal functions, if you have any function like this, 3 over 2x plus 1, and you're given the domain of the function that's x greater than 0, we think about the endpoints of the domain. If x is greater than 0, what does that mean? What's the minimum value for x? The minimum value for x is 0. What's the maximum value for x? It's greater than 0. So on the maximum side, it's basically going up to infinity. There's no limit as such. It can go as far as possible. So we consider the endpoints of x. We say, okay, one possible value for x is 0. Another possible value of x is infinity. So what happens when x is 0? What happens when x is infinity? We think about those extreme points. So we input x equal to 0 in this function. X equals 0 gives us 3 as the result. We think about what happens if x becomes infinity. Now, what happens if x becomes infinity? You have infinity in the denominator. Any number divided by infinity, that is going to be extremely small, so it's going to approach 0. If you find that hard to think about, another idea about this could be that in your calculator, just input that function 3 divided by 2 into x plus 1. In place of x, put a very large number. And think about what the value looks like. For example, I can input 10 raised to power 10 in place of x here. The value turns out to be 1.5 into 10 raised to power minus 10. 10 raised to power minus 10, that's an extremely small value. So that's basically telling you that that this value is going to be approaching 0. It will be very close to 0, right? So you can think about this from a calculator as well. But just remember, when you have infinity in the denominator, the result is going to be extremely small and it's going to approach 0 eventually. So now the endpoints that we're getting for the y value, they are 3 and 0. So what do we say about the range of this function? We say the range of the function is from 0 to 3, right? So 0 is the minimum value, 3 is the maximum value. Now we're not putting equal to sign with any of them. Why is that? Because in the domain, there was no equal to sign with 0. The corresponding y value for 0 was 3. So we don't put any equal to sign with 3 as well. What about 0? Why are we not putting an equal to sign with this? Because when the denominator is infinity, the value is very close to 0, but it does not become equal to 0. So we don't put an equal to sign with 0 as well. We say the range is just between 0 and 3 like this, and that's our final result. Similarly, if you had an example like this, 1 over x plus 5, you want to find the range of this function. The domain of this function is x greater than 0. Now, again, how do you think about that? It's greater than 0. So what's the endpoints of the domain? The minimum value is 0. The maximum value is infinity again. It can go from 0 to infinity. We think about what happens when x is equal to 0. And we think about what happens when x is going towards infinity. Now, the problem in this function is we cannot really input the value for x as 0 here because that becomes undefined. So how exactly do we think about this? Since it's greater than 0, we can think about a number that's very close to 0. So if you input 1 over 0 in your calculator, that's going to be undefined, right? That will not give you any value. So the workaround for that could be that you input a very small value, 0.000, input a lot of zeros there, and think about what the result that you're getting. That's 10 raised to power 23, or whatever, however many zeros that you have there. Depending on that, you'll get a very large number here. So what that tells you is that when x is going toward, and when x is close to 0 here, the value of this whole function, that's extremely large. So that goes towards infinity. Or another way to think about this is, just remember, when you have 0 in the denominator, the value becomes very large. Although, strictly speaking, in mathematical terms, we say that this is undefined. However, since this is greater than 0, when you have a very small value, the overall result is going to become very large. So that's actually going to approach infinity. So that is what happens when x goes towards 0, the value for y, that is going to go towards infinity. So that's one endpoint that we've got for the range, that's infinity. Then think about what happens when x goes towards infinity. When x goes towards infinity, when x is a very large number. Now, if x is a very large number, we get something like this: 1 over infinity plus 5. Now, what's 1 over infinity? 1 over an extremely large number, that's going to become 0. But then we're adding 5 to that. So it becomes 5, and that's the result that we've got. So what's the range then? The range is from 5 to infinity. Okay, that's the range that we've got, 5 to infinity. This is one way to write this, that the range is from 5 to infinity. Another way to write this could be that just y is greater than equal. Y is just greater than 5, because infinity is not a limit as such. It's just y greater than 5. All right. Okay. Let's have a look at this example. 1 over x minus 3 whole squared. The domain is x is greater than or equal to 5. Domain is x greater than or equal to 5. That's the domain of this function. Again, we think of the endpoints. We think of what happens when x is 5 and what happens when x goes towards infinity, right? These are the endpoints of the domain from 5 to infinity. Now, what happens at 5? We can just input 5 in the function, and that gives us 1 over 4. What happens at infinity? When you have infinity in the denominator like this, again, what happens is the number is going to approach 0. So you get 0 from that. So the endpoints that you're getting for the range here are from 0 to 1 over 4. So that's the range that we write here. Now, do we put an equal to sign with any of those numbers? How do we think about that? It's x greater than or equal to 5. So the corresponding value for 5, 1 over 4, that is going to have an equal to sign here. But when the denominator is infinity, in this case, the value is going to be approximately equal to 0. It's not going to be exactly equal to 0. In that case, we don't put an equal to sign with this case. Okay, all right. Let's move on. So, okay, just a reminder. Question. I'll be taking your questions at the end. Okay, so otherwise it'll take too long. It's already going to take too long. Like four and a half hours today. So just a reminder what we discussed yesterday, that while I'm explaining this, I'll be reading some of your questions. If I can incorporate them right there, I will do that. Otherwise, I'll be answering your questions once we're done with the topic. Okay. Otherwise, it will become too slow and we'll not be able to do many topics today. Okay. Okay. All right. Now, the function is defined as follows. So keep a note of your questions. We will be answering them. Okay. All right. The function f is defined as follows. F of x is equal to square root of x minus 1 for x greater than 1. That's a function that we've got. Now, find an expression for f inverse of x. Now, that's fairly straightforward. Now, let's think about this part. It says the diagram shows the graph of y equals g of x, where g of x is equal to this. Now, we've got a graph of this function. This is the reciprocal function. In this case, we think of the graph to state the range of the function. How do you do that? Look at the graph. Remember what the range represents. Range represents what's the maximum value going to be on the y-axis and what the smallest value is going to be on the y-axis. What's the highest value on the y-axis on this graph? The highest value on the y-axis is 0.5. You can find that by inputting x equal to 0, the y-intercept of the graph, put x equal to 0 here, that gives you 0.5. So you say the maximum value for y is 0.5. And what about the minimum value? You can see it's becoming an asymptote here on this side and also on this side. So on the lower side, the value is getting very close to 0. You can think about what would happen if x becomes very large here on this side. In the denominator, you would end up getting infinity, and then the value is approaching 0. So what's the maximum value that you're getting on the graph? 0.5. The minimum value, that's 0. So what's the range going to be? It's going to be from 0 to 0.5. We put an equal to sign with 0.5 there because 0.5 is actually part of the graph. But we do not put an equal to sign with 0 there because it's not becoming equal to 0. It's only approaching 0 on the x-axis. Okay? That's what the range of this function is going to be. So for reciprocal functions, if you do not have a graph given, I would not recommend that you draw the graph. It's going to take time and it's a bit complicated. Just think of the endpoints. If you have the domain given, just think of the endpoints. In this case, for example, if x is greater than 0, 0 is one endpoint, infinity is another endpoint. Just check what happens at those points. If you have a graph given, in that case, you think of the graph itself. In that case, think of the graph itself. Think of what the maximum value on the graph is, and think of what the minimum value on the graph is, and that will give you the range of that function. Okay. Now, so in general, when you're finding range of any function, these are the important points that you have to consider. Endpoints of the domain, we've seen them in the previous examples that we've seen in straight line functions as well, and also in the reciprocal functions. We think of the endpoints of the domain. However, there are some functions that have turning points as well. For example, in this reciprocal function that we had, we also had to think of this turning point. Now, for reciprocal functions, they will always give you the graph in case you have to think of the turning point. If they do not give you the graph, then there would not be any turning point, and you can just think of the endpoints. However, there are some functions for which you need to be able to think about the turning points yourself. For example, quadratic functions and trigonometric functions. For these two functions, you will have to consider these two sets of points, endpoints of the domain and the turning points of the function. These are 2 points that you will always have to consider to understand what the range of the function is going to look like. Let's have a look at some examples of quadratic functions now. Let's say we've got a function like this, 2x squared minus 12x plus 24, and the domain is all real values. Now, for a quadratic function, if the domain is all real values, the range is not going to be all real values because the quadratic functions look either U-shaped or N-shaped. So they will have some maximum value or some minimum value. So how do you find range of quadratic functions? You always have to find out the turning point of the quadratic function. We know how to do that, minus p over 2 a differentiation, completing square. You find the turning point using any method. Let's say, in this case, the turning point turns out to be 3 and 6. Now, since x could be any real value, it could be all real values. What that means is, on this graph, you think about it, what's the lowest point on the graph? The lowest point of the graph is 6. On the upper side, there is no limit. The value of y could go up to infinity. So we say the range of this function is y greater than or equal to 6. That's the range of this function. Remember, the range is on your graph, what's the maximum point and what's the highest point and what's the lowest point. That's the range. The lowest point in this case is 6. There's no highest point. So we say the range is y greater than or equal to 6. Now, if they restrict the domain, so if it's the same function, but they restrict the domain like this, they say that x is now less than 5. X is less than 5. Now, what does that mean? How do you think about the range of this function? Now, you have to think of the turning point and you have to think of this point 5 and consider both of them to figure out what the range is going to look like. Find the value for y when x is equal to 5. That turns out to be 14. Mark that point on your graph. Now, this is what the graph is going to look like. It's a U-shaped curve. You mark the turning point. Where is this point going to be? X equals 5 is going to be on the right side of the turning point. That point is 5 and 14. That's this point. Now, which part of the function is valid? X less than 5. That means we're looking at the part that is towards the left side of 5. So all of this part of this graph is valid. Now, in this yellow part, what's the lowest point? The lowest point is 6. What's the highest point? On the left side, you can see the graph is going as far up as possible. It's going up to infinity. So what's the range of the function then? It's y greater than or equal to 6 in this case. Take another example. If we had that same function, but the domain was now x greater than or equal to 4. What about this now? You think of the value for y when x is equal to 4, that turns out to be 8. This is the point on the graph when x is equal to 4. What part of this graph is valid? To the right side of 4. To the right side of 4, this is the part of the graph that is valid. What's the corresponding part on the curve? I've shaded that here. So vertically now, what's the range? The lowest point on the graph is 8. The highest point on the graph is infinity. So the range turns out to be y greater than or equal to 8. So for quadratic functions, you always have to sketch the graph, mark the part of the graph that is valid for the given domain, and in that part, think about what's the lowest value on the graph and what's the highest value on the graph, and that will be the range of the function. Let's consider another example. If it was x less than 0, again, you think of that point when the value for x is 0, the y value turns out to be 24. It's the same turning point because it's the same expression as before. 3, 6, which side of the turning point is this point going to be? X equal to 0. It's on the left side of the turning point. So we mark that point. Now, which part of this graph is valid? To the left of 0. So what's the range? This is the highlighted part. This is the valid part of the graph. On the graph, think about what's the lowest point. The lowest point on the shaded part, on the valid part, is 24. The highest point, that's infinity. So the range is going to be greater than 24. We don't put an equal to sign here in this case because the point 0 was not included. So the corresponding value for y, 24, that's also not included. We don't put an equal to sign in this case. Okay. Let's take one last example in this, or the second last example. The domain is x between 0 and 4. Okay, so now one of these points is on the left side of the turning point, 0. The other point is on the right side of the turning point, 4. So this is one point, this is another point. You find the corresponding values of y at both of them. They turn out to be 24 and 8. And think about what part of this graph is valid. So this yellow part is valid between those 2 points, between 0 and 4. This is the part that is valid. Now, what's the range going to be? Look at the graph. Look at what's the lowest point of the graph. The lowest point of the graph is 6. And the highest point of the graph is 24. So what's the range going to be? It's going to be between 6 and 24. Now, since the point 6 is included because that's in the middle of that valid part, 24 is also included. Is that included? No, 24 is not included because the value for x here, 0, that 24 corresponds to, that was not included. So we don't put an equal to sign with 24 here. So that's the range. It's from 6 to 24. That's the range of this function. If you had something like this, if the domain is from -1 to 2, now which part of this function is valid? Again, think of the turning point. The turning point is here. Where are these 2 points going to be? Both of these x coordinates are less than the x coordinate of the turning point. So both of these points will be on the left side. So this is x equals 2. This is x equals -1. The value for x has to be between these 2 points. So now this is the valid part of the graph, the shaded part. What's the range? Think of the lowest point in this region and the highest point in this region. The lowest point in this region is 8, and the highest point in this region is 38. So that's the range of this function. It's from 8 to 38. That's what we write there. We do not include 38 because -1 was not included. So we don't put an equal to sign there. But there was an equal to sign with 2 here, so the corresponding value 8, that does have an equal to sign. Okay, so these are all the different cases that you could have in a quadratic function. You always have to sketch the graph, find the turning point, shade the part of the graph that is valid, and in that shaded part, think of what's the lowest point on the graph and what's the highest point on the graph, and that will give you the range of the function. Next, we've got trigonometric functions. How do you find range of trigonometric functions? Let's say we've got a function like this, y equals f of x equals 3 minus sine x, and the domain is from 0 to 360 degrees. And we want to find the range of this function. Now, whenever a trigonometric function, sine and cos in particular, whenever their cycle is completing, whenever their cycle is completing, so from 0 to 360, sine x completes its one cycle. For sine and cos in particular, their values are between -1 and 1, right? The graph of sine and cos, both of them, their lowest value values are -1, their highest values are +1. They're always between -1 and 1. So whenever they're completing a cycle, if you want to find the range of a function that includes one of these functions, all you have to do is consider the extreme values of sine and cos. So in this case, you've got sine. What are the extreme values of sine? The lowest value of sine could be -1. The maximum value of sine could be +1. So once we input sine x equal to 1 in the function, that gives us one value. And then we input sine x equal to -1 in the function, that gives us another value. And we say the range of the function is going to be from 1 to 5. And that's our final answer. Take another example. Let's say we've got this function. Now this is tan. On tan, that rule does not work. So this function is actually this misprint here. It's 3 minus 2 into tan of half x. That's what the function is. You want to find the range of this function. Now tan does not have its values between -1 and 1. Tan can go from negative infinity to positive infinity. In this case, you just have to check the endpoints, check what happens at 0, check what happens at pi, and that is going to be the range of the function. 0 is giving you 3, pi is giving you negative infinity. So you say the range is going to be from -infinity to 3, or if you say -infinity to 3, that's the same thing as saying that it's just y less than or equal to 3. Now for sine and cos functions, you try 1 and -1. If the cycle is completing, for tan, you just check the endpoints, check what happens at 0, check what happens at pi, and that will give you the result. But if you have sine square or cos square, what about that? Look at this example. So let's say we have a function that looks like this. Y equals 2 sine square x minus 3 cos square x, and the domain is from 0 to pi. Okay, now what about this? Whenever you have a square function, now, if you have sine or cos, their values are between -1 and 1. But when you square something, you cannot have a negative value from that. So cos square is going to be between 0 and 1, right? So these negative values are also going to become positive. And so it's the values for cos x are basically between -1 and 1. So these negative values, when you square the function, they also become positive. So now the square function only has values between 0 and 1. So for sine square and cos square, what you would do would be, you would consider 0 and 1 as the endpoints. But for finding range of these functions, first of all, you would have to convert them to the same function. For example, in this original expression, you have both sine square and cos square. In order to find the range of this function, you either want to convert both of them to sine square or both of them to cos square. That's why they make you do that in the first part of this question already. They make you convert the function to cos square first of all. Now, once you have done that, in this expression now, 2 minus 5 cos square, all you have to do is try the extreme possible values of cos square. What were the extreme possible values of cos square? They were 0 and 1. Input 0 once, and then you input 1. The result that you get from that will be the range. You'll say -3 is the minimum value for y, 2 is the maximum possible value for y, and that's the range of this function. This is one way of doing this, although I now actually recommend using your calculator for this as well, and that makes it even easier. And that is basically this idea that you just put this function on your calculator. Just put this function on your calculator. It's the same for sine square, yes. For cos square, sine square, you just input 0 and 1 as the extreme points. But there's another way to do this, and that is the way that we use to sketch functions. Use the table function. This function is in degrees right now. So what we can do is we can select degrees from here. In the table function, input this 3 minus 2 sine x. Now the interval that's given is from 0 to 360. So start at 0, end at 360. And what about the step? I recommend whatever is the interval that's given, you divide that by 8 generally, right? So if this is the interval that's given, 0 to 360, 360 over 8, what does that give you? That gives you 45. Take that as the step, and that will give you enough values to basically understand what the maximum value of the graph is going to be, what the minimum value of graph is going to be. So step 45, just input this on your calculator and see what you get. This is the function these are the values that you're getting just look at the table and see what the maximum value is and what the minimum value is. In these values, you see 1 is going to be the minimum value. There's no value that's less than 1. And 5 is going to be the maximum y value. And that's what you write there. You write that the range is from 1 to 5. Similarly here, again, you can just input this function in your calculator directly and see what the highest value for y is in the table function and what the lowest value of y is in the table function, and that should work. In this case as well, for the square function, you can just input that directly like this. You would say f of x is equal to 2 sine square x sine of x whole squared. So in your calculator, you have to write down sine square x in this form. Sine square x minus 3 cos square x just input this function on your calculator, and then what's the domain that you're given? It's in radian first of all. So you have to convert the angle unit. Sorry, let me go back there. That's the table function. 2 into sine of x squared plus, or in fact minus 3 into cos of x whole squared. You could input this form, or you could also input this form. Both of them will work because it's the calculator doing it, so you won't have to worry about this. What's the starting value? It's 0. What's the end value? You're ending at pi. And what's the step going to be? Divide that by 8. Pi over 8, and see what that gives you. Look at whatever is the maximum value in this table. So minus 3 is one value that we're getting. That seems to be the least value. Keep going on. What's the maximum value? The maximum value that we're getting is 2. The maximum value is 2. Minimum is minus 3. Maximum is 2. That's what you write there. That's the range of this function. So you can use use your calculator to do it as well. Okay, that will also work. All right. Now, sometimes what happens is they give you the range of the function themselves. They give you the range of the function themselves. For example, in this function, they tell you that f of x is equal to a minus b cos x. And they're saying that the maximum value of f of x is 10 and the minimum value is minus 2. Now, how do you think about this? How do you find the values of a and b? In this first part, we have to find the values of a and b. Now, for this, as we'll see later, you can think of the graph. That's one idea. That the graph of the cos function, it has its maximum value at 10 and its minimum value is at minus 2. So where is the baseline going to be? The baseline of the graph is going to be exactly in the middle. What's the midpoint of minus 2 and 10? That is 4. That's the midpoint. 4 is the midpoint. Now 4 is the baseline. So the number that's outside here, that represents the baseline, as we'll see in function transformations as well. This represents the baseline. So you can write a equal to 4 there. And then this number b, that represents the amplitude. What's the amplitude going to be? The maximum vertical distance from the baseline, that is 6 units from 4 to 10 or from minus 2 to 4. That's the value of b that you get. You say the value of b is going to be equal to 6. That's one idea. Thinking of the graph, think of the baseline, and think of the amplitude of the graph. The other idea is, this is the function that you've got, a minus b cos x, and you are given the range of the function. Again, it's a cos function. It's completing one full cycle. You input cos x equal to 1 once, and then you input cos x equal to minus 1. Input those two values and see what you get from that. 1 is giving us a minus b. Minus 1 is giving us a plus b. Which of these values is bigger? A plus b, you're adding two numbers up. So a plus b has to be bigger. So we say that is going to be 10. And a minus b is the smaller value. We say that's going to be minus 2 because they told us that the least value of the function is minus 2 and the maximum value of the function is 10. So we say a minus b equals minus 2 and a plus b equals 10. We get two simultaneous equations from that, solve them, and you get the result from that. Now, this is one idea, but thinking of transformations makes it much quicker. So when you have the range given like this, you can think of the graph, think of where the baseline is going to be, think of what the amplitude is going to be, and based on that, you write down the values of those unknowns. All right, so this is the next thing that we need to know about the different types of relations two variables can have with each other. So there are four different types of relations that any two variables can have with each other: one-to-one, many-to-one, one-to-many, and many-to-many. Now, what's a one-to-one relation? One-to-one relation means that for each value of x, we've got only one value for y, and for each value of y, we've got only one value for x. So for every x, we've got for each x, we have only one y. For each y, we've got only one x. What kinds of functions are these? For example, straight line like this. You could have a curve like this. In this curve as well, you have one value for x for every one value of y, and one value for y for each value of x, right? The other type of function is many to one. In these functions, you can have multiple x that can give you the same value for y. For example, in this case, you've got these two values of x that are giving you the same value of y. One very common example of this is quadratic functions. In quadratic functions, for example, if you have y equals x squared, -2 gives you 4, +2 also gives you 4, -1 gives you 1, +1 also gives you 1. These are called many to one relations. All polynomials apart from linear functions, they are generally many to one. Cubic function, for example, if its graph looks like this, if this is a many to one function. Then you have a one-to-many relation. In one-to-many relation, you can have multiple y values coming from one single x. So one x can give you many y. That's a one-to-many relation. For example, you would have a curve that looks like this. This one value of x that's giving you multiple values of y. One value of y here, another value of y here. That's called a one-to-many relation. For example, if you have a function like this, y squared equals x, this is a one-to-many relation. And then you have a many-to-many relation. For example, if you have a circle or an oval, this is a many-to-many relation because one x can give you many y, one y can also give you many x. So on both sides, it's many-to-many. This is a many-to-many relation. For example, this value of x that's giving me this y and also this y, and this value of y that's giving me this x here and this x here. This is called many-to-many. Now, what's important to know in these relations is, I'm sorry. Yeah. So these are four different types of relations: one-to-one, many-to-one, one-to-many, and many-to-many. Only the first two, one-to-one and many-to-one, we classify only these first two as functions. The last two, one-to-many and many-to-many, they are not functions. They are relations, but they are not functions. Only one-to-one and many-to-one relations are functions. So for a relation to be a function, the condition is there should only be one output. So it could be one-to-one or many-to-one. You cannot have multiple outputs. That's not allowed. And out of these functions, only one-to-one functions have inverse. Many-to-one functions do not have inverse, because when you inverse a many-to-one function, that will become one-to-many, and one-to-many is not a function. So for many-to-one functions, the inverse does not exist. Inverse only exists for one-to-one functions. So you need to know about these relations for understanding inverse functions. Now, how do you identify if a function is one-to-one or not? We have this test for this that we call the horizontal line test. And the test basically says, can you draw any horizontal line on the graph of the function that cuts the graph at more than 1 point? If you can do that, then it's not a one-to-one function. If you cannot draw any horizontal line on the graph that cuts the graph at more than 1 point, then that would be a one-to-one function. For instance, let's try that here. On this graph, on this straight line graph, if I draw any horizontal line, it can only cut the graph at 1 point. So this is one-to-one. On this graph as well, if I draw any horizontal line, it can only cut the graph at 1 point. So this is a one-to-one function. But in this case, in these examples, if I draw a straight line here, a horizontal line here, that's cutting the graph at more than 1 point. If there's even one line that I can draw like this on the graph, that means it's not one-to-one, because there are multiple values of x that are giving us the same value for y. So this is not one-to-one. Similarly here, I can draw this line, and that makes it not one-to-one. So this is the horizontal line test. Can you draw at least one horizontal line that cuts the graph at more than 1 point? If the answer to that is yes, then that's not one-to-one. If the answer to that is no, then it is a one-to-one function. And inverse only exists for one-to-one functions. Okay. So what is an inverse function? You've done this in O levels already for linear functions. How does it work? If you have a function that looks like this, f of x equals minus 2x plus 5. How does the process work? You replace f of x with y first of all, and that becomes x equals f inverse of y like this. Or in fact, I could just ignore that as well because it's not required right now. Okay, so you could say, let's just say let y equals f of x. So I'll just cut out the detail there. Okay, so this is how the inverse process works. You say let y equals f of x. Then once you do that, it becomes y equals minus 2x plus 5. And now you make x the subject. When you make x the subject, eventually all you have to do is replace x with f inverse of x and replace y with x, and you get your inverse function. Now, what exactly is an inverse function? Inverse function basically does the opposite of what the original function does. So in this original function, for instance, if you were to input x equal to 1, what would you get from that? You'll get y equal to 3 from that. In this inverse function, if you input x equal to 3, you get y equal to 1. So the input becomes output in the inverse function. So it basically does the opposite of this. So going in this direction from 1 to 3, we had to apply f. If we wanted 1 from 3, we apply the inverse function. So x and y, they basically interchange in the inverse function. Okay, so their domain and range also reverses like this. So think about this. If you've got this function, f of x equals minus 2x plus 5, if you input x equals 2 in this, you get 1 from that. In the inverse function, when you input x equals 1, you get 2 out of that, right? So it does the opposite of what the original function does. So when you think about the domain and range of these functions, this is what happens. If the original function f of x has a domain that is x greater than 0, then that becomes the range of the inverse function. That the range of the inverse function that becomes greater than 0. So if this is greater than 0, the range of the inverse is greater than 0. If the range of the if the range of the original function is less than 5, that becomes the domain of the inverse function. So that's the relation between the domain and range of a function and its inverse. The domain of original function becomes the range of inverse. The range of the original function becomes the domain of the inverse. So if the domain is x greater than 0 for the original function, the range for the inverse function would also be greater than 0, but we have to be careful about the variables. When we're talking about domain, it's x. When we talk about range, it's y. So this was x greater than 0 on the left side. For the range, it becomes, for the inverse, it becomes y greater than 0. Similarly here, the range of the original function was y less than 5. The domain of the inverse function becomes x less than 5, because domain are values of x and range is values of y. So if you think about a point, any random point on the original function, if its coordinates are, let's say, a and b, for the inverse function, what happens is the coordinates get interchanged and they become b and a. So x becomes y and y becomes b. The coordinates switch like this. Now, this is shown in graphs as well. When we draw a function, an f of x function and its inverse, when we draw both of these graphs on the same line, on the same graph, what happens is they are always reflections of each other in this line y equals x. If you remember your O-level transformations, when we used to reflect anything in y equals x line, the coordinates used to switch. X used to become y used to become x. That's exactly what happens in a function and its inverse as well. Whenever you draw these functions on a graph, they're always going to be reflections of each other in the line y equals x. So whenever they say draw a function and its inverse and explain or identify the relation between the two graphs, you would always draw this y equals x line as well and show or write that they are reflection of each other in the line y equals x. Now, while you do that, you need to make sure that on both the axes, you're using the same scale. Whatever you have marked as 1 unit on the horizontal axis, you should mark as 1 unit the same distance on the vertical axis as well, because otherwise your transformation, the reflection is not going to look good, and it will not actually look like a reflection if the scale on both axes is not the same. So whenever you draw the inverse function in its original graph, always draw y equals x line and also use the same scale on both axes. Okay, so that we talked about how to find inverse of linear functions. Sometimes you'll have to find inverse of trigonometric function as well. Now that's not very complicated. For example, if you have a function like this, f of x equals 5x, 5 sine x minus 2, what is the inverse going to look like? First of all, we say let y equals f of x. Okay, so that becomes y equals 5 sine x minus 2, make x the subject. Now when you make x the subject, if you have sine x here, when sine goes to the other side, that's going to become sine inverse. So we get x equal to sine inverse of y plus 2 divided by 5. And then at the end, all we have to do is replace x with f inverse, and on the right side, replace the variable y with x, and you get the result from that. Inverse of quadratic functions. Now, quadratic functions also have inverse. Now, how does that make sense? Quadratic functions are generally not one-to-one, and inverse only exists for one-to-one functions. So if you have a graph like this, if you consider this whole graph is not one-to-one because it fails this horizontal line test. But you can still find the inverse if you restrict the domain of this graph. So for example, if you had this quadratic function, x squared minus 2x plus 3, and the domain of this function was x less than 0. Now, the turning point of this graph is actually when x is equal to 1. So where is this point going to be? X equals 0. This point is on the left side of the turning point. So that point is somewhere here. This is the point 0 and 3. So which part of this graph is valid? Only this part, to the left of x equal to 0. Now this yellow part, if you just focus on this part of this function is indeed one-to-one. So for this yellow part, we can find the inverse. Now, how will that process work? How will we find the inverse of this quadratic function? Whenever you have to find inverse of quadratic functions, the first thing you always have to do is complete the square, because otherwise you would not be able to make x the subject. So whenever you have to find inverse of quadratic functions, you always complete the square for that function first of all. So in this case, for instance, when you replace f of x with y initially, then what you have to do is you have to complete the square for that, because then you can make x the subject. When you have completed the square and you got this form, you take the constant to the other side. So you get this thing, x minus 1 whole squared equals y minus 2. And now you take square root on both sides. When you take square root on both sides, do not forget the plus minus, because whenever we take square root, we always have plus minus. But then we have to decide whether to use the plus sign there or the minus sign there. So when we make x the subject, in this case, we're getting 1 plus minus square root of y minus 2. That's the result that we're getting. But that's the expression that is basically the inverse of this whole thing. And that graph, basically, the graph of this thing would look like this. The one that you see at the bottom here, you have one part here, you have another part here. And that's not even a function. This is one to many. So plus is giving you one part and minus is giving you another part. You only have to consider one of them. It can either be plus here or minus here. You always have to first write plus minus there and then figure out whether to use plus there or minus there. Now, how do you do that? Once you've made x the subject, you look at the domain that is given for that question. The domain is x less than 0 in this case. So you say, okay, the domain is x less than 0, and we are getting 1 plus minus square root of y minus 2. How can we get a value of x that is less than 0? Do we get less than 0 value when we do 1 plus something or 1 minus something? We can only get less than 0 when we do 1 minus something. So in this case, we choose the minus sign, and we say the inverse, therefore, is going to be 1 minus square root of x minus 2. So using the domain of the function, when we have made x the subject, we have to decide between the plus and minus in this function, and then just write one of them. Sometimes it's going to be negative, sometimes it's going to be positive. You have to think about it using the domain like this. Consider this example. Let's say we've got this function, x squared minus 2x plus 3. How do you find the inverse of this function? Again, you complete the square first of all, you make x the subject. Eventually, you will get something like this. 1 plus minus something. It's actually the same expression as before, but I've changed the domain now. The domain is from 1 to 6 now. What about the inverse of this? Now the domain is from 1 to 6. How can you get a number from this expression that is between 1 to 6? Would you have to do 1 plus something or 1 minus something? If you do 1 minus something, that value will be less than 1. That's not what we want. We want something that's greater than 1. So the final sign that you use here, it's going to be a plus sign. So the inverse function therefore becomes 1 plus square root of x minus 2, and that's your final result. So always complete the square, and then you make x the subject. Do not forget to put plus minus with the square root there. And then you use the given domain of the function to figure out whether to use plus or minus in your final result. That's how you find inverse of quadratic functions. Let's have a look at a couple of examples in this quickly. Let's say we've got this function, 2x squared minus 8x plus 11. And the first part is just about completing the square range. I just want to focus on this part. First of all, explain why f does not have an inverse. So this function is defined for all real values of x. Why this function does not have an inverse? Because the graph of this function would actually look like this. It's a U-shaped function. It's not one-to-one. So whenever they ask you something like this, whether a function whether a function has an inverse or not, you think about whether that function is one-to-one or not. So in this case, this is not one-to-one, because it fails the horizontal line test. That means that the inverse does not exist. So that's what you write there. It's not a one-to-one function. But then this last part is important. It says there's another function g of x, and that is 2x squared minus 8x plus 11. It's the same function as before, same expression as before, but the domain has changed. And the domain is that x is less than or equal to some value. Now, we need to state the largest value of a for which this g of x function would have an inverse. Now, what's the graph of this function going to be like? It's a U-shaped graph like this. And they are saying that the domain of this graph is x less than or equal to a. Now, we will have some turning point of this graph. We have already found that in the second part for finding the range, the turning point of this graph is 2 and 3. That's the turning point of this graph. Now, if on the x-axis, you have some point A somewhere, what's the largest value of A that you can have so that this function would have an inverse? It becomes a one-to-one function. If I put A here on this side, then this part of the function would be valid. To the left of A, this is not one-to-one, and that would not work. If I put A on the left side here, then to the left of A, this part of the function would be valid, and this is one-to-one. This could be one possible value for A, but they are asking us for the largest value for A for which it would have an inverse. So how far can A go toward the right side so that it would still have an inverse? So I can start from the left side of this function. I can keep going on. The yellow part still has an inverse. It still has an inverse. I can go up to the turning point. At this point, if I were to go any further, the function would not remain one-to-one. So what's the largest possible value of A that we can have? The largest possible value is when we are at the turning point. So what's the value of x at the turning point? That is 2. It was the domain of the function, right? X less than or equal to A. So we say the largest possible value of A here could actually be 2, and that's the result that we write down there. We say the largest A is there for 2 because that is when this function would still have an inverse. It will be the x coordinate of the turning point. Similar to that, sometimes they ask you for the smallest value of something for the function to be a one-to-one function, and then the domain has x greater than or equal to something. In the previous case, it was x less than or equal to something. In that case, we were looking for the maximum value. Now it says x is greater than or equal to k. Now, that means in this quadratic function, so you can go through the rest of the parts in your own time later on, but this is the function, and the domain is x greater than or equal to k. We want to find the smallest possible value for k for which this function would have an inverse. So again, think of it the same way. It could be at the turning point. If the value for k was even slightly to the left here, then the function would not be one-to-one anymore. So any such question like this, where they ask you for the maximum or smallest value of a constant such that the function remains one-to-one, what you do is you think of the turning point. The turning point is going to be that maximum or minimum value, the x coordinate of the turning point, that will be the value that you write there. It's k equal to 3 in this case. Okay, then you have composite functions. Composite functions are when you have one function inside another function. Yeah, and you have one function inside another function. Now, what do they look like? So let's say we've got a function f of x and we have another function g of x. They're both defined for all real values of x. F of x equals 4x minus 3 and g of x equals x squared plus 2. These functions are defined for all real values of x. How do you evaluate the function fg of x? Now, fg of x basically means that you want to input g of x inside the function f. Okay, you want to input g of x inside the function f. So the way to evaluate this is that you introduce an extra bracket here like this. And then you say, inside the function f, you have to input g. Input g there, the function g is x squared plus 2. And then you're saying f of x squared plus 2. Inside this function, wherever you have x, you just replace that with x squared plus 2. Simplify this, and you get the function fg of x. What about gf of x? Gf of x would be that inside the function g, you input f of x. Now, what's f? F is 4x minus 3. So you basically say, inside the function g, wherever you've got x, you replace that x with 4x minus 3, and that gives you the function gf of x. That's how you evaluate fg or gf. Now, it's important to remember fg and gf are not equal to each other in general. These are not numbers that are multiplying, that if you change the order, it would remain the same. These are functions. If you input f inside g, that's a different function. If you input g inside f, that's a different function. They're not equal to each other in general. Then you have this notation, f square of something or g square of something. What does that mean? F square is not the same thing as saying if the function f of x is 4x minus 3, f square of x is not this, that you say 4x minus 3 whole squared. That would be for f of x whole squared. That's a different thing. F of x whole squared, that would be 4x minus 3 whole squared. But when it says f square of x, what that means is you've got the function f coming twice there. So it's a composite function such that you're inputting f inside the function f. Okay, so function f is being put inside itself. So inside f, you're inputting f 4x minus 3. So wherever in that function you've got x, you replace that with 4x minus 3, and you get that result. To simplify that, you get that result. You could have three functions like this sometimes as well. You've got f here, you've got g here. You may have to evaluate f squared g of x. What does that mean? You first of all break it down into parts like this. You say, okay, f squared means f, and then g. And then you put a bracket with the function that is closest to x. What's the function that's closest to x? That's g right now. Input the value for g there. The value for g is x squared plus 2. You input that here. And now you put another bracket to the next function like this. Evaluate f of x squared plus 2. So inside the function f, you input x squared plus 2. That becomes 4 into x squared plus 2 minus 3. Simplify this. When you simplify this, you get something like this. Now, finally, it means you input 4x squared plus 5 inside this expression. So when you have three functions like this, you go step by step like this. You put this bracket, you evaluate this thing, then you put another bracket, you evaluate this thing, and then finally, you will get something like this that you can simplify finally. Okay, so you can have three functions like this as well in composite functions. Okay, now sometimes what you end up getting in these problems is, in recent papers, you'll find this multiple times. If you have a function f of x equals 4x minus 3 and another function g of x equals x squared plus 2, and you are given that f h of x is equal to g of x, and you want to figure out what the function h of x is in terms of x. So we are given this equation, f h of x is equal to g of x, and what we have to find out is the function h. So we want to make h of x the subject somehow. Now, how can we do that? We want to get rid of f from this side. Now, the way to do that is we apply the function f inverse on the left and also f inverse on the right side of this equation. So we can apply the same operation on both sides. Since we want to get rid of f from there, we say, let's find the f inverse function. First of all, f inverse turns out to be x plus 3 over 4. And now we apply the function f inverse on both sides of the equation in the beginning because f is on this side. So we have an f inverse introduced here because f inverse and f, they're opposite of each other. They will cancel each other's effect. So we will get rid of them on the left side. We're just left with h of x there. On the right side now, we have f inverse of g of x, and that's something that we can evaluate. We know the function f inverse. Inside the function f inverse, all you have to do is input x squared plus 3 in place of x, and you would get that function h of x. Now, in this case, it was fh equal to g. It could also be reversed. So what if we had h f of x equals g of x? What do you do in this case? Again, if you had to find the function h of x from this, you want to get rid of f from this side. How do you do that? How do you get rid of this function f? Now, the function f is coming on the right side here, as in after h. In order to get rid of this, you will have to introduce f inverse on this side now. Rather than in the beginning, you have to introduce f inverse afterwards at this point. So you do the same thing on both sides of the equation. You have an f inverse here, you have an f inverse here. Now on the left side of the equation, these two basically cancel each other's effect, and we're just left with h of x, and that equals g f inverse of x. Inside the function g now, you have to input f inverse, and that gives you the function h of x. So if you want to make one function the subject from an expression like this, whatever function it is that you want to eliminate from that side, you apply the inverse of that function, either in the beginning or at the end, to get rid of that function from there. Okay, now this is an important part of composite functions, and that is, if you have a function fg of x that looks like this, fg of x, how exactly does this function work? This function works like this. Step by step, what happens is, the input that you give to the function, that is first going to go to g, the function that's closest to that. So input goes to g first of all. And then g gives you an output. That output is g of x. And then what happens is, that output that you get, that goes as an input to the next function, which is f. And from that, you get the final result, which is fg of x. That's how a composite function works. The function that's closest to the input, that's applied first, and then the next function after that. Now, this gives us something very important about the domain and range of composite functions. So you'll have problems like these where they say, you have a function f of x that looks like this. You have another function g of x that looks like this. And you want to figure out if the function fg of x can be formed or not. Now, in this, we consider the function f as the outer function. We consider the function g as the inner function. The function that comes first, we call that the outer function. The first function that is close to x, that comes after, we consider that the inner function. Now, there's a condition for the function fg of x to be formed here. And this is what that condition looks like. So think about this. The function f can take any positive value. The function g, that can take all real values. Now, remember what's going to happen? The input is going to go to function g, and g is going to give you an output, and that output is going to go to the outer function, and that outer function is going to give you the final output. Now, for this to work, the output that you're getting from the function g, the range of function g, since that has to go as an input to the function f, it should be possible to input all possible values from here in the function f, otherwise the function would break. So the range of the function g, it should be compatible with the domain of the function f. Otherwise, we would have a problem. The function f would not be able to take that as an input, and the function would break. For instance, in this case, if you find the range of this function g, it's a quadratic function, you can find the range of this. The range of this function turns out to be y less than or equal to 3. So it can give you any value that's less than or equal to 3. So at this step, the function g could give you any output that's less than or equal to 3. But the problem is the function f that can only take values that are greater than 0. And now we've got a problem because the function g can give any output that is less than or equal to 3. Now, less than or equal to 3 also means that you could have some negative values. When you have a negative value and that goes inside the function f, you would have a problem because the function f cannot accept it and the function would break. So from this, we actually get this result that this function cannot be formed in this particular example because the whole range of the function g, all the possible output values from function g, they cannot be input in the function f, or in other words, the whole range of g is not part of the domain of f. Since it's not part of the domain of f, the function would break, it cannot exist. Now, the summary of all of that is this condition that we've got, and that is a composite function, for example, fg of x, it can only be formed if the whole range of the inner function, in this case, the inner function is g, is part of the domain of the outer function. If this condition is met, then the composite function can be formed. If this condition is not met, then the composite function cannot be formed. The whole range of the inner function, it should be part of the domain of the outer function. You need to memorize this. Range of the inner function, domain of the outer function. They should be compatible, otherwise the function cannot be formed. Inner function is the function that's next to x, outer function is the function that comes first. This condition needs to be met for this condition needs to be met for the function to work, otherwise it will break. And if a function can be formed, if a function can be formed, in that case, let's say if the function is fg of x. If the function is fg of x, the domain of this function is going to be the same as the domain of the inner function. Domain of the composite function is the same as the domain of the inner function. Why is that? Because remember, in fg of x function, the input was first going into g, right? G was the first function that took an input. So if function g cannot take something as an input, that means the composite function cannot take that as an input. So the domain of the composite function should be the same as the domain of the inner function. This is the summary of all of that. The condition for a composite function to be formed is this: range of the inner function should be part of the domain of the outer function. And if a function can be formed, the domain of the composite function is the same as the domain of the inner function. Let's have a look at this example. Let's say we brought this function f of x equals 2x plus 3, x is greater than or equal to 0, and we have another function g of x that's ax squared plus b, and x is less than or equal to q. Now, in this case, in the first part, they ask us to find the values of a and b. Let's say we've done that, and we found that the composite function is this. The composite function is fg of x equals 6x squared minus 21. Now, the second part says find the greatest possible value for q. Greatest possible value for q. Now, what is q? Q is coming in the domain of the function g and the domain of this composite function. Now, what does it mean, find the greatest possible value of q? You've got a composite function here. What's that composite function? The composite function is fg of x. This is the composite function. The inner function in this composite is g. This is the inner function. So g is the inner function and f is the outer function. What's the condition for the composite function to be formed? The condition is that the range of the inner function should be part of the domain of the outer function. What's the domain of the outer function? Domain is x greater than or equal to 0. So this is the function g. This was the inner function. This is the function f. This is the outer function. The domain of the outer function is x greater than or equal to 0. That means the range of the inner function, that should also be y greater than or equal to 0. What's the inner function? It's the function g. So we say this y value, the y value of this function, all of this, it should be greater than or equal to 0, right? This represents the y value. This whole thing is y. So this has to be greater than or equal to 0. So we put that greater than or equal to 0. We solve that inequality like we solve quadratic inequalities, and we get this result from that. X is less than or equal to -2, or x is greater than or equal to 2. Since the question said x is less than or equal to q here, we consider the case that has the less than or equal to sign, and we say the greatest possible value of q that we can have in this case is this number here, which is -2. That's the value of q. That's the greatest possible value of q. That's how we use that rule. This is one way that we use that rule. Then you may have to find the range of the composite function sometimes as well. So in this case, they give us the value for q, and the value of q now they're saying is -3. We found the greatest possible value for q. Greatest possible value for q was -2, but then they're saying the value of q is -3 now. If the value of q is -3, they are asking us to find the range of the function fg. The range of the function fg. Now, how would you do that? How do you find range of a composite function? Range of a composite function is found just like you find the composite function, or just like you find the range of any function. So since we know that the domain is now x less than or equal to -3, and this is a quadratic function, you find the range of this quadratic function like you find the range of any quadratic function. Think about the turning point. Think about the graph of the function. Highlight the valid part of the graph and see what's the lowest point on the graph and what's the highest point on the graph, and you get your range from that. So finding the range of composite functions is done using the standard way, just like it's done for any function. Then how do you find fg whole inverse? Inverse of the composite function. Inverse of the composite function. Again, that's also done the normal way. If this is the composite function, just think of this whole thing as y, and then make x the subject, and you get the inverse function from that eventually. All right, so that it works the normal way as well. This is another example. So I'm going to skip the other parts. Just look at the last part here. This is the function f of x. F of x is x squared minus 4 divided by x squared plus 4. The domain is x greater than 2. Now, they're saying explain why the composite function ff cannot be formed. How do you think about that? In the function ff, what's the inner function f? What's the outer function f? So that means the range of f should be part of the domain of f. We know the domain of f, that is x greater than 2. In the second part, they make us find the range of the function f as well. It's a reciprocal function. You find the range of the reciprocal function like we normally find the range of any reciprocal function. The range turns out to be 0 to 1. Now, the function f is both inner and outer function. Now, the range of this is from 0 to 1. Domain of this is x greater than 2. Is this whole range part of the domain? It's not. The range is from 0 to 1. That these values cannot be input inside the domain of the same function. That is why you can say this function cannot be formed. Okay. Let's look at one last example. It's been a long session on functions. Let's have a look at this. We have a function f. We have functions f and g. They're defined for all real values of x. We did a very similar example in quadratics in this as well. So let's let's consider that again, just as a reminder. So we have this function f of x. That's a quadratic function, and they say that g of x is another function which is 5x minus 1. Given that the range of the function gf is greater than or equal to 39, find the value for k. Now, how do we think about this? We're given the range of the composite function. We're given the range of the composite function. Now, what's the composite function? You have to find that first of all. How do you find that? Gf of x, you input inside the function g, the function f, simplify everything, and it turns out you end up getting something that looks like this. 5 into 3x minus 2 whole squared plus 5k minus 1. That's the function that you end up getting. Now, they are saying the range of the function is greater than equal to 39. This is the range of the function, greater than equal to 39. So what's the range of the function from this? The number that's written outside, that's 5k minus 1. That's the y coordinate of the turning point. What's the y coordinate of the turning point going to be? This is the y coordinate, right? 5k minus 1. In the standard form, y equals a into x minus h whole square plus k. So the range of this function would be greater than or equal to 5k minus 1. So that means 5k minus 1, that corresponds to 39. So 5k minus 1 equals 39. And that gives you the value for k, that is 39. So if they give you the range of a function themselves and there's something that is unknown, what you can do is you can find the range of the function yourself in terms of that unknown variable, and then you compare both of them and you get the value of that unknown from that. All right. Uh, the next part is something that we already discussed. You can have a look at this. That's it on functions. I hope that was helpful, although we ended up taking a lot of time and even though I was trying to be very quick as well. I hope that made some sense. If you have any questions, you can let me know. And now we can have your questions quickly. Will we do past papers? It's a revision session. How can we do past papers? So just revising these concepts is going to take us like hours and hours. Doing one past paper takes like 1 hour 45 to 2 hours. I have a separate past paper session going on. If you want to join that, you can do that. But in the revision session, it's not really possible to uh, do past papers as such. Okay, so what we're going to do is we're going to do circular measure, and then we're going to have a long break after that. Okay, circular measure is a small thing. It's not going to take much time, and then we have a break after that. Okay, because then trigonometry is going to take longer. So after circular measure, we'll have a longer break. Okay. अभी तो time नहीं हुआ. You want to pray before it's time? It's 25 minutes till Maghrib abhi. We can probably get done with circular measure in that time. We have a lot to do. We have like 5 topics left. We've got a lot to do. We can have a longer break. Yeah, we're starting circular measure. I'm just going to answer some questions quickly. If there are any quick questions in this, let me know. So you can ask them again if you asked them earlier. Let me actually allow you to unmute yourself as well. Yeah. Okay, so some of you seem to have problems understanding the standard methods for some of these questions. For that, you need to make sure that you understand the detailed method. Again, the point of the session is revising what you already know. If you do not understand something at all, then you have to make sure that you go through a detailed video for that. So, for example, reciprocal functions, how to find range of those functions. You can, what I'll do is I'll add to the group description the P1 playlist. You can watch that particular video, range of reciprocal functions from that, to understand how that works. Because going into a lot of detail right now, unfortunately, is not going to be possible because there's so much that we still have to cover, and we will be otherwise, pulling an all-nighter. Then you guys already will get tired by 9 p.m. I think you're already tired at this point from the messages that I'm seeing. It seems like that. So if we start going into too much detail, that'll be very difficult. Okay, so that's one question that I can quickly answer about x equals 0. Where's that? Reciprocal functions. Okay, so some of you got confused here. Okay, so in this case, for instance, when you have domain x greater than 0, you cannot input x equal to 0 in this function directly. If you try doing that on your calculator, that will give you an error. One way to think about this is you say, okay, 1 over 0, just remember that's going to be an extremely large value. So you can think of that as infinity. So infinity plus 5 is still infinity. So that's going to give you infinity. Or another way to think about this is, since you cannot input 0 as such, think of a very small value instead. It's x greater than 0, right? Greater than 0 means any value that's greater than 0. So you want to check what happens at 0, try a value that's very close to 0, like 0.0000, and then put many zeros there, just to understand what it is going to look like. Now, 1 over an extremely small number like this, what do you think is going to happen? The overall result is going to be very big. Now, in that result, even if you add 5, that does not change much. It's still infinity. So that's what you get. You get infinity in this case. So that's one extreme value that you're getting for y. The other extreme value that you're getting is 5. So you say the range is between 5 and infinity, or in other words, it's just greater than 5. That's the range here. Okay. Graph of reciprocal functions, you would not have to do that. You can do everything without sketching graphs yourself. If you need the graph, for example, if the graph has a turning point, in that case, this method would not work. In that case, they will always give you the graph themselves, like in this example. There are only, I think, 2 questions like this in recent papers in which you have a turning point on the reciprocal function, and both of them, they give you the graph themselves. You won't have to draw the graph of a reciprocal function yourself. That's not something that's required in your syllabus. Okay, any other quick questions? Okay, let me go back there. So this is clear now, the 5 to infinity one? Okay, so when we write this 5 to infinity, both of these are acceptable. Both of these are acceptable. So 5 to infinity means the value has to be greater than 5 and up to infinity. Now, infinity is not a number as such, so that's not a limit. So you can also write that as y greater than 5. Both of these are acceptable according to the marking schemes. So you can write any of them. You can say y greater than 5 or y is between 5 and infinity. Both are fine. Okay, so in this case, we're saying it's 1 over x minus 3 whole squared. So it might have a turning point. No, it's not a quadratic function. It's quadratic in the denominator. These functions still do not always have turning points as such. Uh, Even if they have it, the domain that they would give, it would always not include that turning point. So we won't have to worry about the graph. Okay. So in reciprocal functions, when they do not give you a graph themselves, it always means it's going to be a one-to-one function. That means it's not going to have any turning points. So you don't have to worry about the turning points in that case. Okay. If there is a turning point, they will always give you the graph themselves. So that's not going to be a problem for you guys to figure out. Okay, all right. Is that it? Can we move on to circular measure? No further questions? Okay. Let's do circular measure next, and then we have a break after that. Okay, now this is a very short topic. Circular measure. Now, the first thing we need to know about circular measure is another unit for measuring angles, and that's called radian. Now, this is one thing for which the syllabus explicitly says that you need to know the definition of radian as well. You need to understand what 1 radian means. So what is 1 radian? When you have a circle, and in that circle, there is a sector such that the arc length of that sector is equal to the radius of that sector. So in a sector, if the arc length and radius are equal, if this and this, they are equal to each other, these lengths are equal, the angle that you get at the center, that angle is 1 radian. Okay, you need to have this understanding of radian. When the arc length is equal to the radius, the angle at the center that you have, that is 1 radian. All right. Now, if the arc length is r, angle is 1 radian, what's the arc length of the complete circle? For the complete circle, the arc length is 2 pi r. So what is the rate? What is the angle going to be? Multiply 1 with 2 pi, the angle turns out to be 2 pi. So for a whole circle, the total angle in radians is 2 pi. Okay, for a complete circle, for a full circle, the angle is 2 pi. Now, this is the exact value. You can also write this in decimals. That's 6.28. So you see, it's a much smaller number than the number in degrees. The angles in degrees, they are larger numbers generally. 360, that's a large number. 360 degrees corresponds to 6.28 radian. Okay, so radian is a bigger unit, so its values are smaller. They correspond to so 2 pi radians corresponds to 360 degrees in this case. Okay, so now that you understand what 1 radian is and what the angle in a full circle is 2 pi radian, you need to be able to convert between degrees and radians. So 360 degrees corresponds to 2 pi radian. That means 180 degrees corresponds to pi radian, and that's the ratio that we've got between degrees and radians. And that's what we can use to convert from degrees to radians. 180 degrees to pi radian. That's the ratio that we have. Sometimes they ask you for 1 mark to convert a degree angle to radian or a radian angle to degree. This is the ratio that you use for that. And you should also memorize some of these common angles and their corresponding radian values. A lot of people cannot do well in trigonometry questions that have radians in them because they cannot visualize properly what these angles are going to be. Pi over 2, pi over 3, pi over 4. You need to memorize what each of these corresponds to in terms of degrees because you're used to working in degrees since your early years. Radian is the first time. This is the first time that you're studying radian. So you need to be able to connect that to the corresponding degree angle. So you need to memorize this without any calculation. You should be able to figure out that pi over 2 radian corresponds to 90 degrees, pi over 3 is 60 degrees, pi over 4 is 45, pi over 6 is 30 degrees, and 0 is 0. You need to memorize these angles. Okay, pi over 2 is 90, pi over 3 is 60, and so on. Now, this is the ratio that we've got, 180 to pi. If you want to convert an angle from degrees to radians, you multiply that with pi over 180. If you want to convert an angle from radians to degrees, you multiply that by 180 over pi, or just use ratios, and that will give you the result. Now we've got these two formulas mainly in this topic, one for arc length and the other for area of a sector. Now, arc length in degrees was given by this, theta over 360 into 2 pi r. In radians, that formula becomes this, arc length equals r into theta. S equals r theta. S represents the arc length, and theta is supposed to be an angle that is in radians for this formula to work. Okay, S equals r theta. That's one formula that we've got. In degrees, the area of sector formula was this. When we convert that to radians, that becomes half r squared theta. This is the second formula that we've got, half r squared theta. So there are two formulas primarily that you need to know about in this topic, first of all, and they are S equals r theta and area of a sector that's equal to half r squared theta. In both of them, the angle theta has to be in radians, otherwise these formulas don't work. And in circular measure, generally you'll be doing everything in radians anyway. Okay, so these are two formulas that we've got primarily. Now, this is all that you need to know in terms of concepts as far as circular measure is concerned. However, along with these concepts, you have to use some other concepts that you know about already. For example, you will need to find areas of triangles. How do you find area of a triangle? There are two formulas that we normally use for that, half into base into height. For this formula, base can be any of the three sides in the triangle. You can take any side as the base. Okay, you can take this as the base. If you take this as the base, height is going to be perpendicular to this. That's the height. If you take this side as the base, height is going to be the perpendicular coming from the third point to that point, and so on. The other formula that we will be using more, because we will not always have the perpendicular height. Sometimes we will, but sometimes, most of the times we won't. So we'll be using this other formula, that's half AB sine C. What's half AB sine C? A and B are two sides of the triangle, and C is the angle between those two sides. Two sides and the angle between them. We can use this formula then for area of triangle. Now, make sure your calculator is in radian mode for this. Otherwise, you will have problems. You get wrong answers. So always doing any questions, make sure that you always look at the top of your calculator, whether it's saying R or D. Otherwise, you sometimes you end up doing careless errors in the exam. Instead of degrees, you use radians. Instead of radians, you use degrees, and that makes you lose a lot of marks. So make sure that you're careful about this. Always, when you're doing calculations involving sine, cos, tan, look at the top of your calculator whether it says R and D and whether that's correct or not. All right. Now, using this area of triangle, we can actually find area of segment as well. It's not necessary to memorize this formula as such. You can just do sector minus triangle as well, but you have to do this a lot in this topic, finding areas of segments. So if you want to memorize this formula as well, you can do that. It's not given in the formula sheet, and it works like this. If you have a sector like this green shaded part, this is known as a segment. Remember, sector has 3 sides, 2 radius, and 1 arc length. This whole thing is a sector. And this shaded part that you see there, that's called a segment. That only has 2 sides, one chord and another arc. That's a segment. How do you find area of a segment? How do you find area of a segment? You can say find the area of the sector, that's half r squared theta, minus the area of the triangle, that will be half AB sine C. Both the sides are the same in this case, R and R, into sine of the angle, sine theta. If you simplify that, that gives you this formula, half r squared into theta minus sine theta. For area of segment, you can use this directly as well, or you can just use sector minus triangle, do whatever you prefer. Then you'll have to use some trigonometry here as well. So you need to remember the basic trigonometry, like the ratio sine, cos, tan, and what they mean in terms of a right angle triangle. So whenever you have a right angle triangle, you have these ratios defined like this. Sine is perpendicular over hypotenuse, cos is base over hypotenuse, tan is perpendicular over base. Just be careful. The angle, whatever angle it is that you're considering, the side opposite to that, that's the perpendicular. The side adjacent to that, that's the base. Okay, and then hypotenuse is just the side that is opposite to the 90 degrees or pi over 2 radian angle. I'm sure you're already familiar with this. If you do not have right angle triangles, you only use these ratios when you have a right angle triangle. When you do not have right angle triangles, in that case, you can either use sine rule sometimes or cosine rule sometimes, although they're used very rarely in circular measures, but sometimes you do need to use them. So in triangles that are not right angles, you can also use sine rule, cosine rule if you want. Okay, okay, I missed that. Let me just add that here. Okay, so you need to know something about isosceles triangles as well. A lot of people end up not doing these questions correct that involve some isosceles triangles for some reason. So let's say we've got an isosceles triangle that looks something like this. We've got 2 triangles. Now these are isosceles triangles. They have 2 sides equal. That means these base angles are also going to be equal. Now in isosceles triangles like this, in which you have 2 sides equal, and you have to do some calculations, always think of something like this, breaking this triangle into half from the middle. The side that has the 2 equal angles in an isosceles triangle, we call that the base side. So to the base side, make a perpendicular from the 3rd vertex. You will always get a 90 degrees here, and this point will always be the midpoint. In the second form on the right side, if this was an isosceles triangle, but these 2 sides equal, you can say this is the base side of the triangle. If you were to break the triangle into 2 parts like this, the angle here, if the angle is 90, if you make a perpendicular here, this point has to be the midpoint. This helps a lot. Rather than using cosine rule formulas or sine rule formulas in triangles like this, always break them into 2 parts and then use simple sine, cos, tan ratios in either the triangle on the right side or the triangle on the left side. Otherwise, when they ask you to prove something in a question and they want a specific form, using sine rule and cosine rule, getting that form that they ask you to show, that becomes very, very difficult sometimes. So always break isosceles triangles into 2 parts like this and use sine, cos, tan ratios on them directly. Then there are some angles for which you need to use the exact values. In degrees, these angles are 0, 30, 45, 60, 90. In radians, those corresponding angles are going to be 0, pi over 6, pi over 4, pi over 3, pi over 2. When you have these angles, and you have to find sine, cos, tan of these angles, the question often will ask you to give your answer in exact form. In this case, never use decimals. Now, you do not necessarily have to memorize these values. You can just use a calculator for them. You must have a calculator that gives you these exact values. For example, if you try this on your calculator, cos of 3 or pi over 3, pi over 6, in fact, that should give you under root 3 over 2 and not just a decimal value 0.866. If your calculator is not giving you under root 3 over 2, I would highly recommend upgrade that calculator. You need something that can give you exact values. Otherwise, you'll be in trouble in your A-level exam. So you need exact values. So for these angles, you would often be asked to write exact answers. In that case, how should you show your working? If you have to find area of this triangle, for instance, and the angle is pi over 3, sine pi over 3, you'll evaluate that on your on your calculator, and you would first show that the value of sine pi over 3 is under root 3 over 2, and then you simplify that afterwards to give the exact answer. So they would either ask you to give an exact answer, or they will say give your answer in terms of pi, or they will say give your answer in surd form. In all of these cases, make sure that you show all the working, make sure that show all working, and you're not skipping any steps. Okay, so do this calculation on a calculator style, but show clearly that you're inputting this value and then simplify that afterwards. And then these circle theorems that we talked about in equation of circle as well. You need to know these for this topic as well. We talked about an equation of circle as well. You need to know about these circle theorems. All of these properties, they are used in this topic as well. Angles in the same segment are equal. Angle made by diameter is 90. If the angle is 90, the chord is supposed to be a diameter. It works both ways. And this property, line coming from the center to the midpoint of a chord, it always makes a 90. If the angle is 90, then the line cuts at the midpoint. And this property, tangents coming from outside a circle, if you were to find their lengths, they're going to be equal to each other, PQ and PR. And if you were to join those points with the center like this, the shape that you get, that's always going to be a kite. And all of these angles, y and y, they're going to be equal, x and x are going to be equal, and so on. We talked about this in equation of circle before as well. Angle at center is twice the angle of the circumference. Cyclic, quadrilateral, and tangent is perpendicular to radius. You still need to know all of these properties for circular measure as well. Sometimes you will have to use them. Again, some are used more often than not. The same four properties, they're going to be used more. The kite one, this is used a lot. Tangent is perpendicular to radius, this is used a lot. And then diameter makes a 90 degrees at the circumference. And then finally, this one, line coming from the center to the midpoint of a chord, that's always perpendicular. All right. Now, how will the questions look like? You will have to find areas, you'll have to find perimeters, arc lengths. And for areas, for instance, you would have to figure out what area to subtract from which area. For example, if you have to find this shaded area, you have to think about how exactly you can get this region. For example, one idea could be that you find the area of this rectangle, and then from that rectangle, you subtract the area of this triangle, and then you also subtract the area of this sector. So you'll have to do this thinking and then just apply the formulas and do that plus minus and get the result. It's fairly straightforward generally. When they ask you for exact answers, you just need to make sure that you don't put anything in decimals. For example, in this particular question, they're asking that you should give your answer in this form, a square root of 3 minus b pi. Now, don't get confused by just reading this form, that what form it is that they're asking for. All it means is that you should not use decimals, and you would automatically get this form as the result, as long as you're using exact values. Okay. You should always use radians. You should never use degrees in this topic. Always use radians. Unless a question specifically asks you to convert an angle in degrees, in that case, you just do that for that part. Otherwise, for all the formulas, these formulas only work when the angles are in radians. Otherwise, they don't work. Okay, sometimes what you have to do is you have to add some additional lines in your diagram as well. So when you do a lot of practice, you know understand how to make these extra lines. Sometimes, for example, in this part, for example, in the first part, they're asking you for the length of SR. Now, how do you find the length SR? You can add another line here, and that's XQ. And now you get a right angle triangle that you can actually use to find the length of XQ. XQ will be the same as RS. So keep a lookout for this, that you may sometimes need to add some extra lines on the diagram to basically make the problem simpler. All right. Okay, this is on going on here. We'll just have a 1 minute break and then we'll resume.
Well, it is just was before we got huh? She won't use it.
Okay, so sometimes you may have to add extra lines to your diagram to make your problem simpler. So make sure that you practice a lot so that you can recognize problems like these. In this case as well, again, you have to find the value of theta. This is the value of theta, this value. Now, in this triangle on the right side, there isn't much that you know. You only know this hypotenuse. If you make this triangle on the left side, you have more information on the left side here. You know the hypotenuse, you also know this angle. So using that other triangle on the left side, you can find this length, and this length would be equal to this length. And then you use trigonometry in the triangle on the right side to find that value of theta. Again, in the original figure, you did not have these lines, and you have to think about these yourself. In this question, in fact, they do give you a hint that you consider the perpendicular distances from each of those points to the base, but sometimes they might not give you this hint as well, and you might have to think about this yourself like this. Okay, so have a look at the solution. These are fairly straightforward problems. Generally, once you figure out what to do, the actual working after that is fairly straightforward. For perimeter, remember, perimeter means the length of the boundary, right? So perimeter does not have any standard formula as such. Whatever figure it is that you have, all you have to do is just sum up all of those sides. For example, if this is the shaded region, you want to find the perimeter of that, you find this length. However you can use the arc length formula for this. You find this length, that's dx. Use the arc length formula in the other sector, and de, find that length. In this case, that is basically found by considering this complete length and subtracting from that these two separate lengths, and that gives you this value of yz in the middle. That's the same thing as de, and that gives you that value. Then you can find the overall perimeter from that. Now it changes from question to question. You have to figure that out yourself, and the questions you do a lot of practice for that, and that helps you do that. Again, this is another example in which you have to draw some lines yourself to figure out whatever you have to. How do you find the shaded region, for instance? It's not some standard shape that you have the direct formula for this. So one idea that we could use here is that we break this figure into two parts like this. And now this becomes a segment. So we can find the area of the segment by using this sector, for instance, and then just multiply that by 2, right? Find the area of the sector, multiply that by 2, of the segment, sorry, and then multiply that by 2, that will give you the complete shaded area. Okay, so think about how you can add any additional lines to make the problem relatively easier. Sometimes you will get areas that are a bit hard to spot as in how exactly to calculate. That will require more working. You need to break them down into smaller chunks. You need to break them down into smaller chunks. How do you do that? For example, in this case, this is not any standard shape. So how do you think about it? You do it step by step. So this is the figure. You can think of it like this. First of all, you say, okay, we've got the semicircle. And in the semicircle, we have this shaded part from which, from the semicircle, we are subtracting this part to get that shaded part. Okay, so area of semicircle, we can find that somehow. Now the problem would be how to find the area of the segment. So think about this separately. For finding the area of that segment, you can add these lines here. Find the area of the sector. Find the area of the sector and then subtract from that area of this triangle. And that will give you the area of the segment. Once you get that area of segment, you had the area of semicircle earlier, subtract from that area and you get the result. So sometimes it's not very easy to spot. You have to break that down in parts. So in this case, what you can do is find the area of the semicircle. As I said, find the area of that segment separately. How do you do that? Area of segment formula, or if you want area of sector minus triangle, you get the area of that segment, and then eventually you find their difference, and that gives you the result. Again, you have to do practice for that. And in questions, sometimes the difficult part is where in the first parts, they ask you to show something, they ask you to prove something. They will give you some information in the question. For example, in this case, they're saying, in this diagram, AC divides the sector into 2 regions of equal area. So we have 2 regions here. One region is this. This is one area. This is another area. It's dividing this region into 2 areas like this. We need to show that sine alpha into cos alpha is equal to half alpha. Now, don't worry about how exactly this form is going to come. Just use the information that's given in the question. They are saying AC divides the sector into 2 regions of equal area. This is one area. This is another area. Just make an equation out of that somehow. You can find the area of this triangle, find the area of the region on the side, and then equate them somehow. Now, in this case, finding the area of this region is going to require some work, right? You'll have to find the area of the whole sector. From that, subtract the area of the triangle. So an easy way of thinking about this could be, you could say, if this is area A, this is another area A, that means the total area of this whole sector, what would that be? That will be 2 times A. So this statement that they've written here, this could be simplified to a form like this. You could say area of this complete sector. Area of the complete sector. The sector is AOB. That would be equal to 2 times the area of the triangle OAC. You make an equation using that information and then just simplify that. It will automatically turn out to be something like this. You just keep simplifying and keep the end in mind that this is what you want, and you will get that eventually. Don't start thinking about this, that, okay, how will you get that form? Just use that given information, simplify that, and you get the result. For example, in this case, when we do that, area of sector OAB, that's equal to 2 times area of that smaller triangle. Simplify that, we automatically get that form that we wanted there. All right. Okay, and then the rest you can figure out in the questions. That's the key. These are the key concepts that we got in circular measure. The rest is all practice. Can we begin? So I think I've got most people right now. Okay, let's start with trigonometry now. So in trigonometry, again, first of all, we've got to know these basics, the definitions of sine, cos, and tan, how they're defined in terms of a right angle triangle. Sine is perpendicular over hypotenuse, cos is base over hypotenuse, tan is opposite, perpendicular over the base. You need to make sure that you understand that the side that's adjacent, that's base, side that's opposite to any angle, that's the perpendicular with respect to that angle. For example, with respect to theta 2, X is perpendicular and Y is the base. If you don't have a right angle triangle, in that case, we can use sine rule and cosine rule sometimes. That also works. Now, this is what you know already. Then we talked about these exact values already in circular measure as well. That when you have these specific angles, you need to be able to write their exact values when required and use them in your working, and how to show that in your working as well. We also talked about that. Okay, now this is the new stuff. So until O levels, you saw that whenever you had to find sine, cos, tan, you basically thought of a right angle triangle, and you defined sine, cos, tan with respect to the right angle triangle like this, which is correct. You do it like this, but that was a restricted definition in the sense that you could only have acute angles uh, in a right angle triangle. You cannot have any angle that's greater than 90 degrees in a right angle triangle. So these definitions only used to work for acute angles, right? Angles that were less than 90 degrees. But what if you had some bigger angles? So 150, 225, 420, minus 60. Sine, cos, tan exist for all of these values. If you try these on a calculator, you get values, you get results for these values as well. Now, what are these angles? How are sine, cos, tan defined for this? That's the first thing that you understand in trigonometry. First of all, how do we understand angles? Where do angles greater than 360 come from? Where do angles in the negative direction come from? If you have quadrants like this, if you have x and y axes like this, let's say this is x axis and this is y axis, remember angle is always going to be measured from the positive x axis. Angle is always measured from this side, from this yellow line. It's measured from this line. And if we go in the anti-clockwise direction, we consider that angle to be positive. If we go in the negative direction, if we go in the clockwise direction, we consider that angle to be negative. Okay, anti-clockwise positive, clockwise negative. So if you had a line, this blue line here, for instance, this line that you see here, if this line makes an angle of 30 degrees with this horizontal, then we could say this line has an angle this, which is 30 degrees. So the angle of that line is 30 degrees. But that's one way to describe the angle of this line. We could also say that we can go one full circle and come back to that line. And that would become 30 plus 360, which is 390. So that same line can have an angle of 390 as well, right? And similarly, you can keep going on in circles, keep adding 360, 230, and you get more and more angles, 390, 750, and so on. All of these angles are equivalent angles, right? All of them have the same signs, the same cause, the same time. These are equivalent angles. So that's where the angles greater than 360 come from, that we can go beyond 360 and we get to the same point again. What about negative angles? If you go in the clockwise direction, that's where negative angles come from. For example, in this case, the complete angle in a circle is 360. Subtract 30 from that, that's 330. But since we're going in the clockwise direction, we say this is negative 330. So that same blue line can also be said to have an angle that's negative 330. This angle is also equivalent to this angle, to all of the other angles here. So this is how we measure angles anti-clockwise or clockwise. You can go one full circle and go beyond that to find more angles as well. Now, in this region on the left side, if this line was to have an angle of 45 degrees with the horizontal, we could say one way to measure that angle is that this angle is 180 minus 45, and that's 135. That's this angle. So we could say this line has an angle of 135. But then we could also say, let's go one full circle, come back to that point again. This line could also have an angle of 495. Similarly, we could also say, let's go in the clockwise direction. We can also say this line has an angle of minus 225 degrees. So there are different ways that we can measure the angle of that same line. All of them are equivalent. All of these have the same sine, cos, and tan. Now, the region on the right side here on top, that's the first quadrant. That's how we name these quadrants. We number these quadrants. This is quadrant 1, this region. Then on the left side, this is quadrant 2, this is quadrant 3, this is quadrant 4. Now, in each of these quadrants, you can measure angle on the same format like this. You start measuring from this positive x-axis, and then you either go anti-clockwise or you go clockwise to find that particular angle. Anti-clockwise is positive, clockwise is negative. For example, this line at the bottom here, we could say it has an angle of 240. 600 minus 120, all of these are the same angles because this is 240, 180 plus 60. This is 180 minus 60, 120. But since you're going clockwise, that's negative 120. So you should be able to measure these angles. That's where these angles come from. Now, what happens is in the first quadrant, since the values of, in fact, should we go into this detail? Okay, so I'll go through this very quickly. So the definition of sine, cos, and tan, they're basically extended like this, that instead of saying base, hypotenuse, and perpendicular, we say instead of base and perpendicular, we will say sine is defined as y over r, where y is the y coordinate of that point and r is the distance from the origin. If we have a circle like this, that on the circle we've got points like this, then we have the definitions of sine and cos like this. Sine is y over r, cos is x over r, and tan is y over x. And from that, we basically get that since at this point the x, y coordinates are both positive, the value of sine is going to turn out to be positive here. The value of cos is also positive. The value of tan is also positive. But I think it's going to take too much time to explain that in a revision videos, but in a revision class. What I'll do is I'll just get to the result right away. So all of you know this already. I'll just move on from this. This is actually the logic behind where you get to it, how you get this ASTC. But now for the exam purpose, this is all that you need to know. So you have these four coordinates. And in these quadrants, what basically happens is in the first quadrant, all ratios are positive. In the second quadrant, only sine is positive. In the third quadrant, only tan is positive. In the fourth quadrant, only cos is positive. You need to remember this ASTC. In the first quadrant, all ratios are positive. In the second, sine is positive. In the third, tan is positive. In the fourth, cos is positive. You need to memorize this. There are different ways of memorizing this. Add sugar to coffee and some others. You need to remember this. Now, that's one thing that you need to understand to be able to solve equations, that in which quadrant which ratio is positive. The second thing is the concept of a basic angle. Basic angle is defined as the acute angle that any line makes with the horizontal axis. So for example, if you have a line like this that makes an angle of 30 degrees to the horizontal here, the basic angle for this line is 30. If we have this line that's 150 degrees angle, because this angle here is 150, the angle that it's making with the horizontal there on the left side, that is also 30. So this line that has an angle of 150, the basic angle for that is also 30 degrees. Similarly, in the third quadrant below, if we have this line that has an angle of 210 degrees, the basic angle here, that's also 30 degrees. And we have another line here that's 330 degrees. The basic angle of this line is also 30 degrees. So this is what we call a basic angle, the angle that a line makes with the x-axis. This is another very important angle to be able to solve equations, because what happens is whenever the basic angle of two angles is the same, their sine values are going to be the same, their cos values are going to be the same, and their tan values are also going to be the same. So for instance, all of these angles, 30, 150, 210, 330, all of them had the same basic angle. If you were to find their sine values, sine 30, sine 150, sine 210, sine 330, you would see that all of them turn out to be 1 over 2. All of them have the same magnitude. They're all 1 over 2. The only difference is that some are positive, some are negative. The first two are positive, the next two are negative. And why is that? Because the first two angles are in the first and second quadrants, and we know that sine is positive in the first and second quadrants. These values are positive, and the third and fourth values there in third and fourth quadrants, those values are negative, but the magnitudes are all the same. They're all 1 over 2. So that basic angle, that basically tells you what the magnitude of the sine, cos, and tan ratio is going to be. So in this case, the magnitude is 1 over 2. For cos, for instance, cos 30, cos 150, cos 210, cos 330, all of them have the same magnitude. Why is that? Because all of them have the same basic angle. So whenever the basic angle is the same, the magnitude of these ratios that you get, that's always going to be the same. The only difference is going to be the plus minus, and that is decided by quadrants. So these two things together, they will help us find solutions to trigonometric equations, in which quadrant what ratio is positive, and the basic angle, because basic angle tells you this number, the magnitude, and the quadrants tell you plus minus. Okay. Now, how are they going to be used to solve equations? This is the process for that. So let's say you have to solve an equation like this: sine of x equals 0.5, and the interval that you're given is from 0 to 360. How do you solve this equation? How do you find all possible solutions of this equation? The way to do this is you first of all find the basic angle. How do you find the basic angle? This is the process that you follow for that. Replace x with alpha. So we denote basic angle with alpha. Okay, so this is what you'll always do. Whatever is the equation that you're given, what you start with would be you would replace x with alpha, and on the right side of the equation, whatever is the number that you've got, you will make that positive. Now, in this case, that was also already positive, so you would not have to do anything. But in case it was not positive, you will make it positive. So it becomes sine alpha equals 0.5. You get an equation like this. And now you put this on your calculator, evaluate sine inverse of 0.5, and see what that gives you. And that will give you 30 degrees in this case. So the basic angle turns out to be 30 degrees. Now, if that's the basic angle, what you do now is you use quadrants to figure out what the solutions of this equation are going to be within the given interval. Now, how do you do that? The basic angle is 30. The basic angle 30 could be in 4 different positions. It could be here, it could be here. All of these are 30 degrees, right? All of these basic angles. Basic angle is the angle with the x-axis. All of these are basic angles. But now we know that sine is positive. Where is sine positive? We know that A, S, T, C. Sine is positive in the first 2 quadrants. So we only consider the first 2 quadrants. We ignore the ones below. And now we write down all possible angles in these first 2 quadrants inside the given interval. The interval is from 0 to 360. All you have to do is, this is the first angle, that's 30 degrees. This is the other angle, that's 150 degrees. That's 180 minus 30. And that's how we solve any trigonometric equation. Let's look at some examples of this. Let's say we have cos theta equals minus 0.3. How do you start with this? You say the basic angle is alpha. You replace the left side with an alpha, the theta on the left side with alpha, and that gives you cos alpha equals 0.3. Find the basic angle. The basic angle turns out to be 72.5 degrees. And now you make quadrants. The quadrants look like this. Since cos is negative, you think about where the basic angle can be. It's ASTC. ASTC tells you that cos is positive in the first quadrant and in the fourth quadrant, but cos is supposed to be negative here. So which quadrant should we consider? The second and third. In those quadrants, now we write down all the possible angles inside the given interval. The interval is from 0 to 360. That means you have to consider angles in the positive direction, in the anti-clockwise direction. This is the first angle that you get, 180 minus 72.5, and the second angle is 180 plus 72.5, because this is 180 plus 72.5. That gives you the angle in the third quadrant. Similarly, you could do it for other angles as well. They could change this interval. So if you have an interval that has some negative values as well, what do you do in that case? So if you have tan theta equals 0.3, the first thing you do is you first of all replace theta with alpha, make the right side positive, find the basic angle, see what the basic angle turns out to be. In this case, the basic angle turns out to be 16.7. Now you draw that basic angle in the quadrants that are valid. Since tan is positive here, tan is positive in the first quadrant and in the third quadrant. So it's either this or this. Now you consider the basic angle, but now look at the interval. The interval is from minus 360 to plus 360. How do we write down all the possible angles in this? This is the first angle that we get, 16.7 degrees. That's straightforward. This is the other one that we get, 180 plus 16.7. Okay, now in the positive direction, we have found the 2 angles that we needed. However, the interval is also going in the negative direction. So we also have to check if there's any possible angle in the negative direction that also falls inside the given interval. So how do you go in the negative direction now? You go clockwise like this. This is the first angle that you have. It's 180 minus 16.7. However, since we're going clockwise, you put a negative sign with that, and that turns out to be minus 163.3. Similarly, we go beyond this and we see, is there any other angle here inside the interval? This is another angle that we're getting. 360 minus 16.7, put a negative sign with that, and that gives you minus 343.3, and that's another angle that you are getting. That's inside the interval. So it has 4 possible solutions that look like this. Whenever you have an interval that has some negative values as well, always check if you can find any possible angles in the clockwise direction. In this case, we can, so they're also your solutions. Okay, let's consider this now in gradients. Let's say we have sine theta equals 0.7. Now, sine theta is positive here. Again, the first thing we do is we find the basic angle. Sine alpha equals 0.7, find the basic angle from that. Now, in this case, the angle is in radians, so make sure your calculator is in radian mode for this. Find the basic angle and see what that turns out to be. The basic angle turns out to be this. Now, you have to write down all the possible angles with this basic angle in which two quadrants? Sine is positive. Sine is positive in the first quadrant and in the second quadrant. That means it's either this quadrant or it's this quadrant. It's one of these two quadrants. Now, what angles are going to be possible here? In the first quadrant, you get this angle first in the positive side. That's 0.7754. You get another angle that's this. What's that going to be? This is 0. 180 degrees corresponds to pi radians. So in the second quadrant now, what you'll do would be, you would say the angle is pi minus 0.7754. Pi is the complete angle. You subtract from that 0.7754, and that gives you that result, 2.37. Now, these are two angles that we're getting in the positive direction. However, look at the range, look at the interval that's given. It's also going on the negative side. So we also have to check if there's any possible angle that we can get, in the clockwise direction here. What are the possible angles that we can get in the clockwise direction? This is one angle. That's 180 plus 0.7754. That's pi plus 0.7754. But since we're going clockwise, we put a negative sign with that as well. And then we have another possible angle that we're getting here. That's this angle here. What's that going to be? 2 pi. Complete circle is 2 pi. Subtract from that 0.7754. Since that's in the negative direction, we put a negative sign with that. That's minus 5.51. These are four possible solutions that we get in this. These are our final answers. Okay, anti-clockwise was done there as well. So depends on the intervals. In the interval, if you have both anti-clockwise and clockwise, if you have both positive and negative values, you have to check in both directions, anti-clockwise and clockwise. So in this case, we had these angles in both directions, anti-clockwise and clockwise. Now, these are some cases that are relatively special. For example, if you have sine theta equals -1. Now, what happens in this case? Sine theta equals -1. When you try finding the basic angle in this case, it turns out to be 90 degrees. So you replace theta with alpha, make the right side positive, it becomes sine alpha equals 1. Alpha turns out to be 90 degrees. Now, where is 90 degrees going to be? 90 is the basic angle. What does that mean? It could either be here on the vertical axis above, or it could be here on the vertical axis down. Now, which one do we consider from that? Sine is negative. Now, 90 degrees is not falling in any quadrants, right? It's on the y-axis. It's not in any quadrants. It's on the boundary. Now, we know that sine is positive. Sine is positive in these two quadrants, and sine is negative in these two quadrants. So the angle that we're getting on the upper side, that is not going to be possible because we have positive here, positive here. We want sine to be negative, so it can't be there. So when it's 90 degrees with a negative sign, what we do is we consider only the part that is on the lower side. That's the angle that we consider here. And we say inside the given interval, this angle turns out to be 270 degrees like this. All right. Let's take another example of a similar situation. Let's say we have sine theta equal to 0. What about this case? Find the basic angle from this. What does the basic angle turn out to be? The basic angle turns out to be 0 in this case. Where is 0 going to be? Now, 0 can either be on the right side here, or it can be on the left side here. Which one do we consider inside this interval from 0 to 360? Now, we know that sine is positive in the first and second quadrants. It's negative in the third and fourth quadrants. This is 0. Is 0 positive or negative? 0 is neither positive nor negative. 0 is actually between plus and minus. Okay, that's interesting. Between plus and minus, what does that mean? The angle that we're getting on the left side here, this one, this is between plus and minus. That means that works. The one that we're getting on the right side, this is also between plus and minus. That also works. So we consider both of these angles. In the first, on the right side here, this angle is 0. So that's one possible answer. On the left side, this angle is 180. That's another possible answer. However, the interval is going until 360. So we can also go further and we can say, when we complete one full circle, this angle here, when we come back to the x-axis, that's another possible angle. So sine theta equals 0, it actually ends up having three solutions inside this interval, 0, 180, and 360. All of them are possible solutions of this equation. Okay, let's take another example. If you have cos theta equals -1, what do you do with this? You find the basic angle, cos alpha equals 1. The basic angle turns out to be 0 in this case again. Like, what does that mean? We have to consider this side on the right side and this side on the left side. That's when the basic angle is 0, right? On the x-axis. Now, which one of those two is going to be possible? Cos is positive in the first quadrant and in the fourth quadrant. It's negative in the second quadrant or in the third quadrant. So which one do we consider? It has to be negative. Negative means it has to be on the left side, right? So we only consider the part on the left side. That's this part here. What's the angle there? That turns out to be 180 degrees, and that's a final answer. It has to be 180 degrees in the given interval. All right, so that's how we solve equations that look like this using quadrants and basic angles. Now, for these special angles, when you have a basic angle of 90, 0, or 0, in this case, you can also think of the graph. When you understand the graphs, when you remember the shapes of the graphs, sine, we know that looks like this. So you can just think of it in your head as well. The sine is negative 1 at this point. This is 270 degrees. So without any working as well, you can write down the answers. In this case, that will turn out to be 270. If you want to use coordinates, you can do it like this. But if the basic angle is either 0 or 90, you can also use your graph. Think about the graph in your head, maybe do a rough sketch of that, and based on that, you can write down what the angle is going to be. In this case, for instance, sine is 0 in the second case. In this example, sine is 0. Think about the graph. Where is sine 0? This is what the graph looks like. Sine is 0 here, sine is 0 again here, and sine is 0 again here. These are the 3 points where sine value is equal to 0. What are those three points? 0, 180, and 360. You could write down those answers without any working as well if you remember your sine graph well. Cos theta is -1. Again, this is a special case because the basic angle turns out to be 0. So when the basic angle is either 0 or 90, you can just think of the graph and write down the answers directly from that. So in this case, it's cos. What does the graph of cos look like? The cos graph looks like this. Now, on this graph, we know that it's equal to 1. The value is equal to 1 at x equals 0. Then it becomes x is equal to 1 when x is equal to 0. Y is equal to 1 when x is equal to 0. And when it's 90, the y value is 0. When it's 180, the y value is -1. So just think of the graph, and you can write down directly that the solution in this interval for this equation would be that theta is equal to 180, because that is when the value for the function becomes equal to -1. So for these special angles, when the basic angle is 0 or 90, you can think about the graph. For the rest of the angles, you make quadrants like this, find the basic angle, mark the quadrants, and write down all possible angles in the given interval. If it's positive angles, you go anti-clockwise. If it's negative angles, you go in the clockwise direction. Sometimes the interval that's given might go beyond 360 as well. For example, if this interval goes beyond 360 and it goes up to like 720, what will you do in that case? You will complete one full circle and then come back to those points again to see if there's any other point that also falls in the interval. So you have to consider 3 possibilities. One, it's just 0 to 360. That's just one full circle in the positive direction. Then if it's negative, like in this case, you also have to go in the clockwise direction. And number 3, if sometimes the interval ends up going beyond 360, let's say it goes up to 720, then you have to complete one full circle and come back to those lines again in case you find any other angle in the interval as well. Okay, so that's how we solve these basic equations. But mostly you'll get something more complicated than this. For that, you have to use these identities. There are 2 identities that you have in your syllabus for paper 1 trigonometry. Before we do them, you need to remember these notations. So whenever you have sine theta whole square, this is the actual function, sine theta whole square. There's a short form for writing this, and that is sine square theta. Similarly, if you have cos theta whole cube, there's another way of writing that, and that's cos cube theta. So whenever you have square like this or cube like this, sine square, cos cube, remember that the correct form of writing that is sine theta whole square. The proper mathematical form is this. This is a short way of writing that. So you need to understand that this is how this notation works. It does not work for negative angles. So if you have sine theta whole raised to power -1, it does not work for negative powers, not angles. It does not work for negative powers. So if you have sine theta whole raised to power -1, this is 1 over sine theta. Sine inverse theta, this is a different function. These are not equal to each other. So this is a very common error that happens here. Sine theta whole raised to power minus 1. This is 1 over sine theta. Sine inverse theta is a different function. That's the inverse function of sine. Inverse is different from reciprocal. Okay, so in negative powers, we cannot use this notation to mean that it's power minus 1. Power minus 1 is different. Sine inverse is a different thing. In positive powers, we say that these are equivalent. This is just a short way of writing that positive power. Now, we have two identities that we basically have here. Sine square theta plus cos square theta, that's identical to 1, and tan theta is identical to sine theta over cos theta. If we rearrange these, we get something like this. Sine square theta can be written as 1 minus cos square theta. So a lot of times what we have to do is we have to convert sine square to cos square or cos square to sine square. We can use these identities to do that conversion. If we have sine square, we can write that as 1 minus cos square. If we have cos square, we can write that as 1 minus sine square. In this other identity, tan theta equals sine theta over cos theta, this is written in the formula sheet directly. Sometimes you have tan square. What do you do in that case? Tan square can be written as sine square theta over cos square theta. Okay, so that's also something that you have to use sometimes. Make sure that you remember this as well. If tan is sine over cos, then tan square theta is equal to sine square theta over cos square theta. However, these are not correct. For this identity to work, you need to have squares. You can't have single powers. Sine theta is not 1 minus cos theta. That's wrong. Cos theta is not 1 minus sine theta. That's also wrong. Indices rules do not work when you have plus minus like this. They don't. Those rules don't apply in this case. They apply only in multiplication division. So this works for both power 1 and power 2, but this only works for squares. It does not work for this. Okay, and this is also incorrect. Sine theta plus cos theta whole squared, that's also not equal to 1. Okay, only sine square theta plus cos square theta, that is equal to 1. Now, why are those identities important? Because you get equations that look something like this. You'll have multiple functions inside an equation. So we know how to solve, for example, sine theta equal to something, cos theta equal to something. We know how to solve equations like those. But what if we have something like this where we have multiple functions, sine, cos? Whenever you have to solve any equation involving trigonometric functions, we have to convert that equation to a single function. So in this case, we've got multiple functions, sine and cos. How do we convert them to a single function? In this case, when you have sine and cos, a lot of times what you do is you simplify everything and then divide cos on the other side to convert it to tan. That's something that will happen a lot. Keep that in mind. When you have sine and cos, you try to convert them to tan somehow when they have single powers. Right? When you have powers 1, then you try to divide cos on the other side and make it sine over cos so that it can be converted to tan. And then once it converts to tan, then it's fairly straightforward to solve. After that, you can just find the basic angle, find quadrants, and that equation can be solved like that. Another idea is that you could just divide that whole equation by cos theta. So one idea is that you take sine to one side, cos to another side, and then you divide cos like this, that you take it to the denominator on the other side. This is another idea that you think directly like this. If you have an equation like this, 3 sine theta minus 3 cos theta minus sine theta, divide the whole equation by cos. What happens in that case is cos and cos, they get cancelled. Sine over cos, that becomes tan, and then you can solve that equation further. If you have squares like this, for example, 3 sine square minus 2 cos theta. Now, this is where that sine square theta plus cos square theta equals 1, that identity is going to be useful. You can convert sine square to cos square so that it becomes a quadratic equation like this. And then you solve it like a quadratic, find the possible roots from that, use quadrants and find the basic angle. Now, this is something that can happen as well sometimes, that you get disguised quadratic equations in trigonometry. 2 sine raised to power 4 theta plus sine square theta minus 1 equals 0. So they want you to convert this form to this form. First of all, that's straightforward, that you convert tan square to sine square over sine cos square, and then you simplify that, and that gives you this form. How do you solve this equation further? It's a disguised quadratic. We've got powers that are in the ratio 2:1. One power is 2 times the other, right? So this is something that can be solved as a disguised quadratic. What we do is we substitute the smaller power with another letter. So we can say let u equal sine square theta, and then you solve it like a quadratic. At the end, you put that substitution back and you get this result. Now, in this case, you're getting sine square theta equals -1. That's not possible because a square cannot be negative. But from this, you get sine theta equal to plus minus square root of 1/2. Now, do not forget plus minus in such questions. You're getting plus minus. That means sign could either be positive, it could be negative. What does that mean? It could be in any one of the four quadrants. Because it's plus minus, sign is positive in the first and second quadrant, it's negative in the third and fourth quadrants. You have to consider all possible quadrants. So we find the basic angle turns out to be 45 degrees here. And then we say it could be in all four quadrants. So we write down possible angles in all four quadrants like that. Then you have to prove identities somehow as well. What does it mean to prove identities? You have two sides of this. What you have to do is you have to go start from one side and prove that equal to the other side. Okay. How will you do that? These are two identities that you can use to prove an identity. Sine squared theta plus cos squared theta is 1, and tan is equal to sine over cos. So you start from this and you think about, okay, what's the final result that you want? In the final result that you want, you don't have any sign in that. So you have to eliminate sign somehow from this. Also, on the left side, you have multiple fractions. On the right side, you only have one fraction. So what you want to do is you want to convert it to a single fraction. For that, you take LCM on this side. First of all, when you take LCM, you simplify that, try to use those identities, and eventually get this form that you want on the right side. Now, while you're proving identities, these are some things that you need to keep in mind. You start from the more complex side generally. So the side that looks more complex, you start simplifying that and prove that to be equal to the other side. So in this case, for instance, the left side is more complex because it has two different functions. It has sine and cos. It also has two different fractions. The right side only has one fraction. So how do we identify which side is more complex? The side that has more different types of functions. For example, if one side has sine and cos both, and the other side only has sine, the other side only has cos, then the one that has more types of functions, that's more complicated. And then if one side is a fraction and the other side is not a fraction, you start from the side that is a fraction because that will be easier to work with. And then if the first two rules, you cannot differentiate them based on these first two rules. So think about which side has more number of terms. If one side has two terms and the other side just has one term, it will be easier to convert these two terms to a single term rather than breaking this single term down to two terms, right? So these are some things that you need to keep in mind to decide which side to start from. Now, in most of the questions, 90-95% of the questions, you will be starting from the left side. So they uh, give you identities in a form like this that the left side is generally more complex. But in some rare case, when it looks like, when you figure out that the right side is more complex, and you can also start from that and prove that equal to the left hand side. And how do you decide that? Based on these rules that I've given you. So there are three ways of proving identities. One, you start from the left hand side, prove that equal to the right hand side. You start from the right hand side and prove that equal to the left hand side. Both of them are acceptable. If both sides look a bit complicated, this is another way that you can do. You can say, let's simplify the left hand side a bit, simplify the right hand side, and then somewhere in the middle, they will both become equal to each other. And then you say that the identity is proved. That's also possible. This is also allowed. However, while you do that, you cannot take terms from one side to the other. You can't say, let's take one side from one side and take one term from one side and minus that on the other side or divide that on the other side. That's not allowed. Both sides of the identity, they should be dealt with separately. You can't take terms from one side to the other while you're proving identities. That's not allowed. Okay. You can simplify both sides separately and then meet somewhere in the middle. That's okay. But don't take terms from one side to the other. Now, these are some things that will help you prove identities more efficiently. When you have any fractions, and there's some denominator somewhere, do not simplify that denominator. Why is that important? Because a lot of times what happens is you end up having an opportunity to cancel something in a later step. So if you have the denominator in a factorized form like this, sine theta into 1 plus cos theta, it'll be easier to cancel something there. For example, it might be that the numerator ends up having 1 plus cos theta and you can cancel it out. Or you might be able to cancel sine theta somewhere. If you multiply it like this and write it sine theta plus sine theta cos theta, yes, you can factorize that again if you want to convert it to that form, but it's very likely that you would not get that idea in the exam that you can, factorize and then do cancellation. So whenever you have in the denominator something like this that's factorized form, always consider the possibility of a cancellation at a later step and do not simplify this. Keep it in this form. When you have figured out that there's no cancellation possible, then yes, you can see if you need to simplify that further. This is an identity that's used a lot while proving identities. Keep that in mind as well. A square minus b square, that's a minus b into a plus b. So often in this direction. For instance, you might have something like this, 1 minus tan square theta. And to simplify that, you may be able to write it in a plus b into a minus b form. How do you do that? You can write 1 as 1 squared. So it becomes a square minus b square then, and then you write this as a plus 1 plus tan theta and 1 minus tan theta. If it was a fraction and you had something in the denominator as well, it's very likely that the denominator would have either this term or this term, and you can do some cancellation there. So this identity is used a lot, this algebraic identity. Whenever you have a square minus b square, you can factorize it like this. This is another thing that you will find very helpful when proving identities. When you have tan in any identity, I'll show you some examples of this as well. When you have tan on one side of an identity that you're starting from, and there's no tan on the other side, it's mostly more efficient to convert that tan to sine over cos right away in the very beginning. And that will help you prove that identity more efficiently than if you were to not convert it in the beginning and just simplify it as it is, and then at a later step convert it to sine over cos. It will make your working much longer. So if there's an identity in which on one side you have a tan term, on the other side there's no tan. For example, you might have sine there or might have cos there. You know that tan has to be eliminated eventually, because if you want to convert it to sine or cos somehow, rather than waiting for later, you would right away replace it with sine theta or cos theta. And that will simplify your working in most cases. You can try that while we're proving identities. Now, tan can be written as sine over cos. When you have cos over sine somewhere, you can also write that as 1 over tan. Okay, and then you can, sorry, if you have 1 over tan somewhere, you can also write that as cos over sine. And that will simplify your working. Let's have a look at this example. So you have 1 minus 1 over sine theta minus 1 over tan theta whole squared. And you have to prove that this is identical to 1 minus cos theta over 1 plus cos theta. Now, one idea could be that we take LCM here first of all, and then we square that, and then we somehow, simplify everything and then convert tan to sine over cos. Compare that with replacing 1 over tan with cos over sine in the very beginning. What happens when you do that is the denominators become the same and the simplification becomes much easier, much quicker, right? It becomes much quicker and you are able to prove the identity much faster. So whenever you have tan in an identity and you do not want tan in the final result that you got, convert tan to sine over cos right away, or 1 over tan to cos over sine right away. Okay, and that will help you do this better, do this quicker. And then a lot of times what happens is they make you prove an identity in one part and then they make you use that in the next part. For example, they ask you to prove this identity in the first part and then they ask you to solve this equation. Okay. Now, how do you solve this equation? You say you've proved in the first part that this thing is equal to this thing. So you replace it with that. So the equation becomes 1 minus cos theta over 1 plus cos theta equal to 2 over 5. And now that's straightforward to solve. You make cos theta the subject, and then you use quadrants in basic angle to find out the final answer from that. Now, this is a relatively complicated part, and that is okay. So I'll answer that later. Solving equations having angles that are not just x or theta, not just x or theta. Now, what does that mean? So until now, the equation that we have seen looked like this. For example, cos theta equals 3 over 7. We know how to solve that. You could have x here or theta here. However, what if you have something like this? Sine of theta plus 60. How do you solve this equation? Now, this is what I recommend that you do for this. Let's say you've got this interval given, theta from 0 to 360. That's the interval that's given, right? What you do is you say, whatever is inside the bracket, you substitute that with another letter. So you say a equals theta plus 60, you do substitution like this. Whatever is written inside the bracket, you substitute that with another letter. So in this case, a becomes theta plus 60. So now that equation is reduced to sine a equals 0.5, and that becomes much simpler. and you can solve it using the previous way. However, there's a catch, and that is the interval that was given, that was for theta. The angle now is A, that's not theta. So you also have to adjust the interval. How do you do that? Theta is from 0 to 360. And you are saying that A is equal to theta plus 60. How do you find the corresponding interval for A? You input 0 here in place of theta. What's the corresponding value of A that you get? That's 60 degrees. So the minimum value for A is going to be 60 degrees. Input 360 here in place of theta. What's the corresponding value of A that you get from that? That's 420 degrees. So the interval that you got for A, that's from 60 degrees to 420 degrees. So now when you solve this equation, you have to solve this within this interval. So you do it the normal way now. Find the basic angle. The basic angle turns out to be 30 degrees. And now sine is positive. Sine is positive in the first quadrant or in the second quadrant. Since the basic angle is 30, the first angle that you get here is this angle. This is the first angle in the first quadrant. That's 30 degrees. However, if you notice, that falls outside the interval. That's not in the interval. So you do not consider that. Okay? Because 30 does not fall in the interval. You cannot consider that. So you go beyond that. This is the next angle that you get. That's 150. 150 does fall in that interval. So that's your first angle. That's your first angle. Okay? And then, since the interval is going beyond 360, that means you have to go in one full circle, and see if there's any other possible angle that you can get inside that interval. So you can go for one full circle, that's 360, come back here, that's 390. 390 falls in this interval. You will consider that another possible angle. You'll say the value for A could be either 150 or it could be 390. And then you put that substitution back. Theta plus 60 is equal to 150. Theta plus 60 is equal to 390. And that gives the corresponding values of theta. If you had not adjusted that interval, you would miss out on this possible answer, 360 plus 30. So adjusting this interval is very important. Whenever you do a substitution like this, you always have to adjust the interval as well. Let's take another example of this. There's actually a plan going on here. We'll have a 1 minute break and then we'll resume after this. You can have a look at this example. We'll discuss it then. Okay, before we resume, any one having problem understanding what I'm saying? Am I speaking too fast or is it okay? Because I'm feeling that I'm sometimes speaking so fast that I can't understand what I'm saying myself. Is it okay? Does everyone understand what I'm saying? It's okay. Of course, if you've done these concepts, then if you're seeing something for the first time, then you have to cover that concept in detail. That's going to be important. Okay, good. All right. We're doing more examples of that, Abdul Hadi. We're doing more examples of that. Okay. Okay, let's resume. Sine of 2x plus 3 cos 2x again. You see, the angle is not x or theta, it's 2 times x. So what do you do in this case? You use a substitution. You say, let a or any other letter equals 2x. Before that, we have converted that to one function. So this was sine 2x equals minus 3 cos 2x. So we divide cos 2x on the other side, it becomes tan, and we have tan 2x equals minus 3. And now, since the angle is not x, it's 2x, we use a substitution. We say let a equals 2 times x. So whatever is the angle, you substitute that with another letter. In this case, we say a is equal to 2x. Now, the interval for x goes from 0 to 180. What's the interval for a going to be? You input 0 in place of x here, that becomes 0. Input 180 in place of x here, that becomes 360. That means the interval for a, therefore, is from 0 to 360. So now when you solve this equation, tan a equals minus 3, find the basic angle. The basic angle turns out to be this. When you are looking at the quadrants now, this is the interval that you have to consider from 0 to 360. Now, tan is negative. Where is tan negative? Tan is negative in the second quadrant or in the fourth quadrant. Find out the angles within this interval. So in the second quadrant, it'll be 180 minus this. In the fourth quadrant, it'll be 360 minus this. And you get two angles from that. Put that substitution back at the end. Put 2x equal to this, 2x equal to this, and you find the corresponding values of x from that. The final answer that you get, when you follow this method correctly, the final answers are automatically going to fall in the given interval that you started from. So these are the values of x that we had. Okay. Now, when it comes in radians, it becomes a bit too complicated. For example, if you had something like this, sine of 3 theta minus pi over 4. Let me actually show you this example first. We have to solve this equation. Sine of 2 theta plus pi over 3 equals 1 over 2, where theta is between 0 and pi. That's this. This is the equation. Angle is between 0 and pi. What do we do? The angle is not just x or theta. It's something multiplying with theta and something adding as well. How do we deal with this? Whatever is inside the bracket, you substitute that with another letter. So you say, let a equals 2 theta plus pi over 3. Okay. Now you have to find the interval for a as well. How do you do that? Input 0 in place of theta. That gives you pi over 3. Input pi in place of theta, and that gives you 7 pi over 3. So now when you solve this equation, sine a equals 1 over 2, you have to find all possible angles in this interval, that's pi over 3 to 7 over 3 times pi. Now, you solve it the normal way. You find the basic angle. The basic angle turns out to be pi over 6. And now sine is positive. Where is sine positive? Sine is positive in the first quadrant, and it's positive in the second quadrant. Okay. In the first quadrant, the angle turns out to be pi over 6. So in the first quadrant, we've got pi over 6. Now, is that in the interval? The lowest value that you have here is pi over 3. Pi over 6 is smaller than that. So you cannot consider that. It does not fall in the interval. Even though in the original interval, the smaller value was 0. But we're not solving for theta here. We're actually finding the value for a. The value for a has to be between pi over 3 and 7 pi over 3. So the first angle that we're getting here, pi over 6, we cannot consider that. That's outside this interval. Then, what about the next angle? This is the next angle that we're getting. This is going to be pi minus pi over 6. And that gives us another value. This is inside the interval. This is 5 pi over 6. You can compare that with pi over 3. That is in the interval, so you consider that. Then you go further. You go one full circle. Since the interval is 7 pi over 3, 7 pi over 3 is greater than 2 pi, right? Complete circle is 2 pi, 7 pi over 3 is 2.33 pi. So that's more than one full circle. That means it may be possible that you go one full circle and come back to get another possible angle. So if you go one full circle, that's 2 pi, plus that basic angle pi over 6, that's 13 pi over 6. Is 13 pi over 6 in the interval? Yes, 13 pi over 6 is in the interval. So you just equate that to 2 theta plus pi over 3, find the value of theta from that. That's another possible angle that you get. If you are finding it difficult to compare these two, just put them on your calculator. 13 over 6 and 7 over 3. 7 over 3 is bigger, 13 over 6 is smaller. That means it does fall in the interval. So you get two possible solutions from this. These are the two values of theta that you get. Now, sometimes you end up getting something more complicated. It happens more in paper 3 later on. Less in paper 1, but it can happen, that you end up getting 4 answers like this. So you can have a look at this example. So basically, this is the angle. We replace that with another letter. We say let a equals this. We adjust the interval the same way. That turns out to be from minus pi over 4 to 11 pi over 4. And then since the interval is going in the negative direction, we also have to consider angles in the negative direction. So we have to check if there's anything in the interval in the negative direction. And the upper limit is going beyond 2 pi. So that means we also have to check if there are any angles in the positive direction after completing one full circle. So one full circle, and then you can come back here. get more angles. So in this case, you end up getting 4 possible angles, all of them in the positive direction, none in the negative direction. You can check that, have a look at this working, go through this. This is a good example. Okay, now sometimes you end up getting equations that look like this, where they have sine inverse, of something. Sine inverse of x squared minus 1 equals pi over 3. Now, how do you solve this equation? Sine inverse of x squared minus 1. That's not something that you can evaluate on your calculator, because this is x here now. On the other side, you've got pi over 3. What you can do is you can take sine inverse to the other side, and that gives you sine pi over 3. And now it becomes a simple quadratic equation. You've got x squared and you've got a number on the other side. Just solve it like you would normally solve any quadratic, and you can solve it and you can get the value of x from that. So when you have sine inverse in an equation given, consider if so sometimes they can have something like this as well. Sine inverse of maybe under root 3 over 2. If you have some number inside, just evaluate that on a calculator and that will work. If they have some variable inside, like in this case, they have a variable inside. In that case, this is something that you cannot evaluate from a calculator directly. So what you would consider doing is, you would consider taking this to the other side. So in this case, when you take sine inverse to the other side, that becomes sine pi over 3. And then you can solve that equation like this. All right, let's move on. Now, these are some identities that you need to know about. When the question does not specify if it has to be a fraction or decimals, it doesn't matter. You can write any of them, and that'll be fine. If the question specifies, then you have to follow that instruction. Okay, complementary angle identities. Now we've got some identities that are not given in the formula sheet that you need to know about. Complementary angles are those angles that add up to 90, right? So for example, 40 and 50, these are complementary angles because they add up to 90. We have these identities that, for example, if you have sine of 25, that is equal to cos of 65. If there are two angles that add up to 90, sine of one is going to be cos of the other. So for example, if you have sine of 70, that's the same thing as cos of 20. Because they add up to 90, sine of one is going to be equal to cos of the other. Now, there's a logic behind it. You can have a look at this, but that's the identity that we have. Sine of 90 minus theta, that's cos theta. Cos of 90 minus theta is sine theta. And tan of 90 minus theta is 1 over tan theta. These are three identities that you need to remember. These will be helpful. These will actually be needed in some trigonometry questions. Sine 90 minus theta is cos theta. Cos 90 minus theta is sine theta. And tan of 90 minus theta is 1 over tan theta. In radians, those same identities become this. Sine of pi minus theta, pi over 2 minus theta is cos theta. Cos of pi over 2 minus theta is sine theta. And tan of pi over 2 minus theta is 1 over tan theta. You need to remember these identities. They're not given in the formula sheet. You need to use them sometimes. Let's have a look at this example. So they have given you that cos of x equals p, where x is an acute angle in degrees, and we need to find the value of sine x, tan x, and tan of 90 minus x in terms of p. Now, one way to do this is using identities. You can say, okay, if cos x is equal to p, we know that sine square of x plus cos square x is equal to 1. Just input the value of cos x in that, find the value of sine from that. So sine turns out to be plus minus square root of 1 minus p squared. Now, do we use the plus sign or the minus sign? Since the question says it's an acute angle, that means it has to be in the first quadrant. In the first quadrant, sine is positive, so we only consider the positive value here. We say sine of x equals square root of 1 minus b squared. Now, in the second part, they say, find the value for tan x. Tan is equal to sine over cos. We already are given the value for cos. We have found the value of sine in the first part. So we can say tan x equals sine x over cos x, and that gives us the result. And then they say find tan of 90 minus x. How do you do that? We just did that identity. Tan of 90 minus x is the same thing as 1 over tan x. If we know tan x, we can just take reciprocal of that, and that will give us the value for tan of 90 minus x. That's one way to do this. You can do it like this. But sometimes there will be some questions that you will not be able to do using only identities. And for that, there's another method that you also need to know, and that is by making right angle triangles. So if they're saying cos of x is equal to p, and x is an acute angle, what we can do is we can say x is an acute angle, that's in the first quadrant. We can make a triangle like this in the first quadrant, such that this is the angle x, right? If this is the angle x, and we're given that the value of cos of x is equal to p. Now, we can consider p as p over 1. That's the same thing, right? Cos x is equal to p. That's what the question said. We could say that's p over 1. Now, cos is defined as base over hypotenuse. So we can say if the base is p, then the hypotenuse is going to be 1. So we can say base is equal to p, hypotenuse is 1. Can we find the perpendicular from that? Using Pythagoras, we can find the value of perpendicular from that. And in this triangle now, we know that the base is p, the perpendicular is square root of 1 minus p squared, and this hypotenuse is equal to 1. So now once we have this, we can write down the values of sine, cos, tan directly from that triangle. Sine is perpendicular over hypotenuse. Perpendicular is square root of 1 minus p squared over the hypotenuse. That's 1. That gives you the value for sine. Tan is perpendicular over the base. Perpendicular over base. That gives you tan. Tan of 90 minus x. If this angle is x, the angle on top here is 90 minus x. So if you find tan of that angle, that turns out to be opposite over adjacent. That's p over square root of 1 minus p squared. Okay. Now in this particular question, you could use identities as well, and they will work just as well. However, you'll find some examples in which you would not be able to use identities, or you'll have to remember too many identities in that case. Like there are like 15, 20 of them. If you want to memorize all of them, you can do that. But that's too much. It'll be very difficult to remember all of them. So understand the logic behind it. Acute angle x is such that tan of x is equal to k, where k is a positive constant. Expressed in terms of k, tan of pi minus x. Now, we don't have any identity that we have learned for this, tan of pi minus x. How do you figure this out? You make a right angle triangle for this. What right angle triangle? The angle x is acute. Okay, so where is x going to be? X is going to be in the first quadrant. So let's make a triangle in the first quadrant like this, first of all. Such that this is the acute angle, that's x. Now, we are given that tan of x is equal to k. So we can say tan x is equal to k, right? If tan is equal to k, we can say that's k over 1. That's the same thing as that. Tan is defined as perpendicular over the base. So if perpendicular is equal to k, then base is equal to 1. Use Pythagoras to find hypotenuse, and that turns out to be the square root of 1 plus k squared. Okay, so now that tells us that this is k, this is 1, and this is square root of 1 plus k squared. Okay, now this will help you solve some of these parts. For example, in the last part, that's the 2-mark part, they're asking you for sine x. Okay, what is sine x? Sine x is perpendicular over the hypotenuse. Perpendicular is k in this case. Hypotenuse is this. So the value of sine turns out to be this, k over square root of 1 plus k squared. Now for the other parts, for the second part as well, let's do that as well. So tan of pi over 2 minus x. Pi over 2 is 90 degrees. We can say if this angle is x, then this is going to be pi over 2 minus x, right? Because this is pi over 2. So the remaining angle is pi over 2 minus x. Find the tan of that, and that tan of that turns out to be opposite over the base. That's 1 over k. But the problem is, what about pi minus x, tan of pi minus x? Now, where is that going to be? If you think about it, x is an acute angle. X is an acute angle. If you do pi minus that, so think about an acute angle in degrees, 40 degrees. Pi is 180 degrees. So 180 minus 40. What is that going to be? 140 degrees. That's an obtuse angle. So if x was an acute angle, pi minus x is an obtuse angle, right? That will go in the second quadrant. So now we've got this triangle in the second quadrant, this one, such that the angle here, this angle is pi minus x. Now, what's the basic angle in that case? If the straight line is pi, then, sorry about that. We were here, right? Yeah. So this is the triangle in the second quadrant, and this angle is pi minus x. Now we know that the straight line is pi radian. The straight line is pi radian. This straight line is pi radian. If this is pi minus x, that means this angle here is going to be x. So the basic angle is x. If the basic angle is the same, that means the triangle here that we would get, it would have the same length as that first triangle. The perpendicular is k. The hypotenuse is square root of 1 plus k squared, and the base is going to be 1. So that means whatever was the tan value earlier, k, the value of tan here is also going to be k over 1. However, since we're in the second quadrant, we know that tan is negative. We put a negative sign with that, so the value turns out to be negative k. Okay, so you need to understand how to work with these triangles. I'm going to show you some more examples that you can have a look at in your own time. Have a look at this working. And then have a look at this working as well. Okay, then the next thing that you have is graphs. So you can have a look at those examples later on in your own time. So trigonometric graphs, that's the next major concept that you have here. You need to be able to sketch these graphs, sine x, cos x, and tan x, and any of their transformations. You might have something multiplying with them, something adding, subtracting with them. You need to be able to sketch these graphs. Now, you need to remember the shapes of the graph. Sine x looks like this. Its shape is this. Okay. You need to remember the shape. The cos graph looks like this. You need to remember the shape. And the tan graph is in multiple parts like this. And it has asymptotes at different points as well. How would you actually draw these graphs? Whatever function is given, whether it's just sine x, or if it's sine of 2x, or if it's 2 sine x minus 4, whatever is given, all you have to do is put that in the table function on your calculator. Put that in the table function on your calculator, and you get some values of y from that. For example, if you want to draw the graph from 0 to 360, all you have to do is put this in the table function on your calculator, go to menu, table. In this case, the angle unit is degrees, so we choose degrees here. F of x equals sine of x. Put that in your calculator, start from 0, end at 360. Take a step so that we have enough values. You can make 45, you can make 90 degrees. If you know the shape, dividing the interval by 4 is generally going to be enough. So you divide 360 by 4, and that's 90. You have these values, plot these values, and through those values, just draw the sine graph, and that's it. That's all that you have to do. Whatever transformation it is, if it's multiplying by something, if something is being added or subtracted, you don't care about that. Just put that in the table function, plot those points, join those points, and you get your graph. All you have to do is remember the shape of the graph. Sine looks something like this. It could either be like this or some reflection of this. Cos looks like this, and the tan shape as well. You need to remember those shapes. As long as you remember the shapes, you will plot some points. You will recognize what the shape looks like, and that's it. You'll get your graph. Okay, so you just use table function for sketching any of these graphs. Now, we have some things that are defined for these graphs that you need to know about. First of all, we've got period. Period is the interval in which the graph completes one full cycle. For sine and cos, the period of the graph is 360 degrees or 2 pi radians. For tan, the period is 180 degrees of pi radian. Then you've got the baseline of the graph. Baseline is the line about which the graph moves up or down. For example, in all of these graphs, in the standard graphs, the x-axis is the baseline. This is the line in the middle of the maximum point and the minimum point. It's exactly in the middle. The graph is oscillating about this line like this. This is the baseline, the x-axis in the standard graph. For all of these functions, for sine, cos, and also tan. Now, for sine and cos, you'll be able to figure out the baseline by finding the midpoint of the maximum and minimum point. So if there's some transformation, I will see some examples in which you have to figure out what graph it is, what function it is. You can find the baseline by just finding the midpoint of the maximum point and the minimum point. For tan, however, since no maximum or minimum exists, it goes from negative infinity to positive infinity. For recognizing what the baseline in a tan graph is, you basically identify where the graph is changing its direction. So it goes in one direction first and then goes in the other direction like this. So when it changes direction, that's the point where the baseline is going to be for a tan function. Okay. Now that's the baseline. Amplitude is the maximum distance the graph can go from the baseline in the vertical direction. In sine and cos, the standard amplitude is 1. For tan, there is no limit. So this is the summary. For sine and cos, the amplitudes are 1. For tan, it's infinity, or you can say it's undefined. Periods for sine and cos are 360 and 2 pi. For for tan, it's 180 degrees or pi radians. Now, you need to understand what happens when there are some transformations of these graphs. So when there's something multiplied outside, or some number multiplied outside, a sign multiplied outside plus minus, or something being not plus minus, just minus multiplied outside, or something is being added or subtracted outside. What happens in each of these cases with this function? When you multiply by a negative sign, that's a reflection in x-axis. When you multiply by a number, that's a stretch with scale factor a. But in terms of the sign function, you can also understand that this number represents the amplitude of the graph. For both the sine and cos functions, if you have a number multiplying outside, that represents the amplitude of the graph. For tan, the amplitude does not exist. So for tan, that's not the case. You just think of that as stretch. But for sine and cos, you understand this number as the amplitude of the graph. And the number that's adding or subtracting outside, that translates the graph up or down generally. But in terms of the trigonometric function, you can also understand that it represents the baseline of the graph. So the number that's outside, that's the baseline of the graph. So if you have sine of x plus 3, the baseline of that graph is y equals 3, this horizontal line. If you have a function that's 2 sine x, the amplitude of this graph is equal to 2. So this is what these numbers represent. So in vertical transformations, something is happening outside the whole function, right? A number multiplying or minus multiplying, or something adding or subtracting. Only the y coordinates change because of this, right? Then you have horizontal transformations. In horizontal transformation, what happens is you have some operations applied inside the function with x. X could be multiplied with negative, x could be multiplied by a number, or there could be something adding or subtracting to x like this. Now, when you have minus multiplying here, that means it's a reflection in the line y-axis. When you have a number multiplying, that's a stretch with scale factor 1 over a, as we'll see in function transformations as well. But in terms of trigonometric functions, this number that's multiplying inside, it also means that the period is going to change because of that. So if you have tan of 3x, for instance, tan of 3x. Now, this basically tells you that the period of the graph is going to get divided by 3. So what's the original period for tan? Original period for tan is 180 degrees. When you have 3 times x, the period gets divided by 3, and now tan completes one full cycle in 60 degrees. If you had sine of half x, what about the period? Its original period is 360, or in radians is 2 pi. That gets multiplied by 2 because 360 over 1 over 2, what's that? That's 360 times 2, that becomes 720. So because of this number that's multiplying, what happens is the period changes. The period gets divided by that number, okay? And then the number that's adding or subtracting here, there's no special interpretation of this. It's just translation. If you have plus here, that means you're going left. If you have minus here, that means you're going right. So for example, if you have tan of x minus 90, what that means is you're going 90 units to the right side. Let's have a look at some quick examples, and then we finish this, and I'll take your questions if there are any. It says, sketch on a single diagram the graphs of y equals cos 2 theta and y equals 1 over 2. How do you do this? You put this on your calculator. Y equals cos 2 theta. Make sure your calculator is in radian mode. Take an interval of maybe 2 pi divided by 4, that's pi over 2. Or if you think you need more values, you take an interval of pi over 4, take a step of pi over 4, plot those values, join those values, you will get the cos graph. Okay, there's no thinking that's required here. Just plot values and draw the graph. What you do need to remember is the shape of the graph so that you can draw that correct shape through those points. Y equals 1 over 2 is just a horizontal line, so we've drawn those 2 lines here. Now, they will ask some questions based on this. They're saying, write the number of roots of this equation. Remember, graphs of functions in O levels, you want the function that you have sketched on one side of this equation. How do you do that? This is 2 cos 2 theta minus 1. So you rearrange this in such a way such that on one side you get cos 2 theta. Now on one side you get cos 2 theta, on the other side, in this case, you end up getting 1 over 2. So that means it becomes cos 2 theta equals 1 over 2. The solutions of this equation are going to be the same as the points of intersection of these two graphs cos 2 theta, and 1 over 2. And these are the same two graphs that you've drawn in the first part. Look at the points of intersection. There are 4 points of intersection, 1, 2, 3, 4. So you say that's the number of solutions. That's 4. They will not ask you to find the exact solutions because that's not possible from a sketch. They will only ask you for the number of solutions. Just look at the number of points of intersection and you write down the result. Now, there could be something more complicated like this as well. They're saying reduce the number of roots of that same equation in the interval from 10 pi to 20 pi. Now, from 0 to 2 pi, there were 4 solutions. Now, since the graph is symmetric and it's going to keep repeating like this, it's a cyclic graph. It's going to keep repeating like this. In an interval of 2 pi, we're getting 4 solutions. Using ratios, we can say if from 0 to 2 pi, we're getting 4 solutions, then from 10 pi to 20 pi, that's a gap of 10 pi radians. In that interval, it's going to be 20 solutions because 2 times 5 is 10 pi, so 4 times 5, that gives us 20. That's the number of solutions that we would have in that case. They sometimes ask you to solve inequalities using graphs like this as well. So in the first part, they just ask you to solve this equation in this question, and then they ask you to sketch 2 graphs. Let's say you've done that again using the table function on your calculator. You just sketch these 2 graphs. But then in the last part, they're saying use your answer to part 1 and 2 to find the set of values of x for which x is between 0 and 360, for which 2 cos x plus 3 sin x is greater than 0. Now, how do you make sense of that? You have solved this equation in the first part. 2 cos x plus 3 sin x. We're almost done. We're almost done with trigonometry. 2 cos x plus 3 sin x equal to 0. We've got this equation, right? Now, we solved this equation. We found 2 solutions from that. One solution was this, and the other solution was this. And then they want us to solve this inequality now. What did they make us do in the second part? They made us sketch these 2 functions, 2 cos x and minus 3 sin x. Now, if 2 cos x plus 3 sin x is greater than 0, that's the inequality that we want to solve. If we rearrange this, what do we get from that? We get 2 cos x greater than minus 3 sin x. Now, these are the 2 functions that we have drawn. We have drawn 2 cos x, that's one function that we have drawn, and minus 3 sin x. And the inequality is saying 2 cos x is greater than minus 3 sin x. 2 cos x is greater than minus 3 sin x. In what region on the graph is the 2 cos x graph above the minus 3 sin x graph? So I've represented the 2 cos x graph in orange and the other one in green. Where is the orange graph above the green graph? In these highlighted parts, this part and this part. That is where the orange graph is above the green graph. So those are going to be the values of x that satisfy this inequality. Now, what are those values of x? We have found in the first part the points of intersection. So we know that this point of intersection is 146.3, and we know that this point of intersection is 326.3. So what are the solutions going to be? X between 0 and 146.3, this left side, and x between 326.3 and 360, that's this part of the graph. These are the solutions of this inequality. That's why we can do that using this graph. Okay, so sometimes they can ask you to solve inequalities like this as well from the graph. One last example. So you've got the sketch, y equals 2 sin x. Again, you do that using the table function in your calculator. And then they ask you to add a suitable straight line to your sketch. Again, graphs of functions, O levels. To determine the number of real roots of this equation, 2 pi sin x equals pi minus 6. Now, how does this connect to the first part? This is the graph that we have drawn. We rearrange this equation in such a way that on one side of this equation, we get 2 sin x somehow. How do we do that? We divide pi on the other side. And then on the left side, we're just left with this 2 sin x. And now we simplify this. And that means this is one function, y equals 2 sin x. We already know the graph for this. And the other function is y equals 1 minus x over pi. We would have to draw this graph and then look at the points of intersection of these 2 functions. Now, this is a straight line, although it looks a bit weird, but it is a straight line because it's mx plus c form. Minus 1 over pi is just a constant. So that's the gradient of the line, x plus the y-intercept. So what you do is you draw this graph, take 2 points in this, draw that graph, look at the points of intersection. There are 3 points of intersection. So that's the number of real roots. And what's the equation of the straight line? We already wrote that there. That's y equals minus 1 over pi times x plus 1. That's the equation of that straight line. And the points of intersection are 3. So there are 3 solutions because of that. Okay. I hope that makes sense. If you have any... Okay, so let me know if you have any questions now. I'll be answering those questions. Before that, just a small pointer. You have questions on function transformations. You have function on trigonometry transformation in which they give you graphs and they give you a graph, and based on that, they ask you to figure out what the equation of that function would be, right? Now, for that, we will, those questions we'll actually discuss when we do function transformations. That's the next thing that we'll be doing. In that topic, we will also discuss the transformations of trigonometric graphs. We would have graphs given, and using those graphs, we'll have to find out what the function is going to be. Okay, so let me know if there are any questions that you guys have. Okay, how do you determine the period for sketching the graph using calculator? Period is generally given. So this is 0 to 2 pi. So that start is 0, end at 2 pi. What do you mean by period? The starting point and the end point? You can actually open this mic as well for you guys. Okay, you can do that later. Period for sketching the graph using calculator. What do you mean by period? And the step. Okay, so the step, you're talking about the step. Step is the interval that you want, the gap that you want between values. So if the graph is from 0 to 2 pi, how much gap do you want between each value? For example, in this case, you have a graph of 2 sine x, right? I generally recommend that you divide this interval into 8 parts. Whatever the interval is, divide that by 8. So 2 pi over 8, that gives you pi over 4 in this case. However, if you remember the shapes of the graphs well, taking 4 points is also going to be enough in a lot of cases. So if you think you remember your graphs well, you can get away with just dividing by 4 as well. So take an interval of pi over 2. So in radians, you take an interval of either pi over 2 or pi over 4. In degrees, you either take an interval of 45 degrees or 90 degrees generally. That's the interval that you take. Either 90 degrees or 45 degrees. It depends on you. Depends on the number of points that you need. Okay. So divide the interval by 8. That will give you enough values. If you know your graphs well, you can also just divide by 4. And then if you remember the shape, you can draw that shape through those points, and that will also be fine. So for figuring out this straight line, remember graphs, how do we solve equations graphically? We have one function that we have sketched already, that's 2 sine x. And the equation that we want to solve is 2 pi sine x equals pi minus x. We want, on one side of this equation, this function, 2 sine x. So we want to get rid of this pi from there. How do you do that? You divide pi on the other side. When you divide pi on the other side, this is what you get. Pi over pi minus x over pi, that becomes 1 minus x over pi. That's the equation. I've just rearranged that here. It's not required to do that. You can just leave it like this as well. That's the equation. And then how do you sketch that? Take any 2 points. It's a straight line. Put one value of x, you get some corresponding value for y. Put another value of x, you get another value of y. And then draw a straight line through those points. If your calculator is not giving you exact values, I would highly recommend that you change that calculator. So if you have this version and that's not giving you exact values, then that's not original, that's some copy, and that can cause some other problems as well. It might give you some wrong results for some expressions. It can happen. It's a risk. I would not recommend that you take that risk. Change that calculator and upgrade that. Yeah, if you take any copy, that would not be reliable. You can end up getting wrong answers from that as well. Any reliable shop. So if you are, I only know about Lahore. If in Lahore, you can go to main market. You've got those big bookshops like Anis, I think, and there's another in front of that, uh, Iqbal Book Corner, I think. You've got readings. You get it from anywhere there. It's expensive. It is expensive. There is another brand uh, that has an exact same version, and that's relatively more reliable as compared to the fake copies that you have in the market. I'm forgetting the name for that. I think people from Karachi would be familiar with that because I think it's very common. There's some teachers, they also recommend that. I've seen Saad, I think, recommend that. Maybe not Saad, so Salman probably. I'm forgetting that name, unfortunately. So that's basically another brand that makes copies of this as well, but that's a relatively reliable brand as compared to the copies that you have in the market generally. But I don't remember the name for that right now. Let me think about it and get back to you. Have I told about that calculator, about that brand before? Urdu Bazaar has this calculator for 1000. Aisha, it's very unlikely that all the functions work on this. Make sure that you check that thoroughly. Make sure that check that thoroughly. That everything that you are doing, it's giving. Yeah, Abaco calculators. Thank you for finding out about that. Abaco. That's another brand. That's relatively cheaper. It has the exact same version, and that's relatively reliable. I think that's half the price of this. If you can get that in Lahore, that would be a better choice. Online, Abaco. I think it might have a website that you can order from. You can check online. I think it does have a website. What about this? Okay, so if you're sure that it's working fine for you, then that's okay. In the second part, we'll just sketch these graphs. Or the third part. Are you asking about the second part or the third part? Can you just ask verbally? That will be easier. That will be quicker. Okay, third part. Okay, 2 cos x plus 3 sin x. They're saying this is the inequality that you need to solve. We rearrange that and we get this. 2 cos x is greater than minus 3 sin x. What does that mean? On your graph, you've got two functions. One is 2 cos x and the other is minus 3 sin x. The inequality is saying 2 cos x should be bigger than minus 3 sin x. That means the value of 2 cos x should be greater than the value of minus 3 sin x. So look at the graph and see the region in which the 2 cos x graph is above the minus 3 sin x graph. So that's in two regions. That's this region, this highlighted region. That's where the orange graph is above the green graph. And the region on the side, that is when the orange graph is above the green graph. So what's the interval that you've got for that? You know the points of intersection. You know this point. You know this point from the first part. So it's either between 0 and 146.3, or it's between 326.3 and 360. So those are your values of x. Okay, all right. Let's begin. Function transformation. So this is the next the next topic that we're doing. Function transformations. So there are three types of transformations that you need to know about in A levels: reflection, translation, and stretch. Reflection and reflection and translation I've done in O-levels as well. Stretch is something new for you. Now, there are only going to be two types of reflections: reflection in x-axis and reflection in y-axis. Okay. So if you have this triangle here on the left side, it can either be reflected in x-axis like this or y-axis like this. How would you describe this? You would say either reflection in x-axis, in y-axis, if it's in y-axis, or you would say reflection with y-axis as the line of reflection. Do not write reflection along y-axis. That's not acceptable. So you can either write in this short form. In the short form, you would use the word in. Okay, reflection in y-axis or reflection in x-axis. Or to be safer, you can write it full like this: reflection with y-axis line of reflection or reflection with x-axis as the line of reflection. Now, when it's reflection in y-axis, what happens is, if you've got this original figure and that gets reflected to this, the movement of the points is horizontal, right? The movement is horizontal. If the movement is horizontal, we call this horizontal reflection. When it's reflection in x-axis, the movement of these points is vertical. So we say this is a vertical reflection. So reflection in y-axis, we will be calling this horizontal reflection. Reflection in x-axis, we'll be calling this vertical reflection, because horizontal reflection means the direction in which you've got the points moving. Okay, now that's something that you can understand in this. Y-axis, when that's the line of reflection, it's horizontal reflection. When x-axis is the line of reflection, that's vertical reflection. These are two types of reflection that you need to know about. Then you've got translation. There are two types of translation that you need to know about: horizontal translation and vertical translation. In this case, you will always have to write down vector. So if you have a point, if you have a triangle that's going from ABC to this transformed figure, A double dash, B double dash, C double dash, what's the translation vector for that? It's going 1 unit left and 1, 2, 3, 4 units up. The translation vector is going to be -1, 4. -1 means you're going 1 unit to the left. 4 means you're going 4 units up. 4 units up. Now, for describing a translation, you always write down a vector. You cannot write this in words. You always have to write down a vector. That's necessary. Now, these are two transformations that you already know about from before, from O-levels as well. Then there's one new transformation, that's stretch. How does stretch work? There are two types of stretch that you have in the syllabus: vertical stretch and horizontal stretch. In vertical stretch, what happens is you see the distance from the x-axis. If the scale factor is 3, for instance, the stretch works like this. Every point, whatever its distance was before, it becomes 3 times that distance. For example, if you have this point C, this point C has a distance of 1 unit from the x-axis. After transformation, what happens is it becomes 3 units from the x-axis. That's a stretch with scale factor 3. For B, the distance was 2 units from the x-axis. After transformation, what happens is it becomes 2 times 3, and that becomes 6 units. That's a vertical stretch when the y coordinates get multiplied by the scale factor. If it's a scale factor of 3, then you say whatever was the y coordinate before, it gets multiplied by the scale factor. You can have a horizontal stretch as well. In horizontal stretch, you think about the distance from the vertical axis, distance from the y-axis. So, for example, if ABC, this was the original figure, and you want to stretch this by a scale factor of -1/2, what would you do for that? You would say B point is 3 units away. You multiply that 3 by -1/2, and that becomes -3/2. That's where the point B is going to be. Right. Similarly, for A, this point is at a distance of 1 unit to the right side. If it's stretched by a scale factor of -1/2, what happens is the x coordinate 1, it gets multiplied by -1/2 and it goes here. And that's how stretch works. So all you have to do is, in case of vertical stretch, multiply the y coordinate by that number. In case of horizontal stretch, multiply the x coordinate by that number. And that's how the graph moves. Your figure becomes bigger in one direction. If it's a vertical stretch, you will see that the height of the figure will change. If it's a horizontal stretch, you would see that the base, that the width of the figure, that's going to change. So it was 3 earlier, it becomes 1.5 like this, right? So if it's a vertical stretch, the height changes. If it's a horizontal stretch, the width of the graph changes. Now, these are three transformations that you have. How do you describe these transformations? You have to describe these in exactly one of these ways. Exactly one of these ways. So there are three types of transformations. First of all, you've got reflection. You either we talked about this before as well. Either say reflection in x-axis or reflection with the x-axis of the line of reflection. Similarly for the y-axis, this is vertical reflection because the movement of the graph is vertical. Then you've got translation. You have to write down the translation vector for this. If it's a vertical translation, you have something in the y component here. If it's a horizontal transformation, you have something in the x component here. For stretch, you always describe it like this. If it's a vertical stretch, you either say it's a vertical stretch with scale factor something. If it's a horizontal stretch, you say horizontal stretch with some scale factor. Another way to describe this is you say for vertical stretch, it's a stretch along x-axis, stretch along x-axis with that scale factor. And similarly for the horizontal stretch. Or you can say stretch parallel to y-axis for vertical and stretch parallel to x-axis for horizontal. These are the only three descriptions that you can have for stretch. Don't write anything apart from these three, okay? Just one of these three. Don't write multiple. If one of them is wrong and the other is correct, that will be marked wrong. So just write one of these, whichever we are most sure about. You can write just vertical or horizontal, and that will be fine as well. Or you say either stretch along that axis or parallel to that axis. In reflection, do not use along. If you want to write it in short form, use in, or just say it's a reflection with that line as the line of reflection. Okay, that's how you describe these transformations. So you've got 6 transformations in total here. 3 vertical, 3 horizontal. In vertical, y coordinates change and horizontal x coordinates change. Now, how is that relevant to functions? Right? These are transformations. How do they relate to functions? So basically, what can happen is you may have a function f of x, and it can have something multiplied or a minus sign multiplied or something adding or something added or subtracted outside. When you have something like this, something adding or subtracting outside, minus multiplying outside, or a number multiplying outside, these are vertical transformations. The y coordinate changes because of that, because you're multiplying something with f of x, right? The y changes. In vertical transformations, the graph moves in the vertical direction. Only the y coordinates change, and the operations, some operations are applied outside the function, either plus minus, multiplication with negative, or multiplication with a number. These are 3 things that can happen. When you multiply by the negative sign, that means it's a reflection with x-axis as the line of reflection. If you had points x and y, since the movement of the points is vertical, the point that was above that goes down, the point that was down that goes up. So the y coordinate changes, plus y becomes minus y, right? The sign of the y coordinate changes, x coordinate remains the same. What about this number that's multiplying? When you have a number multiplying outside the function, that means it's a stretch along y-axis, or you can say vertical stretch with scale factor, that number, which is a. So if you have xy as the original point, that becomes x, a, y. The y coordinate gets multiplied by that scale factor. And if you have something adding or subtracting outside, if you have plus or minus something, that's a translation, that's a vertical translation. Plus means you're going up, minus means you're going down. Okay. And if you have a point xy, that becomes x, y plus minus b. The y coordinate has b added or subtracted like this. Then you have some horizontal transformation. In horizontal transformation, what happens is operations are applied inside the function, and the graph moves horizontally, and only the x coordinates change. Instead of outside the function, you've got something happening to x inside, x plus minus something, or minus into x, or a into x, right? Now, these are the 3 transformations that you've got. You can have something, you can have minus multiplied outside, minus multiplied with x. What does that mean? It's a reflection with y-axis, the line of reflection. It's horizontal reflection, so the x coordinate changes, x becomes minus x, y remains the same. When you multiply by 8 here, you multiply by a number, that's a stretch, that's a horizontal stretch, or you can say stretch along x-axis. with scale factor reciprocal of this number. So in horizontal transformations, things work a bit counterintuitive. When you multiply by a number, it's basically a compression. So the scale factor of the stretch is going to be reciprocal of that. That's 1 over a. So what happens to the coordinates? If the original coordinate was x, y, it becomes x over a. X is divided by that scale factor. X is divided by that scale factor. And then for a translation, if you have plus minus b, what happens in this case is when you have a plus in the function, you go left. When you have a minus in the function, you go right. Okay. Now the translation vector, what is that going to look like? If you have plus here in the translation vector, you would have minus. And when you have minus here in the translation vector, you would have plus, because plus in the function means you're going left, minus in the function means you're right. You're going right. So for example, if you have something like this, f of x plus 3, that means it's a translation 3 units to the left. The vector is going to be minus 3, 0 for this like this. Okay, that's what happens in horizontal transformation. When you add or subtract something, that's translation. Outside the function vertical, inside the function horizontal. When you multiply, divide by a number, that's a stretch. If you do outside the function, that's vertical. Inside the function, that's horizontal. When you multiply by -1, that's a reflection. When you do outside the function, that's vertical reflection. When you do inside the function, that's horizontal reflection. These are 6 transformations that you've got. Now, this is very important, order of transformations. So sometimes you can have multiple transformations happening at the same time. So when you have only one transformation, describing that is straightforward. Okay. But when you have multiple transformations, in that case, the order is important. You have to apply those transformations in the correct order. Now, how do you figure out what the order is? When you have horizontal and vertical transformations, some horizontal and some vertical, in that case, the order does not matter. You can do horizontal first, you can do vertical first. It does not matter. Both of them have because the horizontal transformations are only going to change the x coordinates. Vertical transformation is only going to change the y coordinate. So they don't have anything to do with each other. You can do any of them first and that will be fine. When you have multiple vertical transformations, for example, when you have something like this, -2 of f of x plus 7, or let's just stick this for now, -2 into f of x plus 7, what you do in vertical transformations is you follow BODMAS. Whatever BODMAS says, that's the order that you follow for transformations. Now, BODMAS says you do multiplication first. So that means you do stretch or reflection first, right? -2, that's multiplied. So you do this first, and then you do translation. So you do plus 7 later on after that. However, if it looks like this, when they have an extra bracket sometimes like this, and that happens a lot in recent papers, when they have extra brackets like this, what that means is, now BODMAS says bracket gets evaluated first. So plus 7 has to happen first. So that means in this case, you do translation first. It's a translation 0, 7 first, and then number 2, you do the stretch after that, and reflection after that. Right? Stretch and reflection, they have the same priority. Between them, it doesn't matter which one you do first, but translation in the second case happens first because that's what BODMAS says. And in the first case, translation happens second because that's what BODMAS says. In vertical transformation, you just have to follow BODMAS. In horizontal, however, you just do the opposite of that. You do opposite of BODMAS. Whatever BODMAS says, you do the opposite of that. So for example, in this case, you have f of minus 5x plus 3. Now, what does BODMAS say? BODMAS says that you would multiply by -5 first and then add 3. In horizontal, you do the opposite. You say, no, you'll do this first. That means you apply that translation first. And then after that, you do stretch. Okay. If you have something like this, that's the most complicated, the most confusing one. So you have f of -2 into x plus 4. What do you do in this case? Again, this is horizontal transformation because something is happening inside the function. You're doing something to x. Now, what does BODMAS say? Because of this extra bracket, BODMAS says that you would do plus 4, and then you would multiply by -2. But this is horizontal transformation. You'll do the opposite of that. You'll say multiply by -2 first. That means do stretch reflection first, and then do translation. So in horizontal transformations, you just have to do opposite to whatever BODMAS says. That's the order. That's the way you figure out the order of transformations. Okay. Now, for instance, if you had 2 into f of 3x, look at the first example. You've got one vertical, one horizontal. It does not matter which one you do first. You could do this first, you could do this first. It does not matter because between them, we don't care which one we do first because horizontal only change x, vertical only change y. If you have multiple vertical transformations like this, -4 and then the +1, in this case, you do stretch and reflection first. Or you can just say it's a stretch with scale factor -4. That's also fine. And then you say it's a translation after that. That happens second. In this case, the order matters. That's important. When you have horizontal transformations multiple, f of -6 -2, -6 is -2, you do the opposite of BODMAS. That means you have to do translation first, and then you do stretch or reflection after that. That happens second because that's the opposite of BODMAS. Sometimes you can have all of this happening at the same time, like this. You've got all vertical transformations, all horizontal transformations. What's the order going to be? You can start with either horizontal or vertical. That would not matter. You can start with either horizontal or vertical. It would not matter. So let's start with vertical, for instance. In vertical, you have to do stretch first in this case, because that's what BODMAS says. You do stretch first. And then you do this translation that's 0, 2. And then you can start with horizontal. In horizontal, you do translation first in this case, because opposite to BODMAS, that's 1, 0 translation, and then stretch scale factor -1/4. Now, when you have multiple transformations like this, and you have two translations coming one after the other, it's also possible to combine them as a single transformation and single translation, and you can say 2 and 3 could be combined to give 1, 2, and that will also be acceptable. Okay. However, if you had another transformation between these two translations, then you could not combine them. Then that would not be allowed. But if two translations are coming one after the other, then it's possible to combine them and write them as a single translation as well, and that will be fine. Y equals x, reflection in line y equals x, we do that when we have a function and its inverse, but we don't consider that in function transformations. The only place where that is relevant is when we have a function and its inverse function. So we don't study that in function transformations here. Let's look at this example. If you have a function f of x equals x squared, and it's being transformed to this function g of x, and we have to describe the transformations that are happening. How do we describe these transformations? So we've got two vertical transformations. X squared was the function, right? Outside the square, we've got two things happening. We've got 2 multiplying, and outside the square, we've got 3 adding. Which one do we do first? We apply BODMAS. BODMAS says, because this is vertical transformation, right? We apply BODMAS here. So BODMAS says you do +3 first. So you do translation, vertical translation. In this case, I've written horizontal first. It doesn't matter. Between horizontal and vertical, it doesn't matter. Let's start with horizontal first. This can come at any place. It would not matter because there's only one horizontal transformation, and that's this -2. That's a translation 2, 0. Okay, so that's one translation that's happening. But then vertical transformations are 2 here. This is one vertical transformation. This is another. So in this case, between those two, the order does matter. So you do translation first in this case because that's what BODMAS says, 0, 3, and then you do vertical stretch, scale factor 2. Now this is one way of describing this. You could also say, this is an actual exam question, this particular function. Another way to think about this could be that you simplify this expression first of all. And you say, let's simplify g of x in a way that this 2 gets multiplied with this and this, so that the bracket opens and you write it like this. And now if you do it like this, you can say it's a horizontal translation 2, 0. That's the same as before. But vertically, now since there's no extra bracket there, you do multiplication here first, and then you do addition. So that means now you can say it's a vertical stretch scale factor 2, and then it's a vertical translation that's 0, 6. And that's also acceptable. These two are equivalent to each other. Even though these vertical translations that you have now, they are different, but since the order is changing, that takes care of that. So these two are equivalent. You can either do it the way on the right side or on the left side. Both of them are equivalent to each other. Now, when you have quadratic functions, so this is how you apply transformation, right? This is how the order of transformation works. This is the easier part, that you are given some transformation and you have to describe that. Okay, that's relatively easier to do. The difficult thing normally is that you have to identify the transformations yourself. In this case, though, we're doing that as well. So let me show you that example. Okay, so this is what I'm talking about. So sometimes what they do is they give you something like this. They give you equations like this. Y equals x squared plus 2x minus 5. And they say it's transformed to this. Figure out the transformation. So this is normally the tricky part. How do you understand how to go from this to this? So normally when they give you quadratic functions, you should always complete the square for those functions first. That will make it easier for you to spot those transformations. Okay, so whenever you have a quadratic function and you need to describe the transformations, as in identify what transformations are happening to go from one function to another function, first complete the square, and that will help you identify what transformations are happening there. Okay, so that's another important thing. Now let's have a look at some examples, because that's where people get confused. The concepts are not that difficult, but its questions are a bit tricky sometimes. Let's have a look at this. This is a very straightforward example. First up, we've got this function f of x, and this is transformed to this. What kind of transformation is that? That's a reflection in the line y-axis. Now you have to be careful. Is it a horizontal reflection or vertical reflection? It's a horizontal reflection because the movement of the graph is horizontal. We want to write down the function f, the equation of this graph in terms of the function f. F was the original function. What's the equation of this transformed graph? This is horizontal reflection. That means inside the function, we will multiply with minus. So that's f of minus x like this. What about this now? You've got this original graph, and that's being transformed to this. Now, stretch is the easiest to spot, because not the easiest, but it's like very easy to spot because you would always have the size of the figure changing, right? In this case, you can see vertically, the height of the figure is changing. It was 2 earlier, now it's becoming 4, right? Horizontally, however, there's no size change in size. There's only one. It was 2 earlier. After that as well, it's 2. So it's a vertical stretch. It's a vertical stretch by what scale factor? Height was 2 earlier, then it becomes 4. So it's multiplying by 2. So what's the function that we have here? We say this is 2 times f of x. Now there's no translation here. When you do stretch, the points automatically move up because of that, because this was 1 unit. After stretch, it becomes 2 units, so it moves up. This point was 2 units up. After stretch, it becomes 4 units up. So there's no extra translation that's happening. It's the stretch that is moving this graph vertically upwards as well, because the y coordinates are getting multiplied by 2. So this is 2 times f of x. That's a vertical stretch by scale factor 2. Think about this. You've got this original function. It's being transformed to this. Now that's clearly a translation. The graph is shifting from one point to another. How many units to the left? 1, 2, 3. 3 units, and then 4 units left. So that's minus 4. And then 1, 2, 3, 3 units down. So the translation vector for this is going to be minus 4 and minus 3. 4 left and 4 down. However, we are not looking for translation vector. We want the equation of this function in terms of f of something. How do we write that now? Translation is when you have plus minus something. Now, minus 3 is a vertical translation. So we have minus 3 outside the function. Horizontally, the graph is going 4 units left. Left means inside the function, you would have plus. So inside the function, it will be f of x plus 4, right? In horizontal, things work a bit counterintuitive. Plus means left, minus means right. Okay. So when you're going left, inside the function notation, you'll say it's plus 4. And that's what the function becomes in this case. Let's look at this. Now, you have to describe the transformation that takes you from this graph to this graph. Now, whenever you have to identify transformations, always think of stretch first. Always think of identifying the stretch first, because that's going to be very clear to spot in that case. As in, you can't be wrong with that, because you know exactly what stretch is happening just by looking at the figure. Look at the width. That's not changing. So there's no horizontal stretch that's happening. But vertically, The height was 1 earlier, afterwards it becomes 3. So you know for sure it's a stretch by scale factor 3. So when you have to identify transformations from a diagram, always identify the stretch first and clearly show that on the diagram. And then think of the next transformation. So in this case, we have figured out that, okay, this has to be a vertical stretch scale factor 3. Stretch along y-axis, scale factor 3. That is definitely there. Okay. Now, you don't think of the next transformation until you have sketched the result that you would get from this first transformation. So when you stretch this figure by a factor of 3 in the vertical direction, this point goes here. Sorry, this point goes here. 1 goes to 3. The point at 2 goes to 6. So that's here. And this point at 2 goes here. And after that stretch, the figure comes here. Now, when it comes here, now you think of what further you have to do to this to take it to this graph now. Now, that's a translation, just 4 units to the right, and that's what you write down. It's a stretch along y-axis scale factor 3 and a translation of 4, 0. If you do not draw this intermediate step, this step, you would wrongly think that there is a vertical translation happening as well. That's not happening. The vertical movement is because of the stretch itself. So when you show what happens after that stretch, it becomes easier to spot what the next transformation is going to be after that. That's just a horizontal translation. There's no vertical translation after that. Okay, and then you have to write down that function in terms of f of x. So that's what it becomes. 3, that's a vertical stretch, and then minus 4 inside because it's 4 units right. That means inside the function you do minus 4. Another very similar example, you have to spot this transformation. This is the original graph. Let me share that for you. This is the original graph, the highlighted one. And this is going to become this dotted graph. Now, how do you figure out what transformations are happening? Again, the first thing you should think about is what stretch is happening. Then think about any other transformation. What stretch is happening? Is there any horizontal stretch? Horizontally, it's 4 units afterwards, and it's 4 units before. There's no horizontal stretch. Vertically, however, it's 2 units before, and it becomes 4 units afterwards. So it's a vertical stretch, scale factor 2. That's what you write down first. You say it's a vertical stretch, scale factor 2. First of all, do that stretch. When you apply that stretch, you get a figure like this. So this was the original graph. The green one is the original graph. After applying stretch, you get this yellow graph. After applying the stretch, you get this yellow graph. Now that you've done that, now you think of what further you have to do to this yellow graph to get to that dotted graph. Okay. Now, there could be multiple ways of thinking about this now. You could say, let's go 1 unit to the right. There are 3 transformations, right? So you can say, go 1 unit right, and then do a reflection in y-axis. Or you can say, do a reflection first, so that you get this green graph, and then you go 1 unit left. So after you've applied that stretch, then identifying the next transformation becomes quite straightforward. So this is what you get. This is one way to describe this. There are other possibilities as well. Stretch is definitely going to be this, but apart from stretch, the other transformations, they could be described in other ways as well. This is one way to do this. You say you reflect in y-axis, and then you have a translation minus 1, 0. And then you have to express g of x in terms of f of x, as in the transformed function was g of x. Express that in terms of the function f, the original function. How do you do that? It's a stretch in the y direction, scale factor 2, so you multiply by 2 outside. Reflection in y-axis, that's a horizontal reflection. When you reflect in y-axis, that's a horizontal reflection. So you multiply by minus x inside. That's happening first, right? So you multiply by minus x first inside the function. And then, once you have that, you do this translation. Translation is minus 1, 0. What does that mean? You replace x with x plus 1. Put that inside bracket because you have a negative outside. Inside bracket, you would say x gets replaced with x plus 1, because that's what this translation means. Then you simplify that. That's the result that you get. 2f of minus x minus 1. That's the function g of x in this form. Okay, this is a good example. Have a look at this later on as well. Try to think about this again. Let's move on. Let's have a look at this now. Find a translation that transforms the graph this to this. How do we think about this now? So you've got 5 over x squared minus 3x, and it's transformed to this graph. Now, just by looking at it, you might get the wrong idea first that it's a horizontal translation of 2 units, right? Because it's going from f of x to f of x minus 2. So you say it's a translation of 2 units, right? And there's a plus 10 outside. So that's 210 translation, right? That's what you would think of at first. If you do it in a hurry, you would get 210 from this. But that's not correct. That's not correct because even though this x is going and becoming x minus 2, what about the other x? If you go from f of x to f of x minus 2, every x should be replaced with x minus 2. The other x is staying x. That's not changing. So again, that's why it's important to do it step by step. What's the transformation that you're very sure about? X is becoming x minus 2. Inside the square, we can say that, okay, this is becoming x minus 2. Apply that transformation first. That, okay, f of x is going to f of x minus 2. Apply that transformation, and that gives you this. So you replace x with x minus 2, and you get a function like this. Replace x with x minus 2 here, replace x with x minus 2 here. Now you simplify this. After simplification, you already have a plus 6 outside like this. After doing that horizontal translation, you already have a plus 6 outside. And then you think of how much more do we need to add here to get to that point 10? You have to add plus 4, and that gives you a vertical translation of only 4 and not 10, and the translation vector turns out to be 2, 4. So when you have to identify transformations, do it step by step. Write down the transformation that you're very sure about first. Apply that transformation and see, okay, what happens after that? Okay. Otherwise, you can often get wrong results. Let's have a look at this. It says the curve with this equation is translated by minus 1, 3. Find the equation of the translated curve, giving an answer in the form y equals ax squared plus bx plus c. Now, this is just an application of a transformation. The transformation is already given. It's minus 1, 3. What that means is if you had the function f of x, that would become f of x plus 1 plus 3. Inside the function, you have plus 1 because of this horizontal transformation. Outside the function, you've got plus 3 because of that vertical translation. All you have to do is just replace x with x plus 1 here, and outside the whole thing, have a plus 3, and then simplify that. Completing square in this case is not necessary because you had the transformations given and you just had to apply them. But when you have to identify the transformation, for example, in the second part now, you've got this equation, and it's transformed to this equation. Describe fully this single transformation that has been applied to go from this step to this step. Now, how do you think about this? Okay, let me actually come back to that example in a moment. Let me do this first of all. I'll go back to that because that this single transformation, that there's another complication here. Let's do this one first before that. We've got this f of x function that's x squared minus 2x plus 5. This is another function g of x equals x squared plus 4x plus 13. We have to figure out what transformation transforms the graph of y equals f of x to the graph of y equals g of x. How do you go from this graph to this graph? How do you identify this transformation? You should first complete the squares. Otherwise, it will become difficult to identify the transformations. It will not be clear. This is x squared minus 2x plus 5. When you complete the square, it becomes x minus 1 whole squared plus 4. And then the final result is x squared plus 4x plus 13. When you complete the square, it becomes this x plus 2 whole squared plus 9. And now you can look at this. What is changing in these functions? Outside the function, plus 4 is going to plus 9. What do you have to do to go from 4 to 9? You have to add 5. You have to do plus 5. And that gets you to this final result. To plus 5 outside. And then what else? Inside the function, you have minus 1 right now. That has to become plus 2. How do you go from minus 1 to plus 2? How much do you have to add? You have to add 3. You have to do plus 3. So inside the function, you say it's f of x plus 3. What transformation is that? You have to describe this transformation. Plus 5 means the vertical translation, 0, 5. Plus 3 means it's a horizontal translation, minus 3, 0. When you combine them, it becomes minus 3, 5. That's the transformation that you've got. It's a translation minus 3, 5. It's very difficult to spot directly from this unless you complete the square first. So when you have quadratic function, then you have to identify the transformations, complete the square first, and that will help you understand that better. Sometimes when they say it's a single transformation, in that case, it is sometimes possible to do it directly as well, but you have to think a bit about that. For example, in this case, you've got this function x squared plus 2x minus 5, and another function 4x squared plus 4x minus 5. The function on the left side is being transformed to the function on the right side. Now, what transformation is this? You can think about this in your head as well. Minus 5, minus 5. The constant is not changing. That's remaining the same. That means if anything was applying to the whole function, then this constant would also change. This is not changing. So this is not a vertical transformation, right? Because in vertical transformation, the whole function changes. In this case, minus 5 is remaining the same. That's not changing. So that means it has to be a horizontal transformation. Now, what transformation? X squared is becoming 4x squared. So that looks like something is getting multiplied. And 2x is becoming 4 times x. Something is multiplying. So it's horizontal. We figured that out. And something is multiplying. What transformation is it when we multiply something? That's a stretch. Now, what do you multiply x by? If you think about it, 2x is becoming 4x. You're basically multiplying by 2 here. X squared, if you replace that with 2x whole squared, that becomes 4x squared. So yes, that's what is happening. You have f of x going to f of 2x. So that's a vertical stretch. That's a horizontal stretch. Scale factor 1/2. Okay. Sometimes you can identify it directly, but in very rare cases, when it's a single transformation, you can just think about it in your head as well. But when it's multiple transformations, you cannot do it directly. You have to complete the square for that necessarily. Okay, this is an alternative method for that. If you were to do it using completing square method, in this case it's a bit long, but you can have a look at this. It gives the same result eventually. Okay. Let's move on. Now, you have transformations in trigonometry as well. These are sometimes a bit tricky. Let's have a look at this example. So you've got this original curve. This is the graph of y equals cos theta. Okay, and this is being transformed to the upper curve, this curve here. They are saying, find in terms of a cosine function the equation of the upper curve. What's the equation of this curve? How do you figure that out? Now, what's the baseline of the original graph? It's the x-axis. What's the baseline of this graph? How do you identify that? The maximum point that you have here is 5. The minimum point on this graph is 1. Where is the baseline going to be? The baseline is going to be in the middle. That's at the point 3. So that means the baseline is going up. The baseline is going up by 3 units. What does that mean? It's a translation. It's a vertical translation by 3 units up. So you would say that becomes cos of theta plus 3. That's one thing that's definitely happening. Okay, so baseline is moving. What about the amplitude? Is that changing? Just think about that. The amplitude earlier was 1. Now the baseline becomes this at 3. What about the amplitude now? That's 2. So amplitude is becoming twice. That means the vertical stretch, scale factor 2. So we multiply by 2 outside. It becomes 2 cos of theta plus 3. What else? Is there anything changing horizontally? Is there anything changing horizontally? Is the period changing? Is the graph shifting left, right? The period is clearly changing. It's completing 2 cycles in 4 pi. In fact, let's consider 2 pi, the standard period. In 2 pi, this is 1 cycle, right? This is 1 full graph. The period for the transformed graph has doubled. It has become twice. It was 2 pi earlier for the original graph. The period is 2 pi. For the transformed graph, the period becomes 4 pi. The period is becoming double. When period becomes double, that means it's a stretch scale factor 2. If scale factor is 2, you've got half theta here. This is going to be half theta. Okay. Yes. So sometimes it's easy to figure out these two transformations, the vertical transformations. Horizontal, some people find it a bit difficult. One way to do that is that once you figure out these two transformations, then you could say this is 2 cos of a theta plus 3, and then input some value there, and take some value on the graph. For example, at 0 it's 5, see if that works. If that gives you a value for it, 0 will not give you a value because a will get eliminated. But take another value, for example, at 2 pi it's 1. Input that and find the value of a from that. That's longer. You can do that. If nothing else works, then yes, you can do that. But it's much easier and much quicker to understand transformations well. Since the period is getting double, that means it's a stretch scale factor 2. It's a horizontal stretch scale factor 2. If the scale factor is 2, inside here we have it divided by 2 like this. You can also understand this in terms of the period of the graph. The period is becoming, so the original period is, so this is the equation that we can use for this. The new period of the graph, the period of the transformed graph, it's always equal to the original period divided by that number that's multiplying. So let's say this number is b. You can just input values in this formula. Original period of a cos graph, what's that? In radians, that's 2 pi. The period of this transformed graph, that's 4 pi. Find the value of b from that. That turns out to be 2, and that's what that turns out to be 1 over 2, and that's what we were looking for. Okay. If you cannot think of it in your head directly, you can use this equation, and that will give the value for b as well. All right. Let's take another example on this. If you have a tan function like this, what about this now? For tan, there's no amplitude as such. What about the baseline? What did I tell you about the baseline of the tan function? It says the diagram shows the graph of this function, a tan of x minus b plus c. How do you figure out the values of a, b, and c from this? For a tan function, the baseline is when the direction of the graph is changing. So look at this graph. It's going in this direction, and then it changes its direction like this. So where's the baseline? Baseline is at this point here. That's where the direction is changing. If you look closely, that's the point where the direction is changing. So that's the baseline of this graph. Now, if this is the baseline, that's 1. So you say this number outside, plus minus, the graph is shifted upwards, right, by 1 unit. The original tan graph, it has its baseline at 0. So it looks like this, right? The original tan graph. Its baseline is at this point. That is moved 1 unit up. That's translation, vertical translation, 1 unit up. So you have this plus 1 outside. The value for c, therefore, is equal to 1. Okay, what else? Is there any stretch that is happening? Look at the horizontal direction. What's the period of this graph? What's the period of this graph? Period of the original tan graph is pi radian. What about the period of this graph? This is completing one full cycle from minus pi over 4 to 3 pi over 4. What's that distance? 3 pi over 4 minus pi over 4, that's pi radian. Is the period changing? No, period is not changing. So original period was pi, this is also pi. So period is not changing. Okay, period is not changing. What else is changing? The graph is shifted. Original tan graph, what does that look like? Original tan graph looks like this. It starts from 0 and it goes like this. Right? That's the original tan graph. It looks like this. Now, we have figured out that it's moving 1 unit up. So that would have moved somewhere here. After moving 1 unit up, it'll look like this. But then this point, where is that going? That's going here. What's that? That's a translation. Pi over 4 units to the right. Pi over 4 units to the right, that's a translation. That means this number here, b, that has to be pi over 4. It's the minus sign. Minus means you're going right in horizontal transformations. So that number is therefore pi over 4 because you're moving pi over 4 units to the right like this. Now, what else? What about the number outside? They're saying there is a vertical stretch there as well. What vertical stretch? How do you figure that out? Now, in this case, one idea is that, because this is actually a bit hard to figure out, once you have the values for b and c, you input any point on this graph in this equation. So for example, you have this function now, y equals a into tan of x minus pi over 4 plus 1. That's the function. Take any point in the graph, input that here, the values of x and y at that point. For example, you could write this point here. This is pi over 4 and 1, if that works. Tan of pi over 4. Sorry, this was like this. A into tan of x minus pi over 4 like this. If you input pi over 4 there, that's not gonna work because pi over 4 minus pi over 4, that will become 0. It will eliminate a as well. So you'll have to take another point. Take another point in the graph, for example. You can take this point. This is x equals pi over 2 and y equals 3. Input this point here, find the value of a from that. That's one idea that will work. Another way to think about this is the original tan graph, it basically goes like this. It starts from 0 and then it becomes 1 at pi over 4. So the value that it has at pi over 4 is equal to 1. So the tan graph, the original tan graph, it moves 1 unit up. It moves 1 unit up as it goes pi over 4 units to the right. It goes 1 unit up in an interval of pi over 4 units. Now, what about this transformed graph? This graph is basically starting from this point, right? How much is it moving in the vertical direction in a distance of pi over 4? This is pi over 4 distance. In this pi over 4 distance, the graph is going up by 2 units. So it was originally supposed to go up by 1 unit. In this case, it's going up by 2 units. So that means the value of a here, it's a vertical stretch. It's a vertical stretch of scale factor 2, right? So the value of a there should be 2. If you understand that, that's good. Otherwise, this is an easier way of doing this in this particular example, that you input a point and find the value of a from that. Okay. All right, let's move on. Just a couple more examples and then we end. Okay, let's have a look at this now. This is from a recent paper, fairly complicated examples. You've got this diagram that shows the curve y equals k cos of x minus pi over 6, where k is a positive constant and x is measured in radians. The curve crosses the x-axis at points A and B as a minimum, and A and B is a minimum point. Find the coordinates of the points A and the point B. Now, what's the function? It's a cos function. And they have shown you what transformation is happening in the horizontal direction already. It's x minus pi over 6. What does that mean? X minus pi over 6? That means the graph is going pi over 6 units to the right. Now, what's the original cos graph? The original cos graph looks like this. It starts from 1, goes to 0 at pi over 2, and then goes on like this. That's what the original cos graph looks like. This is the graph of y equals cos of x. Now, if you move it pi over 6 units to the right, what happens? This point, which was at 0 earlier, that moves to the right, and it becomes pi over 6 here. So the graph moves pi over 6 units to the right like this. And then they're asking you to find this point A. How do you do that? How much is this distance? Pi over 2. So that means this distance from that maximum point to this point, this should be pi over 2. And then from this point to the minimum point, this is another pi over 2. This is another pi over 2. So that's pi over 6 plus 3 pi over 2, and that gives you this point. That's 5 pi over 3. So the value of A, therefore, the coordinates of A, they are 5 pi over 3 and 0. What about the minimum point B? You do the same thing here. You know the point A now. Let's go to the right. It's pi over 2 more here, another pi over 2 here, another pi over 2 here, and that's the point B. So 3 pi over 2 more added to that. That gives you 19 pi over 6. The coordinates of B, therefore, what are they going to be? The x coordinate is 19 pi over 6. What about the y coordinate? The graphs, the function that they've given, it has k multiplied outside. So that means k is the amplitude of this graph. If k is the amplitude, this point is k units below the x-axis. It's k units below the x-axis. So what's that point going to be? That's minus k. The y coordinate therefore turns out to be minus k. Okay. Let's have a look at this example. Similar to that, the diagram shows the curve with equation y equals k sine of half x. The curve has a minimum point at A. Now it's a sine function. Think about the original sine function. What does the original sine function look like? It starts from 0. It goes to 1 at pi over 2. It comes back to 0, goes to minus 1 at 3 pi over 2, and so on. Now, what's the function? It's k sine of half x. You know what transformation is happening in the horizontal direction. Half x. What does that mean? The period becomes double, right? It's a horizontal stretch, scale factor 2. What's the period of the original sine graph? For the original sine graph, the period is 2 pi. For this, the period becomes 4 pi. It's a horizontal stretch, scale factor 2. Okay. They want us to find the coordinates of this point A. Now the y coordinate, just like in the previous example, is going to be minus k. Why? Because we've got k multiplying outside. So the amplitude is k. So this point here has to be minus k. What about the x coordinate? How do you figure that out? In the original graph, this minimum point comes at 3 pi over 2, right? The minimum point comes at 3 pi over 2 in this original graph. When it is stretched by a scale factor of 2, that gets multiplied by 2. 3 pi over 2 times 2. What does that give you? That gives you 3 pi, and that's the x coordinate of that minimum point. So it's 3 pi and minus k. That's the point that you get there. And then it says a sequence of transformations that is applied to the curve in the following order. Now, this is the curve that you have. They're applying some transformations in that. Translation of 2 units in the negative y direction, that's 0 minus 2. Reflection in the x-axis. Reflection in the x-axis, that's a vertical reflection, right? The y coordinate gets multiplied by y, multiplied by minus 1. And then it says, find equation of the new curve and determine the coordinates of the point on the new curve corresponding to A. So the corresponding to the point A, the minimum point, you have to find the new point. How do you do this now? The original graph looks like this. K sine of half x, that's the original function. What are they doing? Translation of 2 units in the negative direction. What does that mean? You've got minus 2 outside the function. And then that's the first thing that happens. And then they're saying it's a reflection in the x-axis. That's a vertical reflection. So you have minus multiplied with the whole thing. Vertical reflection, minus gets multiplied outside the function. So you multiply minus outside the whole function like this. Simplify that, and that's the result that you get from that. And then what are the coordinates of the point A going to be? Originally, it was 3 pi and minus k. Apply those same transformations on this as well. Translation of 2 units in the negative y direction. Minus k was the original point. You subtract 2 from that, it becomes minus k minus 2 initially. After that, translation, first of all, k becomes minus k minus 2. All right. And then you have a reflection in the x-axis. It's a vertical reflection. You multiply that y coordinate with minus 1. So you multiply with minus outside. That's the second thing that you do. This is the second thing that you do. So it becomes minus into minus k minus 2. And that simplifies to k plus 2. There's no horizontal transformation. So the x coordinate remains the same. That's 3 pi. And the result that you get is 3 pi and k plus 2. That's the final answer that you've got. These are most of the difficult questions that you find in transformations in recent papers. We have these in the notes. Have a look at them in detail, and that should prepare you well for transformations as well. All right, I hope that was helpful. It again took a lot more time than we were expecting initially, but I hope that was helpful. If there are any questions, you can let me know now. This okay, so remember in horizontal transformation, the rule is you do opposite of BODMAS. Whatever BODMAS says, you say, no, I'm not going to do that. I'm just going to do the opposite of that. This is minus 2 into x plus 4. This is horizontal because everything is happening inside the function, right? So these are horizontal transformations. Now, BODMAS says you evaluate this bracket first. So you do plus 4 first. Plus 4 means translation. But you have to do the opposite of that. So you don't do translation first. You do stretch deflection first. So that's what you do first, and then you do translation after that. So it's just opposite of BODMAS. Right? It's okay. A paper would not have all difficult questions. You'll have like 2-3 difficult questions, 2-3 very straightforward questions, and then 6 average questions. So if you get a difficult transformation question, you'll get some other easier questions. It's okay. It'll get balanced as long as you're prepared well. You can rely on the threshold as well, and of course, duas वो तो है ही. Yes, I'll be doing it for all components, inshallah. That's what the plan is. For M1 and S1, at least, I will be doing it. P3, after the P1 experience, uh, I think that's going to take forever to end. So I'm not too sure about that right now. I do plan to do that, but I still have to see how to schedule that. It'll be like 6 hours, 2 days. Let's see what we can do. For P3, can I share the updated quick notes before the worksheet? Well, I thought you knew me from the class that you studied with me at ISL. I do everything at the last minute. So for this class, I was preparing until 4:30. So I told you we will start at 4:15, but we started at 4:30. Why did we start 15 minutes late? Because I was still making these notes. I cannot do anything before time. That's not how I'm built. So that's not going to be possible. They will only be available when the the actual workshop happens, because I will keep procrastinating, leave it for the very end, and then it'll be made at that time. But I'll try. I say that for everything, but that's what mostly happens at the end. I'll do it at the very end. I will try, however. I'll try if I can do that. I'll share them with you. But the older ones are available, but I'll be adding much more to that from the recent papers. But that will only happen at the end. I can't promise that I'll be able to do that earlier. -4, -4. I can't find that. Was it this? How much more do I zoom out, Amradi? Is that fine? Can you read anything? Okay, whatever it was, just remember this is the rule. This is the rule. Multiple vertical transformations, you follow BODMAS. Multiple horizontal, you do opposite of BODMAS. Okay, that's the rule. So that's the rule that will work. Now, when you have vertical and horizontal both, it does not matter whether you start from vertical or horizontal. You can start from any of them, and that will be fine. But within vertical, within horizontal, you have to follow this order. Yes, Eamon. Okay, everyone, let's begin then. P1 differentiation. This is the next thing that we're doing. So what's differentiation? First of all, in coordinate geometry, we learn how to find gradients of lines. Y2 minus y1 over x2 minus x1. For straight lines, we can find gradients like this. But what about curves? If you have a curve like this, how do you find gradient of a curve? Gradient of a curve changes at every single point, right? So there's no one gradient that exists at every single point. So it changes at every point. For finding gradients of curves, what we do is use differentiation. Now, what's the idea of differentiation? There's some background to it that you also need to know for your exam. I'll show you some questions on this as well. The idea is, if you want to find the gradient at any one particular point, for example, if you want to find the gradient at the point A, this is point 1, 1. This point is right here. Now, what we do is we say, let's take another point on the same curve. So we want to find the gradient at the point A. We take another point as well on the curve. That's point B here. And we say, let's find the gradient of the point of the line AB. That gradient turns out to be 5. Now, that's not a very good estimate for the gradient of the curve at that point, because this direction and the direction of the tangent at the point A is not very similar. So it's not a very good estimate. However, if I take that point closer to A than it currently is, for example, if it becomes C, such that the coordinates of C turn out to be 3 and 9, And then I find the gradient of the line AC, this line. That turns out to be 4. Now that's a better estimate than the earlier line, which was AB. 4 is a better estimate than before for the gradient of the curve at that point A. Now, as we keep bringing this other point closer and closer to that point A, what happens is the estimate for the gradient of the curve at that point keeps on improving. It keeps on improving like this. And then from that pattern, what we can say is, if we were to reduce that difference a lot, for example, eventually we got a point that was like 1.01. The point A was x equals 1. And here we got 1.01. So that's a point that's very close to the point A. At that particular point, the gradient of the line AF, that's turning out to be 2.01. Now, looking at the pattern, you can see what value these numbers are approaching. It started from 5, 4, 3, 2.1, 2.01. If you take some more values, it'll be like 2.001, 2.00001. And that's telling you that the gradient is approaching this value too. So you can say that the gradient of the curve that at that particular point is supposed to be equal to 2. That's the idea of differentiation, that if we want to find the gradient at any one particular point, we take another point and then keep bringing that point closer and closer to improve the estimate of the gradient. Now, in general, we could say something like this. If we have the point x, we take another point that's x plus h. What we want to do is we want to find the gradient of this line AB. That turns out to be something using y2 minus y1 over x2 minus x1. And now if we bring this second point very close to this first point, how would that happen? We would want this value h to be as small as possible. So h is the distance between these 2 points. If this h becomes very small, this other point will get very close to the point x, and the gradient of the curve will be the gradient of this line will become a very good estimate for the gradient of the curve at that point. So we want to bring that second point very close to this first point, and that will give us a good estimate for the gradient of the curve. Now, what do you need to be able to do about this? Let's look at this example. Let's say we've got this equation of a curve that's y equals 2x squared minus 3. We have 2 points. One is 2 and the other is 2 plus h. Okay. First of all, it says find and simplify an expression for the gradient of the chord AB in terms of h. We've got 2 points. One when x is equal to 2, the other when x is equal to 2 plus h. We input those points and that input those values of x in this function, we get the corresponding values of y from that. Eventually, when we do that, we end up getting 2 points. One point turns out to be 2 and 5, and the other point turns out to be 2 plus h and 2h squared plus 8h plus 5. Now, we can find the gradient of that line using y2 minus y1 over x2 minus x1. This is y2 minus y1, this is x2 minus x1, and that simplifies to this value. This is 2h plus 8. And now they say, explain how the gradient of the curve at the point A can be deduced from the answer to part A and state the value of this gradient. Now think about this. We took a point that was 2 and 5. And the other point that was 2 plus h and 2h squared plus 8h plus 5. They were 2 points on the line like this. 2 points on the curve like this. 2 separate points A and B on the curve like this. Now, how would we get the estimate for the gradient of the curve at that point? We would want the second point to be as close to the first point as possible, because that is going to improve the estimate for the gradient. Now, for the second point to be as close to the first point as possible, we would want the value for h to be approaching 0. So now in this gradient value, if the value of h becomes 0, what's the value of the gradient that you get from that? The value of gradient that you get is 8, and you say that the gradient of the curve at that point would therefore be equal to 8. Let's take another example of this. So they have this function that they've given, f of x equals this, and they say that these points lie on the curve. So you've got point A, B, C, D, E, F, points like this. And you see what they're saying. That first of all, find the value for k. Now, what's k? K is this point here. You can do that. That's you've got the x coordinate of this point given, and you have to find the corresponding y coordinate. Just input that value of x in this function. You'll get that point. So once you have that point, now they're saying this table is showing the gradients of the chords AB, AC, AD, AF. Now, what's a chord? This line that you're drawing here in the context of curves as well. we can call this a chord. Okay, so this is the chord that they're talking about. And what they're doing is they're finding the gradients of all of these chords like this. We have the point A here. They're finding the gradient of AB, A with B, A with C, A with D, and so on. They're finding all of these gradients. Now, you see what's happening? The points are getting closer and closer to the original point A. So this point F, it has an x coordinate of 3. E has an x coordinate of 2.1. This is 2.01. This is 2.001. This is 2.0001. So that point is getting closer and closer to the point A. So when we find these gradients from here, you can see the pattern that it emerges from those gradients. So in part B, they're just saying find the gradient of the line AE. You can do that using the formula. But then they say deduce the value for f dash of 2 using the values in the table. Now, what's f dash of 2? That's the gradient of the curve at the point 2, because f dash represents the derivative. So we are looking for the derivative of the curve when x is equal to 2. Now, that means the gradient of the curve when x is equal to 2, that's what we want to figure out. Now look at the pattern that emerges from these points. 7.22, the next gradient was 6.35, 6.26, 6.2551, 6.2511, 6.2501. And you can see these values seem to be approaching 6.25. So that's what you say, that the gradient of that curve at that particular point, it should be equal to 6.25, because that's the value that it's approaching. Okay, so that's one thing that you need to know about differentiation. You'll find very few questions in this. You need to make sure that you practice these ones. Have a look at these again and make sure that you understand them well. For a detailed video on this, you can see the playlist for differentiation. You'll find the first lecture on differentiation that explains this concept in detail. Now, the main part of differentiation is then this. You need to be able to differentiate functions using the power rule of differentiation. Now, how does that work? Let's say we've got a function that looks like this, f of x. First of all, we need to know some notation. F of x is one function. What's the derivative of that? That's f dash of x. This is the notation that we have for differentiation. Second derivative, that's f double dash of x. That's one notation that you need to know about. And if you have a function y, the derivative of that is given by dy over dx. And if you have dy over dx and we differentiate that again, we get d square by over dx square from that. So this is some notation that you need to know about. If the original function is f of x, the derivative of that is denoted by f dash of x, and the second derivative is denoted by f double dash of x, or f prime of x, f double prime of x. If the original function is represented as y, we represent the derivative as dy over dx and the second derivative as d square by over dx square. Now, what does this derivative represent? It's the function of gradient for this original function. It's the gradient function of the original function. It represents the gradient of the graph. Now, dy over dx, this basically represents that you're taking the derivative with respect to x. So d represents derivative, dx represents with respect to x, and you're finding the derivative of y with respect to x, right? That's what dy over dx represents. Now, how do you do differentiation? We've got some rules for this that are derived from this background. Now, how exactly? That's out of scope for your syllabus. Now, we have these rules that are derived. Number one, we've got this power rule, this simple power rule, and that works like this. If you've got x raised to power n, the derivative of that is given by nx raised to power n minus 1. So what that means is, whatever is the function, if it's a power function, what you do is you multiply by the power and you subtract 1 from the power. So whatever is the function, you multiply by the power, subtract 1 from the power if it's x raised to power something. For example, if it's x raised to power minus 5, that becomes minus 5 raised to power minus 5 minus 1, and you get your result. Now, if there's a constant multiplying outside, for example, 7 over 4, if a constant is multiplying or dividing, that remains the same. That does not change. Okay, so 7 over 4 in this case, that remains as it is. And then what you do is you multiply by the derivative. So you multiply by the power and subtract 1 from the power. And then you just simplify that and you get the result. Have a look at this example. If you have something in the denominator like this, if you have x in the denominator, to be able to differentiate this, you first need to bring x to the numerator And then you can apply the rule on that, because that rule works when you have x raised to power n in the numerator. This is in the denominator. To be able to differentiate this, you first need to bring this to the numerator. How would that happen? This is x power 1 over 2. When it comes to the numerator, it becomes x power minus 1 over 2. 3 does not come up with that. 3 remains there because there's no power in 3. We're not bringing 3 up. That remains there. So now we've got this function and this constant outside, minus 2 over 3. We apply the rule in that. What's the rule? We multiply by minus 1 over 2, subtract 1 from the power, and then simplify that to get the derivative, right? And similarly, for these other examples, you can have a look at this. The rule is you multiply by the power, subtract 1 from the power, and you get the derivative from that. Now, if you have something like this, 2 over 3 times x, what's the derivative of that? If you apply the rule on this, it becomes 2 over 3 as it is, but then the power is 1. When you subtract 1 from the power, it becomes x power 0. X power 0 is 1, so x gets eliminated. If you have minus 4 times x, if you apply the rule on this, it becomes x raised to power 1 minus 1, that's x power 0 again. The x gets eliminated. We can generalize this, that whenever we have some constant with x like this, the derivative is just going to be the constant value that you have. You can also compare this with y equals mx plus c, remember? So m represents the gradient. Differentiation also gives you the gradient. So since the gradient is 2 over 3 for this line, the derivative is also 2 over 3. So when you have a function of this form, where you just have a constant multiplying by x, the derivative is just this number that you have outside. And what about constants? If you have a constant like this, y equals 3, what's the derivative of that? You can think of it like this, it's 3 into x raised to power 0. When you apply that rule in this now, it gets multiplied by 0 when you multiply by the power, and everything becomes 0 for that. So whenever you have a constant, the derivative of constant is always equal to 0. So these are two special cases that will help you do things quicker if you just remember them. If you have k times x, some constant times x, the derivative is just going to be the constant that's multiplying, and that's it. And if you just have a constant y equals k, the derivative of that is going to be equal to 0. Derivative of a constant is always equal to 0 because you can also think of it graphically. It's a horizontal line that has a derivative of 0, gradient of 0. So that's why it turns out to be 0. This is a straight line. Straight line has this gradient. So that's the derivative. So these two gradients you can write directly. For anything else, you will apply the power rule and get the derivative from that. Now, when you have multiple terms adding or subtracting like this, when you have plus minus between terms like this, all you have to do is just differentiate each term separately. So in this case, you can just differentiate one term at a time, differentiate this separately, this separately, this separately, and then just put the same signs with them that are there already, plus or minus, and you will get the result. Okay, you can have a look at this working. But then, what if we have something more complicated? So sometimes you can have something like this. 2x squared plus 5 raised to power 1 over 3. Now, what about this? This is not x raised to power something. The previous rule was when you have x raised to power something, the derivative of that was nx raised to power n minus 1. What if you have something other than x inside, some other expression in terms of x? This is a more general form for the power rule. If you have anything raised to power n, so this box represents that you can have any expression in terms of x in place of this. Okay, any expression in terms of x. It could be anything. Now, what's the derivative of this going to be? You multiply by the power, you subtract one from the power, and you multiply by the derivative of the base of the power, the derivative of that box, whatever is that it isn't that box, you multiply by the derivative of that. Okay, so these are 3 steps that you follow for this. Multiply by the power, subtract one from the power, and multiply by the derivative of the base, whatever is inside the brackets inside the power. Now, if you think about it, for x raised to power n as well, we were, even if you apply this rule, that will still work there, because this is x raised to power n, right? X raised to power n, you can consider this as the base. It becomes n into x raised to power n minus 1, and then you multiply with the derivative of x, that's the base, and the derivative of x is 1. So when you multiply by 1, it doesn't change anything. So because of this, we were not explicitly multiplying by 1 in the previous examples, because the derivative of x is 1. It doesn't make any difference if you multiply by that or not. However, if x is replaced with anything else, for example, if x is replaced with something like this, x squared plus 5 whole raised to power minus 4. Now, the base that you've got here, the derivative of this is not equal to 1. So we have to separately multiply by that derivative like this. So how would you differentiate x squared plus 5 whole raised to the minus 4? You would say multiply by the power, subtract 1 from the power, and multiply by the derivative of what you have in the base of the power. And then simplify that, you get a result from that. Take another example. If you have minus 5 over 7, that's a constant that's multiplying, that will remain as it is. You multiply by the power, that's minus 4 over 3, subtract 1 from the power, and you multiply by the derivative of the base of the power. Now, when you subtract 1 from the power, notice this part initially will remain as it is. Okay, so inside the power, it's going to remain as it is. You are not going to differentiate this inside the power. That will remain as it is. X cubed minus 4x, that is the same thing here. But then the power only reduces. Then outside, you multiply by the derivative of that base, and that gives you the result. This is another example. If you have x in the denominator like this, first of all, you have to bring it to the numerator and write it as power minus 1 over 2. Simplify that and differentiate that, and then simplify everything. You get the result from that. Now, that's the only rule that you've got in differentiation. The power rule of differentiation, you need to be able to differentiate functions using this rule. Now, next, we've got some applications of differentiation. What is differentiation used for? As we said, differentiation is going to be used to find gradients of curves at different points. For example, this is a very simple case. You have this function. You want to find the gradient of this curve at this point when x is equal to 3. How do you do that? You first of all differentiate this function using the power rule. This is in the denominator right now. You bring that to the numerator. It becomes power minus 1, right? Like this. You apply the rule, multiply by the power, subtract 1 for the power, multiply by the derivative outside. And then this is the function of gradient. This is the gradient function for this curve. Okay. Now, how do you find the gradient at this particular point? You input the value of x in this, x equals 3, and that will give you the derivative, which is the gradient of the curve when x is equal to 3. So if you want to find gradient of a curve at any particular point, all you have to do is find the derivative, put that value of x in the derivative, and that will give you the result. All right, let's take another example. Let's say you've got a curve like this. This has equation y equals x cubed plus 2. And what we want to do is we want to find the equation of the tangent at a particular point and the equation of a normal at a particular point. So this is another application of differentiation. Now, you'll need to find equations of tangents and equations of normals. Let's have a look at this example. So we've got this curve x cubed plus 2. And this curve has a point. This is point A here. And we want to find the gradient of the tangent at this particular point. The tangent looks like this. It's the line that's in the same direction as the curve at that point, and it just touches the curve. And the equation of the normal at that point. What's the normal? Normal is a line that's perpendicular to both the curve and the tangent at that point. Now, how do you find these equations? Now, these are both straight lines. In order to find equations of straight lines, we need two things. Number one, we need a point on that line. Number two, we need the gradient of that line. Do we have a point already? Yes, we know that the point A has coordinates 1, 3. They could also just give the x coordinate, and you may have to find the y coordinate yourself, first of all, because if x is equal to 1, you can easily figure out what the value of y is going to be by just inputting that value here. But now, assuming that we have the point, now we need the gradient of the tangent and the gradient of the normal. Now, how does that work? You will have the equation of the curve given. What you would do would be you would differentiate that first. You'll find the derivative of that, and in that derivative, you'll put this value of x at which you want to find the equation of the tangent and the equation of the normal. And when you do that, you will get the gradient of the curve at that particular point, right? Derivative is going to give you the gradient of the curve at that particular point. And now, tangent has the same gradient as the gradient of the curve because its direction is the same as the direction of the curve at that point. And what about the normal? Normal is going to be perpendicular to the curve, so its gradient is going to be negative reciprocal of the gradient of the curve. So all you have to do now is, once you've got those derivatives and you found the gradient of the curve at that particular point, you say, what's the equation of the tangent going to be? Gradient of the tangent is 3 because that's the gradient of the curve at that point. So it will be the same as that. And we have a point that's A. We use y2 minus y1 equals m into x minus x1 and find the gradient of that, find the equation of that tangent like this. For the normal, we take negative reciprocal of that gradient because normal is perpendicular to the curve. So whatever was the gradient of the curve, the gradient of the normal is going to be negative reciprocal of that. So that's negative 1 over 3. We change the sign, take reciprocal. So now we've got the gradient of the normal. Gradient of that point is the coordinates of that point are also given. That's this. You can find the equation using y2 minus y1, sorry, y minus y1 equals m into x minus 6, and that will give you the result. Now, this is what you need to remember here. Gradient of the tangent at a particular point is the same as the gradient of the curve. Gradient of the normal at a particular point, that's negative reciprocal of the gradient of the curve at that particular point. The next thing that you need to know about is how to find stationary points and their nature. Now, what are stationary points? Let's have a look at this example. It's a quadratic curve. It's a U-shaped curve. Stationary point is just another name for the turning point. Turning point, vertex, stationary point. This point has all of these names. How do you find this? So for quadratic functions, we have done multiple ways of finding the turning point before. For example, we know how to do that using minus b over 2a. We can do that using completing square, but this is another method that we can use to find the turning point, and that's using differentiation. Now, this is a general method that works for any kind of function. Minus b over 2a, completing square, they were specific for quadratic functions. For any other kind of function, differentiation is the general method that works for finding turning points. Now, how do you do that? At a turning point, you can see if you were to draw a tangent, that will always be a horizontal line. Horizontal lines have a gradient of 0. So when you have to find a stationary point, we know that the gradient of the curve at that particular point is going to be 0. Now, if the gradient is 0, derivative represents gradient. That means at any stationary point, the derivative is always going to be equal to 0. So whenever you have to find stationary points, what we do is we find the derivative, put that equal to 0, and that will give you that point that you're looking for. For example, in this case, this is the curve. What you do is you find the derivative. That turns out to be this. You put the derivative equal to 0 for finding the stationary point, and that gives you a value for x. X equals 2. Put that value of x back in the function. That will give you the corresponding value for y as well. And this is the point that we were looking for. Now, you do not always just, whenever you find derivative, always put that equal to 0. That will not work. You cannot always just put the derivative equal to 0 for no reason. When you're finding stationary points, you put that equal to 0 only in that case, not in general. Okay. Let's take another example. So this can also work for cubic functions now, but for which completing square minus b over 2a could not work. So if you have a cubic function like this, x cubed minus 12x squared, and so on, and we want to find the stationary points of this function, how do you do that? You would find the derivative, put that equal to 0, you get two values of x from that. X equals 1, x equals 7. You can find the corresponding values of y now by inputting those values back in the function, and that will give the corresponding value for y as well. That turns out to be, the points turn out to be 125 and 7 minus 83. These are the 2 points that we were looking for. Now, these are the stationary points. The next thing we want to figure out is whether these points are minimum points, maximum points. One is minimum, the other is maximum. How do you figure that out? Now, this is what the curve is going to look like in this case. This is what a cubic function looks like. This is one possible shape of a cubic function. In this case, this is one point that we're getting. This is 125, and the other point is 7 minus 83. Now, the first one that you see on the left side, we call this a maximum point. So whenever you have a shape like this point is going to be a maximum point. So this point we consider a maximum point. And whenever you have a shape like this, we consider this point as a minimum point. This is the minimum point here, and this was a maximum point here. Now, I showed you how the graph looks like. Now, if the graph is not given, and you had to find and you had to figure out whether these points are maximum or minimum yourself without the graph, how would you do that? This is where the second derivative comes in. So what you do is you have the derivative. If you differentiate it once more, that's called the second derivative of this function. So 3x squared minus 24x plus 21, that was the derivative. You differentiate it again, and that turns out to be 6x minus 24. And now, if the second derivative is negative, that is going to mean that it's a maximum point. If the second derivative is positive, that means it's going to be a minimum point. Now, how do you do that? This is 6x minus 24. It depends on the value of x, whether this number is positive or negative. So if the derivative is in terms of x, you have to input those points. So we found two stationary points there. One had an x value of 1. The other had an x value of 7. So what we do is we input x equals 1 in this one, and that gives us minus 18. And then we input x equals 7 in this, and that gives us plus 18. Now, when the second derivative is negative, that means that it's a maximum point. When the second derivative is positive, that means it's a minimum point. This is what you need to remember about the second derivative. If it's positive, it's a minimum point. If it's negative, it's a maximum point. Now, for stationary points, this is the summary. If you have a function and you want to find, the stationary points, what you do for that is you find the derivative, put that equal to 0, and that gives you the x coordinates of the stationary points. Put those x coordinates back in the function, and that will give you the corresponding y coordinates. For figuring out whether that stationary point is maximum or minimum, what you do is you find the second derivative, put the values of x in that. If the second derivative is positive, that's a minimum point. If it's negative, that's a maximum point. So that's what you need to know about stationary points and whether they're maximum or minimum. There's a terminology that you also need to be aware of. Sometimes they will not say whether they'll not ask for whether it's a maximum point or a minimum point. They will use this terminology, find the nature of the stationary point. So nature of the stationary point means if it's a maximum or a minimum, right? That's what nature represents. Okay. So sometimes they will ask you to find the maximum or minimum value of the gradient of the function, not of the original function, but the gradient of the function. Now, how would you do that? Let's say we've got a function that looks like this, for which they have given you the derivative. So they give you that the derivative of function dy over dx, that is equal to x plus 4 over x squared. Now, we want to figure out the minimum value of the gradient of the curve, and we have to clearly show whether it's a minimum value or a maximum value. Now, how do you do that? This is dy over dx. Now, normally, to find the maximum point or the minimum point, what we do is we put the derivative equal to 0, right? But that's something that we do for finding maximum or minimum point of a function. We're not finding maximum minimum point of the original function, as in we're not finding the minimum point or maximum point of y. We are finding the minimum point of the gradient. Now, what's gradient? We can say dy over dx is the gradient function of the curve. So we treat this as a new function. We say this is the gradient function. This is the gradient of the curve, right? So dy over dx, which is x plus 4 over x squared, we say this is the gradient. This represents the gradient of the curve. And now what we're looking for is the maximum or minimum value of the gradient, not the original function y. So this is the gradient function. What we do is we find the maximum or minimum value of this. The normal way for any function, when you're finding the maximum minimum value, what you do is you find the derivative, put that equal to 0. So this is the function now. You find the derivative of this function and put that equal to 0, and that gives you the value for x, that is 2, and that tells you at this particular value of x, the gradient would be minimum. Okay, so you put that value of x back in this function, and that gives you the corresponding value for gradient. When x is equal to 2, the value for gradient is 3, and that's the minimum gradient. Now, how do we show if it's a minimum gradient or maximum gradient? We find the second derivative. We find the second derivative of this gradient function. The second derivative turns out to be this. We put that value of x in this, that turns out to be positive. That means that gradient was a minimum value. Okay, so when they ask you for the maximum or minimum value of the gradient of a function, what you do is you treat dy over dx as a new function. I would recommend write it as g of x. So that's the gradient function, and then find the derivative of this function, put that equal to 0 to find that stationary point, and then you can differentiate it again once more to find whether this point is the maximum or a minimum. Okay, so that's an important concept that you need to know about. The next thing that we have is increasing and decreasing functions. Increasing and decreasing functions. That's another concept that we've got in differentiation. What are increasing functions? Increasing functions are those functions that have a positive gradient. Whenever the gradient is positive, that's an increasing function. Decreasing function is when the gradient of a function is negative. For example, the curve on the left side here, you can see as we go from left to right, the curve is going in the upwards direction. So the gradient is positive. If gradient is positive, derivative is positive, this is an increasing function. On the right side, the gradient is negative. As you go from left to right, you're going in the downward direction. Gradient is negative throughout. If the gradient is negative, that means dy over dx, that is supposed to be negative. These are examples of some increasing and decreasing functions. On the left side, you've got increasing. On the right side, you've got decreasing. Now, these functions are throughout increasing, and these functions are throughout decreasing. But some functions can be increasing in some part and decreasing in another part. For example, in this case, on the left side, the function is decreasing. On the right side, the function is increasing. In this cubic function, it's increasing here, it's decreasing then, and then it's increasing. So some functions are throughout increasing or decreasing. Some functions are increasing in one part and decreasing on another part. For example, let's say we got a function that looks like this. Y equals 1 over 6 into 2x minus 3 whole cube minus 4x. And let's focus on the last part of this. Find the set of values of x for which this expression is an increasing function. It's an increasing function. Now, what do we do? What do we do for that? In the first part, they made us find the derivative. So we have the derivative for this. The derivative of this turns out to be 2x minus 3 whole square minus 4. Now, if it is an increasing function, what that means is the derivative dy over dx, that is supposed to be greater than 0. So what we do is, if it's an increasing function, we say, let's find the derivative dy over dx. That turns out to be this. Put that derivative greater than 0. So 2x minus 3 whole square minus 4, that should be greater than 0. You get a quadratic inequality from that. Solve that quadratic inequality, simplify everything, and you get the result. These are the values of x for which this function is increasing. Okay, so you find the derivative, put that greater than 0, and you find those values at which the function is increasing. This is what the function looks like. The original function was cubic. This is what it would actually end up looking like. It was increasing in this part, decreasing here, and then increasing again. You find that using calculation, even without knowing the graph, you find the derivative, put that greater than 0, solve that inequality, and that gives you the set of values for which the function was increasing. Now, sometimes they will ask you to show that a function is increasing or decreasing. So sometimes they will tell you if it's increasing or decreasing. Sometimes they will ask you to show that it's increasing or decreasing. How do you do that now? This is the function, and they're saying show that this function is an increasing function. Now, notice this word show. You cannot assume already that it's greater than 0. You would find the derivative the normal way. This is what the derivative turns out to be: 6 into 2x minus 5 whole squared plus 1. Now, you're not going to say this is greater than 0 and solve and find the values of x from that. You will not get any values from that anyway, but you would not do that. You would not put this greater than 0. You would argue that, okay, now this is the greater that we have. How can we show that it is always positive? We have to show that this is positive. How do you do that? When you have this form, you can say 6 is positive. This is a square that can never be negative. So the first term, therefore, this whole thing is positive, or at least 0. And we have a plus 1 here. So 0 plus 1. The minimum value of this expression, therefore, is greater than or equal to 1. That means the derivative is always greater than 0. Since it's greater than 0, that means it's an increasing function. And that's the proof that this is supposed to be an increasing function. Similarly here, you've got this function, and they're saying show that it's a decreasing function. How do you do that? You find the derivative. The derivative turns out to be this. And now you have to show that it's a decreasing function. How do you show that? The derivative has to be negative. The derivative has to be negative. One will do that here. It would be you take minus common outside. Now this expression inside is always positive inside because we've got x power 4 here, we've got x squared here. Even powers can never be negative. All the numbers are positive inside, and we have a negative outside. That shows that this overall number is always negative. So you say the derivative is negative. That is why it's a decreasing function throughout. So notice the difference. Sometimes they ask you to find the set of values of a function. In this case, for instance, they ask you to find the set of values of a function for which that function is increasing. In that case, you find the derivative, put that greater than 0 and make it an inequality, solve that inequality to find those values of x. Sometimes they ask you to show that it's an increasing function or show that it's a decreasing function. In that case, you will not make an inequality. You will find the derivative and show that it's always positive or always negative, and that will give you the result like this. Now, in the question that you will see, sometimes you will have mensuration as well. And using mensuration, you have to prove something in the first part and then use that to find the stationary points sometimes, find the nature of those stationary points. For example, this is one case. In the first part, they ask you to show this thing. Now, as usual, you will have some information given in the question that you can use to make some sort of an equation and come to this result. For example, in this case, they're saying in the question that the surface area of this cardboard is 200. So what you do is you find the areas of all the surfaces of this cardboard, just like we used to do in O levels. Find the areas of all the surfaces, all the faces of this container, and then you put that equal to 0. Rearrange that, you'll get this result at the end. And then similarly, they ask you to find the volume. It's a prism. That's area of cross section times the length, or area of base into height, whatever formula you want to use. And then based on this, they will ask you to find something like this. Find the value of x for which v has a stationary value. What does that mean? Stationary value? Stationary value means it's either maximum or minimum. How do you find stationary values? You find stationary values by putting derivative equal to 0. So for this, you would say dv over dx in this function, that should be equal to 0. You'll find the value of x from that, and that's the result that you were looking for. Then they say determine whether it's a maximum value or a minimum value. How do you do that? You find the second derivative of that. Find the second derivative of that and put that and figure out whether that's positive or negative. If it's positive, that's a minimum point. If it's negative, that's a maximum point. Then you've got rate of change and chain rule. Now you need to understand this terminology. If you have dy over dx, what that means is it's the rate of change of y with respect to x, right? The rate at which y is changing with respect to x. Now, mostly what happens is we talk about rate of change in terms of time. So you would have time in the denominator like this, dy over dt, for instance. That implies it means rate of change of y, the rate at which y is changing with respect to time. Dx over dt, this means rate of change of x, the rate at which x is changing. So whenever they say something like this, rate of change of anything, rate of change of y, that's dy over dt, rate of change of x, that's dx over dt, even if they don't mention that it's with respect to time, it's understood that if they don't mention with respect to what variable, it is going to be with respect to time. So rate of change of y, that's dy over dt, rate of change of volume, that's dv over dt, rate of change of area, that's dA over dt, and so on. Now, how do you use that? Let's say you've got a container that looks like this. Now, this is the container, and it is in the shape of a cuboid. And we are given that the water is being poured into the container at a rate of 2 meter cube per second. We've got the rate at which the water is being poured into the container. Now, how do you measure water? Water is measured in terms of volume. So what do you understand from this statement? That water is being poured into the container at a rate of 2 meter cube per second. That means the rate of change of volume, dv over dt, that is equal to 2. dv over dt, that is going to be equal to 2. That's what you understand from that statement. You can also understand that from the units here. It's 2 meter cube. Meter cube is the unit for volume, so that's dv over dt. And then they're saying, find the rate at which the height is increasing. The rate at which the height is changing. So we are given dv over dt, and we are supposed to find the rate at which height is changing, dh over dt. So we're looking to find dh over dt. Now, for finding dh over dt, we make something that we call the chain rule like this. We say, okay, dh over dt, that's what we're looking for. We make two fractions like this, and we multiply them such that the numerator of the first fraction is supposed to be the same as the numerator here, and the denominator of the second fraction, that's supposed to be the same as the denominator here. So these two have to match. And then in the third place here, and the fourth place here, we've got that whatever the third variable is. In this case, the third variable was volume. So we say we've got dv there. And now, how exactly do we find the value of dh over dt here? We were given the value for dv over dt, that was 2. We input that value of 2 here. And dh over dv, that's not something that we know. Now, for that, we need some equation that connects these two quantities, volume and height. Now, what's the shape of this shape? That's a cuboid. What's the volume of a cuboid given by? It's given by length into width into height. We were given that the length is 8 meter and the width is 4 meter. So what's the volume going to be? 8 into 4 into h, base area times the height. That's the volume of this shape. So from that, we get an equation like this. From this, you can find the derivative dv over dh, that turns out to be 32. Take reciprocal of that, and that will give you 1 over 32. You can input that value there, and that gives you the result. Now, sometimes it ends up being a bit more complicated. We have a look at some examples for that. But quickly, how does chain rule work? How do you make equations like those? In case you get confused by that, whatever you have to find out. For example, sometimes you have to find dv over dt, sometimes you have to find out dh over dt, sometimes you have to find out dA over dt. What you'll do is, you'll write it on the left side, whatever you have to find out. On the right side, you'll have two fractions like this. You would say, these two fractions are multiplying. The numerator of the first fraction is going to be the same as this, so that's dv. The denominator of the second fraction is going to be the same as this denominator, that's dt. And then in these places, the remaining places, you've got whatever the third variable is. So if it's v, a, and t, what's the third variable? That's a. So you would say that's dA. So it becomes dA and dA here. If you had to find dA over dt, you'll make a fraction like this. You'll say it's a product of two fractions. The first numerator is going to be dA. The second denominator is going to be dt. And then in these places, you've got whatever the third variable is, that's dv. And that becomes the chain rule. This is equal to this. Now, this is a very simple example of this. Volume of a spherical balloon that's increasing at a rate of 50 centimeter cube per second. Volume is increasing. That's the rate of change of volume. So we say dV over dt is equal to 50. Now, sometimes they might say it's decreasing. In that case, if they had said the volume is decreasing at this rate, we would say this is minus 50. In this case, they're saying increasing. So we just write 50 here like this. And what we have to find out is find the rate of increase of the radius. Rate of increase of the radius. What's that? That's dr over dt, rate of change of radius. How do you find that? You make a chain rule like this. You say dr over dt, that's supposed to be equal to dr, the numerator of the first fraction, dt, the denominator of the second fraction. And then in these places, you've got whatever is the third variable. That's what the chain rule looks like. And now, in place of dv over dt, you put whatever you have there, that's 50. However, this is something that you do not know, dr over dv. So you have to find that out. How do you do that? You need some relation between those two variables that you've got, volume and radius. Volume of a sphere is given by this. You have this here. You find the derivative of that. Put that value of r. So they wanted the rate of increase of radius when the value for r was equal to 10. So what you do is you input that value of r, 10, inside this derivative, that gives you some value, which is 400 pi here. That's dv over dr. Now, you have dv over dr. For this, you want dr over dv. So what you do for that is you take reciprocal of this, reciprocal of 400 pi, that's 1 over 400 pi, and that will give you the value for dr over dv. So that's how this chain rule works. That's how you deal with this, with these rate of change problems. Sometimes you end up getting something more complicated. For example, if you have something like this, water is being poured into a tank at a constant rate of 500 centimeter cube per second. The depth of water in the tank t seconds after filling starts is 8 centimeter. That's what we're given. And what we need to find out is the rate at which h is increasing at the instant when h is equal to 10. Now, what's the information that's given? It says water is being poured at a rate of 500 centimeter cube per second. So that's dv over dt. So that's one piece of information that we're given, dv over dt. And what we have to do is we have to figure out dh over dt. Now, we can make a chain rule like this. dh over dt equals dh over dv into dv over dt. Now, dv over dt is something that we know. dh over dv is not known. How do you figure that out? You've got the volume function given here. You find the derivative of that. For that value of h, they wanted wanted that rate when the value for h was equal to 10. You input that value of h here, h equals 10, and that gives you the value for dv over dh, and that's the final result. When you input that 4900 in this chain rule, you get that rate of change of height. Sometimes they will want you to find some particular value, not the rate. For example, in this case, they're saying at another instant, the rate at which h is increasing is 0.075. So we were given the value for dv over dt already in the first part. In fact, at the start of the question, and that was dv over dt equals 500. And now we are given that dh over dt, that is equal to 0.075. These are two values that we're given. We are given both rates. We are given rate of change of volume, and we're also given rate of change of height. We're given both of these values. And what we have to find out is dv over dh. We have to find out dv over dh. Okay, I'm sorry. We have to find the volume at a particular point. Not dv over dh. We have to find the volume at a particular point. Now, how do you do that? These are two things that were given, dv over dt and dh over dt. In the first part, what we've done already is we had the volume function. We want to find the value of v at this particular point when this is the rate of change of height. Now, that will come from this volume function. Now, for this volume function, you need the value for h. You need some value for you need the value of h at that particular instant when the rate is given to be 0.075. Now, how do you find that particular value for h? What you can do is you can say if dv over dt is equal to this, dh over dt is equal to this, you can use chain rule to find dv over dh. You already have an expression for dv over dh from the previous part when you differentiated the volume function. That turned out to be this. dv over dh, its expression was given by this. What we can do is we can say, using the chain rule, we can find the specific value, the constant value of this this derivative dv over dh using chain rule, and that turns out to be 500 into 1 over 0.075. This value, if we input that in this derivative, that gives us the value for h. Once we've got that value of h, we put that value in this function, the volume function, that gives us the corresponding volume value. And that's the result that we wanted. So sometimes you're given both of these rates, and what you're supposed to do is you're supposed to use both of those rates using the chain rule and find the value of the derivative at that particular point. Now, in this case, we found the value of that derivative, and we had this expression for the derivative. We put that there, and that gives us the value for h. When we input that value of h in the volume function, that gives us the final result for the value for b. Now, this is the more complicated type of question that you will see in chain rule. That's how you would approach that. Okay, so one last example. Sometimes they say something like this. You've got these two curves. Look at the last part of this question. The rest is integration. We're going to skip that for now. The tangents to these two curves, we've got two curves there. One is y equals 9 minus x cubed, and the other is y equals 8 over x cubed. They are saying these two curves, they have tangents that are parallel to each other. At some point, the two tangents of these two curves are parallel to each other. So there's some point x equal to c, and that point is between 1 and 2. So that's somewhere here, let's say. That's the point c. At this point, the gradients, the tangents are parallel to each other. So you might have a gradient, have a tangent that looks like this here for one curve. And you might have a tangent that looks like this for the other curve. They're both parallel at this particular point. At this particular point, both of these tangents are parallel. Now, if they're parallel, how do you find the value of that point at which they're parallel? If at any particular point, tangents of the two curves are parallel, what that means is both of those curves have the same gradient at that particular point, right? If the tangents are parallel, that means at this particular point, the gradients of the curves are going to be equal to each other. Now, if the gradients are equal, we find the gradients of curves using differentiation. So what we do is we say, we've got this curve, we've got another curve, find the derivative of both of them and equate those derivatives. Because if the tangents are parallel, the gradients of the curves are going to be the same at that point. Gradients of curves are found by differentiation. So we find the derivative of both of them. These are the derivatives. And then we equate those derivatives. And that gives us the value of x that we were looking for. And that's what they're calling c. So c equals under root 2 here. Now, sometimes they will use this statement in questions. They will say, some line makes an angle of tan inverse of k with the positive x-axis, tan inverse of something with the positive x-axis. What do you understand from statements like this? In this case, they're saying normal. It could be any line. Whenever any line makes an angle of tan inverse of something with the positive x-axis, what do you understand from that? In coordinate geometry, we've done a formula that's tan theta equals gradient that gives us the angle of a line with the x-axis. If you make theta the subject here, that gives you tan inverse of the gradient. So gradient, the angle of any line with the x-axis, that's given by tan inverse of gradient. If they're saying the angle is tan inverse of k, what that means is this value that you would have after tan inverse, that would always represent the gradient of that line. So in this case, if they want you to find the normal at a particular point, you know from this statement that the gradient of that normal is supposed to be k. Okay, so this is something that you will see come up a number of times in past paper questions. As I said, you would have some questions in which in the first part, they will ask you to use some mensuration. So you should be familiar with all of these formulas that you've done in O-level. Some of them are given in the formula sheet, some are not given. You will need to make sure that you remember them. For cone, pyramid, and sphere, you will have the formulas given. For cube, cuboid, cylinder, prism, the formulas are not going to be given. Now, the volume formulas are important. For surface area, you can just find the areas of the faces and then just add them up together. It's not necessary to remember these formulas as such. Just find the areas of the faces and then add them up together. Okay, let's have a look at this one last example. I'm sorry, I said the previous one was last, but that was not the last one. Let's have a look at this. This is a curve that we've got. We need to find the set of values of x for which y decreases as x increases. Now, what does that statement mean? Y decreases as x decreases. Now, think about it. On an xy plane, as x increases, that means as you go to the right side, y decreases. You're going downwards. So which direction is the curve going in? It's going downwards like this. Now, it could be any shape. It could be like this. It could be like this. It doesn't matter. All that matters is as x increases, y decreases. That means the gradient of the function is going to be negative. If the gradient is negative, that means the derivative is negative. So it's a decreasing function. It's a decreasing function. That means the gradient is negative. What you would do in that case would be you'll find the derivative, put that less than zero, solve that inequality to find the values of x that they're looking for. So instead of saying it's a decreasing function, sometimes they can say something like this as well. That means the same thing. As x increases, y decreases. That means it's a decreasing function. So the gradient is supposed to be less than zero. If they say some line is a tangent to some curve, and they ask you to find this value of k, if this function was a quadratic function, and we had that the line was tangent to the curve, we would say that b square minus 4ac is equal to zero. But b square minus 4ac does not work for cubic functions. In this case, it's a cubic function, and in this cubic function, they're saying this line here is a tangent to the curve. Now we can't use b square minus 4ac here. So what do we do then? If this line is a tangent to the curve at a particular point, what that means is whatever is the gradient of this tangent, can we find that? In this case, that's compared this with mx plus c, the gradient is 9. Gradient of the tangent to the curve at that particular point should be the same as the gradient of the curve at that point, right? So whatever is the gradient of the tangent at this point, that's 9 in this case, the gradient of the curve at that point should be the same as well. Now, this is what the curve looks like. We want to find the point at which its gradient is equal to 9. So what we do is we find the derivative, because that's how we find gradients of curves. We find the derivative of this function. This is what the derivative turns out to be. We put that equal to 9. That gives us the value for x. Once we have the value for x, we put that back in the function. That gives us the corresponding value for y. And that's the point that we were looking for. Once we got that point, they're saying find the value of the constant k. Just input that point here, and that will give you the value of the constant k. So whenever it's a non-quadratic function and they say some line is a tangent to the curve, what you do is you find the gradient of that tangent, put the derivative of the curve equal to that number, and then solve that equation, and that will give you the result. Okay. All right. So that's what you need to know about differentiation. That's all on this. We'll have a break now. If you have any questions, you can let me know. Otherwise, we're going to end this differentiation part here. When we come back from the break, we'll have a quick look at differentiation, at integration as well. Any problems, anyone? 15 minutes, 10, 15 minutes. Abdullah, the first part or second part? First part or second part? B part. Okay, so the question says the line is a tangent to the curve. So whatever the curve is, let's say it looks like this. It's a cubic function, though its shape is going to be different. But let's suppose this is a random curve. At this particular point, this is what the tangent looks like. They're saying this tangent is y equals 9x plus k. Now, what's the gradient of this tangent? That's 9. So the gradient of the curve at that point should also be equal to 9. So what we do is we say at this point, dy by dx is supposed to be equal to 9. So we find the derivative and put that equal to 9. Because whatever is the gradient of the tangent at that point, the derivative of the curve, the gradient of the curve, that is also supposed to be the same. Make sense? Okay, any other questions on this quickly? So now, was your question answered? That's not stationary point. Why would it be a stationary point? If it was a stationary point, its derivative would be 0. No other questions? Yes, Eamon.
Uh, I Okay, we have to tell if it's increasing, decreasing, or neither. I don't understand how to do those. Like you told us about how to tell about increasing and decreasing. But how do you tell if it's like none of them?
Okay, let me go back to one of those questions, increasing and decreasing. For example, this one. When they ask you to find the set of values of x for which this function was an increasing function. Now, this function, we can say it's neither increasing nor decreasing because in some part it's increasing, in some part it's decreasing. So if you have a function like this, the derivative turns out to be this. 2x minus 3 whole squared minus 4. Now, you think about whether this derivative is always positive or always negative, whether it's always positive or always negative. Now, we can't say that because in some part, the derivative is negative, and another part, it's positive, right? So in this part, it's negative between 1 over 2 and 5 over 2, and in the remaining parts, it is positive. So in this case, we would say it's neither increasing nor decreasing. So that will be that case. Does that make sense? All right, so next we've got integration. So first of all, integration is just the opposite of differentiation. So we also sometimes call it reverse differentiation, just the opposite of what we do in differentiation. So let's say if you got a function that like this, y equals 5x squared, what's the derivative of that? That's 10x. If we want to go in the backwards direction, that we have dy over dx given, and we want to find y from that, the process that we would have to use for that would be called integration, right? So from 10x, we can find that the original function was 5x squared. For that, we do integration. Now, how does this process work? There are two steps that you do for functions that look like this, x raised to power n. You just reverse the process in differentiation. We used to multiply by the power and also subtract from the power, subtract 1 from the power. Now we do just the opposite of that in the opposite order as well. We say add 1 to the power and divide by the new power. For example, if we have 10x, what's the integration of that going to be? 10 remains as it is, that's a constant. Just like in differentiation, if we have a constant multiplying that remains as it is, that does not change. We add 1 to the power and we divide by the new power. So x raised to power 1 plus 1 divided by 1 plus 1, that gives us the integration. This is what the rule looks like. In fact, before that, we've got this notation as well. In differentiation, the notation used to look like this. Derivative with respect to x of x cubed, for instance, that is 3x squared. That's the differentiation notation that you need to know about. In integration, we have this notation, this symbol that represents integration, and this dx that represents that you're integrating with respect to x. The variable in terms of which you're integrating, that is x. So that's the notation that we use for integration. So if you have something like this, for instance, x raised to power n, and then the sign dx, that means integrate x raised to power n with respect to x. What's the integration going to be? We add 1 to the power, divide by the new power, and we get the result for that. Now, whenever we integrate, we always have this plus c, that's the constant of integration. I'll tell you the reason for that briefly later on, but we always have this plus c whenever we integrate. So let's say we've got 5x raised to power minus 3. How do we integrate this? 5 is a constant that remains as it is. We add 1 to the power, divide by the new power, and that gives us the result. Minus 5 over 3, that's a constant that remains as it is. Add 1 to the power, so 1 over 4 plus 1, divide by the new power, 5 over 4, and that gives you the result after simplification, and you have a plus c with that. So that's how integration works. If you've got x in the denominator, just like in differentiation, we have to bring x to the numerator first of all before we can apply that rule. So this is x power 1 over 3 in the numerator, in the denominator. When it comes to the numerator, it will become x raised to power minus 1 over 3. And then we apply that rule. We say 7 is a constant that's outside. We add 1 to the power of x, divide by that new power, and that gives us the result. Similarly, 5 over 2x cubed comes to the numerator, it becomes x raised to power minus 3. We add 1 to the power, divide by the new power, we get the result. If we have a constant, what's the integration of a constant? We just have an x multiplied with that like this. Why is that? Because 7 can be thought of as x raised to power 0, 7 into x raised to power 0, and then we can say add 1 to the power, divide by the new power, and that gives us x like this. So whenever we have a constant, just remember the integration of that is going to be just that constant multiplied with x like this. All right. So if you have k, integration of that is k times x. If you have multiple terms, just like in differentiation, we can just integrate each term separately if there's a plus minus between them. So if you have plus minus like this, you integrate one term at a time, and that gives you the result. This is often quite helpful in integration when you have complicated integrals. Just remember, if you have a constant that's multiplying or dividing by the whole thing, since that is not going to change after integration, as no integration rule applies in that constant that's multiplying, you can just write down that constant outside the integration sign as well to simplify things sometimes. So this k can be written outside, and that will not change anything. For example, if you have something like this, 2x minus 4 whole raised to power 7, and you have to integrate this, to simplify things, we could write the 7 outside so that it becomes 1 over 7 into 2x minus 4. And then 1 over 7 outside remains as it is. Just apply the integration rule on what is inside, and you get the result from that. Now, this is why we have a c there. Should I tell you about this quickly? Okay. So if we have a function like this function, all of them have the same derivative 16x. Now, if we were to integrate 16x, what's the integration of 16x? That's 8x squared. That only gives us this. What if there was a constant here? If it was plus 5, if it was plus 3 here, their derivative were also the same. How do you get those other functions? Why are we only getting 8x squared when we integrate this? Because when we differentiate something, this constant basically gets eliminated, right? We don't have any constant in the derivative that we have. So when we integrate, we consider this possibility that there could be a constant in that original function as well. So we always have a plus c. This is called constant of integration. We always have a plus c. Whenever we integrate, we always put plus c with that. Unless when we have limits, in that case, even if you ignore this, you can get away with this because it gets cancelled there. But otherwise, apart from that, you always put c there. Otherwise, you can end up getting wrong answers. You need to make sure that you remember that. Now, we talked about how to integrate x raised to power n. What if you had some other expression in place of x inside the power, and you had to integrate that expression? For example, if you have 2x minus 3 whole raised to power 4, how do you integrate this now? We call this the general power rule of integration. It's the generalization of that previous rule. That was just a specific case of this. 2x minus 3 whole raised to power 4, how do you integrate this? This is the rule that we use for this. These are the steps that we follow to integrate this. We add 1 to the power just like before. We divide by the new power just like before. But then we have an additional step, and that is we divide by the derivative of the base. So in differentiation, we used to multiply by the derivative. In integration, to reverse that, we divide by the derivative of the base of the power. So for example, if you have something like this, mx plus c whole raised to power n, what's the integration of that? We add 1 to the power, we divide by the new power, and we also divide by the derivative of the base. What's the derivative of the base? If it's mx plus c, derivative would be m. We also divide by m in the denominator, and that will give you the integration of this. Now, for this rule, we have a condition, and that condition is that the part that is inside the function, inside the power, this part has to be something linear. It has to be linear. It cannot be non-linear. In differentiation, we did not have any such condition. In integration, we have this condition. The part that is inside, it has to be linear. If you have a non-linear expression inside the power, that does not work. You cannot integrate that using this rule. Okay, this rule would not work if the part inside is not linear. These are some examples of that. You can have a look at them. If you had this 7 over 3 into 4 square root of 4x minus 1. Again, the first thing you have to do is you have to bring this to the numerator. So it comes to the numerator and becomes 4x minus 1 whole raised to power minus 1 over 2. Minus 7 over 3 was just a constant. Simplify things, you can write that outside like this. And then you apply the power rule on this. You add 1 to the power, divide by the new power, and also divide by the derivative of that base, and simplify that to get that integral. If you have 7 over something like this, minus 3x plus 1 whole squared, now when you bring this to the numerator, first of all, it becomes this power minus 2. So if you had to integrate this, if you want to integrate this thing, how would the integration of this work like? You would say, first of all, bring this to the numerator. The power becomes negative 2. 7 remains as it is. You add 1 to the power, minus 2 plus 1, that becomes minus 1, divide by the new power, and also divide by the derivative of the base, that is negative 3. Now, what about this now? 3x squared minus 1 whole squared. How do you integrate this? If you apply the power rule in this like this, that would be wrong. This is not acceptable because the power rule does not work here. You're dividing by x here. That is problematic. This will not work. Okay, the power rule does not work in this case. The inner part of the function, it has to be linear. If it's not linear, we cannot apply this. So how exactly do we integrate this function then? If it comes up, how would we integrate this? 3x squared minus 1 whole squared. We would first have to expand this. This is very important now. When you have a nonlinear function inside, generally with the power 2, because for higher powers it'll become very complicated to expand that, but with power 2 what you'll do is you will say, let's first of all expand this using a minus b whole squared or a plus b whole squared, and then after you've expanded this, then you just integrate each term at one term at a time, this separately, and this separately. It can't be done directly because the inner part is non-linear. If the inner part was linear, we could apply the power rule directly. In this case, we cannot do that. We have to expand it first. Now, these were the rules that you need to know about integrating functions. Now, what are the applications of integration? Number one, you should be able to find equation of a curve from its derivative. Sometimes what happens is they give you the derivative of a function, for example, like this, and they want you to find the equation of the curve from that. Now, if you want to go from dy over dx to y is the original function, right? How do you do that? You do that by integration. In order to go from y to dy over dx, we used to differentiate. In order to go the other way around, now we would have to integrate. So you have dy over dx equal to this, you integrate that function using the power rule. Do not forget the plus c. Whenever you integrate, you always have a plus c. Now, when you have a plus c here, how do you find the value of that c? You're given a point that lies on that curve. That's the point 3, 8. You input that point here, input the value of x as 3, input the value of y as 8, find the value of c from that, and then that's the equation of the curve that you end up getting from that when you input that value of c. So that's one thing that you have to do. Then you need to be able to integrate using limits. So sometimes what happens is they have these numbers written on top and at the bottom. These are called the limits of this integration. The number at the bottom, that's called the lower limit. The number on top, that's called the upper limit. Now, how do you evaluate this? You integrate like you normally do. So 2x plus 3, the integration of that turns out to be x squared plus 3x plus c. Now, what you do is you input the upper limit once, input x equal to 5 in this once, and then you input x equals 3 in this once. That's the lower limit. Subtract from the upper limit case the lower limit case, and you get the result from that. Now notice c is getting cancelled here. So you can get away with not writing c here at all. So when you have limits, you can ignore c as well, but otherwise you will always write this. And that's how you evaluate these limits. You integrate the function, input the upper limit, subtract from that the case when you have the lower limit. And that gives you the result. Now, what exactly does this represent? This number that you get from this, it actually represents the area under the graph of this function. So this 2x plus 3, that's a straight line. That's a straight line that looks like this. It's 2x plus 3, that's the straight line. The limits that we input there, they were from 3 to 5. Now, these are the points 3 and 5 on this graph. That value that we got there, 22, that's basically the area of the region below that line with the x-axis, the shaded part. This number represents the area under this graph. Now, this is the trapezium. We could find that area using the area of trapezium formula as well, and that also turns out to be 22. However, integration is very helpful when instead of straight lines, we've got some curves, and we want to find areas like that. And that brings us to this: how to find area between a curve and x-axis or y-axis. We've got these formulas for that we can use to find areas between a curve and the x-axis and the y-axis. Area between the curve and x-axis, the formula for that is integration of y with respect to x, and we have these limits here. Limits are supposed to be values of x in this case. And the other formula is area between the curve and y-axis. That's the formula: x with respect to y, integration of x with respect to y with limits of y there in this case. This is y equals something, and this is x equals something. Now, let's talk about these in a bit more detail. Let's say we've got a function like this, y equals x squared plus 2, and we want to figure out what this area is. Okay, and we are given that this is the area between x equals 1 and x equals 3. How do you find this area? This is an area between graph and x-axis. Now, the formula for that is integration of y with respect to x, and we have these limits, x equals a to x equals b. These are the values of x from which the graph, between which we have to find the area. Now, when you use this formula, you have to make sure that y is the subject of the function that we're given. So in this case, it already is the subject. Otherwise, you have to first make it the subject so that you can input y equal to that thing, inside this equation, then inside this formula, then y, in place of y, you write x squared plus 2. And the limits that you input there when you're finding area between a graph and x-axis, the limits are supposed to be values of x. These are the limits from 1 to 3. And all you have to do now is integrate this, input those limits, and you get a result that will give you the area between graph and x-axis. Now, this formula and the volume formulas, they are not given in the formula sheet. You need to memorize these. They're not given in the formula sheets. So when you have to find area between graph and x-axis, the formula is integration of y with respect to x. When you have to find area between graph and y-axis, the formula has x in it, right? So it's the other way around. With x-axis, the formula has y. With y-axis, the formula has x. Okay, now this is another example of this. You can have a look at this. Sometimes what happens is the area turns out to be below the graph like this, below the x-axis like this. Now, how do you find this area? The formula that you have, that is basically for the area between the graph and the x-axis. Now, in this case, since this area is below the x-axis, you will find when you apply the formula, the end result that you would get from that formula, that's going to be negative. That's negative 36. The reason for that is this area is below the x-axis. If it was above the x-axis, that would turn out to be positive. If it's below the x-axis, that turns out to be negative. Now, since we're just looking for area, we would just make it positive and we would say the area is actually equal to 36. Even if it's a negative value, that's only representing that the area is below the x-axis. Now, sometimes what can happen is you have an area like this, some part of the graph, some part of the shaded region is above the x-axis, another part is below the x-axis. How do you find this total area? Now, since the part that is above the x-axis, that's going to turn out to be positive from the formula, and this area is going to turn out to be negative. We cannot calculate it all together. We would have to split this into two parts. So what we do in this case is we say, let's integrate the function. Let's integrate the function from 0 to 2 separately. And that gives us some value that gives us 20 over 3 here. And then integrate the function from 2 to 6 separately. And that gives us another value that's minus 128 over 3. Now, the area above the x-axis, this A1, that is 20 over 3. And the area below the x-axis, that's 128 over 3. This negative sign is only representing that the area is below the x-axis. So what's the total area going to be? You will make both of these numbers positive. So this is already positive. You make this positive as well. And then you add them up together. The total area turns out to be 148 over 3. That's the total area that you have from this. So when some part of the area is above the x-axis, some is below the x-axis, you have to break it down into two parts and then integrate. This is also an important point here. How do you integrate function like this? X into x minus 2 into x minus 6. Now it's a product. We've got multiple expressions multiplying with each other. We cannot integrate it separately. We can't do something like this, that it's x square over 2 and then x minus 2 whole squared over 2 and x minus 6 whole squared over 2. We can't use the power rule on each of them individually. It's a product. We could do that if there was a plus between them. We could integrate each of them separately. But this is a product. This whole thing is one. We can only integrate it if we first simplify this. So we simplify it first like this, and then we integrate one term at a time. And that's how I've done it in this example on the left side. All right. So that's what happens when you have some area above the x-axis, some area below the x-axis. You break it down into two parts like this, and then you integrate. You could have area between a graph and y-axis as well. That's the formula that we have for this, integration of x with respect to y. Now, in this case, x needs to be the subject. Limits are supposed to be values of y. Now, what does it look like graphically? It looks like this. We could have a function that's this, and we're looking for this area between the graph and y-axis. Now, how do you use the formula for this? If the function is given like this, y equals x cubed plus 5, the formula has x in it. The x variable should be the subject. So first of all, you have to rearrange this and make x the subject. How do you do that? You've got y equals x cubed plus 5 here. You make x the subject. Take 5 to the other side, take cube root on both sides, and that gives you x equals this. And now this is something that you can input in the formula. You get y minus 5 whole raised to 1 over 3 with respect to y. That is what you integrate here. Okay, so now only the variable name has changed here. It's y in place of x, so you just integrate it like you normally would, and then input the limits, you get that area that you're looking for. Now, in case of y-axis, area on the right side, that will turn out to be positive. Area on the left side, that will turn out to be negative. From the formula, again, area cannot be negative. You will just make that value positive, and that will be your final result. If they just want an integral, by the way, so sometimes what they do is they ask you the value for an integral. So they do not refer to area. They will just find the find this integral x plus 2 whole squared with respect to x, and maybe let me actually use another function that could actually be negative as well. Let's say they ask you to find the area of this integral x cubed minus something with respect to x, and limits are, let's say, from -1 to 0. Now, in this case, if you were to find this area, find this integral, it might end up having a negative value. You will keep it negative because they're not referring to area. If they just ask you to integrate this, evaluate this result, if it turns out to be negative, you just leave it as negative. If they specifically mention that they want the area from a function, in that case, you will evaluate it like you normally do. If the value turns out to be negative, you will just make that positive and say the area is positive. All right, so that's what you do. You don't necessarily need to put a modulus sign there. That's not necessary. If it turns out to be negative, just make it positive. If they're referring to area, if they're not referring to area, you keep it negative. That remains as it is. You just leave. You just write the negative number as the final answer. Okay. Now, a lot of times, what happens is it's not just area between a graph and x-axis or area between a graph and y-axis. It's area between two functions, two graphs, two different graphs. So if you have something like this, you've got these two curves. We say one of these is the upper curve. So in the shaded part, look at whatever is the upper curve. So in this case, this green one, that's the upper curve. And the blue one, that's the lower curve. So what we do is we find the area between the upper curve and the x-axis. We subtract from that area between the lower curve and the x-axis. So we find all of this area between the upper curve and the x-axis, and subtract from that all of this area between the lower curve and the x-axis, and that will give us the area between the shaded region, area of the shaded region. So we find one area, subtract from that the other area. For the upper curve, we find the area first and subtract from that the area for the lower curve, and that will give us the result. Now, one way to do this is like this, that you do it separately for each function. You find it for the upper curve separately, you find it for the lower curve separately, and then you find their difference, and that gives you the result. That works. You can do it separately. So that saves you from careless errors a lot of times, that you do these two calculations separately. You say, let's do the calculation for the upper curve separately, and let's do the calculation for lower curve separately. And then at the end, what you do is you find the difference and you say that's the result. For example, if this is A1, this is A2, you say the final area therefore is going to be A1 minus A2. That's one idea. Now, to make it more efficient sometimes, because in recent papers, sometimes papers do tend to be long as well. So you need to be efficient with your time as well. If the limits are the same for both functions. So in this case, for example, both the upper curve and the lower curve, they have the same limits. If the limits are the same, you can do it directly like this as well. You can say one function is 9 minus x cubed, and the other function is 8 over x cubed. If the limits are the same, you first subtract the functions like this, 9 minus x cubed minus 8 over x cubed, and then you integrate it, input the limits directly. If you understand that and are comfortable with this, you can do this as well. Otherwise, if you're confused about it, just do it the normal way. If you're used to doing it this way, that's okay. It just take maybe 1 more minute, and that's okay. That doesn't make much difference. But if the limits are the same, it is sometimes more efficient to subtract the functions first, like we have done in this case, and then input the limits directly, and that gives us the result. Okay. Now, what about volume of revolution? Let's say we've got a line like this, y equals half x, and we've got this shaded area, the yellow shaded area. If we were to rotate this area about the x-axis, in this case, if it's a triangle, when it gets rotated 360 degrees about the x-axis, the shape that we end up getting from that is a cone. Now, for cone, we have a direct formula that's 1 over 3 pi r squared h. Now, instead of a straight line, what if you had a curve like this? And the area between the curve and the x-axis or the y-axis, what if that was rotated about the axis? In that case, we get a shape. It's a 3D shape, but that's not a standard shape for which we have any direct formulas. So for cases like these, what we do is we use integration to find these volumes as well. Now, what are those formulas that we've got for this? For volume of revolution about x-axis, we've got this formula, pi into integration of y squared with respect to x. But for volume of revolution about y-axis, we've got this formula, pi into integration of x squared with respect to y. Again, when you're doing it about x-axis, the formula has y squared. When you're doing it about y-axis, the formula has x squared. So the opposite of the axis, that's what you have in the formula. Let's start with this one first. Volume of revolution about x-axis. this is the formula that we've got. V equals pi into integration of y squared with respect to x, right? And then you input limits of x in this. Now, for using this formula, the first thing you have to do is you have to make sure that y squared is the subject in the given equation. If it's not the subject, you have to make it the subject. First of all, make y squared the subject. Then you input that in this integral. And the limits that you have, they're supposed to be values of x. And what does the formula give you? The formula gives you the volume when the area between the graph and the x-axis, area between the graph and the x-axis is rotated 360 degrees about the x-axis. So if you're rotating about x-axis, the area should be between the curve and the x-axis as well. Okay, and then you'll get that correct volume. That's what the formula is for. It's the volume when the area between the graph and x-axis that is rotated 360 degrees about the x-axis. Now, how does it work? If you had a function like this, y equals x squared plus 5, and you had to find the volume of revolution from 0 to 3 in this case, you would first of all find y squared from that. Y squared turns out to be this, x squared plus 5 whole squared. If we input that in the formula, it becomes x squared plus 5 whole squared. Now, how do we integrate this? It's a nonlinear function inside the power. We cannot apply the power rule directly. So we expand it first. We expand it to this x power 4 plus 10x squared plus 25 using a plus b whole squared. And then we use integration on each term separately, input the limits, and at the end, remember to multiply pi there, and that gives you the result. A lot of times in these cases, they ask you for exact answers. Always write them in terms of pi in that case. If they want an exact answer, do not use decimals in your working. What about volume of revolution about y-axis? If it is about y-axis, then the formula has pi into integration of x squared with respect to y. So in this case, the subject that you need to have in the function is supposed to be x squared, and the limits are values of y. And this formula gives you the volume when the area between the graph and y-axis, when the area between the graph and y-axis, that is rotated about y-axis. Now, this is important, as we'll see in a couple of examples later on. How do you use this formula now? Find this volume of revolution, for example, this is with the y-axis. How would you do this? You would say this is the function y equals x squared plus 5. Let's make x squared the subject first of all. So it becomes x squared equals y minus 5. Now you input that in the formula, it becomes y minus 5 here. What are the limits? Limits are supposed to be values of y. They're going from 5 to 14. These are the limits that you input there, integrated, and input those limits, you will get that volume. Now, what if you had to find volume of revolution of the area between two graphs? So you have this area between two graphs. How do you find this volume of revolution? Now, it works very similar to how we used to do this in area. We find the volume of revolution of the area under the upper curve, subtract from that the volume of revolution of the area under the lower curve. And that will give the result. Find one volume, find the other volume, find their difference, and that gives you the result. So just like we used to do in area, we do the same thing here as well. For example, if you have something like this, we want to find the volume obtained when this shaded region is rotated 360 degrees about the x-axis. Now, how do you rotate this about the x-axis? If you think about this curve, if you apply the formula directly on the curve, that would not work, because when you're rotating about x-axis, the formula, if you just apply that in the curve, that will give you the volume when this green part is rotated about the x-axis, right? That will give you this volume when this green part is rotated about x-axis. But the shaded part is not the area between the graph and x-axis. So how do we think about this? We think of it as two graphs. We say, okay, we've got this one line. It has the equation y equals 2, right? That's just a constant. It's a horizontal line. So y equals 2. That's a horizontal line. And the other graph is this curve. So we've got this graph, that's a straight line, horizontal line. And the other graph is y equals square root of 3x plus 1. So what we do is we find the volume of revolution under the upper graph. So that's y equals 2. We integrate that separately. We apply the formula on that. And then we integrate the lower part separately. Apply the formula on that. As in, first of all, you have to make y squared. So this becomes y squared equal to 4. This becomes y squared equal to 3x plus 1. Apply the volume of revolution formula on both of them. Subtract this one from the other, and that will give you the volume. Okay, so you can't apply the formula directly only on the curve, because that will give you the volume of revolution for this part, for this area, that's not what we're looking for. So again, this is what you have to do. Volume of revolution of the upper graph, that's y equals to, do that separately, do this separately, and find their difference, and that will give you the result. Okay. Then another concept that you have here is of improper integrals. Sometimes you get integrals in which infinity is one of the limits. Infinity is one of the limits. Or this is not something that you'll find a lot in past papers, but it is something that you need to know as well. And that is when you get 0 in the denominator after inputting one of the limits. So improper integrals is when one of these two things happens. Either infinity is in the limit, or when you input any limit, you get 0 in the denominator. If you have one of these cases, we call that an improper integral. Now, let's take an example. Let's say we have a curve that looks like this, y equals 1 over x squared. Now, this is what the shape of the graph is. We want to find the area under this graph from 2 onward to the right side. Now, this looks like it's an infinite area because it's going on forever like this on the right side. There's no limit to it on the right side. What are the limits going to be for this? If you want to find all of this area, we apply the formula integration of y with respect to x, limits from x equals a to x equals b. Now, what are the limits going to be in this? Y is equal to 1 over x squared. We can say that's x raised to the power minus 2. That's the function that we've got. What are the limits? It starts from 2 and goes up to infinity. So the limits are from 2 to infinity like this. Now, how do you evaluate this? You just do it the normal way. You say integration of x power minus 2. What's that going to be? You add 1 to the power, you divide by the new power, and the integration turns out to be minus 1 over x from this. Now, input those limits. The upper limit is infinity. Just input it like this, and that's okay. At this level, this is fine. That will work. You just input infinity here, minus 1 over 2. And then you evaluate this 1 over infinity, 1 over an extremely large number. What's that going to be? You say this approaches 0. And then this is plus 1 over 2. So you evaluate that. That turns out to be 1 over 2. Now, another case could be that when you integrate, you end up getting 0 in the denominator. For example, in this case, the lower limit is 0. The upper limit is 2. When you integrate this, you end up getting minus 1 over 2 minus 1 over 0. And that's something that's undefined. You can't have 0 in the denominator. But in this case, we consider this as an extremely large number. 1 over 0, that's basically telling us that. So in this case, for example, when you look at the limits here, it's going from 0 to 2. Now, it's not becoming exactly equal to 0 because the graph is becoming an asymptote here. So this value is basically approaching 0. It's becoming very small. So when you have 0 in the denominator, you think of it like this, then it's a very small value in the denominator. And that basically gives you infinity. In case of that, you write infinity. And the overall area in this case turns out to be infinity. So the takeaway from that is when you have infinity in the denominator, when you input the limits, when you have constant over infinity, we approximate that as 0. When you have constant over 0, we approximate that as infinity. Now, the first case you'll find a lot in past papers. The second one, not so much. So this is more important, the first one. When you have infinity in the denominator, just remember, you would replace that part of the fraction with 0, then let's simplify that. Okay, this is ongoing on here. We'll have a break, and we'll have a look at a couple of questions quickly, and then that's it. Okay, so this is what happens when we have infinity as one of the limits, or we get 0 in the denominator. When you have infinity as the limit and it turns out to be in the numerator, then the result would be infinite. But that's, again, something that you would not see in past papers until now, because they will normally ask you for something that has a finite value, something that results in infinity at the end. I haven't seen any question in past papers, at least, in which the result is infinity. But that's what would happen. If infinity is in the numerator, then that means that the overall thing is going to be infinity. Now, sometimes you end up having areas like this in which you have to add two parts of the area. For example, if you have something like this shape, how do you find this area? How do you think about this? Is it area under the curve minus the area of triangle or something else? How do you think about this? It's not going to be done as one of those examples in which we say find the area under one curve and subtract from that area under the other curve. This is actually two different parts that you have to do separately. For example, this is one triangle, so you find the area of this triangle separately, and then you say find the area under the curve from this point A to the origin separately. So sometimes you have to break your area into two parts like this, even in integration questions, like you do in mensuration. You do it in separate parts like this. You say, okay, this is a triangle, find the area of this part separately using area of triangle. And the left part, this is the area under the curve, find the area of that area under that curve separately, and then just add those two areas together. In this case, you don't subtract one area from another, but you find two areas separately and then add their values. So this is how it would be done. You find the area of the triangle separately. So in the first part, we have found the coordinates of B and C. Using that, we find the area of the triangle. That turns out to be 1 in this case. And then for the curve part, we find the x-intercept for that. First of all, inputting y equal to 0. And then we use these limits, find the area under the curve from that point to 0. And that turns out to be, after this integration, minus 1/6. Since it's a negative area, I calculated it with using the y-axis formula. If you calculate it using x-axis formula, that would turn out to be positive. Using the y-axis formula, it turns out to be negative. Either way, the area is 1/6. The numerical value is 1/6. You just add this value to 1, and that gives it the total area. That's 7/6 like this. So that's something that you need to be aware of as well, that sometimes you can break your area into two parts like this, evaluate them separately, and then add them up together. Now, this is another type of question that you will see in past papers, that you have the second derivative given, and using that second derivative, they sometimes want you to find out the original curve or something else sometimes. So in this case, you've got the second derivative given. And they're giving you that the minimum point of this function is 3 minus 10. Now, that's the minimum point. Now, if it's the minimum point, that means it's the stationary point. At stationary points, we know that the derivative is equal to 0. So what we know about this point is, at this point, the value for x is equal to 3, the value for y is equal to minus 10, and at this point, the derivative dy by dx, that is equal to 0. X equals 3, y equals minus 10, and dy by dx equals 0. So that's what we know about this point. So how do you find the coordinates of the maximum point from this? How does that work? You have the second derivative. First of all, you integrate it once, and that gives you the first derivative. When you integrate it, you get a plus c there. When you get a plus c, how do you find the value of the c now? For this value of c, you need some value for x and dy over dx at a particular point. Now, in this case, for example, you know when x is equal to 3, dy over dx is equal to 0. So you input that value here, input x equal to 3, and dy over dx equal to 0. That gives you c equal to minus 6. So now you've got the value for the derivative. Now, what were we looking for? You were looking for the coordinates of the maximum point. How do you find the coordinates of maximum point? By dy over dx equal to 0. So now you've got dy over dx equal dy over dx, the expression for that. You put that equal to 0. When you put that equal to 0, you get two values of x. One is x equals minus 2, the other is x equals 3. X equals 3 was already given. That was the minimum point. We already found that before. So x equals minus 2 is the other stationary point, and that's what we were looking for. But now the problem is, they wanted us to find the coordinates. That means we also need the y coordinate. How do you get the y coordinate? For that, we will need the original function, y. How do you get to that now? We've got dy over dx. So we integrate it again, integrate dy over dx again, and that gives us this function. But then you have another c. So for that, you use the point that was given. The point that was given was 3 minus 10. You input that point here, 3 minus 10, find the value of this c now. Once you've got the c, now you've got that function, you know the value of x of the stationary point, put that value of x in this function, that will give the corresponding y value, and you finally get that maximum point that you were looking for. So sometimes you have the second derivative given, and you have to go back to the original curve. For that, what you do is, you integrate it twice. So you integrate it twice like this. You say, you have the second derivative first, you integrate it, and that will give you dy over dx. You integrate it again, that will give you y. Now, in each step, you are going to get a plus c. In each step, you'll get a plus c. For finding the value of c, you will have to use this information that's given. If it's a stationary point, you know at this point, the derivative should also be 0. So you can use this point now to find the values of both of those c's, both in the derivative and the original curve, and that will give you that final result that we were looking for. Let's have a look at this one last example. Again, you have to find this shaded region. Now, how do you think about this? Sometimes it's a bit confusing from the shape that's given. So how do you find this shaded part of this? So the way to think about this would be, you could say it's area under the curve from the point A to the point x equals 2 there. This is the curve that we've got. Area under the curve, that's all of this region. If you want the shaded part from that, we would have to subtract the area of this triangle. So how do you find the area under the curve? You just integrate it, input the limits from 1 to 2, and that gives you area under the curve. That turns out to be 0.2. And then to find that shaded part, you find the area of the triangle as well. How do you do that? For that, you'll have to use some information from the previous part because you'll have the point B there. Once you have the point B, you know this point is 1. You have the height somehow. This is also 1. In fact, height is 1, and the base can be found using the point B. You have the base. You find the area of that triangle, and then subtract those two, and that will give you the area of that shaded part as well. So you have to think about which area you have to subtract from which area, or sometimes which area you have to add to which area. This is going to be important in these problems. Now, for area, just one last point. For area, mostly what you can do is, for finding the same area, you can use the x-axis formula and also the y-axis formula. For example, this part on the left side here, you could use area between graph and x-axis here with these limits. And you could also use area between graph and y-axis formula with these limits. Both of them will work. Both of them will work. In area, you can use any of the two formulas in some cases, and they will work. But when they talk about volume, if they're saying find the volume of revolution about x-axis, then it has to be the x-axis formula. You cannot use the other formula because the shape totally changes when you rotate about the other axis. When they say rotation about y-axis, it has to be the volume of revolution about y formula. It cannot be the other formula. You have to use the y formula. In area, you can sometimes use the other formula as well and still get the correct answer. But with as in, think of that area as area between x-axis, area between graph and x-axis or y-axis, and use the limits appropriately, and you will get the result from both of them. But for volume, that does not work. If the question says find the volume of revolution about x-axis, it has to be the x-axis formula. If they say find the volume of revolution about y-axis, it has to be the y-axis formula. You cannot use the other formula in that case. That's all about integration. I hope that was helpful. We'll end this here. If you have any questions, you can let me know. And that finally completes paper 1. Took a lot of time, but we got done with it finally. Let me know if you guys have any problems now, any questions, any feedback, because it's been 10, 12 intense hours of paper 1. Let me know if you have any quick questions. Okay. Can you get a different angle other than 360? I haven't seen any in the past papers until now, but if you can figure that out just by ratios. So this formula is for angle for when the angle is 360. If they say the angle is 180, it's rotated 180 degrees, you just halve that volume that you found there. Whatever the angle is, you just find the ratio for that. For example, if it's 270, you just multiply that by 3/4. If it's 90 degrees, you divide that by 4 and so on. Just find the ratio and you will get that volume. I haven't seen any question like that in past papers until now. But if it happens, you just find the ratio. Okay. Just use this method, find the volume for 360 degrees. At the end, find the ratio for whatever angle that they have given. Okay. Anything else, anyone? Any other questions? No? You're welcome. Good to know that. Happy to hear that. For the next workshops, those of you who would be attending, just any suggestion about the speed at which we went and any other suggestions you might have for the next workshop, how we could improve something for M1, S1, P3. Those of you who will be attending any of them, if you have any feedback, as in terms of suggestions for what else we could do or how we could improve it, do it quicker than this, do it slower than this, or remove some of the parts. If some of things were very straightforward, could we just ignore them, or to save time, or any other suggestions that you might have, you can let me know. Topicals for a particular topic, functions, function transformations. Quadratics, recent questions, last couple of years. Equation of circle questions. These are some topicals that you can attempt this time. Equation of circle, function transformations, some recent quadratics questions, functions questions in general. They should be helpful. I think the pace was fine for the people who are well prepared relatively, but then I felt that some people probably went blank at some point because of the difficulty level of some of the things that we discussed, and at a quick pace, maybe they could not understand much. But there isn't much that can be done in a revision session to help with that, actually, because if it's a difficult question, then you have to spend time on that. And unfortunately, in a revision class, if we do that, then it ends up taking like double the time. Yeah, P3 will be like 7-8 hours, 2 days. It's going to be like that. Although, if you think about it, in paper 3, there isn't much variation in questions. So in this case, since the concepts are not very difficult, they try to change a lot in the questions. In P3, if you've done enough practice on integration, if you've done enough practice on differentiation, there's only a few different types of questions that they ask in them. There isn't much variation there. So if you understand the concepts very well in paper 3, it becomes kind of repetitive at some point. P3 is difficult. P3 is difficult. Although, if you understand the concepts well once, as in you make that effort of doing a lot of practice questions, then eventually you can still score 65 plus, 70 plus in that as well. To find increasing function, we have to use x values. What do you mean by that? Okay, so the video that I shared in the group, that was in another group. So there's a playlist for the calculator function that I have on my channel. I can share that with you here. So what I'll do is after the class, maybe I'll share that playlist. If I don't, give me a reminder about that. I tend to forget things sometimes. But I'll do that. I'll share the playlist link with you in the group that has like 4 or 5 videos and some useful functions. Some are not going to be relevant for you because I think some of them are for P3 as well, like complex numbers. but some of them are going to be useful for paper one as well. For example, the table function one, the sketching trigonometry graphs, and things like that. Yeah, complex numbers is one in which in recent papers they're trying to change a lot. That's true. Apart from that, it's pretty repetitive. Calculator functions, I'll do that. I'll share that with you. For S1, it will be 10th of May, inshallah, Saturday, the Saturday before your exam. So 3rd is a Saturday and then 10th, yeah. So for S1, most likely Saturday, 10th May, because on Friday, some people have an exam already. And I think it's in PM as well, so we might not be able to do that on Friday. 9th of May. What's the exam on 9th May? I think I was looking at the date sheet and I think there was some big exam on 9th, maybe chemistry or biology, one of those. So it'll be on 10th, most likely. 10th May for S1. And again, next week, before paper 3, there is an exam on Friday, but since we need 2 days for P3, that will have to be, and your P3 exam is on Monday. We can't do it on Sunday for that reason, because that will be too late. So it'll be Friday, Saturday for paper 3. We can't do before Friday because Friday is a major exam from what I remember from the date sheet that I saw. So P3 will be 16th. No, P3 will be 16th, 17th. Yeah, 16th and 17th will be P3, 16th and 17th. And S1 will be 10th, inshallah. P3 is difficult, but when you are well prepared on that once, then it becomes easy. S1 is like, you can say it's sometimes unexpected, the permutations and combination questions. It's unpredictable what question you'll end up getting in the exam on permutation combination, because sometimes it makes you think a lot in the exam, and you cannot figure that out unless you've done like 80, 100 questions on that. P3 is not like that. If you have done sufficient practice, there isn't much that they change in the exam, or they can change in the exam. In S1, in permutation combination and probability, they can sometimes end up giving some totally, unusual scenarios that you need to think about a lot. So that requires you to think logically in the exams. That's what a lot of people find difficult. In that time pressure, it becomes difficult for that reason. P4 is mechanics. Mechanics will be this coming Saturday, inshallah. So that's 3rd May. 3rd May will be the M1 workshop, inshallah. Yeah, permutation combinations is a difficult topic. It is a difficult topic. Although the standard questions, once you do enough practice, they are fine. But sometimes you end up getting something that's totally different, and that becomes difficult. Yes, you have P1 this week. You have it on Friday. You have 3 days left. So, yeah. All right. So that's it then. I will see you again in another class, and inshallah, all the best for your exams. What I'll do is I'm thinking of making a group in which I can just add every one of my students, because I'm getting so many questions recently that it's becoming humanly impossible to respond to all of them. So what I'll try to do is I'll try to connect everyone so that you guys can help each other out as well, and that might help. I'll of course keep responding to your questions, but it's just that a lot of times students get impatient, and I cannot respond immediately. So what I'll do is I'll be adding you guys to another group in which you can help each other out as well. There are actually some people. There are some people. Okay, by the way, I would want to get this feedback as well. So how many of you would prefer having these workshops in Urdu? Or the normal way we speak generally, it's bilingual, and आधा English बोल रहे होते हैं, आधा उर्दू बोल रहे होते हैं, इसी तरह से, so like that. Okay, actually they are, I think, registered as well, so it might be difficult to switch to Urdu. Unfortunately, that will be difficult. Although you should all know your own language as well. So some people, when I go to these elite schools, I am really disappointed sometimes. Urdu नहीं आती होती बच्चों को, बिल्कुल समझ नहीं आती. That's not good. You totally lose connection to your culture, to your home country. पर आप कहीं बाहर चले गए तो फिर तो आपको कुछ भी नहीं रहे, कुछ भी आपकी जिंदगी में जो है वो पाकिस्तानियों वाला रहेगा ही. उर्दू तो आपको आनी चाहिए. Even if you're more comfortable with one language, आपको अपनी लैंग्वेज पर भी आनी चाहिए. Yeah. अच्छा चलें, तो उर्दू तो नहीं हो सकेगा unfortunately. It'll have to be that because of some international students, because YouTube पे भी अक्सर जो है वो मेरी वीडियोस कुछ उर्दू में है, कुछ इंग्लिश में है. So I have some audience from outside as well. So when they get registered, फिर वो थोड़ा सा मुश्किल हो जाता है to totally switch to Urdu. Okay, all right. So all the best for your exams, everyone, and I'll see you in the next session, inshallah. If you have any questions, you can keep messaging in the groups. Try to help each other out. I'll try to respond to your question as well. And I wish you all the best, inshallah. Thank you, everyone. Allah Hafiz. Inshallah. I have my duas for all of you, inshallah. I will be making duas for everyone as well. So all of you as well, make sure that you prepare well and make lots of duas, not just for your exams, but for, the whole situation that we all Muslims are in right now. वैसे भी आजकल तो पाकिस्तान के हालात भी थे, क्या होना है अभी कुछ दिनों में. Hopefully everything stays fine, inshallah. I'll see you again in another session, inshallah. Allah Hafiz.